So, hello everyone. My name is Immanuel. I'm from Cornell, and this course is about database management systems, which are systems that manage and process large amounts of data. In this course, we are going to see how to use them and how they work. All of you have already used database management systems, perhaps without being aware of it. Because whenever you enroll in a course, book a flight ticket, transfer money, in the end, in the background, there's data being inserted or read from a database management system. That wasn't always the case. In ancient times, a couple of decades ago, applications would manage data using what we nowadays call the file-based approach. And that essentially means that each application manages its own data in a custom format using its own files. Now, if those applications are running in the same organization, for instance, it can create a couple of problems. For instance, here at Cornell, we might have multiple applications that all need to store data about students. And if they store the data independently, it means that we are wasting space because we are storing the same data redundantly. And what's even worse, if we are updating data, like the address of a student, for instance, then if you are not careful, if the data is stored redundantly, we might introduce inconsistencies between different copies of the data, which of course we want to avoid. And then on the other side, if you are managing data pretty much independently from what specific data you're managing, there's a couple of things that you always want to do. For instance, you want to have some kind of mechanism that recovers your data if you are in the process of editing it, and then suddenly your system crashes, for instance, because you lose power. And if we store and manage data independently in each application, it would mean that we might have to re-implement that functionality for each specific application, which is also bad, of course. This is why people came up with a database management systems, which looks like you see here. There is one system managing all the data from the organization, at least for a certain domain. And then those applications, they access this data via the database management system by a unified interface. So those applications, they don't manage their data themselves and separately anymore. Now, for most of this course, we will be discussing about a specific type of data, which is very common in practice, which is relational data. And for the moment, you can think of relational data simply as a collection of tables. Now, in the first part of this course, we're going to discuss about a language for inserting data of this type, for modifying it, and for deriving insights from that data. And this language is called the structured query language, or short SQL, and it is supported by most relational database management systems. After discussing about the interface, we're essentially going to open up the database management system, and we're going to look at the different components that allow it to manage and to process your data. First of all, we're going to discuss about the way in which your data is stored and about how we can access that data efficiently by the database management system. So we're going to discuss first of all about storage media such as hard disks and about their properties and about the way in which we want to store our data on them in order to make access efficient. We're also going to discuss about specific access methods such as indexes, which allow you to very efficiently find specific data that you are looking for. Next, we're going to discuss about how we can process the data and derive new insights from it. So here we're going to discuss about standard operators, for instance, operators for filtering data or for combining different data sources via so-called joins. We're going to discuss about how to implement those operators and about how to connect multiple operators in query processing plans. We're also going to discuss about how we can estimate processing costs for operators and entire query plans before actually executing them, which allow us to choose the most efficient plan for an incoming query by a process called query optimization. After that, we're going to talk about how we can process transactions. And transactions are groups of commands that either read or modify your data which are semantically related. So typically, you either want to execute all operations of a transaction or none of them. So we are going to discuss about the transactions. In particular, we're going to discuss about how we can ensure that transactions are executed properly, especially in cases where multiple users are using the database management system concurrently, which is the common case. And we will see how we can use a process called concurrency control in order to ensure that multiple users on the same database don't interact in a bad way, which might lead to inconsistent data. And also, we're going to discuss about crash recovery, about how we can bring your database back into consistent state after a system crash. Now, after that, we're going to discuss a little bit more about how we can design a good database. We're going to see tools that allow you to design the schema of a database for a specific use case. We're going to see how we can detect the redundancies in those schemata and how we can optimize those schemata by normalization and at least partially get rid of that redundancy. Now, if you want to serve a large number of users, or if you are dealing with a lot of data, then typically you don't want to run your database on one single machine, but you want to distribute it and run multiple instances on multiple machines. So in the next part of the course, we're going to discuss about distributed data processing. We're going to discuss about corresponding challenges and how we can solve them. We're also going to discuss about terms such as NoSQL and NewSQL, which are some recent trends in data processing. We're also going to see a couple of corresponding systems. Now, in the final part of the course, we're going to broaden our scope beyond the relational data. We're going to look at different types of data, for instance, graph data, spatial data, and data streams. And we're going to discuss about specific systems that have been tailored in order to store and to process those different data types. Now, in order to follow this lecture, you can follow it without additional material, but it can be helpful to look into the book Database Management Systems by Ramakrishnan and Gehrke. Often at the beginning of my slides, I will have the abbreviation RG followed by a section number, and that refers to the corresponding section in this book in case you want to read up more details. Also, especially for some of the more recent systems that we are discussing, I will give you references to specific papers that provide you with more details. And those references are typically at the beginning of my slides titled Reading Material. And then in this lecture, I'm gonna make a lot of examples. I want to show you what it is like to use one of those database management systems in practice and how to get some impression for what's happening inside. And for those examples, I'm gonna use the Postgres database management system, one of the most popular open source database management systems. You can find it, download it, and install it at the web address that you see below. Now, this course was given at Cornell as an online course in fall semester 2020. Students were able to interact with me via the chat. Sometimes I'm getting questions on the chat, which you will not be able to see because we want to keep students anonymized, but I typically read out the question and the corresponding answer. Also, I'm including exercises into my lecture where I ask you, for instance, to write queries in order to solve specific tasks. I encourage you to do those exercises with me. Typically, I give you a couple of minutes to solve them. I'm from the Cornell database group. So if you get interested by this course in database systems in general, and perhaps become interested in database systems research, please check out our website. You see the URL below. And now I wish you good luck and have fun with the course. the last time we have been talking about database management systems, which is a system that essentially manages the data, all the data that you are interested in, and then different applications can access the data by a unified interface. Here you see the high-level architecture that we have discussed. The last time I gave you a quick overview. In the coming lectures, we're gonna look at different components within that architecture, and we're gonna discuss in more detail what is behind that. Now, in this lecture and also in the following lectures, we'll be looking at the interface to the database system. So that is essentially the interface that either you as users are directly using or that the applications are using. If you want to read up on more details beyond what we will be discussing in the course, or if you just want to see an alternative explanation of the same content, then you can have a look into the course book. Here on the left, the lower corner, you see the reference to the chapters that are relevant for the material that we will be discussing in this lecture and in the following lecture. RG, that stands for Ramakrishnan and Gehrke, and the relevant sections, it's primarily section 3 and section 5. The question last time was whether you actually need the book, and you don't need the book if you understand everything that I point out here in the course. So for the homeworks, the relevant material is what we are covering in the course. But if you want additional information, then it might make sense to have a look at the book. All right. So now we are talking about the database interface surrounded with the red circle there. And typically database management systems support a language called SQL, that's the structured query language. This is what you essentially use in order to issue commands to the database management system, telling it to either retrieve data or to change data in some way. It's a very old standard already. I mean, the first version of it appeared in the 70s, and currently the latest version has a couple of 100 pages. So we're not gonna cover all of SQL. It's a very powerful language, but we're gonna see a subset of features which are sufficient for most use cases. Now, people distinguish different types of SQL commands depending on what they do. First of all, you have the so-called DDL, data definition language, and that one essentially allows you to define what the structure of your database looks like. So you can essentially tell the database management system what kind of data entries are admissible. You can set constraints, and then the database management system will reject any changes to the data that would not comply with those constraints. Then, beyond defining constraints, of course, you can also insert and manipulate and retrieve data. That is the DML, the data manipulation language. We will also have the transaction control language. That one is discussed a little bit later, which allows you to group SQL commands into so-called transactions, which have several nice properties that we'll discuss later. Also, you have a couple of commands in order to assign data access rights, for instance, which are controlled by the database system, but that we won't go into detail in this course. All right. Now, in the following, we will first of all discuss about the data definition language. After that, we cover the data manipulation language. The TCL is covered a couple of lectures later, not immediately. So let's start with the data definition language. You are defining a so-called database schema, which essentially describes the content that you can insert into your database. Now, we have heard last time that those relational databases that we are focusing on here, they consist of a collection of relations, where each relation essentially looks like a two-dimensional table, essentially a little bit like a spreadsheet. And one first thing that you can define for each relation is what are its columns, what are the names of the columns, and what are the data types of the columns. Because each column of a relation is associated with a data type. And once you insert data entries into that relation, they actually have to comply with those data types. We're going to see some concrete examples for that later. You can generally introduce more constraints beyond the data type. You can put constraints on single relations. You can also define constraints that link multiple relations. We're gonna see some specific examples for constraints in the following slides. Now, in order to create one relation, this is the command that you use in SQL. In SQL, we are actually not talking about relations, but we're talking about tables. So strictly speaking, there's a couple of fine differences between relations in the relational data model and tables in the SQL language. But for the moment, I'm not going to go in detail here. You can assume that what is called table in SQL is meant to represent what I called relation in the context of the relational data model. And this is the command for creating one of those tables. Create table, then you write the name of the table, and then between parentheses, you have a comma-separated list of column definitions, where each of those column definitions consists of the column name and the column data type. Now, let's make things a little bit more concrete. So in the following, we are going to use a very simple university database with information about students as a running example. So first of all, it might make sense to introduce a table in order to store information on students. And we can do this with the command that you see here. I'm telling the database system, I want to create a table named students, which has an SID, a student ID of type integer, then an S name, student name of type text, and the GPA of type real. All right, and maybe I also want to keep track of which courses those students are enrolled in. So I might want to introduce a table enrollment, which essentially links student IDs to course IDs. So the content of this table that you see in the middle, enrollment, would be pairs of student IDs and course IDs with the semantics that the corresponding student is enrolled in the corresponding course. And maybe the course ID alone, that's not very informative. So ideally, we also want something which links the course ID to the course name. So we can introduce one more table which is doing this, which has the course ID and the corresponding course name as columns. All right, so that is a very simple database with 3 tables, and you can create that relatively quickly with SQL commands. Now, beyond specifying that certain columns have certain data types, perhaps we want a couple of other constraints. Is there any kind of constraints on that database that anyone can think of? Constraints that essentially ensure that the database content will make sense. So if you have an idea for a constraint, please write it into the chat. All right, and here comes already like the, okay, very good, very good. Okay, there's a couple of very nice propositions here, thank you. Okay, and please feel free to still type something if you have another idea. Right, so there's a couple of propositions about restricting, for instance, the value range for the GPA, and that makes a lot of sense because right now it could be any kind of real number. So restricting the value domain further by, for instance, setting a non-negativity constraint, that is good. And the other thing that I see here in different variations, there's many very good ideas here, thank you, that's amazing, is to enforce some kind of uniqueness constraints. For instance, we have all those IDs in our database. And typically in order to make sense, an ID should be unique. So you shouldn't have, for instance, 2 students with the same net ID because that would create all kinds of confusion. So The proposition here is to add some constraints which enforce a uniqueness in certain columns when it comes to the IDs, for instance. And another good proposition is, for instance, that if you look at the enrollment table, the enrollment table links students to courses. So what we want is that the student and the course that are linked, that they actually exist and that a corresponding entry has been inserted into the corresponding other table. So you don't want to store enrollments for a student for which you don't have the name entered, and you don't want to store an enrollment for a course that doesn't exist in your database. So it makes a lot of sense to link those different tables together. So very good propositions. And this essentially covers already the things that we will see in a little bit more detail in the following. So very good. Now, general term here is so-called integrity constraints. They generally limit the content that you can insert into the database. And the database system takes care of enforcing those constraints. So if you try to change the data in a way that violates one of those constraints, then typically the database system will tell you that the update cannot be done, or what we will see later, there's also a possibility that the database system essentially tries to fix things itself, but in the most typical case, it would just essentially tell you, no, this update is rejected because it violates one of those constraints. All right, there's different ways of adding those constraints to the table schema that we have defined before. In general, in SQL, there's always many, many different ways of expressing the same thing. So if you are using SQL over a while, then you will learn about different variants, and you will typically figure out what variant of the commands you prefer. So in the following, we're going to see one way of writing those constraints, for instance, but just so you know, there's many different ways of writing the same thing. All right, so we can add constraints, for instance, by using the alter table command. And this first type of constraint that we will be looking at, those are the primary key constraints. And I have already seen somewhere here in the chat the keyword, the catchword primary key, so very good. That essentially is a constraint by which you say that one column or a combination of columns corresponds to an ID, a unique identifier. So those primary key constraints are placed on single tables, and they identify a subset of columns generally that are key columns. And the semantics is that no two entries in the same table can have exactly the same value combination in those key columns. So that means that if you fix the values in the key columns, then you automatically narrowed it down to one single node. Like for the students, if you have the net ID, you narrow it down to one specific student, because no two students can have the same net ID. So this is the general syntax of the command. We write alter table, then the table name, add constraint, makes sense. And then here we want to add a primary key constraint. So here between the parentheses, you have a comma separated list of the columns that you want to become the key. So those columns must exist in the table that you're altering. For instance, here, you're altering the students table by adding the constraint that the student ID should be a key. So it should be unique, and you must have a value entered there. Also, for the enrollment, it is a little bit more difficult, because for the enrollment, the same student could be enrolled in two different courses. So then you would have two entries in the enrollment table with the same student ID. Also, for the same course, you typically have many students that are enrolled in the same course, which would be represented as multiple entries in the enrollment table with the same course ID. So in separation, we cannot say that either the student ID or the course ID forms a key for the enrollment table. So what we do instead is that we take the combination of the two. So we say that the student is not unique, but the course is not unique, but a combination of a student and a course should be unique, because otherwise you would be storing enrollment information twice. That seems redundant and unnecessary. That might change, by the way, if we add, for instance, a year column in the enrollment. If we say that we don't keep track of the current state, but also of the state in past years, then it might make sense. Somebody is taking the same course twice, then you would have to extend it. But for this very simple database, we can say that a combination of the student and the course is unique. Finally, with regards to the courses table, we have said that the course ID should be unique, and this is the constraint in order to express that. Now, a different type of constraint is the foreign key constraint. This one links together two tables, and in one of those tables, it identifies a set of foreign key columns. And then it links those foreign key columns to the primary columns in another table. The semantics is that you are essentially stating that any value combination that appears in the foreign key columns must also appear in the primary key columns, because you are essentially linking each entry in the table with the foreign key to one entry in the table with the primary key. So if we fix the values in the foreign key columns, then that should narrow it down to one single row, to one single associated row in the table with the primary key constraint. All right, let's make it more concrete. So here you see the syntax for the command by which I add foreign key constraints. We are altering a table again, and we add a constraint of type foreign key, where we specify the foreign key columns between those parentheses. And then we reference another table and the corresponding columns in that other table. Depending on the database system, sometimes there's additional restrictions about what type of foreign key constraints you can define. And the syntax might always vary between different database systems a little bit, but this is the command that should work in the Postgres database system. All right, so here we are extending our running example database. And we already had that in the chat. People suggested that there should be a link from the enrollment table to the students table and also to the course table. Now here we are taking care of the link to the students table. We're linking the student ID column in the enrollment table to the primary key student ID column in the students table. Right? And so if you try to insert an enrollment for a student that hasn't been entered, then for instance, the database system would give you an error. Same principle for the courses. Here we are adding a link between the course ID column in enrollment to the primary key constraint in the courses table, right? And here we essentially ensure that you're not inserting any enrollments for courses that don't exist. All right. Okay. All right. So, and now I'm going to give you a little exercise which links to the example that we have just seen, just to get the hang of it a little bit. While you're working on the exercise, I will also look for questions in the chat. And The exercise is the following. So we are considering a bookseller, let's call it Zamona, who wants to start selling books via a web portal. So your goal for the moment is to create a database, a schema for a Zamona in order to store information on books. So each of those books has a unique integer ID and a book name. You also have writers on the other side, which have unique names. And those writers are linked to books as authors. So your goal is to come up with the commands to define a database with 3 tables for this scenario. And you can either do it just by writing down the command, or if you have already Postgres installed, then you can try it out yourself. I will very quickly demonstrate to you what that looks like using Postgres for once. Let me quickly share my console here. All right. So at this point, you should be seeing the console window. If that is not the case, please let me know in the chat. Here are some first questions on the example. Yes, there can be more than one writer for a single book, and one book can also be written by multiple authors. Very good questions. Okay. Right. So now I'm quickly gonna demonstrate how using Postgres looks like. Maybe some of you have already experienced with Postgres, so you can skip that and already start working on the example. For the others, it might be interesting to have a look. And after that, I'm gonna give you a few minutes to try coming up with a solution for the example. All right. Okay. So first of all, there's many different ways of accessing Postgres. There's different interfaces, and it also depends a bit on which operation system and which version of Postgres you're using. The following, I'm going to use one of the most basic tools to access Postgres, which is the SQL tool. Now, before I'm accessing a database, I first of all have to create it. So in this example that we have seen before, we have been talking about students and courses. So this should be a university database. So I'm entering the command create DB, create database, and what shall we call it? University, for instance. All right, so now the database has been created, but right now it's not populated yet. So now I'm gonna log into that database with PSQL. All right, and now we are in the database and can issue SQL commands. Now, some of the, so you can try out the example that we have seen. I'm not gonna do the entire example, just a few commands just to see what it looks like using Postgres. For instance, we have created a table about students. So what we can do here, we can create a table with the student ID and the student name, right? And if we do that, then the database tells us it has successfully created this table. And we can also create the table enrollment, for instance, which has the student ID, and it also has the course ID. Right. So, all right. And okay, and so depending on your Postgres setup, you have to essentially, you have to make sure that you have installed it properly. Otherwise, you might see some error messages here. You don't necessarily have to do the example with me here, so I'm just giving you a little glimpse of what using Postgres looks like to make sure they have seen the console at least once. And then you can try setting it up and maybe doing the course example or the exercise that we have now. You can try to do that with the database. One good question, how do you list all the tables? The command for that is \d in Postgres. And here you see all the tables that we have introduced so far. All right. So I'm gonna go back to that example later. What was the last table that we had? It had, yeah. All right, I can still add this one. Courses, the CID was of type int, and the course name was also of type text. All right, and here, and here, for instance, I'm adding one of those constraints. All right, and so I'm not gonna go through the entire example here, but this is the principle. You issue those SQL commands, for instance, in a console like this one here in the database system, gives you feedback about whether executing the command was successful or not. All right, so either with the terminal, if you have already installed it, or if you just write down the commands. I give you a couple of minutes in order to do this example here. Let me quickly share the slides again. And here they are. All right, here you have the slides. So I'm going to give you just a few more minutes in order to think about that and in order to try writing those commands. And if you have any questions in the meantime, then please ask them in the chat. Okay, and it seems that somewhere in the slides it says add constraint explicitly. That is a typo. It should just say add foreign key or add primary key. This is what we use in the examples. Okay, it's the exercise. So there is no exam in this course. Was one question about an exam, and there is no exam in this course. And for the homeworks, in general, the syntax should be, so basically whatever syntax works in Postgres. There's slightly different SQL dialects for different database systems. And for the homework submissions, please use the one that is supported by Postgres. In most cases, it doesn't matter. So SQL database systems, they implement the SQL standard quite tightly typically. But every once in a while, there is one detail which is a little bit different in different SQL versions supported by different database systems. So in case of doubt, I suggest to go with the Postgres syntax, which is also the syntax that we will see here in the slides. So the grading is based on homeworks. In general, there will be 7 homeworks and your best 6 submissions are counted. Also, those homeworks are to be done alone. So there's a couple of differences to this course in past semesters. First of all, there's no exams in this course, and also the homeworks are no group homework, but they are done alone. And here the question is, that is a great one, when we can directly set the primary key and foreign key, whether we can set them directly when creating tables. And yes, you absolutely can do this. If you use the primary key keyword in creating the table, for instance, then you can make a column directly the primary key. There's different ways of setting those constraints. Here we have seen how we can add them afterwards, but you can also add them directly when creating the corresponding table. Very good. All right. I think now you had a little bit of time to look into this. So we're gonna publish the complete solution on the website, but the high level idea here is that you essentially have again database with 3 tables. You have one table about the books, you have one table about the writers, and then you have one table linking the books to the writers. Like here you have this table in the middle, which links the students to the courses that they are enrolled in. And in a similar way, you can link the authors to the books that they have written. So it's the same principle as here, just with a different scenario. All right. Now, beyond just defining the schema of the database, of course, you can also insert data that complies with the schema. You can delete data, you can update it, and you can analyze it in various ways. And in the following, we're gonna see commands for doing all of those things. So now this is the data manipulation language. First of all, we want to insert data into our database. And here you see, first of all, the command for inserting one fully specified row into a table in a database. So here we have this insert into table name values. And here you specify the values for different columns for one single row, right? Here I'm saying fully specified. One feature of SQL is that it allows you to essentially handle cases where some parts of your data are unknown. Let me quickly mute everyone. I can hear something in the background here. Right. So, okay. Everyone should be muted except for me. Okay. Good. All right. So here we first of all see a command for inserting a fully specified row, which means that you are specifying values for each of the columns, but you do not have to do that. SQL has a way of representing fields where you don't actually know the value currently. It is called an SQL null value. We will see this in more detail later, but here we already connected that a little bit because the second command that you see here, it allows you to specify values only for a subset of the columns, and the remaining columns, they will be filled up with null values automatically. So in the second case, you have to specify for which columns you actually want to set a value. All right. Now, what we can do here, first of all, we want to store information on some students. So it makes sense. We want to insert an entry for a student named Alice. And here you can see how we do this. We want to insert something into the students table with the values 3 for the student ID, Alice for the student name, and 4.0 for the GPA. All right, and as you see, the corresponding table, the row appears here on the left upper side. All right, now let's also insert a student named Bob, but this time we're only specifying values for the student ID and the student name. Perhaps we currently don't quite know the GPA when entering the data. That will be automatically replaced by this null value placeholder. Okay. So this is how you can insert data, but in practice, if you're using an SQL database system, then if you want to analyze data, you're typically loading it from a file, and Postgres also supports the commands for that. You can load the content of a table from a file by using the command that you see here, copy some table from some file specified as a path with specific delimiters and with a specific representation of null values, for instance. So it's many versions of this command, but it tends to be very useful in practice. All right. So here, for instance, you might be loading the information, all the courses from some comma-separated value file, which we could do by a command like the one that you see here. Okay. We can insert data. Of course, we can also delete data. You can delete rows from a table which satisfies certain conditions with the command that you see here, delete from table name where some condition holds. And that condition essentially specifies which rows in a table you want to delete. We will see in more detail later which syntax you can use for those conditions. SQL supports very rich conditions, but for instance, you could use some inequalities between columns and constants, and we will discuss all the different types of conditions that you can use here in more detail later. For instance, a course database, we might want to delete the 6320 course because that one is not given this semester. So if you here observe the original course table after the command, it will shrink by one row because we delete the one where the condition CNAME equals CS6320 is satisfied. Beyond inserting and deleting data, you can also update it. You can update the specific rows and like the values in specific columns of specific rows using the command that you see here. We are simply writing, we are updating a table, we are setting specific columns to specific values for all the rows where this condition here is satisfied. So this command changes those rows satisfying the condition by writing the given value into the given column. Right? So here, for instance, maybe we want to change the course ID to number 7, where the name is 4320. And here you can see the table changing after we run the corresponding command here. All right. All right. Now, this is an exercise that you can do at home, or at home anyway, but an exercise you can do after the lecture. For the moment, I can show you again how those examples work in Postgres, just to make sure that you have seen that once. Let me quickly share my screen again. Console. Right, and what did we insert here? For instance, okay, we inserted a student named Alice. Okay, and I think they actually didn't define the GPA column when I made the example before. Let me quickly verify that. So here with the \d command, you can show all the tables that are currently defined. So at least I defined the students table, but let's see which columns I have in that table specifically. And with the syntax here, a \d and then the name of a table, you can actually find the different columns of the table. And here indeed, I made a mistake because I didn't, or I mean, it is inconsistent with the example slightly because I didn't introduce the GPA column. So what I can do in those cases is that I delete the students table again with this command. So now I only have 2 tables left. And now I'm creating the students table again. What did we have? We had the student ID, we have the student name, and we have the GPA. There's different versions that I can be using. All right. Okay. And I'm quickly going to finish this. I see there's a couple of questions popping up in the chat. I'm going to take care of them in a minute. And what I just wanted to show you here is how we insert one more row for the students. Some first row here, I'm inserting the student Alice, and the database system now gives me feedback. The first number that you see here, that one will be typically 0. That is only used if Postgres assigns so-called OIDs, but this is not going to be part of this lecture. The second number is more interesting. It tells us that one row has been inserted into the table. And here somebody is already proposing the correct command. Very good. Somebody is proposing a command to say, to essentially show the content of that table, which we will see in more detail later, but I can already give you the command here. We are doing select the star, which means we want to know something about all the columns from the students table, right? And now it shows me this one single entry in the students table, right? So here I want to give you a little bit of a feeling for what it is like to use one of those database management systems. I should also say that this interface is, of course, very simplistic. Depending on which version, which tool, and which operating system you're using, you might have some nicer graphical interface, but the SQL commands, they remain the same. And I mean, in many cases, you would actually, in practice, you might not be using SQL directly, except if you are developing an application. Like in many cases, the end user is actually shielded from issuing SQL commands. you use some kind of interface which in the background generates SQL queries that are sent to some database. But of course, if you want to develop this interface, then you need to know about SQL. Okay, couple of questions. So, all right, so some questions already refer to advanced concepts, some of which we will not necessarily cover in this course, even though it's very interesting questions. Okay, here one question about the previous book exercise. So I quickly sketched out the solution, which uses 3 tables in analogy to the example that we did with students. Here the question is whether we couldn't have done it with 2 tables, like simply one table about books and one table about authors, and then have an array of book IDs in the authors table and have an array of author IDs in the books table. In principle, you can use arrays, but let's say the proper way, the most SQL way of doing things is that you, not sure whether I should formulate it that way, but for this course, we are only working with scenarios where we have single values, scalar values, single integers, strings, and so on in one field of your tables. But depending on which database management system you're using, there might be some advanced features that allow you to do things differently. Several new messages. Okay. One quick question about the first number in the insert statement. So that number is not relevant for this course. It basically, if Postgres would assign something called an object ID, then during the insert command, then this object ID would replace the 0 for this first of the 2 numbers. But since this didn't happen in this case, we have the 0 number. And for the purpose of this course, we will assume that one column and one row only has one single value, like one integer or one string. There's a couple of advanced features where you might not have it that way, depending on which system you're using. But for this course, one column and one row means you have one value. Okay. Good. All right. Good. So we are at the end of our time frame. I recommend you to have another look at the examples that we have seen. We had one in-class exercise, and until the next lecture, you might want to play a little bit with this example database and think about how you would insert or update specific books and authors in this database, and perhaps make one example where you insert data which doesn't comply with certain constraints, and so the database system might reject your updates. In the next lecture on Monday, we will continue seeing some more SQL features. We are going to essentially discuss about the interface to SQL first, and then afterwards we will start discussing about how the database management system actually internally processes your SQL commands. All right. So the last time we have been talking about the interface to the database system. And today we are going to continue talking about that. you're learning a language called SQL, the structured query language. The relevant book chapters are still the ones that I had in my last slides from the Ramakrishnan and Gehrke book, the sections 3 and 5. Now, the last time we have seen how you can define the structure of a database in SQL, meaning you can define what are the tables and what are the columns in those tables, and you can define constraints like the primary and foreign key constraints that we have seen last time. And we have also seen how we can insert and delete and update content that you have in those tables. Now, of course, ultimately, once you put data into a database, then at some point you want to actually retrieve it or analyze it in some way. And today we will start discussing about SQL queries, which analyze the content of your database. Now, generally, such an SQL query describes a new relation or a new table to generate. This new table is generated from the content that you have in your database. So this new table that can consist of one single value can also have multiple rows and multiple columns. And in the SQL query, you define what that table should look like and what content you want inside. So very important, we quickly mentioned that in one of the previous lectures, SQL is a declarative language, so you do not instruct the database management system which steps to execute in order to analyze your data. You just describe a desired result and you leave it to the database management system to figure out what is the best way of generating that result. Now, we're going to start with a simple class of SQL queries, which consists of 3 parts, which describe the desired result relation. Now, in the from part of the query, you are specifying the tables from which you want to generate something. So this is essentially the data sources for your analysis. Then in the where condition, you specify certain predicates, certain conditions that the rows in your result relation must satisfy. And in the select part of the query, you specify the columns of the result relation that you want to see. So we are discarding the other columns. All right. The syntax for this simple class of queries is as you see here. In the from clause, you specify the data sources. In the where clause, you specify conditions for row filtering. And in the select clause, you specify the columns that you're interested in. Now, most of that is pretty intuitive. Perhaps the from clause, that one looks a little bit more complicated. So let me say a few words on that. So here in the from clause, we are essentially combining 2 data sources, 2 tables, and we are using the join keyword to do that. So the semantics of what you see here is that I essentially retrieve a pairs of rows containing 1 row from table 1 and 1 row from table 2. And I only want to retrieve those pairs which match, which satisfy a certain condition together. And that condition is specified as the join predicate. So we are only retrieving those tuple pairs, those row pairs, which satisfy together the join condition. Also, you see those little dots on the right-hand side of the from clause. This indicates that you can add more tables. You can join with a 3rd table on some join condition and with a 4th table on some join condition and so on. So you essentially, you can choose how many data sources you want to combine. Of course, if you are dealing with large data sources, then the more data sources you combine, the longer processing could take. Let's make things more concrete by an example query. Now, this example query refers to the database that you see on top, marked in green. It is pretty much the database that we have seen last time. It's a database containing information on students and the courses they're taking. There's one table, one relation for the students with a student ID and a student name. Then there is a table storing the courses with the course ID and the course name. And then there's this enrollment table, which connects the students table to the courses table and essentially stores pairs of a student ID and a course ID with the semantics that the corresponding student is enrolled in the corresponding course. On the lower half of the slide, you see a corresponding query. And perhaps one last thing I should point out about the database, and you might notice that I have underlined some of those columns in those relations. And that typically means that the corresponding columns are primary key. So this is what it means in this case. In some other books on databases, you might find slightly different notations, but this is a typical notation in order to indicate which are the primary key columns. All right. Now, you see this query on the lower part of the slide, and perhaps on the first sight, when not being used to it, those queries can sometimes look a little bit complex. So if you want to understand what one of those SQL queries is doing, it's typically good to essentially decompose it and look at the different parts. So if I try to understand what a SQL query is doing, I typically start by looking at the from clause. So let's do that. And if you look at this first part of the from clause, then what we're doing here is we're essentially pairing up students with their enrollment. So we are selecting pairs of one row from the students, representing one student, and we want to retrieve a matching pair in the enrollment relation, which is essentially one tuple with a student ID and a course ID, where the student ID matches the student ID that I have selected in my students table. So this essentially combines each student with the related enrollment information. The second part of this from clause over here combines that with the information in the courses table. So after having matched the students with the enrollment relation only gives me the course ID, but I might also need the course name. So here I'm therefore matching the tuple pairs from the student and the enrollment table that match on the student ID. I'm pairing that with a third tuple from the courses relation, which matches on the course ID. So the result of this entire from clause, those are triples of tuples, one from the students, one from the enrollment, and one from the courses that match on the student ID and on the course ID, because those are the two joint conditions you see here. So the next step I'm doing here is that I filter the rows in my result relation using this predicate. And here in this predicate, we are essentially restricting the course name to CS4320. So I want to get, I want to know something about course enrollments for that specific course. All right, so we will discard the rows which don't satisfy this condition in the where clause. Now, finally, we look at the select clause, and here I'm essentially specifying the columns that I want to keep in my result relation. So I will discard those columns which don't appear in the select clause. And as you see throughout this entire query, we have always referred to columns by this notation that you see here. Here I'm selecting the S name, the student name column in the students relation. So if you want to refer to one column of one specific relation, we use the notation relation, aka table name, dot column name. We will also see a couple of alternatives, a couple of simplifications in the following. Now, so now you have seen your first SQL query. In order to get the hang of it, I think it's good to make a little example here. I give you a couple of minutes, maybe 5 is maybe even a little bit much. Here I ask you to find the names of courses in which one specific student named John Smith is enrolled. So give it a try to formulate that SQL query. You can either do it on paper, or you can do it in Postgres if you have it installed, or you can go to this website that I have shown you at the beginning. And here there is one question, whether by doing the select we create a new relation or whether we modify the old one. So in general, this entire SQL query together, all clauses together, is defining one new relation to create. So you cannot say that the select clause alone is creating that relation, but the query in its entirety is essentially creating one temporary result relation that will be shown to the user. All right, so I give you a couple of minutes to make that example. And in the meantime, I'm answering questions that appear in the chat here. Okay, and this is a very good question. Somebody's asking whether we can only join using columns that appear in foreign key constraints. So you might remember from last time, we've seen that we can link the columns from different tables by those foreign key constraints. We essentially specify that values that appear in the columns of one relation must appear as primary key in the columns of in another relation. So you're essentially matching rows from one relation with the foreign key on the columns to rows in another relation. And in those examples here, I have indeed used joins that connect relations which are linked by foreign key constraints. Good observation. Now, in general, this is not necessary. In general, you can formulate arbitrary join conditions and you can formulate arbitrary joins. You can join arbitrary relations. Having said that, the most typical join is actually, so in practice, the most common case is that you join tables with foreign key conditions, but that is not required. All right, and here I'm just accessing the chat. All right, and that is another great question here. Question is whether the order of the tables in the joins matter. Now, the order of the tables does not matter for the query result. Also, internally, the database system might freely choose the order in which it internally executes the operations for joining a table. So it typically does that to optimize the expected running time for answering your queries. So for the final result of the query, the order of your tables in the join does not matter. And if you have a reasonably sophisticated database system, then the order of the tables does not matter for performance either, because the database system internally chooses the order in which it does the joins. We will talk much more about performance later. And left outer joins and right outer joins that as he mentioned here, we will discuss about them later. Yes, so once we come to those left outer joins and right outer joins, which I haven't introduced yet, then the order will matter. But I mean, for the joins that we have discussed so far, the order does not matter. Not for the query result. All right. Okay. And for the solution of the exercise, please currently don't discuss it in the chat yet. I'm gonna show that to you in a minute. If there's questions left after I quickly go over how to approach this exercise, then please feel free to ask them in the chat. Okay, and here another great question. Now we only selected the students.s name, but in the rest of the query we mentioned many other columns, for instance, in the where condition and so on, in the join conditions. But since we only write the student name column in the select clause, it means that this is the only one that we as users will see afterwards. Okay. All right, I think now we had a couple of minutes and we answered a few questions. So let me actually quickly enter the solution here in Postgres. Quickly share my terminal here. Okay. So I still have the database that we created last time. If I call it university, here you see the names of the tables that we have here. And the goal was to select the names of the courses in which student John Smith is enrolled. So we want to find course names. That's why that's what the column that we finally want to see. And as data sources, we need, of course, the students, because we want to check something about the student name. We need to combine that with enrollment information. And here I'm already using a shortcut that we have not officially introduced yet. So let me write out the name of the students table before the column name. The join condition is that the student ID must match the enrollment student ID. And I'm also combining that with the data source courses. And here we must have that the enrollment course ID matches the courses course ID. Now we want to filter to, oh, and here I have made a little mistake, thank you. And here I want to have the student name match John Smith. So here we are selecting the courses.course name from the students, join with enrollment, join with courses, where the student name matches John Smith. So, right. Okay, and here a little mistake. Now we got it. So here we see that the student is enrolled in two courses, CS 4320 and CS 4321. All right. So, and the order of the join relations for the joins that we are considering right now does not matter. All right. So this is how we can solve this exercise. It is very close to the initial query that we have seen, where we are filtering by the course name and we are retrieving the students. All right. Okay. All right. Yes. And the from clause indeed includes, yes, all the joins. So that is something that you find in the from clause. And the the source, meaning the data source, this combines multiple tables. So you cannot answer this query from one single table, since you need, for instance, information about the course name, but also information about the student name, which you don't find in the same table. All right. Now, SQL allows you to write the same SQL query in many different ways. There's many possibilities to reduce writing overheads, and which one you prefer, this might differ from one person to another one. So I'm going to introduce in the following a couple of shortcuts that you may choose to use if you find it easier. Now, one first thing here is that some of those tables in the database, they can have pretty long names, and it quickly gets tedious to write out those names multiple times in the same query. So this is why SQL gives you the opportunity to introduce so-called aliases, which are essentially a shortcut for the names of tables in the from clause. So here you see the same query, but written in two different ways. In the query on the lower half of the slide, we are essentially assigning a shortcut S to the students table here. And then we are using that shortcut in the other parts of the query. For instance, once we are referring to the column that we want to select, and once we are referring to columns in join conditions, right? So this simply saves you typing a little bit when writing the query. And you can even simplify further if column names are unique among the tables that you use in your from clause. So for instance, the student name and the course name columns. The student name column only appears in the students table, and the course name column only appears in the courses table. So if you just write the name of the column, then the database management system should be able to infer the associated table automatically because there's no ambiguity. In those cases, SQL allows you to simply omit the name of the corresponding table. On the other side, if you have something like the student ID or the course ID, the student ID, for instance, appears in the students table, but also in the enrollment table. So if you just write student ID, the database management system does not know which table you are referring to. And that's why for those columns, you have to add the table name or the alias name. All right. And for the alias, both works. You can also use the AS keyword. All right. So this are some shortcuts that you can use in order to simplify the SQL queries that you write. The predicates, for instance, in the where clause that we have seen so far, they have been relatively simple, but SQL supports a very rich set of predicates that you can formulate. Of course, you can use equalities and inequalities. You can, for instance, check if the value in one column is within a list of allowed values. And you can even formulate regular expressions. For instance, here I'm checking whether the course name matches the expression CS followed by some arbitrary sign. Let me quickly move the chat a bit so that I can see more of the slide. And then followed by some arbitrary string. So this percentage sign stands for an arbitrary a number of characters, and this underscore stands for one single character. All right, so those are some ways to formulate more diverse predicates, and SQL supports many more types of predicates. But let's say the things that I'm showing you here in my experience, those are perhaps the things that you use most frequently in practice. So if you learn those things, then you should already, you should be able to treat most cases that arise in practice. Of course, you can also compose predicates using the typical operators. You can formulate a logical conjunction by using the AND keyword, or a disjunction by using the OR keyword. You have the not negation, and for instance here, you could check whether the course name is CS 4320 or whether it's 5320. An alternative way of writing that would be by using the in list, the in keyword that we have seen on the previous slide. All right, good. Okay, a couple of questions here in the chat. I think most of them have gotten answered. All right. So beyond the predicates, there's also many more features that you can use in order to write your select clauses. For instance, the tables that you will be working with in practice, often they have a lot of columns, and it can become very tedious to write out all the columns names if you just want to retrieve all the information in a table. So the star operator in a select clause essentially means that you want to retrieve all the columns that you have in your tables, in all the tables that you selected in the from clause. You can make it more specific by writing a table name dot star, and then you retrieve only the columns for one specific table. You can also formulate arbitrarily complex arithmetic expressions in the select clause. You can, for instance, here you can sum up values in 2 columns, and then you can multiply by some constant and so on. That is fine. And especially if you do this, if you use some complex expressions instead of single column names in the select clause, then in order to not get confused by the output of the query, you probably want to introduce some readable name for the corresponding column, and SQL allows you to do that simply by writing the name that you want for the column after here the column name after the AS keyword. So here, for instance, I'm renaming the student name column at the S name column to the more readable student name. I could also use that in order to assign some name to the expression that you see above. There's also a couple of alternative ways of writing those join conditions that we have seen so far. So far, we have been explicitly formulating the join condition, but there is a couple of frequent cases for which people have introduced shortcuts in SQL. For instance, often those join conditions, they are actually equality conditions between columns of different tables. Here, for instance, you can use the using keyword and simply you write the name of the column that should be equivalent, and then it is automatically expanded into this equality condition. Also quite useful in practice is the natural join. A natural join between 2 tables simply means that you want the values in all columns that have the same name to be equal. So instead of actually typing out the names of all the columns on which you want to match, this one will be expanded automatically. Can be a little bit dangerous because every once in a while, if you're dealing with large tables with many columns, then you know that they have one column of the same name in common, but there might be other columns of the same name that you are not aware of. So the natural join is sometimes a little bit dangerous because every once in a while you will overlook that there is other column pairs than you intend, which also have the same name, and then they get automatically added to the join condition. So table 1 natural join, table 2 means I'm retrieving all the pairs of tuples from the first table and the second table, which have the same value in all columns that have the same name. I'm gonna go to show you some examples in a second. Finally, just so you know, you will sometimes find queries where somebody doesn't use the join keyword at all. That is also admissible if you write something from table 1, comma table 2, where join condition, the semantics is basically the same as if you had written table 1 join table 2 on join condition, right? Okay. All right, and now right. Now you should be able to see my screen again. So here, just to show you one example with the natural join. I see that somebody tried it and it gave an error, but I mean, in principle, if you do it like this, it should work. So here we have the students table and the enrollment table. They have one column of the same name. Let me show you this. Right, so the students table has the student ID, and the enrollment table also has the student ID. So if I do the natural join between the two, then that will automatically match them. And you can also do a natural join on multiple tables, as one of you is asking. That's a good question. So here, for instance, if I join with the courses table in addition, then here implicitly I'm adding a match condition for the course ID, which appears in courses, and it also appears in enrollment. Okay, so that is one way of writing this query. And as you see, I'm using the star notation in the select clause in order to retrieve all the columns of the result. Okay. All right, so those are a couple of alternatives about how you can formulate your SQL queries. I encourage you to play with it a little bit and try out different formulations. One last point, so far we have been using the select clause, and if you do this, then in principle you might get the same row in your result multiple times. Sometimes that's maybe even what you want. Often it's not what you want, and in order to eliminate duplicate result rows, which are kind of boring, you can also use the select distinct notation, and then the database management system will automatically eliminate all the duplicates. Now, so far, we have been generating results that consist of single rows. But if you're dealing with a lot of data, then often you rather want to learn something about aggregates. For instance, you want to count the rows that satisfy certain conditions. And SQL gives you a rich set of aggregates that you can use. Here you see the aggregates that are supported by default. You can count things, you can sum up things, you can average things, you can calculate minima, and you can calculate maxima. Now, we will see a concrete example in a second, just to give you a broad overview of the different aggregates that you can use. You use those aggregation functions typically in the select clause. So instead of getting all the different rows as a result, you would rather get the number of rows, for instance, or the maximum in one specific column. Those aggregates typically have some parameters. For instance, for summing or averaging, you need to indicate which column or which expression you want to sum or average over. One common annotation is if you want to simply count the number of result rows, then you typically use this count and star between parentheses. Sometimes we have already quickly discussed, and we will discuss this in more detail, that SQL allows you to replace unknown values in a certain row, in a certain column, by placeholders, which are called null values. Sometimes you want to count how many result rows you have for which the value in one specific column is known, and you can do this by writing this count, and then as parameter within parentheses you write the name of the column in which you need to have a value. You can also count the number of distinct values that appear in certain columns with the syntax, and this is just some of the most commonly used features. If you're interested and explore a bit, then you would find many more, but this is what you need in most cases, in my experience. This is how we can use that in this example query over here. This is nearly the same query as before, but now I actually don't want to retrieve a specific student names anymore. Now I just want to count how many students are enrolled. So in order to understand what the query does, we can again look at the from clause first, which hasn't changed. So here I'm still pairing up students with enrollment information and combining that with information about courses. Then I'm throwing away all the rows that are not about the CS4320 course. And now, and this has changed compared to before, finally, I simply count the number of remaining rows. And so the result of this query would be one single number, which is the number of people enrolled in CS4320. All right. Let me quickly check whether there's any questions in the chat. Yes. Oh, okay, and this is an interesting question, which already relates to performance. Question is, if we have really large tables, whether it makes a difference for performance, whether we use the count star syntax or the count in one specific column syntax. So the semantics of the two is slightly different. So you might not be able to use both of them interchangeably, but it's a valid question, and it depends a little bit on your database management system. So we will see that in more detail much later in this course. There's database systems which are efficient at retrieving data only from specific columns, and they could potentially benefit from that. There's other database management systems which are not efficient at retrieving data in specific columns separately, but they always retrieve all the information about one row in your table together, so they could benefit less. So it depends a little bit on the type of database system that we are talking about, but that is already a topic that we will discuss later in this course, but great question. All right. Now, here we are aggregating over the entire query result. We are counting all the rows in the result. Often in practice, you actually want to break down things. You want to calculate aggregates for different data subsets. And SQL also allows you a function in order to do that. It's called the group by clause. And there you essentially specify a list of columns that is used in order to partition your data. And then for each partition of your data, for each group, you are calculating, for instance, aggregates separately. So for instance, if I want to know how many students have been enrolled in CS 4320 and how many students have been enrolled in CS 5320, like the second listing of the course, then I could, in this case, issue two separate queries where once I filter to CS 4320 and once I filter to 5320. But it is, of course, more efficient if I can do that just with one single query. And that is the query that you see here. So the beginning is, again, I'm pairing students with enrollments and courses. Then I'm filtering to the rows that either concern 4320 or 5320. And now comes a new aspect, because now I'm partitioning the data based on the value in the course name. So I'm separating the rows for 4320 from the rows for 5320. And finally, I calculate a group-specific row count and display that together with the course name. And I could also leave out the condition in the where clause, and then I would get a breakdown for the enrollment numbers for all courses that are listed in my database. And of course, writing one query like that is much more efficient than to write separate aggregate queries for each specific course. All right. Now, you see here that in the select clause, I'm selecting the count, which is the count of the rows for each group. I'm also selecting the course name. That makes sense because I want to know which group a specific count refers to. But I have to be a little bit careful in general about what I put into the select clause if I'm using a group by query, because the result to a group by query must always contain one single row for each group, only one row per group. And that means that in the select clause, I can only ask for columns and aggregates and general expressions that have one value for each of the groups. For instance, here, for the same course, I could have multiple students enrolled. So for one specific group of results that share the same course name, I might still have different student names. So if I want to add the student name into my select clause, it would mean that I would get multiple result rows for each group, and that is not allowed according to the SQL standard. So here, if I put anything into the select clause which doesn't have one unique value per group, then the database management system will throw an error. Here, I am respecting that because the count is, of course, something which is unique for each group. And the course name is also unique for each group because that is precisely the column that I use in order to define the groups. So by definition, if two rows have different values in the course name column, then it would be in different groups. So within the same group, I only have one specific value in the group by column. All right, and here you see essentially what I just explained, laid out in a little bit more detail. First of all, in terms of evaluation order, as we have seen in this example, grouping is applied after we have filtered by the where clause. And what I also introduced in this example, you have this constraint that the result can only contain one row for each group, and that implies some restrictions on what you can put into the select clause once you're running group by queries. All right. Now, one last feature that I wanted to mention here. Sometimes in practice, you also want to put some condition on groups as opposed to conditions on single rows. So the where clause is where you put conditions on single rows, and that is evaluated before doing the grouping. Then after the grouping has happened, you might still want to have some condition for filtering out entire groups. You can do that using the having clause. For instance, here in this example, we have added a having clause in order to only show the results for those courses where we have a count of at least 100, which incidentally is the case for those courses here. And then in your query result, you're only shown those groups which satisfy those conditions. So this is it for some first intro to SQL queries. We're going to discuss some more advanced features next time. So I recommend you to revise the material that we have seen today, and also to experiment a little bit. So we have seen different ways in which you can experiment, installing Postgres or using this public website, for instance. You might either create a database yourself using the commands we have seen last time, or you might download some data set from Kaggle, for instance, which matches your interest, and then you load it into a database and experiment a little bit with it. So please explore a little bit with those queries. And if you find out something interesting about the data set, then please feel free to share your insight and the associated SQL query and data set on Piazza, so others might also benefit from that. All right, good. Then have a great day, and see you on Wednesday. All right, let's get started. Hello, everyone. Good morning. So today we are still discussing about the interface to a database management system. The relevant chapters are still number 3 and 5 in the Ramakrishnan and Gehrke book. So in the last lecture, we have seen a couple of ways how we can analyze data in our database via SQL queries. Quickly fix that. Yes. So, so today we're going to see a couple of more advanced queries. But before we do this, a little reminder about what we have seen last time. Last time we have seen queries that correspond to the format that you see here. We are specifying data sources from which we want to use data in the from clause. Then we specify conditions that the result rows should satisfy in the where clause. Then we specify how we want to partition our data into groups in the group by clause. And in the having clause, we can specify conditions that those groups should satisfy. All right. And finally, in the select clause, we are specifying which are the columns that we want to see in our results. So many of those parts of the query are actually optional, but this is the things that we have seen in the last lecture. All right. Now, before we go any further, because we haven't seen many examples yet for this type of query, we're gonna do a little bit of data exploration. If you do data exploration, then you first of all want to have a data set. So one possibility to download such data sets is the Kaggle website, for instance. And if you look under the data tag, then here you have data sets about various topics. So I recommend you to perhaps choose one or two of them, download them, and run a couple of SQL queries over them to get a hang of it, which is what we're about to do now. All right. And here specifically, since we want to load those files into a database, we can, for instance, restrict things to comma-separated value files that we can easily import into our data set. And it seems to be a slight problem with the interface here. Okay. All right. Now, I spotted so just before the lecture, I spotted a data set that I wanted to use for this demonstration. And here it is. That is a data set about video game sales. And we're going to use it in order to run a couple of simple queries over it. So let's first of all download the corresponding data. All right, we have downloaded it. And now I'm copying that data. Okay. Here you can see my console. And the data set that we are looking at, it looks like you see here. So we basically, we have values separated by commata. The first row of the data set that you see here, that is essentially the headers of the different columns. And after that, you have the associated data rows. So I just want to guide you through the analysis of one simple data set. So after we downloaded it, we want to create a database in order to import the data. So for instance, we can create this database over here. Now we log into the database. And so the first thing that we would do in order to analyze such a data set is to create a table in order to import the data. And we have already seen the command for that. So let's create this table over here. We have the columns that we want in the table essentially given in this file over here. So for instance, here, we first of all have a sales rank, which is apparently of type integer. Then we have a game name, which is of type text, it seems. There's the platform of type text, the year of type integer, game genre of type text, the publisher. Then first sales column, which seems to be of type numeric. Sales in the EU, this is in millions of units, by the way. That is also numeric. Sales in Japan. All right, and now we have created this table into which we want to import the data, and we have already seen the command for that. So if I want to import the data from a file, I simply write this copy command with the name of the table and then the name of the file, which is vgsales.csv. Now we are telling the database that here we want to import a CSV file. And we tell database that values are separated by commata. It could be a different character. And what you also often want to specify is how those null values that we will talk more about today. Null value essentially means a value that is unspecified, and you need to know how those null values are specified, and then you need to tell the database about it. And I believe in this data set, it should be one null value should be represented as n and a. And also here, we have one header row, and that is also important for the database management system to know. So I'm writing that here. And now let's load that data into the table. And I think maybe the way in which null values are represented, it might be this way around with the backslash. Let me quickly check that. All right. All right. So that was the right representation for the null values. I got it wrong. Now we have loaded the data. The database management system tells us that we have loaded about 17,000 rows. And if we want to, first of all, inspect what we have just loaded, we would write something like select all columns from that table and loading all the rows that can be a little bit too much data. So one small new feature that I wanted to introduce today, that is the limit clause, and that works essentially just by specifying how many rows you want to show in the result of a query. So if I write this, then I get a much more reasonable output, and on first view, that looks okay. Let me quickly increase the size of this window a little bit, then it becomes easier to see. So, all right, so this seems to be the data that I wanted to load, everything fine. All right, and now the last time we have seen different queries for aggregation and grouping and so on. So now I can perhaps apply some of that to this data set over here. Perhaps the first thing that I might be generally interested in is how many of those games people sell in total. And I could express this as a query where I'm summing over the global sales of those games. And the data source is, of course, still the vGames table. Now, if I do this, then I find that in total, about 9 billion units are sold here. That is interesting, but perhaps I want to make it a little bit more precise. I want to break down those sales into different categories. And you can do this exactly with the group by query that we have seen last time. So perhaps what I want to do here is that I group by the genre in order to see which types of games sell better than others. And if I do this, then that's not going to be very useful here. If I do this, then I essentially just would get the numbers here, but I wouldn't get which genres those numbers are associated with. So what I probably want to do is that I also put the genre into the select clause here. All right, and here I have the different categories of games with the number of units sold in millions. And yeah, it seems that certain categories of games, they are significantly more popular than others. In particular, sports and action games seems to be quite popular. All right. Now, another thing that I could do is to group those games, for instance, by the platform for which they have been produced. And I want to know how many units have been sold for different platforms. So I can do this like you see here. Perhaps this is a little bit more data than I actually wanted. I see there's like data for 31 platforms. And maybe I want to focus more on the important ones. And here there is a great question in the chat. Somebody is proposing to order them. And you can absolutely do this. And that is a second feature that I wanted to introduce today. Let me do this in a second. For the moment, I wanted to propose a different solution to how I can reduce the number of platforms for which I retrieve data. For instance, here, I could introduce account statement and only retrieve data for those platforms where the number of titles is above a certain threshold. Now, here essentially, since we use the group by clause, this query is grouping data by the platform. So one group is defined by one specific platform. And if I want to narrow it down to platforms that have certain properties, that is a condition on the groups. So I must put that condition into the having clause. And now let's experiment a little bit. For instance, if I set this threshold, that might be too restrictive, but here essentially I narrow it down to platforms for which we have at least over 100 titles. All right, and now this narrows it down already quite a bit from 31 to 20 rows. Maybe we can narrow it down even further to only the most common platforms. Yes, and now we have only relatively common platforms. So that is how I can narrow down things, but a different possibility would be to order things. So instead of using this conditional to prune out groups associated with platforms that are less commonly used, I could also say that I simply order the results by the number of sales, for instance. And then I would know where in the result to look for those platforms that sell more titles. So here, for instance, I could also write order by count, and I want to order in ascending order. So I'm putting this ask abbreviation here. So if you do this, then as you see here, I tend to get the platforms that have more titles and are also associated with more sales, more units sold, rather later in the query. And if I want to get them first instead, then I can use the desk keyword instead. So here, now we are starting with those platforms for which I tend to have more titles. And as opposed to the count, here I could also use the sum again. And now I will get first those platforms for which I have lots of global sales. And here another proposition is whether it wouldn't be better to first sort and then to limit the number of output rows, right? You can also do this, and that works perfectly. That is a good suggestion. So here I'm first sorting, and then later I'm narrowing it down to only the most common platforms. So the advantage of this one over the query with the having clause that I used before is that with the having clause, I have to decide what kind of threshold I should set. And a priori, I might not know what makes a good threshold. So if I want to narrow it down to a fixed number of rows at most, then this type of query here, where I first sort by something and then I limit to something, that is probably preferable. All right. And here there's a couple of questions. And so the limit clause is applied at the very end. That was a question here. And people have also posted a link to the data set. Thanks. That is the correct one. And the count ordering is indeed the number of rows. Okay, good. So this is just a couple of simple queries that I can run on this data set. And I just wanted to show you the complete cycle from how we download the data set to how we import it, and then how we can run some simple analysis queries over it. So I encourage you to do that as well, perhaps not with this data set, but with a different one. There's lots of choice on Kaggle or on similar websites. All right. Now you should be able to see my slides again. All right. So we have started with a reminder for the type of queries that we have seen last time. And we have applied that. We have also added 2 new features. Now the first feature that we added is the order by clause, and then we added the limit clause. I have already demonstrated how that works, but here is a little bit more details about the syntax. So the order by clause, and as you see, it comes after the having clause, if you have any. The order by clause allows you to specify a list of order items. And each order item consists of a column according to which you want to sort, and a sorting direction, which can be ascending or descending. Now, this statement ensures that the output of your query is sorted by those columns that you specify here. So in order to determine the sorting order between different result rows, the database management system, we first look at the first order item that appears in your order by clause. And then for those rows which have the same value in the first order by item, it will look at the second order by item and sort by that. And if it also has the same value there, then it will look at the third one and so on. So the priority for sorting is on the items that appear earlier in your order by clause. And there was some question about in which order things are applied in general. For the order by clause, it is applied after the where condition, for instance, is evaluated, and also after grouping has happened. And that is important because if you have a group by query, then into the order by clause, you can only put columns that are guaranteed to have the same value for any group. So basically, you can only use columns in the order by clause where all rows in the same group are guaranteed to have the same value. And that means that as long as we're talking about columns, those essentially must be columns that appear also in the group by clause, because if a column appears in a group by clause, it is guaranteed that all rows in a group have the same value for that column, because that column is used in order to define groups. So this is a bit similar to the restrictions that we had for the select clause. Once we have a group by query, then there's also certain constraints on what you can put into the select clause. You can also only put columns into the select clause, for instance, that are guaranteed to have the same value for all rows within a group. And that also means that in practice, you want to restrict it to columns that appear in the group by clause. All right. Now the limit operator, that one is pretty intuitive. I simply give the database system the maximum number of result rows, and then this limit clause is applied at the very end of query evaluation. All right. Now in the following, we're gonna discuss more and more advanced features of SQL queries. First of all, I want to discuss a little bit more about null values. Now, we have already quickly mentioned null values a couple of times. A null value in SQL simply means a value that is currently unspecified, for instance, because it is unknown. Now, those null values, for instance, influence the way in which SQL evaluates Boolean conditions. Typically, you would think of those Boolean conditions as evaluating either to true or false. But if one of those conditions contains a null value, then the overall result of the expression could also be unknown. And we will see a couple of more concrete examples for that in the following. Now, this is how you can essentially check for the evaluation result of one of those Boolean expressions. You can check whether it is true or whether it is false. Careful, if you want to check whether the evaluation result is null, whether the evaluation result is unknown, you cannot simply write equal to null, but you need to write is null in order to check for that. And then if you have any rows in your data that where the condition in the where clause, for instance, evaluates to null as opposed to true, then those rows will not be contained in your query result. Now, let's make a couple of concrete examples. I encourage you to try out at least some of those examples, either in your local Postgres installation or using the website that I have shown you last time, which doesn't require any local setup. Perhaps the first one, we can do it together. If we have a query of the form that you see here, where we want to know whether 3 equals null. Does anyone have propositions for what the result of this query could be? Syntactic error, okay. That would be one possibility. It's a little bit more permissive than that, actually. Okay, there's different propositions, null, empty, okay. So does anyone to explain in the chat, please, why they think, for instance, that the result could be a syntactic error? Or why the result could be null, for instance? Okay, perhaps typing out an explanation like that, that takes a little bit more time. So let me resolve that. So the correct answer here would actually be null. And I expected that perhaps some people write false as a proposition, but that has not happened. I guess one could at first view think that the result here could be false because I have an equality condition and I have different things on the left side of it and on the right side of it. Now the problem is this. Those null values represent an unknown value. So they are placeholders, so to speak. That means if I write a 3 equals null, it essentially asks whether 3 is equal to some unspecified placeholder. But the placeholder, as it is unspecified, we cannot be 100% sure whether it isn't 3 by coincidence. So here I'm essentially asking whether 3 equals to some unknown value, and whether that is the case depends on that unknown value. And since we cannot decide whether this is true or false, the answer to this query would indeed be null. Okay, and there's a couple of other examples here. Yeah, and somebody is posting how that looks like in Postgres into the chat. So those null values in Postgres, they're just represented as empty spaces. So here you have one row, but you don't see any content, and that's because this row only contains one null values. So null isn't a value like in other languages like Java. So there is some differences between Java null values and SQL null values. I mean, in particular, you couldn't perform certain operations with Java null values because at some point you might get an exception, null pointer exception from the Java system. So here in SQL, in principle, you can use null values wherever you can use other values as well. The only thing is that if you have a null value somewhere, it might mean that if the null value is contained within one expression, it might make the result of the entire expression unknown, meaning null in the end as well. And null is like false in this case, so that it depends on which case you are referring to. In some cases, so if you are referring to the semantics, if you have a null value as a result in the where clause for one specific row, then I fully agree having a null there is treated in the same way as if the result had been false. So if the entire condition in the where clause evaluates to null, then the corresponding row will not be included into the query result. All right. So, okay. So now maybe you had a little bit of time to try out some of those examples. I believe it is relatively quick to try because you don't need to type a lot. And yes, so we have already discussed about the first one. The second one is also null as a result, because we are essentially asking, is one first unknown value the same as one second unknown value? And of course, it depends on the unknown values. The third query, null is null, that is always true, because is null is checking whether something is unknown. And in this case, it is indeed unknown. The next query is the opposite of that, and therefore false. Now, perhaps the last two queries are still interesting. We have true or null. And in this expression, we do have a null value appearing. However, an OR expression is true as soon as at least one of the components is true. And in this case, one of the components definitely is true. Therefore, the end result does not really depend on the unknown value. And therefore, the end result of this should also be true. On the other side, for the last query, we have true and null. That means if the unknown value is also true, it makes the entire expression true. But if the unknown value is false, it makes the entire expression false. So the result depends on the unknown value, and therefore the result is also unknown. So this is what is called SQL's ternary logic, because all logical expressions can have as three result values: true, false, and unknown. And the question is, what should select null? Is null do if the predicate is true? This query, frankly, is not very useful, admittedly. So this is just for the sake of an example. In practice, this query, it's not interesting. It essentially has a constant result, right? And by the way, also note that here we are not using any data source in order to calculate the result of our query. So we don't have a from clause. Depending on the database management system, some of them disallow that. You always need a from clause. But in Postgres, you can write queries like that that do not depend on any data in your database, but just evaluate constant expressions. All right. Now, and the is keyword, trick question here still. So the is keyword, it is more precisely the is null expression. So that essentially checks whether the expression on the left-hand side of it evaluates to null or not. And it is true only if the left-hand expression evaluates to null. So null equals null is null, but null is null, that is true. All right. So it is basically not only the single is keyword, but it is null. That is a fixed command. Both words together. All right. So Now that we have discussed in more detail about null values, we can discuss more about some extended variants of the join. So far, we have been looking at joins that essentially retrieve pairs of rows from two tables that match together, meaning that they satisfy some kind of join conditions. For instance, we have seen the example where I'm pairing up the students with the enrollment information for the courses that they are enrolled in, and I'm always matching together those rows which have the same student ID. Now, one problem with that is that it eliminates rows in a table which don't find any matches in the other table. Those rows will not appear in the join result. So if I'm, for instance, joining students with enrollment information, then a student who hasn't enrolled into any courses yet will not appear in the join result at all. And this is not what I want in some cases. Perhaps I want to, for instance, encourage students to enroll for courses who have not enrolled yet. But in order to do that, I first of all need to make sure that those students remain in the join result such that I can see that they haven't enrolled in any courses yet. And SQL offers you some specialized syntax in order to make sure that the result of a join keeps all the rows that appear in the input tables, even those rows which do not have any matching rows in the other table. And that is called an outer join. Now, for instance, for students and enrollment, the result relation of the join between students and enrollment contains columns for the student ID, for instance, but also columns for the course ID, for the enrollment. And the question is, if we want to keep those students without enrollments in our join result, what should we fill in as values for the course ID column? And this is where null values come into play, because those outer joins will fill in the values for rows without matching rows in the other tables. They will fill in those missing values with null values again. So if you have those students who haven't enrolled into any courses yet, then the course ID in the corresponding join result will be set to the null value. This is the syntax that you can use here. You can write in the from clause of the query some first table, left outer join, some second table on some join condition, and that is guaranteed to keep all the rows of the table on the left side of this join. There's also the complement, the right outer join, where we say that all the rows on the right-hand side of the table are kept in the join result. And if you're interested in keeping the values, the rows for both tables, you can also use the so-called full outer join. And very quickly, I'm gonna show that to you. So if we have, for instance, so if we log into the university database where we have those tables with students, courses, and enrollment, then we can, for instance, select all columns from the students, left outer join with the enrollment information. And here I should still add the join condition, which is on the student ID. All right. And here you see the result of this join. Now here, for instance, a student Bob seems not to be enrolled in any courses. That is why the course ID is left empty in Postgres, and that always indicates a null value. And here, by the way, I had also inserted before a student with unspecified student name. So that's why here we have the student ID for that student, but the name has not been assigned yet, and also that student has not been enrolled in any courses. That is why we have empty fields here as well. So this is how the result to an outer join looks like in Postgres. Now back to the slides here. So so let's also see a little example here in the slides. One thing that I might want to do, for instance, I mean, especially, for instance, if I want to remind students who have not enrolled in any courses yet, what I want to do is perhaps to count the number of enrollments for each student. And in the following, we will see how we can do that with an outer join. So here for the moment, we are using the same database that we have used in the previous lectures of students with enrollment information and courses. And as you see, for the moment, we're not using any outer join, we are using a standard join. And that means that students without any enrollment would be filtered out by this query, which is not what we want. So already we probably want to replace this join by a left outer join that is guaranteed to keep information about each student. But now the problem is that we are currently using a count statement, and I just see that some group by statement in this query has been left. So here I actually want to add a group by statement for the corresponding query. So that unfortunately has dropped. So here we want to group by the student name in order to count the number of enrollments for each student. And the problem that we still have here is that for the moment, we are counting the number of result rows. That means for those students for which we don't find any matching enrollment information, we will still count one result row for those students, which is not what we want, because for those students, we want to count 0 enrollments. So the last thing that we need to do in order to make this work is that we replace the count star, which counts any result row, by count CID, which only counts those result rows that have a non-null, meaning a noun value, in the course ID column. So if a student doesn't have any associated enrollment information, then after the outer join, that student will have null values in the course ID column. And if we use this counting variant, then those rows with null value for the course ID will not get counted. So I will get a count of 0 for those students who have no enrollments yet. All right. So this is some useful join syntax that in practice, every once in a while, you might need some of that. I'm also going to post the corrected example on Piazza. Now, in the following, we're going to look at a little bit more advanced SQL features. And one powerful feature of SQL is that you can write queries which combine multiple other queries together. So you can essentially write a composite queries that essentially combine multiple smaller SQL queries in one way or in another one. And the easiest way probably of doing that is with the SQL set operations. So if you have results of queries, then for instance, sometimes you might want to take a union of the result of 2 queries. And with SQL, you can do this using the union or union all keywords. And essentially here, in this specification, query 1 and query 2 refers to queries, for instance, like the ones that we have seen so far, but then you can compose them using the union keyword, for instance, into a larger query. And the result of that query is essentially the union of the results of the two contained queries. What is important here is that those two queries, query 1 and query 2, they must be compatible, meaning that their results have the same structure. So it has to have the same number of columns and also the same column types. There's a couple of different variants. If you use the union a keyword, for instance, then SQL will automatically eliminate duplicate rows that appear in the union result. If you use union all, for instance, then it will keep any duplicate rows. So you might have the same result row multiple times. You also have operations for intersecting the results of queries and for taking the set difference between two query results. But in all of those cases, you must be careful because the result structure of those different queries that you are combining with the set operations must be compatible. All right. And a priori, there's a question about whether the order will be kept when using a union. So in general, without putting the order by clause, you are not guaranteed anything about the result order. So if you want a specific result order, then you can still use the order by clause. And by the way, some of those operations here, some of those set operations, they are, for instance, not supported in some other common database systems, but if you try it with SQL or with the website that I have shown, then you will be able to run those operations. All right. Now, another thing that we will start discussing today and finish next time probably is that we can essentially not only combine queries with set operations, but we can essentially use so-called nested query in many other parts of a query as well. For instance, so far we have seen that in the from clause of a query, we can refer to tables that appear in your database. But instead of that, you could also write a new query inside of the from clause. And we will see some examples on that. Also, for instance, you might use queries as part of a condition in the where clause and so on and so forth. So in general, since queries take SQL relations as input and produce SQL relations as output, you can compose them together in various interesting ways. Now, if we have the situation that we have one large query which is containing a smaller query, so to speak, then we also call that a contained query the subquery as opposed to the containing query. It has different variants of that containment. In the simplest case, the contained subquery is essentially self-contained. So you could run this query independently and it would work with your database management system. That is what we call an uncorrelated subquery. But for more complex expressions, you can actually make the subquery refer to elements outside, to elements of the containing query. And those cases are a little bit more difficult to understand. That is what we call correlated subqueries. Now, in the following, we're going to first discuss about the uncorrelated subqueries, which are a little bit easier to understand. And we start with a rather trivial and frankly not very useful example here. So we simply want to select the names of all students. Then I can, of course, simply use the students table in the from clause. But just to illustrate the principle of subqueries, I can also put a new subquery into the from clause, as you see here. So here, essentially, I have one entry in the from clause which corresponds to a subquery. It's an entire query right there. And what it does is essentially just selecting the student names from the students. And then the result of that subquery is named SQ for a subquery. And as you see in the select clause of the query, for instance, I can refer to the name for the subquery that I have just introduced. So that is important. Postgres actually will force you to assign names for subqueries that appear in the from clause, because typically if you use tables in the from clause, then you always have a name, and I can use that name in order to refer to specific elements from other parts of the query. But if I write a new subquery, then a priori it doesn't have a name yet, so Postgres forces you to specify a corresponding name. And so how that is handled depends a little bit on the database management system. In each case, this query is not yet very interesting, admittedly. So let's see something a little bit more useful. And here we have a subquery in the where clause, for instance. And what we are doing here is that we are selecting the names of students where the GPA is greater or equal to the maximum GPA among all students. So here we are selecting the students with the highest GPA. And here we essentially use one subquery in order to calculate the largest GPA over all students with the maximum aggregation function. And then we are using the result of that query within a condition in the where clause. And here the question is whether the result of that query would not be just one student. That depends actually, because multiple students might have the same GPA. And very good, I see somebody is giving that same reply. So in general, by the way, so I think this is great. I see that often there's some discussions in the chat. I want to encourage that. I often see great replies to the answers from other students. So please feel free to post not only questions, but also replies to the questions of your peers in the chat. I think this is working very well. All right. So this was the first example for subqueries. And here things are already becoming a little bit more useful. So today I wanted to take a little bit of time to show you how to apply SQL in order to actually analyze, do at least some simple analysis of a data set in practice, the full cycle basically. I encourage you to try it out yourself. So I mean, SQL, it's something which is a little bit like a programming language in that it is much easier to understand it if you are experimenting with it yourself. So I encourage you to do that. Now, the next time we're going to see a little bit more advanced features of SQL, in particular when it comes to subqueries. And then we are going to start with a new chapter. We're going to start looking at how the database management system internally processes your queries. All right? Thank you, and have a nice day. Good. So, hello, everyone. Today, we are first going to talk a little bit more about SQL, and probably we will still have enough time to start with a new topic, which is about looking at how your data is actually stored on the computer. Now, last time we have seen one very important feature of SQL, which is that you can essentially nest SQL queries, so-called subqueries, within a larger surrounding query. So you can use a SQL query as part of a SQL query, basically. And the last time we've seen a couple of very simple examples for that. Here you see one of them. Here you're selecting the student names from the students table where the GPA is greater or equal to the maximum GPA across all students. And in order to calculate this maximum GPA, we are actually using a subquery. So here we have one query marked up in red here, which selects the maximum GPA from the students table. And then the result of that query is used as an operand within the where condition of the surrounding query. So that is one possible use case for subqueries. We can also use them in other parts of a query. All right. Now, in the last example, we have seen one possibility to include a subquery into a larger query. There's many more ways in which you can do that. Here you see a couple of more ways in order to integrate subqueries into the where condition or into conditions in general of your query. And one operation that you commonly use in the context of subqueries, that is this exists expression here, and that essentially checks whether the result of a subquery is empty. And we'll also see some more examples on that. So that is commonly used. Or for instance, you could check whether one specific value is within the result values produced by a subquery, and you can do this using the in keyword that we have already seen, but so far we have seen it for checking whether one value is within a list of constant values, and here we are using it to check whether one value is within the results returned by a subquery. Another thing that you can use is the all and any keywords. And here essentially you use that in order to test whether some condition is satisfied either for all result rows of a subquery or for any, meaning for at least some of them. And in that case, the corresponding condition returns true. Let's perhaps see one more example for the last possibility here. What we are doing here is we are selecting the student name from the students where GPA is greater or equal all result rows from this subquery that selects GPAs from students. And can anyone tell me in the chat what you believe that this query is doing? Anyone, any ideas? Yeah, exactly. So here I have multiple propositions. Yeah, so multiple times the same propositions actually. So that is correct. So here we are again essentially checking for those students where the GPA is greater or equal the GPA of all students. So in the end, that comes down to searching for the students with the maximum GPA. Yeah. All right. And one last question is whether the result of this, I assume it means the result of the where expression, whether that can be false or null. So here, I mean, it could be it could be null if we have, for instance, some null values for the GPA. If there's some students where I don't know the GPA, I cannot verify whether one specific student has the highest GPA because I don't know the GPA of some of the other students, right? And I mean, for this to be false, that is the case if there is another student who has a higher GPA than the currently examined student. So you can imagine that here we are iterating over the students that are stored in a student table. We are picking one, then we check whether this condition that student's GPA is greater or equal the list of all GPAs from all students for each of them. And if that is the case, I'm going to include it into the result. If that is not the case, I'm not going to include it into the query result. Right? So we can essentially imagine that we have a for loop pretty much where we iterate over the students, and then the subquery would essentially correspond to another for loop. So we have like essentially two nested for loops. Both of them are iterating over the students. Yeah? Okay. All right. Now, those are a couple of examples for subqueries. Essentially, you just evaluate the subqueries first for the examples that we have seen, and then you get some kind of return value. Then you insert that return value into the surrounding query. Now, what we have seen so far is what we call uncorrelated subqueries. And that means essentially that you could run the subquery all by itself and the database management system would not complain. Correlated subqueries are a little bit more difficult. This is why we are doing them now, and we started with the other ones. For correlated subqueries, the nested query, the subquery, is not independent from the surrounding query. So here the subquery would essentially reference some elements that appear in the surrounding query, which means that a subquery all by itself is not viable because it would include references to something that only exists in the outer query, right? And so here, by the way, I see some interesting discussion going on, and I encourage you to generally answer the questions of your classmates also in the chat. And just because I see that here, let me say one last thing about the evaluation of this subquery that I have shown here. I told you that you can imagine that this is evaluated by two nested for loops. And here, one of the questions is, wouldn't that be inefficient? And I actually agree with that. So if I say that you could evaluate it with two nested for loops, I just mean conceptually, this is how you can imagine what the query result is gonna be. You can essentially, in order to understand what the result of this query is, you can imagine that we would have two nested for loops. But internally, the database management system is probably doing something more efficient, or could be doing something more efficient. And the way in which you write your query generally is independent of how the database management system evaluates your query. So the two for loops, this is not necessarily what's happening inside, but this is what you can imagine is happening in order to understand what the result of this query is. Okay, very good points here in the chat. All right, and now we are switching to correlated subqueries which reference something outside of the subquery and in the surrounding query. Now, let's see a first example. Quickly need to move the chat so I can see the example fully. All right. So here we are again selecting the student names from the students table, and we assign the alias S1 to it in the outer query. And the condition to be included in the result is that the S1.GPA must be greater or equal to all. And here comes a select over students again. This time we assign a different alias S2. And we require that S1.SName equals S2.SName. So can anyone first of all tell me why this is a correlated subquery? Looks kind of similar to the ones that we have seen already, so what makes this one specific? Yes, very good. And here there's the reference to, in particular, S2. So within the, in particular, S1. So here within the subquery, we are referencing table alias S2 and table alias S1. Now, table alias S2 is not particularly exciting because that is defined within the same subquery. Table alias S1, on the other hand, that one is actually not defined within the subquery, but it is defined outside. It is defined in the outer query. That means if you take the subquery select s2.gpa from students s2, where s1.sname equals s2.sname. That's subquery marked in red. And you run it all by itself in a database management system. You will actually not be able to do that because the database system will complain to you that there is some undefined identifier S1. And that's why it is a correlated subquery. So yes, so this is why it is a correlated subquery. And can anyone guess as to what this query is actually doing? So strictly speaking, we have not yet discussed in detail how to evaluate those correlated subqueries, but maybe anyone has a hunch about what this could be. Very good. And here I see the right solution popping up. So what it does is actually the following. So I'm again gonna tell you how you can imagine that this query is evaluated, even though internally inside the database system, it might be evaluated in a more efficient manner. But what you can imagine here is that we are iterating in the outer query, we're iterating over the students again. And for each of those students that we are iterating over in the outer loop, so to speak, we are iterating over the students in an inner loop. And within that inner loop, we are only considering students which have the same name as the currently selected student in the outer loop. And then we check whether for all of those students which have the same name as the students in the outer loop, the GPA from the outer loop student is greater or equal to the GPA of the inner loop student. S1 and S2 basically, those are like two iterator variables. Okay, and because of that, as suggested here by one of your peers, we do indeed retain those students, the name of students which have the maximum GPA among all the students with the same name. So that's maybe a little bit of an artificial example, but of course, in principle, you can have students with the same name, even though not the same net ID. And here we are keeping the maximum GPA student among all groups of students with the same name. One thing that I used here, by the way, besides introducing correlated subqueries, I have one query where the same table appears multiple times. We have already seen that before, but just to point your attention towards that. So in general, you can have the same table appear multiple times in a query, either within different subqueries or even like within the same query. But what you often want to do is to assign different aliases to that same table. So here I have the students table, once appearing with S1 and once appearing with S2. And one interesting question that I see here, whether this query would be possible without two aliases to students. And here, I mean, if you want to, I mean, you could probably reformulate the query in quite a different way. And maybe you could get around that. But I mean, definitely as long as you stay with this structure of the query, here you need to compare students of the same name. So you need to compare two students. And in order to distinguish between those two students, you need to use an alias here. Yes, exactly. So that's why I'm saying that if you keep the same structure, then you need to do this. It would also be ways, for instance, to group by the names, get the maximum GPA in each group. That is a great suggestion. And then joining that with the, and then joining that in order to get the student associated with the maximum GPA within each of those student groups, or you could, for instance, use a subquery in the from clause, and then you would have to introduce an alias for that subquery, but strictly speaking, not for the table alone. Okay, so there's many ways of writing this, but you need some way of correlating different students in order to make this comparison. All right. So the general principle, in order to imagine how the result of those correlated subqueries is generated, I find it quite convenient to imagine nested loops being evaluated, even though that might be inefficient and not what the database management system is doing in the background, but it can help to imagine that. And then you would generally iterate over the rows in some outer containing query. And for a fixed row, you would evaluate the inner query. Now here, the result of the inner query might depend on which row is currently selected in the outer query. That is why, at least conceptually, we would have to re-evaluate the correlated subquery for each different row in the outer query. And then if the where condition in the outer query uses a subquery, then finally you would decide for the currently selected row in the outer query whether to include it into the result set or not. Now, here, for instance, we have another example. So here again, we are comparing students, and we use a correlated subquery. So here we, in the outer loop, iterate over the students again. And then for each fixed student in the outer loop, we check whether the result of this correlated subquery is non-empty. That is what the exists keyword is doing. There exists some result. And for a fixed student in the outer loop, in the inner query, I'm iterating over the students again. And I check whether there is another student who has a higher GPA. Now, and if such a student exists, then the outer loop student will be included into the result set. So what this is basically doing is that here, this time, we're selecting the names of all the students except for the students with the highest GPA, because for each student we test whether there's another student with a higher GPA, right? So those are a couple of simple correlated subqueries that you see here. Now, take a look at this one. Now, what I'm exploiting here is the fact that actually your subqueries can also have subqueries. So you can have multiple levels of nesting. And here, in this query, we are first iterating over courses. Then next, we are iterating over students. Then next, we are iterating over enrollments. Does anyone have an idea what this query is doing? Any propositions? Okay, first proposition, find courses that have no students enrolled in them. Find the courses that have no enrollment. Okay, other propositions? In order to break that down, so that is perhaps the most complex query we have seen so far. Okay, so let's break it down a bit. So let's make it simpler by imagining that we have already fixed one course in the outermost loop. Now, can anyone tell me what the result of this select star from students and so on, what the result of this query is gonna be? So we have fixed the course, and now we have this query select star from students S, where not exists select star from enrollment E, where course ID matches and student ID matches. Find courses with at least one student enrolled. Okay, that is all right. This is the right direction here. Okay, I'm gonna give it a second because I think it's a nice example and it makes sense to think about it for a few seconds. Okay, good propositions here. Okay, I'm gonna resolve it in a minute. Just okay, people are agreeing. Is that agreeing to the solution, perhaps? Okay. All right, so I give it one more minute and just think about it a little bit more. And clearly, as the exists keyword tests whether the result of a subquery is non-empty. Not exists essentially tests whether the result of a subquery is empty. And it is true only in that case. All right, so let's have a look at this. So let's maybe start with the innermost subquery. So what we're doing here is that we're looking at the enrollment information which links students to the courses that they are enrolled in. Okay, and the student as well as the course, they have been fixed in the outer queries currently. So here I'm essentially checking whether some enrollment information exists for the currently selected course and for the currently selected student. Now, this innermost subquery is contained within a not exists clause in that middle query, which selects from the students table, right? And so basically here in that middle query, I am producing students which are not enrolled in a specific course because the enrollment information for this student with the currently selected course in the outer query is empty. Okay, so here let me maybe mark that here. So here this query essentially looks for students that are not enrolled in the currently selected course. And now I'm looking for courses where the result of this subquery is empty. So I'm essentially looking for courses where no student is not enrolled. So that formulated differently means that here I'm looking for the students, for the courses where all the students are enrolled, which most likely is empty, the result of that query, but that is what the query is looking for. Here I'm fixing a course. Then I'm looking for students which are not enrolled in that course. And then I'm checking whether that list is empty, so no student is not enrolled in the course. And if so, I'm including the name of this course into the result set. That's what this query is doing. All right. So that is what we will see about SQL. Now, this is probably the most difficult query that we have seen in the course, and I encourage you to think a little bit more about it, and to make sure that you understand what's going on there, and also perhaps to experiment a little bit with some with some nested queries yourself. For instance, in the data set that we have recently downloaded, or in some other data set of your choosing. We have seen a couple of examples, but in the end, to really get the hang of it, you probably want to write some queries like this yourself. And I encourage you to do that. So now we have seen essentially what is the interface of database management systems. And now we will see in the following a little bit more of what is going on inside of the database management system. So first of all, we're going to talk more about how the data of your database management system is organized and stored. So here we are at the lower part of this diagram that I have introduced in the first lecture. The relevant chapters in the Ramakrishnan and Gehrke book, those are chapters 7 and 8 in particular. And what we are going to do in the following is that we are first going to discuss about the hardware on which data is stored. And then we're going to discuss a little bit about the format according to which data is stored on that hardware. So in the following, we're going to first discuss about the hardware on which your data is stored. And the properties of that hardware will motivate certain design decisions in the database management system. Now, data on your computer is generally stored on different locations, and typically those possible locations are represented as this memory hierarchy that you see here. It's often represented in this pyramid shape in order to illustrate that the capacity of the storage layers decreases once you go up that pyramid. So typically the storage layers towards the upper part of this pyramid, they have faster access times, but they also have less capacity, so you can store less data there. Another important distinction between the different layers of the memory hierarchy is that some of them are volatile, meaning that data there is erased once your computer switches off, while others are permanent, meaning that even if your server switches off, then they will still keep the data stored. And at least traditionally, database management systems, they consider, for instance, updates to your data only as secure once those updates reach stable storage. At the very top of that pyramid, so to speak, sits the CPU, which is doing the actual processing. So what needs to happen in order to do any useful computation over the data is that you move the data through the memory hierarchy up to the processor registers where the processor can access it. Now, in the following, we're going to go through those different layers of the memory hierarchy and get a sense a little bit for what those storage devices look like and what kind of properties they are featuring. All right, so at the very bottom of that memory hierarchy, we have typically those tape storage devices. And you see one of them in the right upper corner. Now, those tape storage devices, they work according to the same principle basically as those music tapes that are not very common anymore, but probably you have seen one already. Those tapes generally store information. They store bits as a magnetic information on that tape. Now, once you have positioned your tape at the correct position, where the data you're interested where you are interested in is located at. In that case, you can get quite reasonable speeds for reading and writing data. It's not going to be fast, but it's not going to be terrible either. The problem is that it might take quite some time until you bring your tape into the position where the data you're interested in is located at. So that might take seconds, tens of seconds even, which in the context of data processing is completely awful, of course. But on the pro side, those tapes are extremely cheap. So I have put a couple of numbers here, and please take those numbers with a grain of salt, because they keep changing over time, and it also depends on which specific devices you are considering. But I think that those numbers, they give you some intuition for how the different layers of the memory hierarchy relate to each other. For that, the numbers are useful, but don't take them too serious either. So the nice thing about tape storage is that it is very cheap. You can store a lot of data for without paying too much money. And that's why it is quite popular for long-term archival storage. So also cloud providers like Google, for instance, they would use tape in order to store backups. So we are not going to discuss that much about tape storage, because the database management system typically assumes that you can access data faster than this. But if you're interested in reading up more, then here I have a link to a corresponding article in the slides. Now, the next higher level of the memory hierarchy, that is hard disk. And hard disk, that is a popular storage medium. And a large part of traditional database management systems, they have been designed under the assumption that the bulk of your data is actually stored on hard disk. Hard disk represents bits in a similar manner as the previous storage medium as magnetic information again, but this time we are writing this magnetic information on a round disk, such as the one that you see on the right upper side. So you see here there is indeed a round disk, or even multiple stacked disks in the middle of that hard disk. And in order to access data you're interested in, you have to do two things. So first of all, this disk containing the magnetic information, it is spinning with a very high frequency, thousands of spins per minute. And you are reading and writing data on that disk with so-called heads, for which you can choose the distance between the middle of that disk and the head. So you can move that head into one direction in order to access different parts of the disk. And as the disk is already spinning, once you have positioned your head properly, you just have to wait, essentially, until the data you're interested in comes rushing by as the disk turns, right? So once we have positioned those heads properly, then again, we can read data at reasonable speeds and write it at reasonable speeds. Again, one problem is that it can take a little bit of time to position that read-write head properly. It can take some tens of milliseconds, which is of course much faster than before, but still in the context of data processing, it is kind of long. So hard disk is not considered a very efficient high performance, at least in terms of speed, let's say, it's not considered the medium of choice. On the pro side, again, It is more expensive than tape, but it is still quite cheap. So that's why you might want to use it for less frequently accessed data. And indeed, traditional database management systems, they assume that you typically store the data that is not immediately used on hard disk. A little bit over the hard disks are those solid state drives which use a different technology to store bits using a small electric charges. They have a comparatively elevated price. Here, those numbers are already slightly outdated, but you see they are significantly higher than for a hard disk. You have in exchange a pretty fast access because you don't have any moving parts, you don't have any mechanical parts that you need to reposition, like the diskettes, for instance. And you can also at least read speeds at quite at elevated rates, let's say. One problem with those devices is that the number of write cycles that you can do is limited. They wear out, but people have been looking into techniques in order to at least partially overcome that, in order to, for instance, have some spare capacity in order to replace cells that fail because you had too many writes on them, and to try to partition the writing load equally on those devices. So we're not going to discuss that in too much detail, but just to give you some little overview of the pros and cons of that storage technology. Main memory. That is the next level of the memory hierarchy. And here we have a big jump in terms of access speed. Again, we are storing bits as small electric charges. And compared to the other storage media, main memory is quite expensive for storage, if you look at the price per gigabyte, for instance. But on the other side, you have some very fast access times. You can read and write data at a relatively high bandwidth. So this is a very significant difference to the storage media that we have seen before. So traditionally, main memory is used in order to hold data that you're immediately working with. And if you can afford it nowadays, more and more people are even able to fit entire databases into main memory. If you have hundreds of gigabytes or terabytes of main memory, that might be feasible. Of course, you have to pay a little bit for it. So there's a big jump in terms of access efficiency between hard disk in particular, also SSDs, and main memory. So in traditional database management system design, we are actually assuming that, the main overhead when it comes to data movements is for moving data from hard disk into main memory. And as we will see in much more detail later, therefore, we try to be efficient about when and what data we move from hard disk into main memory. So main memory and a hard disk, those are typically considered, one for storing the bulk of your data, one for storing the data that is immediately relevant, even if nowadays, more and more often you can fit significant parts of your database into main memory. Finally, we have the CPU caches, and they are typically organized as a hierarchy. So you have not only one cache, but you have L1, L2, and L3 caches. And from L1 to L3, typically, we increase the capacity, but access time increases as well. Now, clearly, those caches are very expensive per gigabyte, so we cannot make them all too large. But on the pro side, they offer essentially near instantaneous access and very high bandwidth. So that data is typically currently being used for some operation, or it has at least been used recently, or it is close to data that has been used recently. So you cannot fit that much data into those caches, but if you can fit data into it, then you have extremely high access times, and that makes it very efficient. Now, the final layer of the memory hierarchy, that would be the registers. But I mean, the registers, they are basically what the processor can access immediately. So I'm not gonna discuss this in detail. So now we have seen a little overview of the different storage layers in your database management system. But we want to discuss about database management systems. It's not a hardware course, right? So I mean, how does the properties of those storage layers relate to design decisions that we make in a database management system? And it will turn out that for the next couple of weeks, many of the things that we will be discussing, they only make sense due to the property of those storage media for data. And so I want you to internalize those high-level points that I'm noting down here, which illustrate a little bit how those storage media properties influence the design of database management systems. So I mean, generally what we have seen is that the capacity of those upper layers of your memory hierarchy is limited. And that means, since we are generally dealing with large data sets, we have to assume that at least one part of our data set is stored on one of the lower parts of that hierarchy, where we have some significant access times. And that is important because typically, if you have been looking at algorithms like sorting algorithms, for instance, you have been looking at the number of computational steps that they are performing. You have compared different algorithms by how many computational steps we are performing. But in the case of databases, if you're dealing with very large data sets, then because you often cannot fit them into the efficient layers of the memory hierarchy, you have to account for overheads just for accessing data, not even doing the computation. If you have, for instance, your data located mostly on hard disk, then just the time for accessing that data, for moving data through the memory hierarchy, that often dominates your total execution time. And this is why many of the algorithms that we will see in the following that are used by database management systems, they are not optimized for minimizing the number of comparisons, for instance, but instead they are really optimized for minimizing how often I need to load data, for instance, from hard disk, right? So we want to design our algorithms in order to minimize data movements. Another property of those devices, we have often separated the bandwidth for reading and writing data and the time for accessing data that was located, for instance, somewhere on the disk. And then in order to access some random location in your data, you have to do things like rewinding the tape or like repositioning your diskette, and those things, they cause quite some overheads. So random data access is often very expensive with those storage media. So that's why once you have already repositioned your diskette, you don't want to read one single bit, but you want to read a reasonable chunk of data to make it worth your while, to pay for all that overhead. That is why we will see in the following that we are generally accessing data in chunks of data, which we will also call pages in the following. And the reason is that doing that is often more efficient than accessing a very small units of data. Another thing that we will see later is that because we can quite cheaply read data that is close together. For a hard disk, it doesn't require you to reposition your diskette, for instance, right? So you can read close by data quite efficiently. And that motivates us to design data structures that keep related data close together in order to make the access more efficient. That's also something that we will see in the following. And one topic that we will discuss about much more in later lectures of this course is the topic of volatility. Because once your database processes updates, as long as those updates are only written in main memory, they could get lost if your server suddenly loses power, for instance. And database management systems, they use quite sophisticated strategies to make sure that your updates are secure, and that even if you suddenly lose power or some other catastrophe happens, that your database remains in a consistent state. And those strategies need to be very aware about which level of the memory hierarchy your data currently resides on, and whether that level is volatile, meaning it loses data once the power switches off, or not. So I want to end with those high-level points. Please internalize them, because without them, many of the things that we will do in the following lectures, they won't make that much sense. So I often get questions about why we do things in a certain way, which could be answered by those high-level points here. The next time, we're going to look more into data storage formats, and we're going to start with indexing. Over the weekend, I encourage you to revise the material that we have seen about SQL queries, because on Monday next week, the homework which focuses on SQL queries will come out. All right. Have a nice day, and I wish you a nice weekend, and then we see you again on Monday. Hello, everyone. Let's get started here. And the last time we have been talking about data storage. Last time we have mostly focused on the hardware on which your data is stored. We have quickly seen the memory hierarchy, and we have discussed about a couple of different common data storage devices and their pros and cons and use cases. I have ended with this slide over here, where I summarize certain common properties of those data storage devices, and summarize points that will become important when we discuss about the design of database management systems, because a lot of that design is motivated by properties of the data storage hardware. Now, this time, I want to discuss a little bit more about not where the data is stored, but how the data is stored. We're going to discuss about different data storage formats. Now, so far, when we have been learning SQL, then you have thought about your data in the form of tables with different columns and rows stored in those tables. Of course, internally, we use a more low-level format. We have to somehow map this high-level perspective on the data to the bits and bytes that are actually stored. So in the following, we're going to discuss about this connection, about how we can map those this logical perspective to the physical storage reality. All right. So generally, for a given table, there's two things that we want to store. So first of all, we have the structure of the table, the schema, meaning like the column types and the constraints on the table. Now, this kind of information is stored in something called the database catalog. So that is a central repository of the database where it maintains certain metadata about all the data that is stored. The actual content of a table is stored as a collection of pages. And one of those pages typically fits a few kilobytes of data. So one page essentially corresponds to a chunk of data stored at one specific location on your storage device. And the size of those pages is chosen in order to maximize retrieval efficiency from the corresponding storage device. We have, for instance, seen for hard disks, there's a certain overhead in repositioning your read and write head. So once you have repositioned that, you don't want to read only a single bit or byte, but you want to read a little bit more data in order to make it worth it. And so those pages, they have a granularity that makes it somewhat efficient to retrieve and store data at those quantities, right? So one of those pages is typically not large enough to fit all the data from a relation, but it is typically large enough in order to store multiple rows from one relation. So that means that in order to store one table, we have multiple pages where each page stores multiple rows. And we have to somehow keep track. So this is an illustration of what we have just discussed. So the metadata about the table schema, which I associate with the table columns, that is stored in a database catalog. And then the content is stored as a collection of pages. All right. So we have multiple pages that store rows from the same table. So we have to somehow keep track which pages store information for a given table. So all those pages together, which contain data from the same table, they are called a file. And we have to keep track of which pages belong to a certain file. There's multiple ways of doing that. Now, one first possibility is that we store those pages that belong to the same table as a linked list, meaning that one page essentially contains pointers pointing to the next and to the previous page. And so if I want to retrieve the data within a table, I just follow those pointers and read all the associated pages. Now, that's a first possibility. A second possibility is to rather store a directory, which essentially are pages again that store references to those data pages. So in the following, I'm gonna illustrate those two possibilities. So the first possibility was that we store a linked list of pages. And this is how that would look like. So we have a so-called header page, which essentially that's the starting page if I want to retrieve data from the table. And then in order to make things more efficient, I can actually maintain two separate lists where I, in the first one, store pages that are full, meaning I cannot insert any more data. And in the second sublist of pages, I store pages that are at least partially empty. So this is helpful because if I want to insert new data into my table, then I can primarily look at the pages where I have some free space. And if I find one page with enough free space, then I can insert my new data there. Otherwise, if none of the existing pages has enough free space, then I want to create a new page in order to store the newly inserted data, right? So you can divide it into those two sublists, but in principle, it's a linked list, and the position of this header page needs to be stored somewhere at a fixed location. So that is typically also stored in the database catalog. The other possibility is that you have this so-called directory. So we have those directory pages on the left-hand side of the slide. And each of those directory pages contains pointers to the actual data pages. And the directory itself can again be stored as a linked list of pages. And again, we have this header page whose address you find in the database catalog. And those directory pages would also store some metadata indicating, for instance, how much free space is left on certain pages. So here, if I want to insert something, then I can mostly go through the directory pages in order to look for suitable data pages on which I have enough free space available. So since those directory pages are relatively compact and they can store pointers to many data pages together with associated metadata, it can often be more efficient to find, for instance, a matching page with enough free space using one of those directories. All right, and here there are some great questions in the chat. So for this format, you would typically only store the header page or the address of the header page in your catalog. And then in order to get to the other directory pages, you can use those links that are stored on the directory pages itself. All right. Okay, and here there's another great question. Why would we ever have more than one page with a free space? And the tricky point here is that the entries that I might want to insert could have different sizes. So at some point, you might want to insert an entry which requires more free space than the current pages offer. So maybe there's just there's a little bit of free space on each page, but not enough in order to fit the entry that you want to insert. So in that case, you would leave the free space on the current pages and rather create a new page which is completely empty and therefore allows you to insert the new entry. So that is one of the things that makes it complicated, that the entries that you want to insert might have different sizes. And the difference between those pages and the pages in the linked list before, there's no big difference. The only difference is that in the previous version, the data pages also store pointers to the next and previous data pages. Here, the data pages themselves, they don't need to store any pointers because their addresses are all stored in the directory. So that is a small difference, but otherwise it is the same. All right. So now those are possibilities how we can bind together different pages that store data from the same table. Now, we have said that one of those pages stores data about multiple rows in a table. So we somehow need to partition the entire page into different sections that store different rows. And those page sections that store specific rows, they are called slots. So we have to think about how we can divide the space on a page into different slots for storing table rows, also called records in this context. So if you have partitioned the page into those different slots for specific rows, then in order to refer to one specific row, we essentially just need the page ID and the slot ID on that page. And both together, we will call that a record ID in the following. And that is indeed the way in which database management systems typically refer to specific records, meaning specific rows in your table, to the, like how they find them, for instance, on hard disk. There's multiple ways to divide pages into slots, and which one we choose depends a lot on whether my entries have a fixed length or whether they have a variable length. Now, for data types such as integers, for instance, Postgres dedicates a fixed number of bytes for storing each integer, 4 bytes, right? So if I have a table where all the columns are integers, then I can tell you a priori how much space I will need for each row in that table. If the table has 5 columns, 5 integer columns, then each row will need 20 bytes of storage, right? Now, the problem is that there's also data types such as text. And the space required by a text is not a priori fixed, it depends on the length of the text that you are entering. So if your table contains at least one column of type text or another data type whose size is not fixed a priori, that means that the space required to store different rows in your table might actually vary across different rows. And that makes it a little bit more complicated to divide those pages into slots. Now, we're gonna start with the easy case, which means that we need the same amount of storage in order to store each row in the table. So we can tell you a priori how many bytes we need per row. Now, in this case, we can essentially just uniformly partition the space on that page into slots that are just large enough in order to store one of those rows in your relation. So if you are considering different relations, different tables in your database, then the size of those slots might vary. But as long as we fix the relation, the number of bytes per slot are fixed and can be stored in the database catalog. So that makes a couple of things easier. The only thing that we still need to keep track of is that if I have multiple slots on a page, not all of them might be in use. So we still have to keep track which of those slots on my page are actually occupied by real records. And there's multiple ways of doing that as well. There's the packed way and the unpacked way, and we're going to discuss both of them in the following. Now, the packed representation essentially means that I'm using only consecutive slots on my page. So that means there will not be any holes, no gaps between used slots. All of those used slots are packed closely together. That's where the name comes from. If I do this, then the only thing I need to keep track of, it is the number of slots that are currently in use. If I know that I'm currently using 3 slots, it is immediately clear which ones it is. It is the first 3 slots because I'm using the packed representation. The unpacked representation is more flexible because it allows gaps between those different used slots. So if I allow this, then I need something like a little bitmap that I also store on the page, which tells me which of the slots are currently in use. In that case, I have a 1 at the corresponding bitmap position. Otherwise, I have a 0 at the corresponding bitmap position. Now, this is the representation of the packed version. Here I'm using the first 3 slots, and towards the end, I have the number 3 indicating how many slots I'm using. Now, this keeps things pretty simple. As long as I'm inserting data, it works actually pretty well. But perhaps think about it a minute. What happens if I'm deleting records? Can anyone write in the chat some propositions for why deleting records might be problematic with the packed representation? Mm-hmm. Mm-hmm. Yes, exactly. So many of you are pointing out that deleting one of those slots creates a hole, or called bubbles, or it leaves some kind of gap between the used records. And once I do this, in order to maintain the packed representation, I have to start shifting around records on my page. If there's a hole somewhere, I have to shift another record into this hole in order to stay with the packed representation. All right. And if I do this, okay, the first problem is that creates a little bit of overhead because I have to copy other records around on my page. Can anyone think of a different problem if you think outside of the current page? if you think about the way in which we refer to specific records. And in the meantime, there's some remark about like how much overhead it would create in order to fill that that gap which opens up. As long as I delete one single record, I could also like move the last current record. I could copy that one or cut and paste that one from the last position into the whole. Then I would have a packed representation again. Okay, very good. Very good. Okay, and here I see what I was looking for. Very good. So we have said that we refer to records, to table rows, by the combination of the page ID and the slot ID. Now, if I move around the records on a page in order to fill gaps, it doesn't change the page ID, but it does change the slot ID. And so if I have external references, then I would need to update them in order to get back to the packed representation. So it would make things difficult. So an alternative way of doing this is the unpacked representation that you see here, and very good answers to the questions, by the way. So the unpacked representation allows gaps between different records, as you see here. And then you need a bitmap in order to keep track of which of those slots are currently in use and which ones are available. So here in the bottom row, you see the bitmap together with the flags indicating whether the slot is already in use or not. All right, now that was the little bit easier case where we have a fixed number of bytes per slot. Now, if I have text columns, for instance, then the number of bytes I need per entry will vary across different records, across different rows. So we are in the variable length case. Now, in order to do this, I need a way of keeping track where on my page specific records start and end. So typically you would store the starting position together with the length of the corresponding record. And we store the information again in a directory. But here we are talking about the directory that is stored on each page and keeps track of where specific record on that page are located, right? Now, that creates a couple of opportunities for space optimizations again. So we have seen that in case of the packed representation, for instance, deleting slots can become problematic. If I start moving, like copying around records on my page, then that might destroy external references. Now, if I use those on-page directories here, that is not a problem anymore, because I can freely move around records on my page. The only thing that I need to update is this directory, which is directly stored on the page and which maps slot IDs to the corresponding positions. So since I have this additional layer of indirection in the form of the on-page directory, moving records around on my page doesn't destroy the external references anymore, right? And I can exploit that in order to regularly compact my used space on a page by filling holes that have been left by deletions, for instance, and thereby I'm maximizing the consecutive free space that I have on my page. We have to decompose things even further, because one row, one record, typically stores data from multiple fields, from multiple columns. And that is why we need to think about how we can divide the space of a slot into space associated with different fields within that slot. And again, we're facing those challenges if my fields have variable lengths as opposed to a fixed length. For fixed length fields, for instance, if all of your fields are integers because all the columns in your table are integer columns, then we can just store the fixed length per column in our database catalog, and we don't need to store any additional metadata on the page itself in order to divide the slot into fields. Variable length entries make things a little bit more complicated again. And here we have two possibilities. The first one would be to use some kind of specialized delimiter symbol in order to separate the data from different fields. So that is one possibility. Another possibility is to use, again, the directories. Here, essentially directories at the beginning of each record, which tells you which part of the slot space is reserved for storing data in specific fields. So this is how we decompose everything down from pages to slots and to fields. Here, that is the summary of what we have been doing. One topic that keeps coming up, that is the topic of fixed length versus variable length content. Fixed length content is often easier to handle. If we have variable length content, then we need some kind of directory, whether that is a directory of pages, a directory of slots, or a directory of fields. So here we have reused the certain common ideas at multiple granularities. All right. And one question that is here currently, in the unpacked representation, do we still use slot IDs? Yes, we always use slot IDs. So in the unpacked representation, so that doesn't change anything. You still have slot IDs for the different slots, just that now you might have empty slots between consecutive used slots. So the slot is essentially the space reserved on the page for storing one specific record. In that space can either be used, occupied by a record currently, or not. So just because one of the slots is empty doesn't mean that it loses its ID. Okay? All right. Now, one last remark on how we store data. What we have been discussing so far essentially assumes that data which belongs to the same row is stored close together on a page. And that is the traditional way of storing data, which is, for instance, used by Postgres. Since it stores data from the same row close together, it's also called a row store architecture. Nowadays, there is another breed of database systems which stores data differently. It rather tries to store data from the same column close together. That can be a performance advantage in cases where your queries tend to access only a few out of many columns of your tables. If you have this, then with the row store format, you would load entire data pages. Like one of those pages is the unit at which we retrieve data, for instance, from the hard disk. And if you load one of those pages with the row-wise format, it would contain data about all the different columns for specific rows. And if I'm not interested in many columns, it means I'm loading a lot of data that I actually cannot use. And in those cases, a column store architecture might be more efficient. But that is a topic that we will discuss in more detail later, where we will also see specific systems that use this newer column store format. All right. Now let me quickly change the slide deck here. We're gonna continue with the topic of how we store data. but we're going to see more sophisticated ways of storing the data that make retrieval more efficient. And those are the new slides. I believe that you should all be able to see the tree indexes slide deck now. All right. Okay. So in the following, we're gonna discuss more about how we can store our data in order to make access as efficient as possible. So within this big architecture of database management systems that I have initially introduced, this concerns the data itself, the way in which we store it, as well as this component that I have named data access within the storage manager, which contains the algorithms that exploit data structures for efficient access and that handle them. The relevant chapter in the Ramakrishnan and Gehrke book, that is chapter 9 for what we discuss in this slide deck. And the problem that we will be looking at in the following lectures, that is the problem of quickly finding specific entries in your data set. Now, to make things a little bit more concrete, think, for instance, of the enrollment table that we have seen in our example database. The enrollment table contains information about the students and the courses that they're taking. So it essentially contains pairs of the student ID and the course ID with the semantics that the corresponding student is taking the corresponding course. And now let's imagine that we are searching for the enrollments for one specific student, for instance. Maybe we want to find the enrollment information for the student with SID 5. Now, if I store data using the format that I have introduced directly before, then I could, for instance, store the data from the enrollment relation as a collection of data pages, and might either have them as a linked list or as a directory. So in order to find the enrollment information for the same student, I would have to go through all of those pages and to look at all records on each of those pages in order to check whether the student ID equals to 5. And as you can imagine, if I have a lot of students, then that is actually quite inefficient because I need to look at all data, but I'm only looking for a small number of entries typically. A better version is already if I just sort the data by the student ID. If I have sorted my data by the student ID, then I can apply something like binary search, for instance, in order to narrow it down quite quickly to those entries that I'm interested in. So that is already significantly better. But the problem is this. For one data set, I have to choose one specific way of ordering it. So here, for instance, if I choose to sort the enrollment relation by the student ID, then it will make it more efficient to find information about specific students. But if I'm now searching for information about specific courses, for instance, even worse, then the student sort order doesn't help me at all. And I have to choose one single sort order. So in order to make multiple ways of accessing your data more efficient, we can use something called an index, which is essentially an auxiliary data structure used for finding data faster. And indexes are really exactly the same principle as indexes for books. I mean, here, for instance, I have this New York tour guide, and in the end, it has an index which contains the names of different attractions sorted in alphabetical order. And for each of those attractions, it has a reference to the pages on which I find the associated data. And indexes and database management systems, they do exactly the same thing. And the nice thing about them is that I can have multiple indexes for the same table. So for the enrollment table, I could create one indexes for quick lookup of specific students and another index for quick lookup of specific courses, right? And that means I can make multiple ways of accessing data in the same table more efficient with that method. Now, in more detail, the index stores references to data records. And as we have just seen, those references have the form of a page ID and a slot ID. Now, indexes, they always refer to one specific table, at least the indexes that we see here in the lecture. And indexes are always specialized for one search key. So the search key, that is essentially a subset of table columns. And then the index helps you to quickly retrieve entries that have specific values in those search key columns. You want to search according to different columns, then you need a new index, basically, right? Okay. So let's start with a simple indexing example. So let's say that I want to retrieve enrollment information for specific students. Then I can create one of those index structures in order to make access by student name more efficient. Now, the data of the index itself, because it's also data, so we again store it as a collection of pages. So the index is also stored as a file. And here in this simple example, you see that I have multiple pages that belong to the index, and each of those pages has on the left-hand side the values from the search key, which in this case is the student name column, and on the right-hand side you find the record IDs, meaning the page ID followed by the slot ID. In order to keep the example simple, I have made those pages fairly small, so we have at most 3 entries per page. In reality, of course, you would have typically hundreds of entries per page. So here you have the index page ID for the pages that store the index data. And as I have already discussed, on the left column, you have the index search key. On the right column, you have the associated record ID. And now, if I search, for instance, for a student named Alan, then I can use something like a binary search in the index. I can first look at page number 14 and see whether the entries on that page come before or after the entry that I'm looking for. So here those student names, they are ordered in alphabetical order. So Alan comes before Kyle. So I have to go to the left side of that page number P14. All right, so that would be P12. And now I compare against, and Alan becomes even before Felix. So I have to check out this one, and Alan also comes before Dora. So now I have found the last page. And here I had to access 4 pages in order to retrieve the data I'm looking for. And we have already very quickly discussed this, but let me remind you that in the context of database management systems, often the cost for accessing data actually dominates entire processing cost. And that is why those index structures that we will see, they're optimized for minimizing the number of pages that I need to load from hard disk in order to find the data that I'm looking for. So according to that cost metric here, we would have loaded 4 pages. So that means 4 cost units for the access. Then finally, since the index only contains a reference to the actual data I'm looking for, I would still need to count 1 more page access in order to load the data that is referred to for Alan, which I find at page number 25 in slot number 3. Now that is one first simple indexing structure, but in the following, we're going to improve on it. Now, the first thing that we want to improve is this. Right now, I have a flat index structure which sorts by the student name, and that means I can use binary search. So with binary search, whenever I load a page from hard disk, it means that I'm essentially narrowing down the search space by factor 2. The index structures that are actually used in database management systems, they try to be more efficient per page access. So they try to narrow down the search space by a much higher factor than 2 for each page load operation. And I can do this, for instance, using so-called index trees, tree indexes. They will be the focus of this and still the following lecture. But already as a little outlook, there's essentially two big branches of indexing types. One is organized as search trees. One is organized as hash tables, basically. And we're going to first discuss the tree indexes. Later, we're going to discuss about the hash indexes. This is how I can use one of those tree indexes for this example here. As you see, now we have more pages in the index. The index data that we have seen before, it's still there. It's now the lower level of the tree. And we have multiple levels above that. Now, if you compare the content in pages on the upper half of the screen to the ones on the lower half of the screen, basically below that green dashed line, then you see some slight differences. So the entries on the lower part of the screen, those are the so-called data entries, because here each entry on a page references specific data. So in this case, there's a specific student names, and next to it is references to where you can find that data. If you look at the entries on the upper half of the screen, then they are organized a little bit differently. So those entries on the upper half of the screen, those are so-called index entries, and they don't point to actual data, but they point to other pages from the index itself, right? So here the semantics is this. On the columns on the left-hand side in those index entries, we essentially have references to specific key ranges, search key ranges, and then on the right-hand side, you have references to associated indexing pages. Now, in order to make things more concrete, let's have a look at a concrete example again. So we are searching for this student again. And in order to use one of those index trees, we always start at the root node, which is the node at the very top. So here I'm looking for student Alan, and student Alan would be ordered before Holly in alphabetical order. That is why I need to go to the corresponding page 2 of the index that is referred to. So now I'm looking at the page number 2, and again I'm comparing, I'm searching for Alan. So Alan comes also before Dora, so I want to look at the index page 10. And now I'm at the right page, and here I'm finding an entry for Alan. And because of that, and now that I find the corresponding enrollment information on page number 25 in slot number 3. And here I have some discussion about like pointers. I assume the question is whether those record IDs essentially correspond to pointers, and that is pretty much the case. So they give you one specific address where you can find data that you are looking for. All right, so here to make things a little bit more formal, a description of the content that we have in those different types of nodes. Now in the inner nodes of the index, we have those index entries, and the content that they store, it's alternating between references to index pages and search keys. So we alternate between the two with the semantics that the references point to entries that are strictly ordered before the key that you find next, right? So here, for instance, reference 1 would point to entries that come strictly before search key number 2, right? So if you're searching for something, then you just need to identify the corresponding key value range within one of those inner nodes in order to know which index node you need to look at next. The leaf nodes are structured a little bit differently. They have keys followed by references, so it doesn't start with a reference, it starts with a key. And for each of those keys, the corresponding reference contains a link to the data that is associated with this search key. So we can use those indexes, first of all, in order to answer queries with equality predicates. And we have already seen that, for instance, if I'm looking for a rows satisfying the condition student name equals Alan, then I can use the index that we have just seen in order to efficiently answer them. What I can also do is to use them for inequality predicates. For instance, if I have an index by the GPA column, then I could use one of those index in order to quite efficiently retrieve those entries with a GPA greater than 3. We're going to see in more detail how retrieval works in those cases in the following. Now, in any case, this works if the predicate that you have in your query references the index search key. All right. So here, to make things a little bit more concrete, how can we use this index for equality predicates? This is the algorithm that you would use for that. So whenever I have an equality predicate in my query and I want to use the index in order to find corresponding entries, then first of all, I start at the root node of the index, which in those slides was on top. And until I reach one of the leaf nodes, I essentially, for each node, identify the right key value range that the entry I'm looking for must be contained in. Then I follow the corresponding reference to the next index node, and so on until I reach one of the leaf nodes. And at the leaf node, I see whether an entry exists for the corresponding key. And if I find such an entry, then I follow the record ID in order to retrieve the associated data. So of course, whenever you use one of those indexes, it is not guaranteed that you find any entry at all for the key that we are looking for. Perhaps we don't have any student named Alan registered, right? But at least the index directs you towards the leaf page on which the entry would be located if it exists. So after we have examined that leaf page in the index, we can be certain one way or another one whether the entry is in the index or not. All right. Now, there's a couple of optimizations of those index data structures that we will discuss in the following. Gonna quickly outline the first one, and then we will discuss more in the following. Now, often I might want to retrieve multiple entries from an index. For instance, if I have one of those inequality conditions, in that case, it can be good for performance if the leaf nodes of my index are also linked to each other. So if I want to retrieve information in neighboring leaf nodes, I don't need to go over the parent nodes anymore, but instead I can leverage those links in order to go from one leaf node to another one. And this is how that would essentially look like. So imagine, for instance, that we want to find all students whose name starts with a letter between D and K. Then I could use this index in order to find the first student whose name starts with a letter D, which is Dora over here. And using those links between the leaf pages, I can just start from the Dora page, which is page number 11, and then jump to page number 12, to page number 13, to page number 14, until I find entries which start with a letter after K. And so I can quite efficiently use the index in order to retrieve those students whose name starts with a letter between D and K. And what enables me to do that is linking the leaf pages in my index by essentially storing the pointer to the next and the pointer to the previous leaf page in each of those leaf pages. Okay. So that was one optimization. We will see more optimization and different indexing variants next time. The homework, by the way, will be out this afternoon. You will find it on CMS, and I had questions about putting it on different platforms. So I will also put it on Piazza. You have 1 week for doing the homework. It focuses on SQL as promised. And yes. Right. Good. Then have a nice day, and see you on Wednesday. Okay, so let's get started here. Let me quickly reorganize that a bit. All right. Okay, so the last time the slide that we finished with, that is this slide over here, I believe. And what we see here, that is a tree index which indexes by student names. So if you have a table, for instance, like enrollment information, and you want to quickly find entries that satisfy certain conditions, then an index is probably a good idea. And in general, those indexes, as we have seen, they work pretty much like the indexes at the end of a book. For a given search key, they provide you with references to the pages where you find the associated information. Now, last time we have been looking at those tree indexes that you see here. So in order to use this tree index here, for instance, in order to look up data associated with one specific student, we would start at the root node, which is page 1, P1, on top of the page. And if you're searching, for instance, for student Alan, then we would compare Alan against the keys that we see here. And we see that in alphabetical order, Alan comes before Holly. So that is why I want to continue with page 2. And on page 2, I'm comparing Alan against the students again, and it comes before Dora. So that's why I'm continuing with page 10. And on page 10, indeed, I see the student named Alan. And if I want to find, for instance, all students within a certain range of names, everything between Alan and Kyle, for instance, then I would start as if I wanted to find only information about Alan. But then afterwards, after I have reached page 10, I would use those links between the leaf pages in order to continue to page 11, page 12, page 13, page 14. And here I find Kyle and the names that come after Kyle in alphabetical order. So this is where my search stops. So this is how you can use those indexes. And you can have multiple indexes for the same table with different index search keys. One index for student names, one index, for instance, for course information. All right. Now this here summarizes more formally the treatment of inequality predicates, which I have just done. So If you are searching for search keys within certain bounds, L and U, then what we do with the index is that we first search for the first page, for the first leaf page on which we find entries for L. And then we use those links between the leaf pages in order to traverse the index, and we keep reading until the entries we encounter come after U in the key order. All right. So this is ways we can use those indexes. And so far we have been discussing about search keys that correspond to one single column. In the examples before, that was always the student name column. But in practice, it is more flexible than that. If you imagine, for instance, an example where we have a big table with information about our customers. Let's say that we are a web shop, for instance. Now, for instance, in this table, we could have information about the customer zip code and about the last product that the customer bought. So if I want to start a targeted advertisement campaign, it might be useful to retrieve customers that are defined by a specific zip and by a specific product that they bought last. So I want the combination of the two properties. And in those cases, an index which uses the combination of the zip code and of the last product as a search key might be useful. And you can do this in relational database management systems. You can define indexes that use a search key, a combination of columns from the same table. What you need to do in that case is to decide on some priority order between the different columns that appear in your key. You must decide whether it is first zip code, then product, or whether it's first product and then zip code, for instance. Now, this order matters for the key comparisons. Now, in order to use one of those indexes, we have already seen that, what you essentially need to do is that you go from one index node to another one, and in each index node, you must perform a couple of comparisons between different keys in order to establish which key comes first in the key sort order. And the priority between different columns in your composite keys matters for how those comparisons are executed. For instance, if we decide to start the index key with the zip code and then later comes the product, it would mean that when comparing those composite keys, when comparing two keys, I would first look at their zip codes. And only if their zip code is the same one, then I'm going further to the product and see which one comes first according to the product. So during those comparisons, I treat those component columns of your composite key in the order in which they appear in the key. And because of that, it means I can use those index data structures in order to retrieve entries that satisfy predicates, which are either equalities or inequalities on all key columns or on some prefix of key columns. So if you have decided to first use the zip code and then the product in your composite key, then you can use this index to answer queries that restrict only the zip code, but you cannot use them in order to answer queries that only restrict the product. Or at least it's not recommended to try that. It would be inefficient. Can anyone tell me why we have this restriction to key prefixes? In your own words, in the chat. Some intuition for why that is the case. Or you don't even need to put it into the chat, just think about it a little bit for a minute. It's good to verify your understanding of indexing structures. So if we have a composite key, the order, for instance, the zip code before the product in our composite key, then I can only use this index for single restrictions on the zip code, but not for single restrictions on the product. Can anyone have some intuition for why that might be the case? If you imagine what the index looks like. particularly if you think about what you have in the leaf nodes of the index. Ordering the zip code before the product means that the zip code will be prioritized in the key comparisons. Give you a few seconds to marinate over it. Okay. Yes, very good. And I think I see the right, yes. So here I see the right references. Okay, very good. You have to think about the sort order indeed. Now, if you think about the order in which the entries appear only in the leaf nodes, for instance, if we prioritize the zip code in our comparisons as opposed to the product, it means that things with the same or similar zip codes will appear close together in the leaf nodes of the index. And on the other side, if we prioritize the zip code in the comparisons, then things that have the same product, customers who bought the same product, they might appear all over the place, basically. They are not necessarily close together. And those index structures, they are only efficient if they are used to retrieve data that appears close together in the index. So if you have prioritized the zip code in your comparisons, then customers with similar zip codes will appear close together in the index, and that is why you can retrieve them quite efficiently. On the other side, if you want to retrieve customers who bought the same product for any zip code, then those customers will be distributed over the whole range in your leaf nodes. So it is not particularly efficient to retrieve them with the index, right? So maybe as a little homework, it might make sense to imagine how that index with the composite key looks like, and for instance, make a little drawing. But here, the core idea why we want to restrict ourselves to the prefix of the key columns is right here, and was in the chat. Good. Now, let's have a look at Postgres. So far, we have been discussing about indexes in a rather abstract manner. Now, let's see how they actually appear in a real database management system. Now, in Postgres, for instance, and in most other database systems too, you can decide which indexes the database system should create. There is commands for that. They might look slightly differently in different database management systems. In Postgres, you simply write create index, then some index name on the table that is being indexed. And here between those parentheses, you have a comma-separated list of table columns. And those are the columns that the index should refer to. So it can be one column, or it can be multiple columns. In that case, it's a composite index. Now, here, yes. So here you have the syntax. And the reason that you can give a name to the index is that you can refer to that name later. For instance, maybe at some point you want to delete the index again, and then you can do this with the command that you see below, drop index, and then you write again the index name. I'm quickly going to demonstrate that in Postgres, just that you have seen in index creation once. All right. Now you should be able to see my terminal here. Let's actually log into that database. All right. And what I have here, for instance, is, okay, and here I have, by the way, an interesting question in the chat. The question is, whether we have to explicitly tell the database management system to create indexes or whether it does this automatically. The answer is it depends on the database management system. Some of them do this automatically. Most of them allow you to control which indexes are created because it's a decision that is difficult to make automatically. I'm going to say a little bit more on this in the following slide about the pros and cons of creating indexes and how to decide which ones to create. But for the moment, let's first of all look at a concrete example where we are creating indexes in a database. So what I have here in the database, that is the results of the Stack Overflow Developer Survey. They make a big survey among software developers every year, and they publish the results. And they ask questions about all kinds of details about their job and so on. And here I have the data from that survey. And here you see it has many columns which correspond to different questions that were asked. And the number of entries here, that is about 90,000 respondents. So as far as surveys go, this is actually pretty large. As far as data sets go in general, of course, this is not yet that large. All right. So for instance, there's a column about the country that the developers come from. I could, for instance, want to count how many participants we had from different regions of the world. And in order to make that efficient, maybe I want to create an index on the country column. Let's maybe first try the query without the index. If we, oh, and by the way, let's quickly enable timing of queries in order to be able to compare performance with and without indexes in the following. So we enable timing. And now let's first of all count the number of participants, for instance, from a country in Europe. Let's, for instance, say Germany. All right. Okay. And that took a little bit. And we have something like about 6,000 participants. I'm running the query again. And now it actually gets already much faster. That is something that we discuss in more detail in the following lectures. Those database management systems, they're able to cache data that was recently accessed. So as you see here, the query suddenly gets much faster. I wanted to get the faster, more realistic time in order to make the following comparison more realistic. All right. Now, let's see what happens if we create an index on the country column. Create index, country index on the Stack Overflow table. And the columns that we want, that is the country column. All right, so now we have created the index. It was actually pretty fast. And now let's run the same query from before. All right. Now, what you see here is the time for the query after we created the index. And as you see here, it's about 5 milliseconds. Now, without the index here, we had something like 124 milliseconds. So this is, I mean, both are very small times, of course. So right now, for data of this size, it doesn't matter so much. But you see that there's a difference of several orders of magnitude. If you imagine that typically would work with much larger data sets than that, then you can see that having one of those indexes actually makes a big difference. Because this country index now has allowed us to immediately retrieve references to those entries that are associated with country Germany. And that is much faster than having to go to through all the pages of the table in order to check whether there's any entries for Germany, for instance. Now, let's drop the index again, just to see whether it was all a coincidence, maybe. Let's run the same query again. All right, so it's still getting a little bit faster due to caching effects probably, but still it is the same order of magnitude as before. We are much faster than using the index. And the command I use to get the time, it is \timing. Exactly, thanks. All right, now perhaps one more example for a composite index, just that you have seen this as well. I could, for instance, use the, I think it was called employed or employment column. And here, I'm first of all showing you what distinct values appear in that column. So this select distinct is, in my experience, pretty useful. If you want to get a first impression of a data set, you want to find out which values appear in a certain column, which is what I'm doing here. Not sure whether the column was called employed or employment. Let's see. Okay, it was actually called employment. And here you see a useful feature of Postgres. It tries to correct the queries that you are entering by making suggestions. So here we have referred to the column employed, and it suggests that maybe I wanted to refer to the column employment instead because it's a similar name. And it is right, so that is useful. Let's look at the employment column instead. All right, so here there's a couple of different employment statuses. And perhaps, for instance, I want to count the number of retired employees in Germany or in France or in the US. So let's actually create an index that allows me to quickly look up entries that satisfy a predicate on the employment status and another predicate on the country. So let's create the country employment index on the Stack Overflow table, which uses the columns country, employment. All right. Okay, so now we have created this index, which is also quite quick to do. And now, for instance, we could select the number of developers where the country equals Germany. Let's actually take France for a change. And the employment status is retired. All right, so that takes 1.006 milliseconds. It's actually very fast to do. We only have 6 entries because it's quite a specific combination of properties. Let's actually drop the index in order to see what we get then. All right, and as you see here, again, we have an execution time that is by orders of magnitude above the one without the index. Even though for those small data sizes, of course, it doesn't matter too much. But if you have a large database and your queries process slowly, then thinking about creating some indexes to support them is probably a good idea. Okay. All right, let's go back to the slides. So this is the syntax in Postgres, and as always, I encourage you to play with it a little bit yourselves if you have already tried some data sets. In principle, those commands also work in the DB fiddle. Now, one question that was already raised here is which indexes should we create generally, or whether the database management system can decide all by itself which indexes to create. Now, first of all, let's discuss a little bit about how you can decide which indexes to create in a specific situation. And in order to decide which indexes to create, we generally have to look at the typical queries. In particular, you have to look at the predicates, meaning the where clause of those queries, which gives you some ideas for candidates that might make good indexes. Now, in the examples that we've seen here, creating the index always reduced query execution time. So I don't want to mislead you into thinking that indexes are always a good thing to use for performance, because that is definitely not the case. Now, first of all, indexes, they are, for instance, not useful if your predicates are not selective enough. So if your predicate actually is satisfied by most of the entries in your table, you don't really need an index for that query. Another reason is that, and we will see this in more detail in the following, if your data often gets updated, it means that each associated index also needs to get updated, which also causes some overheads. So if you have too many indexes, then it will be very expensive to update your data. We're going to discuss more about index updates in the following. And then finally, of course, each index is a data structure again, so it needs some space. That means the more indexes you create, the more space you use up on hard disk. So at some point, you probably run out of space. But a question about which indexes to create is really an interesting one, and it's a difficult one. So in the database research community, you're already looking at that question, how to decide which are the ideal indexes to create, already since decades, basically. And research is still ongoing, so it is a tough problem. There are some tools available which allow you to do this. There's, for instance, the Dexter tool for Postgres, which tries to figure out automatically what indexes you could create. And there are some database management systems that essentially automatically decide to create indexes, for instance, the so-called MoneyDB database management system. And those database management systems, they might create or drop indexes independently in the background. But in general, it's very hard to decide what are good indexes to create. All right. Now in the following, we're going to discuss about a couple of different optimizations to indexes, and also about how we can handle updates in the context of indexes. One thing that I believe was already pointed out by one of your peers in the last lecture is that sometimes you have the situation where your index stores duplicate keys. For instance, maybe for the enrollment table, there's many entries for the same student, somebody who is enrolled in lots of courses. And then the question is, do we really want to store the name of that student repeatedly in our index, each time referencing the corresponding enrollment row? There is a more efficient alternative, which is simply that we store the name of the student once in a leaf node, and then we store a list of associated references. So we just avoid repeating the duplicate key, and index data structures do that. There's a slight disadvantage to doing that, which refers back to the lecture on data layout. There we have seen how we decompose the space on one of those pages into smaller and smaller units. And we have seen that having, for instance, records of the same length often makes it easier to partition the space of a page. Now, if we say that we allow variable length lists of references for one key, it means that we might turn a fixed length record into a variable length record when we are talking about the entries in the index. And that makes a few things a little bit more difficult when handling all the bookkeeping associated to data layout. But that is a reasonable trade-off, and in practice, you would typically avoid repeating the same key in your index. Another thing is this. Right now, the indexes that we have discussed, they store references to the actual data. In the leaf page of the index, we have the so-called data entries, but often those data entries correspond to references to the actual data. Instead of that, you could also just store directly the data that you're interested in the leaf nodes. And if you do so, it's called a clustered index. Now, as long as you don't want to store your data repeatedly, you can only have at most one of those clustered indexes per table. But that can actually be quite efficient because first of all, with this clustered index, you save one reference. Like if you don't store the data in the leaf nodes, then you would have to follow up a reference to the data. If you store the data directly, then you can save the time for that. But even more importantly, if your index stores in the leaf pages references to the data, then in order to retrieve the data, you have to follow all of those references. And even if those references are stored close together in the index leaf node, the associated data might actually be widely distributed in the data pages. And that means in order to collect, for instance, all entries for the same student, you might actually have to access lots of different locations in your actual data set. And that can be inefficient, as we have seen. For instance, if you store the data on hard disk, it means you have to move your read and write head quite a few times, which takes time. So if you store the data instead inside of the index, it means that you are guaranteed that all the data for the same student appears close together and can be retrieved efficiently with one or at most a few page read operations. So that's why you might want to use clustered indexes if you can. Now, this is just some overview of the indexes and the optimizations that we can apply to them. What we have seen so far pretty much corresponds to a very popular brand of index, which is the B+ tree. That is also the default index created by Postgres, which we have just done. There's several variants of that. For instance, there are tree index variants that put data entries, meaning references to data or actual data, in the inner nodes of your tree as opposed to the leaf nodes only. There's some variants that omit, for instance, those useful links between the leaf nodes and so on and so forth. There's many variants of that. But in practice, one of the most common indexes is this B+ tree, which essentially we have been discussing about so far. Now, one important topic in the context of indexes is data updates. The index indexes the data. So if the data changes, the index must change as well. And there's different ways to handle data updates. Now, generally, you might have inserts or deletes to your data, or updates, which you can imagine as a combination of a delete and insert, even though in practice it is typically implemented more efficiently. If your data keeps changing back and forth, then one thing that you might want is that you keep your index tree somewhat balanced throughout all those insertion and deletion operations. And you might already have seen that in the context of general search trees. Now, often with those search trees, it's a good idea to keep them somewhat balanced in order to maximize efficiency. Now, in the following, let's first of all see what happens if we don't balance the tree after updates. So here we have the index tree for students again, and now we are inserting a new student called Bella, for instance. Now, if we start from the root and go down to the leaf nodes, page 10 is where the student Bella should be inserted according to the alphabetical key order. But unfortunately, you see that the page is full. We don't have any free space left. Now, what we can do is that we create a new page, page 19, and we insert the student name there. And that here is called an overflow page in this context, because it becomes necessary as the data in page 10 is overflowing, so to speak. And you also see this little arrow in red pointing from page 10 to page 19. That essentially represents a little pointer reference that we store as metadata on page 10, which points to the following overflow pages. As long as there's no overflow page, we simply set that pointer to null, essentially. Now we are inserting Bruce as well, and we still have space on page 19. Now we insert Kara, and now we want to insert Connor, but here we are running out of space again. So we are creating again a new overflow page here, page 101. And then the first overflow page has a pointer to the second overflow page, right? And now, before we start deleting things, I want to point out that having those overflow pages might make retrieval inefficient, because if you're searching, for instance, for Connor, then in order to get there, would have to pass 1, 2, 3, 4, 5 pages, while for most other entries, I would only have to pass 3 pages in order to find them. So those overflow pages, which make the tree imbalanced, they are not good for retrieval performance. Now let's also delete a few students. Let's say we are deleting Rosa. Let me quickly move the chat so I can see my slide. We are deleting Ryan, we are deleting Sergey, and at this point you see another inefficiency here because we don't rebalance the tree. If you look at page 17, where we have deleted the students, now it has become completely empty. So here we are using space, we are reserving space for that page 17, but we don't actually store any entries on it. So we are wasting space. Now, those are the problems with those static index structures. It has been done. There have been index structures which do that. For instance, the ESAM index, it's an older one. And that is okay as long as your data remains relatively static. But if your data is dynamic and you keep inserting and removing data, then you might have lots of overflow pages, which means bad retrieval performance. And you might also have lots of empty pages, which means that you're wasting storage space. Both are undesirable. That is why data structures such as the B+ tree, they're doing things a bit differently in order to cope with more dynamic workloads that keep updating your data. So we have already seen that this is the default index structure. In Postgres, it is very popular, and it balances the tree after insert or delete operations. The primary goal of B+ trees is always to keep this index tree somewhat compact. And that means you want to make sure that your nodes are at least half full. That was not the case for the previous index, where one of the pages became completely empty. A B+ tree would not allow that to happen. So we call also the number of minimum entries per node the order of a tree, and it is often abbreviated with a little d in those textbooks. And so since we require nodes to be at least half full, with the exception of the root node, by the way, because maybe you only store one single entry in your entire index. But besides the root node, we require nodes to be half full. And that means that the number of entries that we have per node is between the order d, the minimum number of entries, and 2 times d. That is the maximum number of entries per page. Now, in practice, B+ trees are relatively shallow, even for large data sets. Here are a couple of back of the envelope calculations in order to demonstrate that point. A typical order is something like 100. So you would be able to fit between 100 and 200 entries on each of those nodes. Like the number of entries per node is defined by the page size and by the size of the index entries. So typically the page size is a couple of kilobytes, and then with typical entry sizes, you end up with something between 100 and 200 entries per node. Now in practice, your fill state is somewhere in between the extremes. Something like 2/3 full is typical. And that means that the average fan out, meaning the number of child nodes for your index nodes, is about 133. So that means that the second level of your tree can already have something like nearly 20,000 nodes. The third level can have something over 2 million nodes. Then we have over 312 million nodes, and so on and so forth. So just for demonstrating that even just with a handful of tree levels, you can already index most, even the large data sets. And that is one reason why those trees are so popular. It allows you to go to the data that you're looking for with only few nodes, with only few page accesses on the way. Let's see how those trees deal with updates. So let's again say that we are inserting student Bella. And student Bella should be inserted on page 10, but there's no space left. So we have to create a new page in any case. Now here we have created page number 19, and that might look a little bit like overflow pages, but it is actually not. Because with overflow pages, now we would have inserted a pointer from page number 10 to page number 19, and then we would be done. Easy. Here we are more ambitious, and we actually want to insert a reference to page number 19 in the parent node to page number 10, which is the page number 2. So I didn't want to insert the reference to page 19 here. If that works, then great, we are done and we have a balanced tree. In this case, unfortunately, it doesn't work because page 2 is also full. So we have to propagate the page split up the tree, and here we have to introduce one more page, which is page 20. So page 2 and page 20, they now divide the entries among themselves that have been formerly stored on page number 2 together with the new reference to page 19. So now we have another dangling page, page number 20, that no other page is referencing currently. So again, we have to go to the next higher level in the tree in order to insert a reference to page 20. But again, the current root node, page number 1, is full. So we want to insert the reference, but there's no space left. So we have to split the root node again. Now we have introduced one more node, page 101. And now our entire tree is actually split into 2 trees, which we don't want. So in order to come back to an actual tree, we need to introduce a new root node that references page 1 and page 101. And we do that here with page 102. Let me just rearrange the nodes a little bit to make it easier to recognize it as a tree, which is this. And now we end up again with a balanced search tree into which a student Bella has been inserted. As you see here as well, this tree has 1, 2, 3, 4 levels. The original tree that we started with before inserting Bella, let me quickly go back to that one. This one only had 1, 2, 3 levels. So because we inserted that new student, it actually caused several reorganization operations, and now we have a tree that has 1 more level. All right. So now let's see a deletion operation in order to see the inverse. And before we do that, we should quickly proactively discuss about one possible source of confusion. You might have noticed that in my example, each page has up to 3 entries. I'm doing this because this is what just fits best on my slides. On the other side, we have seen that according to the formulas we saw before, the number of entries per node is always between D, between the order D, and 2 times D, right? And that means that you would expect an even number of entries per node. Now in this example, I'm not doing this. I'm working with at most 3 entries per node, but that is just motivated by the dimensions of the slides. Typically, we would say that a node is considered under full, below the fill threshold that is required, if it has less than D order entries. Here we have up to 3 entries per page. So half of that would be 1.5, which is not an integer. So for the example in the following, we will say that a node is under full if it has less than 2 entries on it. All right, so let's actually see what happens if we delete a couple of students here. So let's first of all delete Sergey. And now let's delete Ryan. And so here we have deleted Sergey, and now next one we are deleting Ryan in page 17. And as you see, page 17, now Ryan vanishes. And at this point, we have the problem that page 17 has become under full because we require at least 2 entries per node, and here we do not have that. So what we can do in this case here is if we look at the siblings of P17, in particular at P18, those nodes, they can spare some entries. They are comfortably above the minimum threshold of entries per node. So we can essentially shift a couple of entries from page 18 to page 17 over here. We also need to change corresponding references on page 4. And now we have come back to a tree that is balanced and where each node is at least half full. Here, that was the bad state with the under full node, and here we are getting back to the good state by shifting entries from page 18 to page 17. All right, and now I'm going to show you one more way to deal with imbalances caused by deletions. So in the previous example, we have essentially redistributed entries from the sibling to the node that was under full. Another operation that we can do, which tends to be a bit more expensive, that is that we merge nodes in the tree together again. And then once we merge 2 nodes, then it means that the parent node will have 1 reference less. So potentially the parent node also becomes under full and has to be merged again. So similar to how those page splits can propagate up the tree, which we have seen for insertions, those node merges can also propagate up the tree in case of deletions. So for instance, here, let's say that we are deleting student Bella again. And here, student Bella appears on page 10 on the left lower corner here. So now I'm deleting that from page number 10. And at this point, page 10 has become under full. Now the problem is I cannot really redistribute entries from page 19 because then page 19 would become under full. I could think more about redistributing things, but at some point it becomes too expensive. So instead of that, I might rather want to merge nodes. So if I do this, then so page number 10 has become under full. So if I merge together page 10 and page 19, it means that page 2 has 1 entry less. So we might also want to merge it with page 20. But then page 1 has 1 entry less than before. So we might merge it with page 101 and so on. And then the root node has 1 entry less. So it becomes unnecessary, so to speak. So I leave it to you to trace the example back in more detail after the lecture. But what we are doing here is pretty much exactly the inverse of what we have been doing before. Before we have been inserting student Bella. This is why we had to add 1 level to our tree. Now we are doing the inverse. We are merging together nodes again. And in the end, you will end up with a tree that has 1 level less again. It has 3 levels after deleting Bella. Before it had 4 levels. Here again, each of the nodes is at least half full and the tree is balanced. That's always the state that we want to come back to. Good. So great questions. That was a tree index data structures. The next time we will start with an alternative, which is hash-based indexing structures that are based on a hash function. I wish you a nice day, and I see you on Friday. All right, let's get started. So, hello everyone, and today we are gonna probably finish our section on indexes. The last time we have been talking about tree index structures, which essentially correspond to a search tree. And this time we're gonna talk about a different type of indexes, which is based on hash functions. Trying to advance my slide here. All right, so here we have again this architecture of database management systems. So we are currently still discussing about how the data is laid out in order to make it efficient to access. And we're also talking about the data access component in the storage manager. For hash indexes, the relevant chapter in the Ramakrishnan and Gehrke book, that is the number 10. And so far, we have been discussing about those tree indexes, where you essentially traverse the tree from the root node to one of the leaf nodes in order to find interesting entries. For the hash function, it works a bit differently. If you're looking for one specific key with your index, then you first evaluate the hash function on that key, and then depending on the outcome, you know which bucket to look for, and with that bucket you have a page associated. On that page you find the entries that you're looking for. High level picture, we're going to see it in more detail in the following. Now let's first of all discuss a little bit about the types of predicates that those different indexes can support. Now, tree indexes are fundamentally based on a comparison between keys. So if you think, for instance, about the leaf nodes of an index tree, then the entries in the leaf nodes are sorted by the key. That means that keys, like entries for the same key, are stored close together. It also means that entries with similar keys are stored close together. And because of that, I can exploit those tree indexes quite conveniently in order to treat inequality conditions. Just need to scan some range in the leaf nodes, and there I will find all those entries with similar keys stored together. Also, we have seen that we can use tree indexes with composite keys. And if I sort keys by composite, if the key is a composite of multiple columns, then it means that those entries which have the same or similar values in a prefix of the key columns, they are still stored close together. And that is why I can use those tree indexes also in order to treat predicates that refer to a prefix of the composite key columns. Now let's see how that works for hash indexes. Now hash indexes are based on hash values. That makes them useful for equality conditions, because if two entries have the same key, then the hash value is also exactly the same, and that means they will be stored in the same bucket. Now, on the other side, if two keys are similar, close together, it does definitely not mean that their hash values are close together in any way. And that means that they will probably be stored in different hash buckets, even if their key values are relatively close. And since similar keys are not stored close together, it makes it inefficient to try to use hash indexes for inequality predicates. Also, if you have composite keys, then if you have the same value in a key prefix when comparing two entries, it does not mean that they will be stored in the same hash bucket. Most likely, they will be stored in different hash buckets. And this is why you typically want to use hash indexes only if you have conditions on all the columns of the composite key. So in a way, hash indexes are a little bit more restrictive in terms of the predicates that you can use them for when comparing to tree indexes. Now in the following, we're going to see a couple of different hash indexes. We are going to see 3 different variants. This is a high-level overview. In the following, we're going to go into detail. We are going to start by looking at something called static hashing. And as the name already indicates, it's not a good idea if you have very dynamic data with lots of insertions and deletions. In those cases, you probably want to use something like extendable hashing. Now, this one has one drawback, which is that if you keep inserting data, then every once in a while, you need to perform one expensive operation in order to update the index. And we will see later precisely what that operation is. Then we have something called linear hashing. And this one has the advantage over extendable hashing that it extends the index very smoothly without costly operations. It has a couple of other drawbacks, but we're going to discuss them in detail in the following. So those are the hash indexing variants that we will look at in the following. Static hashing is perhaps the simplest one among those variants. Essentially, you have pages associated with hash buckets, and they store the references to the data. Or what is also possible, like in the case of tree indexes, you might even store the data just directly. Now, the hash bucket pages, they are associated with specific value ranges. So the way you use one of those indexes when looking for entries with a specific key value is that you first of all calculate the hash value for that key you're looking for. And then you look up the bucket page which is associated with the hash value. This is a little illustration here. Again, we are storing entries about students. And on the left-hand side of the screen, you have the hash function, which associates specific student names with a hash value. Just to make sure, this hash function is not explicitly stored as a table. You only calculate it based on the bits that are directly available in the key. I'm just putting the hash function here for convenience, but it is not actually stored anywhere in your database. What is stored in your database, that are those pages that you see in the middle of the screen here, page 0 to page 3. And here we use the simple system that the page ID corresponds to the hash value modulo, that's what the percentage sign symbolizes, modulo the number of buckets. So for instance, if you want to store student Alan, you look up in the hash function, okay, Alan would have a hash value of 1, and 1 modulo the number of buckets, which is 4 here, that would still be 1. So we will store Alan in page number 1, and this is indeed where you can find him. Or Bob, for instance, has hash value of 0. So here we store it on page number 0. Let's maybe have a look at one more. Dora has a hash value 5, and 5 modulo number of buckets, which is 4, is 1. This is why we would store her on page number 1, but we actually haven't stored her anyway. So the hash function here, it gives you the hash values for all the students that we will consider in the following examples. Here, in this example, we have only inserted a subset of students. So let's maybe see one more. For instance, okay. For instance, Salmon. So this one has a hash value of 4, and 4 modulo 4 is 0 again. This is why we store him on page 0, as you see here. So that is pretty intuitive. You calculate a hash value, and then you look up the associated bucket page. There you find your entry if it exists in the index at all. Now, let's see how those indexes change if we change the data, because the index always has to refer to the actual data. So if the data changes, then you must also change the index. Now, deletions are relatively easy. You just remove the associated entries from their associated pages. That always works. And I think there might be a question in the chat. What are keys with the same prefix? So that question refers to the composite keys, I imagine. We have discussed about an example last time, for instance, where we have one index, one composite index that allows you to efficiently retrieve customers in specific zip codes that have bought one specific product. So you have essentially conditions on two columns, and your index can use both columns as a search key. But if you have one of those composite search keys, then with three indexes, you have to choose an order between the different components of the composite index. And if you want to use the tree index, you can only do that if your predicates refer to a prefix of the composite key columns. So for instance, if you have indexed first by zip code and second by a product, then you can use that index in order to answer an equality on the zip code. But you cannot use that index to answer an equality on the product alone. You can only use it for predicates that restrict prefixes of the composite key. All right, sure. Okay, and back to the hash indexes. So we have discussed that deletions are relatively easy to do because it just removes the associated entry. Insertions are a little bit more difficult because maybe the page on which you would insert an entry is already full. So we have something which we call a page overflow. Now, in those cases, you somehow need to add additional pages to the index clearly. And you can do this using so-called overflow pages, which we have already seen in the case of tree indexes. So this is a very similar principle. Now, so the initial bucket page essentially stores a pointer to the first overflow page on which you have stored entries after insertion. And if you keep inserting entries, you might even need multiple overflow pages. So in that case, the first overflow page would store a pointer to the second overflow page. The second overflow page stores a pointer to the third one, and so on. So you will get a linked list of overflow pages in the end. At some point, that becomes inconvenient with so many overflow pages. So what you can do at this point is that you just essentially recreate the entire index from scratch. You rehash every entry that you have in your index, and then you can avoid overflow pages again. But that, of course, is an expensive operation. And while you're reorganizing your index, your database may not be able to accept the new input, which is very inconvenient. All right. And here's one question, very strictly speaking. The hash bucket, that is essentially some range of hash values, and then there is a page which is associated with that range of hash values. So they are linked, very strictly speaking. There's a subtle difference. All right. Now, this is an illustration of those overflow pages. Here you see we have expanded the index that we have seen in the last example. We have inserted more entries, and obviously we didn't have enough space anymore for those entries. This is why we needed to add overflow pages. And you see those overflow pages P101, 105, and P107 on the bottom of the screen. Those red arrows indicate pointers that are actually stored on those original pages, and they link to the first overflow page. If you would have multiple overflow pages, then they would form a linked list for the same hash bucket. So if we analyze the pros and cons of those hash indexes, then clearly what is good is that you can data with one single page read, at least as long as you don't have overflow pages. If you remember, for the tree indexes, in order to find the entries that we were looking for, we typically had to look at multiple pages, starting from a root node, then one node in each of those tree levels. So in a way, those hash indexes, if you calculate the hash function, you know which page to look at, so that can be very efficient. On the other side, of course, with static hashing, if you have overflow pages, then you might have to look on multiple overflow pages to find the entries that you're looking for, or in order to conclude that the entry you're looking for is actually not present in the index. In any case, you would have to look at multiple pages, and that is bad for performance. We also have said that deletions are easy because I can just take out the entries. But of course, it means that at some point, I might have lots of empty pages. That was already a problem that we quickly discussed in the context of the static tree indexes that we have seen. So if you delete more and more data, at some point, you will be wasting space because you have lots of pages in your index that are either empty or is near to empty. What you can always do is that you rehash everything, you recreate your index from scratch, but as discussed, that is quite expensive. Now, an alternative which works better for dynamic data is a so-called extendable hashing. And here the idea is that we introduce one new level of indirection. We introduce a directory which links a specific hash buckets to specific pages. So instead of calculating the hash value and then directly looking up the corresponding page, you would calculate the hash value, then you would look up in the directory which page is associated with that one, and then you would look up the corresponding page. Now, what it gives us, this directory, is essentially more flexibility about how I handle situations in which I need to add pages to the index. So essentially, if I have one specific page that is overflowing, then I introduce a new page and I rehash the entries that were on the original page together with the new entry that I'm currently inserting in order to balance those entries just across those two pages. As I'm adding more pages, every once in a while, I need to increase the size of the directory. It then can be a little bit expensive, but in each case, it is much cheaper than having to rehash, having to recreate the entire index from scratch, which is what static hashing has to do. Let's make things a little bit more concrete by an example. So in this example, I have extendable hashing, and on the top of the page, you see the directory pages. Right now, that's only a single one, page 120. And on the bottom of the screen, you see the bucket pages, page 131. Now, right now, we only have one single page that stores data entries, which is page 131. So the directory only has one single entry. Here on the left-hand side, you essentially see the hash values that we are associating with a page. And in the right column, you see the corresponding page that we are referencing. And to make the following easier to follow, here for the moment I have written the hash values in the hash function according to the normal system. But now let's actually switch and write those hash values in the binary system, because it will make the following examples more convenient to represent. So here we had the hash values between 0 and 7. That means I need 3 bits in order to represent that. And right now in the directory, you see on the left column, we have those 3 stars. And by that, I mean that here we are associating all entries independently of their values for those 3 bits of the hash function with page number 131. Now we have just inserted student Alan into the index, which you see on the bottom of the page. Now let's insert a student Bob next. All right, so here nothing much happens. We insert Bob on page number 131, which is the page associated with all hash values as indicated by the directory ****. So we can have any values for the hash bits. All right, now let's just insert the next student in alphabetical order, which is Chen. And again, we can insert the student here on page 131. Now it becomes interesting because if we insert the next student, Dora, we don't have enough space anymore on page 131. That means we need to introduce a new page, but we don't want to introduce an overflow page. So we need to add an associated entry to the new page in the directory. So now let's do this. And here you see on the bottom, I've introduced a new page 133. And in the directory, I have introduced a new entry. So and now we have 2 entries. So we somehow have to associate them with non-overlapping value ranges of the hash function. So here we say that page number 131 is associated with all entries whose hash value ends with a 0, and page 133 is associated with all entries whose hash value ends with a 1. And here on those pages 131 and 133, I have distributed the entries accordingly. I needed to distribute the old entries on page 131 and the new entry, student Dora, that I have just inserted. And you see, for instance, Bob has a hash value of 000, so it ends with a 0, and that means we put it on page 131, while Alan has a hash value of 001. So we have to put it into page number 133. All right, so let's insert David. And David has a hash value of 001, so it ends with a 1, and we should insert it according to the directory into page number 133. All right, now next student is would be Esther. If we insert Esther, then something interesting happens, because Esther, the hash value ends with a 1, and it would need to go into 133. But that page is already full, so I have to add more pages. If I add more pages, I again need to assign them to non-overlapping value ranges in the directory. So far in the directory, I have only considered one single bit, the last bit. And that was sufficient in order to distinguish 2 different pages. But now if I add a 3rd page, then like 1 bit is not sufficient anymore to distinguish between 3 pages. So that is why the directory will need to consider 2 bits now. So let's do this. So we are adding 1 new page. We quickly move the chat so I can recognize the page number. And that page is 139. And in the directory, we have expanded the directory, because now we need to consider the last 2 bits instead of only the last bit. And as you see here, I'm associating those different pages with non-overlapping value ranges. Now, one interesting thing here happened. So the new student that I wanted to insert, Esther, would have to be inserted in page number 133. So this specific page was overflowing with entries, and that's why I actually only wanted to split that specific page. On the other side, page number 131, that one still has some space available and it is not overflowing. This is why we have not split page number 131. And if you look at the directory, you see that essentially all the hash values ending with 0, 0, and all the hash values ending with 1, 0, they are both assigned to the same page number 131. Eventually, once we add more entries, then we probably need to split 131 as well, and then those entries in the directory change. But for the moment, there's like 2 entries in the directory that point to the same bucket page. All right. So let's insert a few more students. It's the same principle. Now we've inserted Felix, and now we are inserting Gerd. And Gerd has a hash value 0, 1, 0. So that means it would have to be inserted into page number 131. But now that page is also overflowing, so we need to split it into 2 pages. And we are doing this by adding one more page in the bucket pages and redistributing the corresponding entries. And as you see here, now we have updated the directory, and page 131 only has 1 entry left. The other entries have moved to page 126. So, and now we can insert a little bit more, and at some point we have too many bucket pages to index them with 2 bits alone. So at that point I need to expand the directory further in order to consider all 3 bits of the hash function. And if that happens, I also have to increase the size of the directory, and as you see here, now the directory considers all bits from the hash function. There is some pages that are linked to repeatedly in the directory, for instance, page number 131 again, and there's other pages that are linked to only once, depending on how many insertions we had for the corresponding range of hash values. So this approach is pretty flexible. I encourage you to have another look at this example. But the main point really is that we have this directory which associates hash value ranges with specific pages. And having this directory gives us a lot of flexibility in order to only split those specific buckets that are currently overflowing. Now, here you have a little summary of this insertion algorithm that we have already executed so far. So the way it works is that you always start by first calculating the hash value for the new entry that you're currently trying to insert. Then you look into the directory in order to identify the associated page. And if that page still has some space, great. We simply insert the new entry, no problem. If the page is currently overflowing, it cannot store the new entry anymore, then it becomes more interesting. We always have to add a new bucket page, and we have to redistribute the entries on the page that is currently overflowing and the new entry on those 2 pages. In order to redistribute them between those 2 pages, I consider one more bit from the hash function. And if needed, I might have to expand the directory if currently the directory considers less bits than what I have used in order to redistribute the entries after the insertion. There's some terminology that is often used in the context of those extendable hash indexes. You also find it in the book. So I wanted to quickly link this description to that terminology. So we always have discussed about the number of bits that are considered in specific cases. Often people say that global depth, this is the number of bits from the hash function that the directory currently considers. And the local depth for one of those hash bucket pages, that is the number of bits that you need to consider in order to be sure that an entry is located on that page. So let's quickly make that a little bit more concrete by the example. For instance, here, this is the state that we finished in. And in the directory, you see that we have a global depth of 3 because the directory is currently considering 3 bits. On the other side, you have different local depths for the different bucket pages. For instance, take page number 131. So this page is referenced twice in the directory on the first directory page and on the third directory page. I actually just spotted that we have like multiple directory pages with the same page ID, which should not be. So you should have different pages, of course. That's a little typo. But we see that we have a page number 131 linked to twice in the directory, once for the hash values 000 and once for the hash values 100. That means whenever you know that the last 2 bits of the hash function are 00, you can be sure that the corresponding entries are associated with page number 131. So in order to know that page number 131 is interesting to you, you only need to consider 2 bits, and that is why the local depth for page number 131 is 2. On the other side, if you are taking page 133, for instance, then that page is only linked to once in the directory. And that means that in order to be sure that this is the interesting page for the entries you're looking for, you have to consider all 3 bits from the hash function. And that is why the local depth for page number 133 is 3, because you have to consider 3 bits in order to be sure. All right. Now, this is how insertions are handled. And maybe one last word on global versus local depth. You can say that the condition which causes you to expand the directory, that is always if the local depth becomes greater than the global depth. So the global depth of the directory must always be an upper bound on the local depth of all of your bucket pages. That is one way in which this terminology becomes useful. All right. So now we have discussed about insertions into those extendable hash indexes. Now what about deletions? Clearly, if we have enough deletions, then we could merge together again some of those bucket pages if the number of entries on them is low enough in order to fit on one single page. At some point, if I keep merging pages and the number of pages therefore shrinks, I might even be able to reduce the size of the directory. In practice, however, people often assume that insertions are more common than deletions. And so the implementations that you find in practice, they might often not do anything sophisticated in case of deletions. But handling insertions well, that is pretty important. Now, if we analyze the pros and cons of that index, so a first pro, of course, is that we avoid overflow pages. And on the other side, we don't need any expensive rehashing. So when we redistribute entries, it's always only the entries on one of my pages. So that means quite reasonable overhead. On the other side, of course, I'm introducing a directory. So I need one additional access in order to look up things in the directory. And every once in a while, and that is more important, I need to double the size of my directory if the local depth exceeds the global depth. Now, doing this operation double the size of the directory, that takes some time, which is inconvenient. Of course, it is much faster than having to recreate the entire index from scratch, which is what static hashing might do. But nevertheless, it is a little bit inconvenient. So the idea of the next hash index method that we will consider is to avoid this occasional overhead of having to double the size of the directory. Maybe one last question before we switch to the next hashing index. On the last slide, I wrote that we can avoid overflow pages, at least often. The question is, can we always avoid overflow pages with that kind of index? Or is there situations where we cannot avoid them perhaps? Okay, yes. And I already see the right answer here in the chat. Very good. Exactly. So the thing is that hash values are generally not unique. So you might have a hash collision where multiple entries map to the same hash value. And in those cases, there is no number of bits that you could consider in order to separate entries from each other. Then you might not have another choice than to use overflow pages. Of course, you might wonder, maybe if I use a different hash function, I wouldn't have that problem. But in the end, you might even have like multiple entries for the same key. If you think about the enrollment table, where we might have multiple entries for the same student. And if you have too many entries with exactly the same key, then even the best hash function, of course, will not help you anymore. And then you actually have to work with overflow pages. Very good. All right, let's continue with so-called linear hashing. So that is the last hash index method that we will see. So the idea here is that we essentially get rid of the directory again. Now, in a way, it is the directory that gave us the flexibility to choose which specific pages, which specific buckets we wanted to split after insertions. So if I get rid of the directory, then it means I also have to give up some flexibility in choosing which buckets I split next, because I don't have a directory anymore to keep track of that. So what I do, therefore, is that we are selecting buckets to split according to a round-robin principle. And in particular, that means that I might not even be able to immediately split one of those buckets that are currently overflowing. So that can seem inefficient, and it sometimes is. You have bucket number 5 is overflowing, but the next bucket that you have to split is bucket number 1. That might be currently almost empty. So nevertheless, since you are fixed to one specific order in which you need to split the buckets, it means that you would have to split bucket number 1, and you would have to introduce an overflow page for bucket number 5. Of course, eventually, if you keep splitting buckets, then after a while, you will reach bucket number 5, and then you will probably be able to get rid of the associated overflow page. But at least temporarily, you will have to allow for some overflow pages. But typically, they don't persist for very long. So that is the high-level idea behind linear hashing. Now let's see a little illustration for how that works. So generally, splitting proceeds in so-called rounds. And on the left lower corner of the slide, you see the round counter. A round essentially ends once you have split all the buckets that existed at the beginning of the round. And you see there's a big red pointer pointing to the bucket that will be split next. After a round is finished, we will reset that pointer to the first bucket again, and then the next round starts. So right now, we only have one single bucket that exists at the beginning of the round. And those 3 stars here mean again that this page here is supposed to contain all the entries for any value of those 3 hash bits. All right, so now let's assume that we have insertions, and therefore we need to split this bucket over here. So now we are splitting this bucket, and we are splitting it into two buckets, one of them associated with hash values where the last digit is 0, and one associated with hash values where the last bit is 1. And now, since we have split the only bucket that existed at the beginning of round 1, we also immediately enter round number 2, as you see in the counter here, and we are resetting the split next pointer to the first entry, to the first of our buckets here. Okay, so now assume that we have even more insertions into our table and therefore into the associated index. So now we have again to split the bucket that our pointer is referencing. So now we have one bucket that is associated with hash values ending in 0, 0, and one bucket that is associated with hash values ending in 1, 0. All right. So we are still in round 2. We are now pointing to the last bucket that existed at the beginning of the round here. And after we split that one as well, we are resetting the counter again, and we are entering round number 3. So now we have 4 buckets that are associated with the 4 possible value combinations of the 2 last bits of the hash function. Okay, and now we can continue this, and we can split the first bucket here and the second bucket here and so on. But the principle is the one that is summarized here. So if we want to insert something into one of those linear indexes, then first of all, we calculate again the hash value for the new entry to insert. And then we add this entry on the associated page, or if that page is full, we might have to introduce an overflow page, hoping, of course, that this overflow page will be eliminated relatively soon. Now, if some kind of trigger condition is satisfied, we decide to split the next bucket. We have no choice about which bucket we can split. We can only split the bucket that our next split pointer is referencing. And there's some flexibility in how we can choose that trigger condition. For instance, we can say that we trigger a bucket split whenever we had a certain number of insertions, or we could say that we trigger a bucket split if we have one page overflowing. But as discussed, it is very important to understand that even if one page is overflowing somewhere, this is probably not the page that we will be immediately splitting. So only over time will we get rid of those overflow pages if we continue splitting buckets. All right. So those splits will eventually eliminate overflow pages. And as we have discussed, the splitting generally proceeds in rounds. So if we have split all the buckets that existed at the beginning of a round, then the current round ends. And if the current round ends, then as we have seen in that little illustration, we reset the pointer to the next bucket to split to the first of the current buckets. All right. And the bucket that we split next, that is always the one that we are pointing to. If we add a new page, then we generally redistribute the entries from the split bucket, and we do so by considering one more bit from the associated hash function. So that is the principle behind linear hashing. And if we compare the pros and cons, then the nice thing about linear hashing is that it avoids the directory, so we don't have any expensive directory doubling. It has the drawback that it might temporarily admit overflow pages, and it sometimes may split pages that are empty or near empty. which means that I probably use up more space than is necessary. So those are a couple of drawbacks, but nevertheless, this is a pretty convenient hashing method. Now, we have discussed about a couple of optimizations in the context of tree indexes, and in principle, we can use all of those optimizations for a hash indexes as well. For instance, if we have many entries for the same search key value, then we can store that key value once, followed by a list of references. So we have also that possibility for tree indexes. The advantage is that I store less redundant data. A disadvantage is that I might transform a fixed length entry into a variable length entry, and that means I would have to store additional metadata on my page in order to save where this list starts and where this list ends, for instance. Also, so far we have assumed that my data entries in the index, that they essentially store references to the actual data. But that is not necessary. I can in principle also store the actual data directly. Now, this is what we also call a clustered index. As long as you don't want to store duplicates of your data, which you generally avoid, it means that you can only have one of those indexes per table, because that index is essentially merged with the table data, right? So that makes retrieval more efficient because you save one lookup, and also you are guaranteed that the data with the same index search key is stored close together. Otherwise, the references might actually point to very different areas of your data set. In general, even if you don't store the data directly in the index, it will help you if your data is sorted according to the index search key, because that means things that are stored close together in the index will also be stored together in the original data set. And that makes it quite efficient to retrieve the associated data with a few page accesses. So if the order of the data is consistent with the index search key, then that is also called a clustered index in general. And here retrieval is also more efficient in general than if that is not the case. So those are just a couple of optimizations in the context of hash indexes, and they're essentially the same optimizations that you can apply for tree indexes. Now, a little word on how you can use those indexes in Postgres, and I'm going to show a quick example about that next time. So in Postgres, you can generally choose the type of index that is generated. By default, it will generate B trees, but you can specify explicitly which type of index you wanted to generate. So with the syntax here, create index, then the name of the index, then on the table that the index refers to. And if you insert here using method, the method can be, for instance, btree or hash or other methods that are discussed in the documentation. Then you can choose what type of index you generate. And again, here between parentheses, you can specify the columns that your index should refer to. So if you want a composite index, you can specify multiple columns here. All right. And now we have already reached the end of the lecture time. So I'm gonna show you quickly how to use those indexes in Postgres next time. The next homework will focus on indexes. So I encourage you to revise the indexing material a little bit over the weekend. And otherwise, have a great day and see you next week. All right. So the last time we have been discussing about index data structures, more generally about how the data is set up on hard disk in order to make access efficient. In order to work with the data, we first of all have to bring it into main memory. More precisely, we even have to bring it to the processor. But today we're going to talk about how we bring the data into main memory. And there's one component in the database system that is the buffer manager, which controls data movements between hard disk and main memory. And moving the data is necessary in order to compute with it. Now, the relevant chapter in the Ramakrishnan and Gehrke book, that is chapter number 7.4, we're going to first discuss about the buffer manager, and then later today, if we still have enough time, we will start discussing about the query processor component. So let's first chat about the buffer manager. Now, the buffer manager generally decides when to move data between hard disk and RAM. The buffer manager tries to be smart about that. It tries to minimize the number of data movements. And for that, it uses a couple of heuristics. We will see one of them in order to try to estimate which pages are most valuable and should be continuously stored. The name buffer manager connects to the term a buffer pool. And the buffer pool, that is an area in main memory that is reserved for the database management system. So this buffer pool, it is essentially divided into so-called frames. And those frames, they essentially, they have enough space in order to store one of those pages. And the page that is generally the granularity at which we receive data from hard disk. So the buffer pool contains lots of slots, those frames where you can store pages, and it contains some metadata about each of those slots. Now, here you see an illustration of the buffer pool. So the buffer pool essentially gets requests from higher levels in the database management systems, and those requests, they are about specific pages. So once the buffer manager receives a request for a specific page, it needs to make that page available in main memory. The buffer manager stores pages in the buffer pool that you see here. At any point, some of those slots, some of those frames might be empty, while others are used up by a page. So when getting requests, the buffer manager would first check whether the corresponding page happens to be already stored currently in the buffer pool. And if not, it will fetch it from the hard disk here. Now, the buffer manager stores some metadata about the content of those different frames. And it also uses internally some heuristics in order to decide, for instance, which pages in the buffer pool to erase in order to create space, and which other pages to keep. So that is the replacement policy. And we are going to discuss about the metadata and about the replacement policy in the following. Now, those are the properties that we store about each of the frames. First of all, of course, we want to store the ID of the page that is currently stored in the frame, if any, because that allows the buffer manager to match incoming requests for specific pages to frames in which the corresponding page is stored, if we are lucky. Also, we store for each of the frames a so-called pin count. The pin count essentially tells you how many processors, how many clients, so to speak, are currently using the content of that frame. And if there is still people using the content of the current frame, then that prevents us from erasing it and replacing it with something else. So the pin count serves as kind of a safety guarantee that people don't suddenly have a page erased that they are currently working with, right? So we can only evict, meaning prune out from the buffer pool those pages where the pin count has reached 0. Also, we store a so-called dirty bit for the frames, for the pages that are stored in those frames. And that dirty bit essentially tells you whether the in-memory page was changed since it was loaded from hard disk. And that is important because changes in main memory are generally volatile, which means that they don't persist if power suddenly switches off, for instance, or of course, if you erase the corresponding page. And the dirty bit essentially tells the database management system that there is some changes on a page which would be lost immediately if the power suddenly switches off. And it also tells us that if we want to erase the corresponding page, then in order to make the changes persistent, we first have to copy the current page to hard disk in order to overwrite the original version of the disk of the page usually. Right? So the dirty bit tells us whether there's any changes that we need to back up before we can erase the corresponding page. Now, this is the algorithm that the buffer manager essentially executes. Whenever we have a request for a specific page, then the buffer manager first of all checks whether this page can be currently found in the buffer pool. In that case, we call it a cache hit. This is case number 1 here. And in that case, it is actually pretty short. What we have to do, we just increase the pin count for that page, meaning there's like one more process interested in that page. And then we simply return the address of the page to the requestor, and then the buffer pool is done. So that is the efficient case. Now, if we have a cache miss, which means that the requested page is not yet stored in a buffer pool, then things become more expensive. The first thing the buffer manager needs to do in this case is to choose a frame for replacement. Of course, in principle, it could be that we have certain frames that are currently unused, that are empty, so we can simply copy a new page into them. Now, when running your database management system for a while, then that is atypical. Typically, your entire buffer pool is taken up. So in choosing a frame for replacement, you're essentially saying that the current content of that frame seems non-interesting, and it can probably be deleted. So that is an important decision for performance, which frame you want to replace. And we're going to discuss more about that on the coming slides. Now, after we have selected a frame for replacement, we have to check the dirty bit, because it could be that the current content of that frame had some changes which haven't been persisted to hard disk yet. So if that dirty bit is set, then we first of all need to write the current frame content back to hard disk. There's one question here in the chat about whether a frame can have more than one page, but those frames, they are chosen in size such that they store precisely one page. So you can have many frames, but each of those frames typically stores only one page. All right, and the address of the page that is returned, yes, that would be often the address of that corresponding memory location. All right, so now we potentially had to write the page back to a hard disk in order to persist the latest changes. After we have done that, we read the requested page from hard disk, and then we write it into the frame in the buffer pool. And still we need to increase the pin count in order to make sure that this page is not suddenly evicted. And finally, again, we return the corresponding address. So this is the algorithm that the buffer manager executes. At this point, you might be wondering whether we couldn't use functionality offered by the operating system. So if you have ever taken an operating systems course, then you will probably have talked a lot about caching. So there's some functionality in the operating system that does something a little bit similar. So the question is, why do we need a specialized component for the database management system? And there's two principal reasons. The first reason is that the database management system has often very specific access patterns. So we'll see in the following that the generic strategies by the operating system often don't work so well for database management system. So a first reason is efficiency. The database management system is particular in its access pattern, so we probably want to implement a specialized buffer management strategy. Another thing is that the database management system makes very strong guarantees to users about having data secure, even in case of a server crash. And in order to make those guarantees, which we'll discuss in much more detail later, the database management system needs very tight control over when pages are written back to hard disk or loaded from hard disk into main memory. So it needs very tight control over that in order to make those guarantees. And that is often not offered by those generic components. Now, for instance, to make that a little bit more concrete, one very popular replacement policy, that's the following one. We call it the least recently used replacement policy. So in general, what you ideally want from the buffer pool manager's perspective is to always replace those pages in the buffer pool which will not be required for the longest amount of time. So you want to drop those pages which will not be required for the longest amount of time. That, of course, is difficult to predict in general. So we typically use heuristics, for instance, by saying, if I haven't accessed one page that is currently in my buffer pool for a long time, then I am unlikely to do so again anytime soon. So that is the least recently used heuristic, and it essentially means that if I have to decide where to create space, for instance, in the buffer pool or somewhere in memory in general, then I'm always deciding to override that page which hasn't been used for the longest amount of time. So that is the least recently used heuristic, and it is a very popular replacement heuristic used, for instance, by operating systems. Now, one case in which that one works badly, and unfortunately, that case is quite common in the context of database management systems. That is cases where I repeatedly scan the same pages. Now, that might seem strange because why would you read something again after you have just read it? But there is common cases in a database management system where you want to do exactly that. For instance, if I'm joining together the relation, the table with the students and the table with the enrollment information. So I'm searching for enrollments matching the students. Then one popular way to proceed would be to first load one chunk from the students table into main memory, and then iterate over all the pages of the enrollment table in order to find matching pairs. And once we have done that, then we load the next chunk of data from the students table and again iterate over the pages in the enrollment table. Then we take the third chunk from the students table and again iterate over the pages from the enrollment table. So this is a case where we will keep iterating over the pages in the enrollment table multiple times in a row. And here, if we keep repeating essentially in a cycle over the relation, over the pages in the enrollment table, it means that the page that I have not accessed for the longest amount of time is always the page that I will read next, because I'm essentially doing a cycle in the enrollment table. And because of that, always deleting the page that I haven't used for the longest amount of time is of course highly suboptimal. That is what the least recently used policy does. So this is just an example for a policy that seems perfectly reasonable in general, but that sometimes works very badly in the context of database management systems. So this is a common access pattern for database management systems, and the interplay between that pattern and this policy, the least recently used policy, that is also called sequential flooding. Okay, and here I have one more question in the chat. What happens if the buffer gets full and no frames can be evicted? Will reads come directly from disk? That is a great question. So there might be a situation where I have a pin count greater than 0 on all my pages in the buffer pool, and then I still have some requests coming in. Frankly, in those cases, it depends on the implementation, but often the database management system would just essentially reject any further work until the memory situation improves. Right? So, I mean, in the end, you always need a little bit of space in main memory to store those pages from hard disk. And if you currently don't have main memory, then you probably want to first process the current tasks before you accept new tasks. So the database management system would often reject further requests. All right, great question. And here, with this example, sequential flooding, we essentially see by using generic buffer strategies for replacement does not work very well in the context of database management systems. All right. So that was a high-level overview of the buffer manager, which is the component that connects the hard disk to main memory. Now, in the following, we're going to start discussing in a lot of detail about the query processor in this and in the following lectures. This is the component here encircled in red, and the associated chapter in the Ramakrishnan and Gehrke book, that is chapter number 12. So at a high level, this is what happens when a database management system is processing an input query. So first of all, your input query is parsed, meaning it is internally translated into a tree representation. And then the database management system uses a couple of heuristics in order to simplify that query. This is what the rewriter component does. Now, the query optimizer is more sophisticated than a rewriter. It also changes the query in order to make it more efficient, but it does so using much more sophisticated methods. In particular, it typically tries to predict the execution cost of different plan alternatives, and then it selects the cheapest one. We will discuss about this in much more detail later. After we have selected a processing plan for the input query, we forward it to the execution engine, which executes it step by step in order to produce the final query result. Now, those query plans that are processed by the execution engine, they essentially describe how data is generated. They describe that process step by step. We typically represent them as a tree, where each leaf node of the tree corresponds to a data source, to a table in our context. The inner nodes of the tree, they represent operations, and the tree edges connecting different nodes, they essentially represent data flow. The inner nodes in the query tree correspond to operations, and in order to process data, database management systems use a fixed set of standard operators. Each of those operators consumes one or two, in case of joins and some others, relations. And the output produced by an operator is also a relation. So this is why you can compose those operators, because the inputs are relations and the outputs are also relations, aka tables. So that means we can flexibly compose those different operators together into a tree. Now, a couple of standard operators that we will be discussing more about is, for instance, the so-called filter operator, which is typically abbreviated by the Greek letter sigma, and that one simply discards rows based on a condition. So it checks for each row whether it satisfies a condition, and if so, it keeps it, otherwise it discards it. Then we have the projection operator, and that one discards columns from a relation. And we have the join operator, which combines two relations by finding matching tuple pairs based on some condition, and so on. So this is some of the operators that we will be considering. And this is an example for one of those operators for one of those query plans represented as a tree. On the right lower corner of the screen, you have the associated query, which essentially combines students and courses over the enrollment information and restricts the focus to the CS 4320 course. And finally, it only wants to retrieve the names of the students which are enrolled in that course. So the data flow always goes from the bottom of the screen towards the top of the screen. So in order to evaluate this plan, we would essentially start with the leaf nodes, which correspond to tables that are already available in my database management system. So here, for instance, we can start with the courses table. And the first operation that is written here, that is this sigma operator with the condition written as subscript c.cid equals CS4320. So we are restricting ourselves to the course with that course ID. And as we have seen before, this little sigma over there, it represents a filter operation. So after this operator, we will discard all the rows which don't have the course ID 4320, right? Now, the output of the filter operation that is essentially coming out of the top of that operator box in the plan, and it is fed into a join operation together with the enrollment table. So this is a join operation, therefore it requires two inputs, and here we are joining those CS4320 course entries with the enrollment table. And the result of this join operator, that will be the pairs of matching tables. So here essentially I'm retrieving enrollment information for the CS4320 course. The next operation is also a join again. Here I'm joining enrollments with the associated students, and the input to that is the enrollment information for CS4320, as well as the information about all students. And the output of that join will be a pairs of students together with one CS4320 course they have enrolled in, basically. So what I'm ultimately interested in is only the names of the students who enrolled in 4320. So the final operation, the root of this plan tree, that is a projection operation written as this P. There I'm essentially discarding all columns except for the one that I have selected here, which is the student name. And therefore, the output of that plan is the names of the students enrolled in 4320. And that would be one out of many possibilities to answer the query below. There's different possibilities. For instance, we could change the order in which we apply the joins, or we could maybe do the projection. Or we could, for instance, do the filtering later in the plan tree. So there's different possibilities how I can process the query. All right. And whether there's some question in the chat about whether there's operators for adding columns or rows as well. So of course, your database management system internally has some operators in order to add rows. It also has operations that allow you to add the columns to a table. But in the following, we're gonna first of all focus on processing queries which do not change the data. Later in the course, we will also discuss transactions which might actually update your data. And there's a couple of new issues that arise in this context. So we will discuss about that. For the moment, we only discuss about queries that analyze your data. Great question. All right, so this is an example query plan that I wanted to show you. Now, the mathematical foundation for those query plans, that is called relational algebra. I'm not going to discuss relational algebra in too much detail, but I want to point out that connection. You can also find more details in the Ramakrishnan and Gehrke book. So essentially, relational algebra is a mathematical version of those query plans. It essentially represents a query plan as a mathematical expression. And just to show you how we would represent a plan like the one we have seen before in a relational algebra. So this plan that we have just seen, if we want to represent this as a relational algebra expression, this is how it would approximately look like. So those relational algebra expressions, as you see, they use the same symbols for the operators that we have also used in the plan tree. They are, in a way, a more concise way of representing those plans as expression rather than as tree. The semantics is that we start evaluating those expressions from the inside, and then we work our way towards the outside. So here we would first start with one of the innermost expressions, which would be this filtering operation applied to C, which is the courses. Then next would be, for instance, next would be the join on the course ID, and then we would join the result of that with the student ID, and finally we would apply the projection. So it's the same thing, but represented differently. So I'm not going to go too much into detail, but I wanted to show you one relational algebra expression at least, and explain how that relates to query plans. All right. Now, this was a high-level overview of query processing. Now, in the following, we're gonna discuss a little bit more about the different components of the query processor, and that will keep us busy for a couple of lectures. Now, in the following, we're gonna start talking about the execution engine, because in order to understand, for instance, how the query optimizer makes its choices and so on, you first need to understand how query plans are processed in the execution engine and what the performance trade-offs are. All right. Now, the first thing we will be discussing about is how we can actually implement those standard operators that we have just seen. I told you that database management systems, they use a set of standard operators in those query plans. And typically for each of those standard operators, like the join, for instance, you would have not one implementation, but many alternative implementations. And this is what allows the database management system to choose in each situation that implementation which is most efficient, right? So that is the reason why you want to have different implementations. For each case, you have an implementation that is just right for that specific case. So we will discuss about a couple of different algorithms. We will also discuss about how to estimate the processing cost for those algorithms, because some of those algorithms that we will be discussing, They might seem a little bit unusual at first. And in order to understand why they are designed the way they are designed, we need to discuss about how we estimate the processing cost for those operators, because otherwise those algorithms won't make sense. So we will discuss about the implementation and about cost estimation. We will use a very simple cost model in the following. It is simply based on the number of pages that need to read from hard disk in order to execute an operation. Now that is of course a simplifying, but it is quite reasonable in the context of traditional database management systems, because there we assume that your data is mostly stored on a storage device like a hard disk that is actually quite expensive to retrieve and to store data. And that means that the main processing overhead in practice is often the overhead of moving data from hard disk into main memory. You might also have some overheads due to the actual processing, for instance, but data movement overheads often dominate total processing cost in those situations. And that is why we will simplify by estimating cost as the number of pages that have been read or written to hard disk. The first operator that we start discussing, that's the filter operator. The corresponding algorithms are simpler than, for instance, for the join algorithm, but we will see that there's already a lot of different ways of executing a filtering operation. So in general, when we filter, we want to retrieve rows that satisfy a certain predicate. And a priori, there's different ways to go about that. The simplest possibility is that I just scan all pages of the corresponding table. And for all the entries on each page, I check whether they satisfy the predicate or not. If they satisfy the predicate, then I add them to the output. That is the simplest alternative. Now, if I know, for instance, that my data is sorted according to a column that appears in the predicate that I'm interested in. For instance, I'm searching for information on one specific course, and my data is sorted by courses. Now, if that is the case, I can typically do something smarter, and I can apply some kind of binary search, as we have already quickly discussed in the lecture on indexes. I can use some binary search in order to quickly identify the page on disk where the information, where the first entries for the course I'm looking for are located. So that is often already more efficient. And of course, if indexes are available for the right table and for the right predicate and the right type of index, all of that, in those cases, I can use indexes in order to find the data faster, depending on the properties of the data and of the index. All right, so that is the high-level outline. In the following, we're going to make that more concrete and estimate processing costs for those different alternatives. Now let's start with a simple, or with an example here. So what we want to do is to retrieve enrollment information where the course ID equals 4320 again. Now, in order to get a hang of a cost estimation, I give you a few minutes in order to try to figure out how we can compute the cost for scanning the enrollment relation. So that would be the simplest way for executing this filter operation. Now, here on the upper half of the screen, we have a couple of numbers that are helpful in order to calculate that. For instance, we have the number of students given, we have the number of enrollments per student, we have the size per enrollment entry, and we have the number of bytes that we can use per page. Now, take a minute to think about how you would fill in those fields on the bottom of the page. In the end, the goal is to estimate the scan cost, but in order to make it a bit easier, I have essentially given you a different intermediate numbers that you probably want to calculate in order to get there. So I first would calculate the number of entries that you can fit on one page, and derive from that the number of pages of the enrollment table. And from that, you can quite easily derive the final cost. I'll give you a minute, and if anyone has questions beside that, please write them in the chat. So this cost estimation is something that the query optimizer would typically do in order to decide on the most efficient way for accessing a certain table. There doesn't seem to be any questions for the moment. All right. I think I can directly resolve it here. All right. So first of all, we typically want to estimate how many entries we can fit on a page in order to calculate cost. And that depends on the page size as well as on the entry size. Here we have 1,000 bytes per page, and each entry uses up 10 bytes. So we can fit 100 entries on each page. And since I have 60,000 students, and for each student I have 10 enrollments, that makes 600,000 enrollment entries, I can fit 100 of them on one page. So if I divide one by the other, I will end up with 6,000 pages. And since I'm simply scanning all the pages, and since I'm calculating cost as the number of pages accessed, that means that here I have a cost of 6,000 page accesses. All right. Now, perhaps some of you are wondering about why we don't count any cost for instance, writing the output of the operation back to hard disk or anything like that. Does anyone have an idea why we are not considering the output cost? So then please put it into the chat. Yes. Okay, some good propositions coming in here. Yes, okay, all of this are possibilities. Yes, exactly. So, I mean, in a way, the output cost essentially, okay, bottleneck is on the scanning. Yes, that is true as well. Yes. Okay, so all of those are great points. And also if you think about the way in which the cost information is typically used. Typically, you calculate cost in order to choose between different operations for the same query. Why doesn't it make sense to consider the output cost in order to choose between different alternatives? Exactly, yes. So in here, so all of those are great points, by the way. And I mean, perhaps the main reason in practice why we don't consider the output cost when using cost to compare different alternatives is that since all alternatives answer the same query, all of them must produce the same output. That is why the cost for processing the output is essentially a constant. And so that is why when calculating cost, we typically neglect any cost that is associated with the output that an operation is producing. All right, very good. Now, let's consider cost for the second alternative that we have seen. We have the same query, but this time we assume that our data is sorted by the course ID, and that is helpful because then we can do a binary search. So via binary search, we would essentially search for the first page containing the CS4320 entries, and then starting from there, we would scan all data in order of pages until we find the first entries that are not for CS4320 anymore. So again, I give you a minute before resolving the example. Here you have again the information on the upper half of the screen. We have the number of students, the number of courses. That information is new because now we need it. And the number of enrollments per student. Again, the size per entry and the number of bytes per page. All right. And here on the bottom, we have already the number of entries that you can fit on a page. We have the number of enrollment pages. Now I would recommend you to first calculate the number of search steps executed by binary search, then to calculate how many pages we scan starting from the first page after binary search has been finished. And from that, you can quite naturally derive the total cost. I give you a minute to think about it. If there's any questions, please put them into the chat. All right. So even if you didn't have yet time to do all the calculations, perhaps you had some time to think about how you would do those calculations. And let me resolve this. So since we are executing a binary search, the number of search steps is given by the logarithm of the number of pages. So in each search step, you're looking at a page and you're deciding whether the entries you're looking for are located to the left or to the right of that page, basically. So in each search step, we are essentially dividing the range of pages that we are interested in by factor 2. And that means that if I want to find one page on 6,000 pages, then after 13 steps, I will have definitely narrowed it down to one single page. And then I know where I can start my scan. Now, the number of pages that we scan, that essentially depends on how many entries I have for the CS4320 course. Now, here the information that I have given you is that we have 100 courses. So we can estimate that if we have 60,000 students, 10 enrollments per student makes 600,000 enrollment entries. And if I have 100 courses, then I can assume that in average, I have 6,000 enrollments for the CS4320 course. And since I can fit 100 entries on each page, 6,000 divided by 100 is 60 pages. So I assume that the result to this query contains 60 pages. And this is how many pages I need to scan after I have found the first page from which to start the scan via binary search. And then in order to get the total cost, you just have to count together the access cost for those two different phases of the algorithm. And then you end up with something which is already significantly cheaper than what we have seen previously. Now, one question to you would be where we have used simplification. I think I'm just going to answer that question for you. For instance, one way in which we have used simplification here is that we have assumed that we have the same number of enrollments for each course, because we simply said we have a total number of enrollments and we are dividing that by the number of courses to get an estimate for how many enrollments we have for the course that we are interested in. And that type of simplification is very commonly done in the context of query optimization, for instance. Once we try to estimate the cost of different alternatives, it is often not too far from the truth, but every once in a while it causes big problems. And we will talk more about the problems which are caused by incorrect cost estimates in the following. Here one question in the chat is why we cannot just do two binary search. I assume this means you are thinking of making one binary search to find the first page and one binary search to find the last page of the course that we're interested in. And that is a great point. The thing is this, we anyway have to scan the pages which are located between the first and between the last page, because those are the entries that we are actually interested in, and we have to read them from hard disk. And if we anyway have to scan those entries, we can essentially save the second binary search, because once we keep scanning entries, we will just notice that suddenly we find the first entries for a different course, and then we immediately know that now we can stop scanning. So we don't need a second binary search in order to find the end of the scan range. But it is a great question. Okay. All right. Now, in the following, I'm gonna we're gonna discuss more about cost estimation for indexes. We will also continue there for the next time, and we will see in practice how query optimizers make those cost estimates by a little demo. I'm quickly gonna introduce the next example, and if you're motivated, I encourage you to have a closer look and maybe try to figure it out yourself. You also have the solution in the slide, so you can find the solution there, but I encourage you to first give it a try to figure it out yourself. What I'm asking you here, that is to estimate the access cost with a tree index which has the data integrated into the index. So that's a clustered index. And here we have some additional information given compared to the previous versions. For instance, here you see we have the index fan out, which is the number of child nodes that each node in the index has. And then I recommend you to estimate the total cost by calculating the number of inner nodes that you visit in the index, the number of leaf nodes that you visit in the index, because each node corresponds to one page access, and then finally to calculate the total cost. All right, so we have reached the end of the lecture. I hope you're having a nice day, and I see you again on Wednesday. So for the moment, we are discussing about the query execution engine, the relevant chapter in the Ramakrishnan and Gehrke book, that is chapter 12. And we have started already last time discussing different operator implementations for the standard operators, because database management systems, they execute your queries by a sequence of steps where each of those steps is one of the standard operators. And for many of those standard operators, such as filtering something or joining two tables, you actually have many alternative implementations for the same operation, and that enables the database management system to always choose the most efficient one. Now, in order to understand why those algorithms are defined the way they are defined, we will discuss the algorithms, and also we will think about how we can estimate the execution cost of those algorithms, because then the algorithmic improvements that we will see over time will actually make sense. All right, and as we have also discussed last time, we will generally measure cost by the number of pages that are read and written to and from hard disk. All right, so those slides we have already started discussing that last time. We have started discussing about the filter operator, and we have seen that there's multiple possibilities to access the same table when trying to retrieve the rows that satisfy a certain condition. We can scan, we can use binary search, or we can use indexes. And the last time we have already looked at a little example for how we can calculate the cost of a scan, which essentially just is the number of pages that we need to read from a relation. So here we have the numbers from the example, and on this slide you also have more details about how you can get to those numbers in the example. All right, we have also discussed that the cost for the output, for writing out the output of an operation, is typically not counted, because that is the same for all alternative implementations of the same operation. We have also seen an example for binary search. Again, here you have the numbers, and here you have the steps that we did in order to get to those numbers. All right. Now, the next thing that I want to discuss about is indexing, and how we can use indexes for evaluating filter conditions. So here we have always this query where we select enrollments for which the course ID equals CS4320. And on the upper half of the screen, you have a couple of properties of the enrollment table and of the entire system. For instance, we know how many students and how many courses we have. We know that we have an average 10 enrollments per student, and we have some information about the size of those different entries and about how many entries we can fit on one of those pages. Now here, since we deal with indexes, we also need some information about the index fan out, which means the number of child nodes for each index node. And here that is 100. So given that we have 100 entries per page, we have already calculated that before, and that the number of enrollment pages is 6,000, think about how you would calculate the cost for using that index. So you have to think about how many inner nodes we have in the index that we need to visit, how many leaf nodes we have, and then what the total cost is. So here we assume that we are given a tree index, and it's one of those tree indexes where the data is already integrated into the index itself. So you find directly the data in the index leaf nodes. So I give you like a minute or so to think about how you would go about that. And question on the index type in the hash. So this is a tree index. Right? So maybe you might not have had enough time for doing the calculations, but perhaps at least enough time to think about how you would go about calculating this. So this is the solution here. We have a fan out of 100. That means the index root node has 100 child nodes. and it has 100 square, meaning 10,000 grandchildren. So that means that we have only an index of height 3 in total, and that means we only have to step over 2 inner nodes in the index before we reach one of the leaf nodes. And then for the leaf nodes, we just have to scan them in order to retrieve all result tuples. And already in the previous calculations, we have seen that the results to this query fit on 60 pages. So the total cost is 62 pages. We also have those detailed calculations summarized over here. All right. Now, last example on filtering. Let's assume that we don't have one of those indexes which integrate the data already, but let's assume that we have an unclustered index instead. So the entries in the index leaf nodes, they are not the actual data, but they point to the actual data, which means we have some additional overheads for accessing the actual data. So here, if you look at the lower half of the screen, you have the same number of inner nodes visited, the same number of leaf nodes read, but then additionally, we still need to access the actual data. And assuming that those entries that we are looking for 6,000 entries in total, that they are located on different pages, it means that I have to read all those 6,000 pages from hard disk. And that makes access with that index actually quite expensive. Here you have, again, a summary of those calculations. Now, altogether, we have seen different ways of answering the same query. We have seen that scanning the entire table can be quite expensive. Using binary search is already much cheaper. It requires, of course, that your data is sorted. Indexing, if the index is clustered and contains the data in the leaf nodes, that is actually quite cheap, typically. Using an unclustered index is typically more expensive, and often it is even more expensive than scanning an entire table. And in this case, that actually happens. So using the unclustered index is a little bit more expensive, at least, than scanning the entire table. So even if you can use an index, it's not always a good idea to do that. You always have to calculate the cost of different options and then select the minimum one. All right. So typically, it's not you doing this, but it is the query optimizer of the database system. Once it receives your query, then it thinks about all the different ways in which it can answer it. It tries to estimate the cost of different possibilities and to compare them and to select the minimum one. But every once in a while, query optimization doesn't work out. And then if you don't understand what's going on inside a database system, you will not be capable of fixing it. So it's good to know what is going on in the background. Now in the following, I'm going to show you a little example for different selection methods and how the query optimizer reasons about different ways of accessing the data. Let me quickly share my terminal. All right. Okay. And so here for this example, I'm going to use again the Stack Overflow developer survey table, which contains results of this developer survey conducted by Stack Overflow. Quickly going to show you some of the columns that the table contains. So each column corresponds to a different question, essentially. All right. And now, for instance, we had one column about the employment status. So perhaps at some point, I want to filter the entries in the table according to the employment status. And in order to make that fast, I might want to create an index on that column. So let's actually do that. So here we are creating an index on the employment column of the Stack Overflow table. The takes a few seconds, and now we have the index. I'm enabling timing. Okay. And now if I have, for instance, a query such as, I want to count the number of people that are retired, then probably internally the query optimizer might be using an index, because it seems that this query is very fast. And last time, in one of the last lectures, we have compared the time with indexing and without indexing. So without indexing, we had times of typically something around 100 milliseconds for queries on that table. So now here it is much faster. All right. Now, if I want to know more precisely what's going on internally, whether the query optimizer decided to use the index or not, you might want to try out the explain command. And the explain command essentially tells you how the query optimizer plans to answer a given query. So if I enter the same query as before, all right, then the explain command tells me essentially the different steps in the plan that the query optimizer intends to execute. Now, what we have here, you see the keyword index in here. So it seems that the query optimizer decided indeed to use the index over here with an index only scan. And the final operation in that plan, which always comes first when representing those query plans in this format, that is an aggregation, because I actually wanted to count those people. All right, so that is how the query would be executed. So for instance, I mean, since here by default I have created a tree index, I can also use that index for inequality predicates. So if I, for instance, replace the equal sign here by an inequality, then what would happen here is that the query optimizer decides to use the index as well. Now, tell me in the chat what you think will happen now. If I replace this inequality by an inequality into the other direction, do you think it will change anything? Can it even change anything? Anyone wants to make a guess? If I'm already asking about it, then probably something is going to change. So let's actually do that. All right. And here actually nothing is going to change. Okay. So it seems that if I replace this inequality by the other direction, then it is still the cheapest to use the index. But if I slightly change the query by adding, for instance, instead of counting the number of people who have a specific employment status, I rather want to select the specific respondent IDs of those people with a specific employment status. And if I do this over here, then you see that the query optimizer has stopped using the index because it seems to think that not using the index is more efficient here. So the thing is this, the index that we are using here is by default an unclustered index. So it will point to the data instead of containing the actual data. And as long as we use account aggregate, it means that we can only work with the index and count the number of entries that satisfy the predicate in the index. But as soon as I add different columns that are not directly a part of the index search key, we actually need to go through the leaf nodes in the index and retrieve the associated data from the data table. And doing that can be quite inefficient depending on how many entries you have to retrieve. So here with this inequality, I'm actually not using the index based on the query optimizer. If I replace it by this one, then it suddenly starts using the index again. So the thing is that here I'm using inequalities with the constant retired. So the letter R comes already pretty late in the alphabet. That means that probably less entries satisfy employment greater than retired than entries satisfying employment smaller than retired. And that is why in one case, the query optimizer decides to use the index. In the other case, the query optimizer does not decide to use the index. And together with the plan that the query optimizer executes, you also always see the cost estimates for executing those different plans. Here you have between parentheses the cost estimates and estimates about how many rows will satisfy the condition that you have in the query. So I mainly wanted to show you how you can get a sense for what's going on inside the database system, how the query optimizer decides to execute certain plans. You can get that with the explain statement. And as you see here, for multiple queries that are somewhat similar because they use the same constant and the same table and the same type of condition, still for some of them, the query optimizer will decide to use an index. While for others, it will decide not to use the index and just to scan all the pages of the table instead. So the query optimizer essentially does this kind of reasoning that we are also doing by hand in order to understand how that is done. And here there's a great question about whether we can force the query optimizer to use the index. Well, indirectly, yes, there's a couple of possibilities in Postgres to at least prevent the query optimizer from choosing certain operator implementations. So essentially, you will force the query optimizer to use the index if you disable all other alternatives. So in a way, yes, there's a way to force the query optimizer. There's other database systems that offer you more diverse possibilities to influence what the query optimizer is doing, but it is possible. All right, now let's go back to the slides. So now you should see the slides again. And on this one, I'm essentially making the point that we always need to calculate the cost of different alternatives in order to select the optimum, because it is a priori unclear what the best alternative is. Now, one last word on filtering. So far, we have considered cases where we have only one single predicate to answer. That is a little bit easier. In practice, you might sometimes have multiple predicates within the same filter operation. So in those cases, what still always works, of course, is to just scan all the pages from the table and to evaluate those two predicates on each entry. You can also make a mix. You can, for instance, use the index in order to retrieve entries satisfying the first predicate, and then you evaluate the second predicate on those entries that you just retrieve. Or you could even, if you have two corresponding indexes, for one index for each of the two predicates, then what you can do is you essentially retrieve the entries that match the first or second predicate from those two entries. And in the end, you merge them together and only keep the ones that appear in both indexes. So once you have multiple predicates, then you have more and more possible combinations if you also have indexes. When predicates become really complex, then typically in practice, the cheapest alternative is often to just scan the entire table and evaluate all of those predicates at once, but it depends on the particularities. All right, so those were a couple of different ways to do the filtering. Next, we are going to discuss about join operators. And we will actually discuss a lot about different join operator implementations, because that is in practice one of the most expensive operations in a query plan. And that is why there has been lots of research on different join operator implementations. And people have developed a whole variety of alternatives. Some of them are more generic and you can apply them for arbitrary join conditions. Others have advantages because they are faster for certain types of join predicates. And some are great because they need particularly little main memory while executing. So there's a lot of different pros and cons, and your database management system typically supports many different join operator implementations, and then it chooses the best one at runtime. So the simplest join operator that we will see in the following, that is the page nested loop join. And the idea here is very intuitive. So you want to join two tables. Let's say I want to join the student table with the enrollments with the join condition that the student ID should be the same, okay? So the way the page nested loop join works is simply this. I designate one of the two tables as the outer table. So let's say that is the student table, and the other table, that's the so-called inner table. We will see why they are called that way in a second. All right. So I would proceed by loading one page from the outer table from the students from hard disk into main memory. And then I would iterate over the pages in the inner table, load one into main memory after the other one. So the new page always overrides the previous page. And for all the tuples that I have in main memory, I will pairwise compare them, evaluate the join condition. And if it evaluates to true, then I add the corresponding tuple pair to the join output. All right. So that is pretty intuitive, but let's see some detailed code on this. So in the following pseudocode, I use the notations that you see here. We have a command for loading pages from hard disk into main memory. We have a command pages of T in order to get the set of pages associated with a table T. And the command tuples of P essentially retrieves the tuples which are stored on page P, assuming that this page has previously been loaded from hard disk into main memory. So we assume that at the beginning of execution of the join, all the data is located on hard disk because it doesn't entirely fit into main memory. Now, let's say that we want to join the enrollment relation with the students relation. So in this example, we actually made the enrollment relation the outer relation and the students relation the inner relation, because as you see in the pseudocode, I have essentially two nested loops, and that is where the name from the algorithm comes from. And then the table that I'm iterating over in the outer loop, that is called the outer table. So what I'm doing here is essentially I'm iterating over the pages of the enrollment table. For each of them, I'm loading the corresponding page into main memory. And now I'm iterating over the pages from the students table. And for each of them in the inner loop, I'm also loading it from hard disk into main memory. And then for all the tuples that are stored on the currently loaded enrollment page and on the currently loaded students page, I'm matching them pairwise and I'm evaluating the join condition, enrollment student ID equals student ID for that tuple pair. And if it is satisfied, I'm adding it to the join result. So that is the page nested loop join algorithm. Now in the following, let's analyze a little bit how we would calculate the cost of this operation based on the number of pages in the enrollment and in the student relation. Now, this load operation over here in the outer loop, that is executed exactly once for each page in the enrollment table, right? Because we iterate over all of them and each one of them is loaded once. Now, if you look at this load operation in the inner loop, that one is executed more frequently because here we are in the inner loop. That means we are iterating once for each page in E in the outer loop. And in the inner loop, we are iterating over each page of the students table. And therefore, this command here will be invoked a number of times that corresponds to the product of the number of enrollment pages and the number of student pages, right? So here on the bottom of the screen, you see that I'm calculating the cost. I'm adding up the different cost components. So I assume that I have some constant cost for loading pages from hard disk. And here I have counted the cost for executing that first loading command E times, pages in E times. And now I'm counting the cost for the second load command over here. What I also might, sorry, what I also might want to count, that is the cost for evaluating the join condition itself. So doing this doesn't require you to load data, but it has some computational cost. So here on the lowest row on the screen, I'm counting the predicate evaluation cost. And query optimizers like the one from Postgres would take this loading cost and this evaluation cost into account. Now here in this course, we use a highly simplified cost model. You're only looking at the number of data load operations. This is why in the following, we will neglect those cost components that relate only to computational cost. All right. So this is the cost of the page nested loop join algorithm, and it essentially just iterates in two nested loops over the pages of the two input relations. Now we can also think about how much main memory that algorithm would need. So first of all, we need enough space to store one page, the current page, from the outer table. And on the other side, we need the space to store the current page from the inner table, and not directly shown in the pseudocode, but what you also want in practice, that is one buffer page in which you can store join result tuples. So in principle, you could imagine like writing those join results directly to hard disk, but we know that data movements become much more efficient if we move larger chunks of data between hard disk and main memory. This is why in practice we would reserve a buffer, an output buffer page in main memory in the buffer pool, and we write tuples into that page. Whenever it is full, we copy its content to hard disk in one operation and erase the buffer again so we can insert more result tuples. So altogether what you need are those 3 pages, which makes this algorithm quite main memory efficient. Now, this is a little example here. Let me quickly move the chat a bit. So we have 1,000 enrollment pages and 100 student pages. So think a second about what the cost of the page nested loop join would be in this situation. And we assume that the enrollment table is used as the outer table. Okay. All right, and here you have the solution. So if you apply the cost formulas from the last slides, then you essentially need to count the cost for reading the outer table pages once. That is associated with this first load operation. And then you need to count the number of loads for the second load operation in the inner loop. And essentially for each page in the outer table, we are reading all the pages of the inner table. And that means this is 1,000 times the 100 pages. And in total, you get a relatively high cost compared to the join algorithms that we will see later of about 101,000 pages. Does anyone see an easy improvement to this cost? Just a small one. Oh yes, very good. Here there's immediately the right answer in the chat. Exactly. So what we can do is to simply swap the order of the join operands, because then I would replace this term 1000 here by the term 100, because if I use the student table as outer relation, then I only need to count the cost for reading the pages of that relation once. So here in this case, it doesn't make a lot of difference, admittedly, but still it is a little improvement, and all it takes you to do is to swap the order of the two join operands and make students the outer table instead. Okay. Now, this was the first join operator. The question is, how can we improve that operator further? Does anyone have any propositions about how we could improve this join operator further? Okay, very good. And that refers exactly to what we will see next. So here the suggestion is to essentially keep pages longer in main memory, because it is true that for some of those pages, we will keep loading them and then erasing them and then loading them and erasing them. So we actually load the same page many times from hard disk during one single join operation. And intuitively, that seems inefficient. All right, so let's see how we can improve over that join operator by keeping things longer in main memory. Now that leads to the so-called block nested loop join. And the main improvement compared to the previous algorithm is essentially the following. In the previous algorithm, we have read the inner table once for each page from the outer relation. Now, the block nested loop join instead reads the inner table once only for each block of pages from the outer relation, if it can fit that block of pages at the same time into main memory. And since one of those blocks contains multiple pages, doing this should be significantly more efficient than the page nested loop join that we have just seen. So let's see what that looks like, and following, I'm gonna use those notations here in addition to the ones that we have seen previously. So here the notation page blocks T, B, that essentially is the set of blocks of pages from table T, where each block contains B pages. And also, in order to mark the difference that I'm loading multiple pages instead of a single page, I'm also using load pages, the plural, for one block of pages. All right, so that is the block nested loop join. And you immediately see that it is kind of similar to the previous page nested loop join, because here we also have two nested loops that iterate over both of the input tables. Still, we are joining the enrollment table with the students table. And now let's see what actually changed. And what changed is mainly what you have marked up in red here. Essentially, instead of iterating over single pages in the outer loop, we're iterating over entire blocks of pages in the outer loop. And correspondingly, in the second line of the pseudocode, use the load pages command for this entire block of pages. All right. Now let's analyze how that changes the cost function. So this command over here, actually nothing much changes. I still need to read the pages of the outer relation, the outer table once. And therefore I need to count the cost for pages in the enrollment table times the loading cost. All right. Now, where the whole thing helps, this is for the second instruction here, because previously I had to invoke that for each page in students and for each page in enrollment. But now I have to only invoke that for each page in students and for each block of pages in the enrollment. And since the number of page blocks is smaller than the number of pages, I'm therefore saving a lot of processing costs, depending on the block size. All right. So this is the entire cost function. And essentially, the only thing that changes is that here we are multiplying by the number of blocks instead of the number of pages. All right. And this is why that factor also appears in the cost function below. So the trade-off here is that the page nested loop join needs extremely small amounts of main memory. There's a very small memory footprint, which is an advantage. But the block nested loop join is faster. And in exchange for that, it consumes a little bit more main memory. We still need one output buffer page, like before. We also need one page to store the current page from the inner table. On the other side, we need enough main memory to store an entire block of pages from the outer table. So this is what takes most of the main memory when executing this join. And you have a bit of a choice there because you can choose how large those page blocks should be. If you make them larger, you need more main memory. But on the other side, you might reduce the number of iterations of the inner loop of the algorithm. So here you can trade between time and between processing memory. So let's make a little example. Let's essentially make the same example as before, but this time we assume that we use a block nested loop join. So here we have a buffer size of 10 for storing outer blocks. I give you a second to think about how you would go about calculating the cost here while I'm looking at the chat to see whether there's any questions. Okay. All right. Yes, and here there is a question about why we do not count the cost of writing something to hard disk. So that's a great question. So the only thing that would be written to hard disk potentially, that would be the result of the join. And we have this convention that when calculating the cost for those operations, we do not consider the cost of writing out the result of the operation. We don't write out count the cost for writing out the final result of the operation. And the reason for that is simply that when calculating cost, we always want to compare multiple alternative operations. And since all of them are generating the same result, their cost for writing out the result will be the same. So that is why we do not count it, because it would be constant for all the different alternatives anyway. And our main goal with those cost calculations is always to compare different operations, different implementations for the same operator. So in practice, of course, you might have some cost associated with that, even if we are not considering it by convention. Of course, it depends also on the context of the operator. For instance, maybe you only want to count the number of join results, but you don't actually want to produce the join results. In those cases, the output of the join would never be directly written to hard disk, but it would only be counted. And in that case, you wouldn't have any output cost. So it depends a little bit on what next steps we want to take based on the join output. And here we don't consider the output cost at all. All right. So let's have a look at the solution to the example. So what we have here is that essentially we still need to read the enrollment pages. So here we still consider enrollment as an outer table for consistency. But then the number of times that we read the student pages is reduced. We have blocks of size 10, and we have 1,000 pages. So we divide 1,000 by 10, and then we multiply it by the number of pages in the students table, which is 100. So here we have reduced cost compared to the page nested loop join from something over 100,000 to 11,000. So roughly by factor 10. All right. Now, one final nested loop join variant that I want to discuss today, that is the index nested loop. And we have already seen that indexes can be useful in order to execute filter operations. We can also use them in the context of joins. And the main idea here is that I have an index on the join column for one of the two tables that I'm joining. And I assume that the join condition is an equality predicate, which is the case in our example where we have an enrollment table and the students table, and we want to find pairs of tuples that match on the student ID. So student ID from enrollment equal to student ID from the students table. So therefore it is an equality join predicate. And now if I have an index, for instance, on the student ID, I can exploit that one during the join. And the main idea to do that is that I'm simply iterating over the pages of the non-index, the outer table. And then for each entry on one of those pages, I use the index in order to retrieve the matching tuples from the other table. So in order to make this work, I first of all need a join with an equality join condition. And also I need to have an index on the correct table and the correct column. Let's see in more detail how that works like. And here, in addition to the notations from before, I'm also using the notation index of predicate, which essentially symbolizes an index lookup in order to retrieve all the entries satisfying the predicate in parentheses. And here I'm also using the notation tuple p, I in order to designate the tuple number I on page number P, because what I'm getting back from the index, that will be those record IDs, which, as we have seen before, always consist of a page ID together with the corresponding slot number. Now, this is how the algorithm looks like. So again, we are iterating over the pages of the enrollment table in the outer loop, and we load each of those pages. Then, for each tuple on the currently loaded page, we consult the index in order to retrieve matching tuples from the other table. So in this case, more concretely, we have one enrollment tuple, and that enrollment tuple contains a course ID and a student ID, and I can use the index in order to retrieve the entries in the student table with the corresponding student ID. And once I have found that, I load the corresponding page, and then I add the tuple combination to the output. In the previous joins, we always had this if condition because I had to verify whether the join predicate holds. Now, if I'm using the index here, then I am essentially guaranteed that this join condition is satisfied. So I don't even need to check anymore, just add the tuple combination to the join result. All right. And if I count the cost for that index over here, then of course here again, I'm loading each page from the enrollment table once. And also for each indexed entry that my index is returning to me, I need to load the corresponding page. Now, the cost of that depends a little bit on where how those index entries are distributed on hard disk. If you're very lucky, then those entries are clustered together, or at least approximately. And that means that since we are using the buffer manager, we can essentially reuse previously loaded pages quite a lot of times. But in order to simplify the cost analysis, we typically make the assumption that each page that we are retrieving for an index result tuple, each of those pages is located somewhere else, and we have to load it for the first time. So this is why typically we would just count the page loading cost times the number of entries returned by the index in order to get the access cost associated with the second load page command in the pseudocode. Of course, all of those cost formulas make simplifying assumptions, as you see, but nevertheless, they often allow you to at least make some rough estimates in order to determine that one option is significantly better or significantly worse compared to a different option. Now, in terms of main memory consumption, that algorithm is also quite reasonable. We just need one page to store the current page from the outer table, and then one page to store the current page from the inner table. And furthermore, we need our typical output buffer page. So altogether, 3 pages should be sufficient. Here, of course, I'm not counting any storage for the index. The index would be typically stored on hard disk. All right. So those are the join algorithms that I wanted to discuss today. Perhaps you can already think a little bit about other things that we could exploit in order to make joins with equality conditions more efficient, or you can just look at the next slides, which are already online. In the next lecture, we're going to discuss about a couple of more sophisticated join algorithms that specifically apply for equality join predicates. But here, those index nested loop joins, they are very versatile. Those nested loop joins in general, they are quite versatile, and they are heavily used in database management systems, also, for instance, in Postgres. All right. You see there's like one question in the chat. I'm going to answer this one, and then all right. So here the question is whether there's other join predicates than equality join predicates. That's a well-justified question, frankly. So in practice, by far the most common join condition is indeed equality join conditions. And in most of the examples that we've seen here, if not all, we have used the join conditions, equality join conditions. Now, in principle, you can also use different join conditions. You can essentially use arbitrary join conditions. And even if that happens less frequently in practice, every once in a while you have a join with non-equality join conditions. That is why it is very important for a database management system to support some join operators which can deal with non-equality join conditions. And for instance, the page nested loop or the block nested loop join, they have that property that they can deal with arbitrary join conditions. Okay, good. Have a nice day, and then I see you again on Friday. All right, let's get started. And currently we are discussing about, and again, I quickly need to make sure that my slides advance. All right, so currently we are discussing about the execution engine, and more precisely, we're discussing about how the standard operators for data processing are implemented. And the relevant chapter is still Ramakrishnan and Gehrke, chapter number 12. So we have discussed about a couple of operators for filtering and for joins in the last lecture. For joins, we have been discussing about those nested loop join variants, which typically have 2 nested for loops that iterate over the 2 input relations, and then they try to find matching tuples. Now in this lecture, we're going to discuss about 2 more join operator implementations. They are very, very popular in practice and are, for instance, also implemented in the Postgres database system. Now, those join operators, they apply in cases where our join condition is an equality between columns, which is perhaps the most typical case in practice. Last time I asked you to think a little bit about what we could exploit in order to make joins more efficient in those cases. And the first possibility that we can exploit is to use hashing. Now, the first new join that we will discuss today, that is the hash join, which uses a hash function in order to speed up the join. So we are now focusing on equality join conditions. That means we want tuple pairs which have the same value in the join column. And of course, if they have the same value in the join column, it means they also have the same hash value in the join column for an arbitrary hash function. So we exploit this as follows. Now the hash join has two phases. In the first phase, we essentially partition all the both input tables using the hash function. So first of all, we essentially make one pass over both input tables. Then we apply the hash function in order to partition the data into buckets that are associated with a specific hash function values. And we try to partition the data into sufficiently small partitions such that one of those partitions fits into main memory. That's what we need. Because in the second phase of the join, we will go over those hash value buckets one by one. And for each bucket, we will load one of them entirely into main memory in order to join the corresponding tuples separately. We can do that because since we are looking for tuples with the same value in the join column, they must be located in the same hash bucket. This is what the join exploits. Now that is the high-level overview. Now let's see some pseudocode. For that, I introduce some new notations. First of all, quite intuitive, the hash function, which calculates the hash function for a tuple in the join column, of course. Then I introduce the full predicate, which essentially tests whether one page is completely full and has no more space left for insertions. And then I introduce the write and clear function over here. So that is used for the output buffers. And it essentially does two things. First of all, it copies the current content of the output buffer to hard disk. And then it erases the content of the in-memory buffer such that it can consume new entries. All right, and with those notations and the ones that I have introduced the last time, this is the pseudocode for executing phase one in this example join between the enrollments and the students. And we want to find pairs of tuples where the student ID is the same. So here, first of all, we are going over the pages of the enrollment table, and we are sorting, we are partitioning those tuples using the hash function. So here we go over the pages of the enrollment relation E. For each page, we load it from hard disk, of course, and then we iterate over the tuples on that page, which we have just loaded. For each tuple, we are adding it. We are essentially copying it to the output buffer that is associated with the associated hash value. And if the output buffer becomes full, then we clear it and write the content to hard disk. So first write the content to hard disk, then we clear it, of course. All right. So this is the first phase of the join in which we partition tuples by the hash function. We apply it here to the enrollment table. We will see the student table in a second. Quickly reasoning about the cost. So this load page command that is invoked once for each page in the enrollment table. And the other one here, the write and clear command, also writes one page to hard disk. So that also costs us something. And since we just partition the data, the size of the input is the same as the size of the output, which means that this one, the second call, is also executed once for each page in the input table. Right? So we have said that we measure cost only by the number of pages that have been read or written to and or from hard disk. Right? So in this case, the cost is simply 2 times the number of pages in the table that we are partitioning. Now here I'm partitioning the enrollment table. I also need to partition the other one. That is the student table. That is the correct slide. So here I'm simply doing the same thing that I did before, but for the student table, iterating over the pages, partitioning them by the hash function, and writing those output buffers to hard disk whenever they become full. All right. So now I have partitioned both my input tables by their hash function in the join columns. Now, in the second phase, I'm treating each hash bucket one by one. So I am iterating over the possible hash buckets. And for each of them, I'm loading entirely the associated tuples from one of the two input relations. So here I have decided to entirely load the pages for the current hash bucket for the enrollment table. And after I have loaded the complete hash bucket for one of the input relations into main memory, then I'm simply iterating over the pages from the other table one by one. Here I'm iterating over the pages from the student table. And I only need to consider those pages from the corresponding hash bucket that is associated with the current hash value. And then for all the tuples that I have in main memory, I compare them and I evaluate the join condition. I still have to do that because just because two tuples belong into the same hash bucket, it does not yet mean that they have the same value in the join column, because typically multiple values get hashed to the same value. All right, and then I simply output the tuple pairs that match together. Okay, and here there's a great question in the chat. Okay, and there's also a great answer in the chat. Okay, I quickly address that. So the question was, we have said that we typically don't count the cost for writing out the output of an operation, because it doesn't really help us to compare different implementations for the same operation, because the output is always the same. Now, in this case, we have counted cost for writing something back to hard disk. Now, the difference here is that what we are writing out is not the final result of the join, but it is just an intermediate result. So if you compare the hash join, for instance, against the block nested loop join, that one doesn't write out some intermediate result which partitions the data according to hash value. So that's why when comparing this join operator to other join operators, we want to count the cost for writing out those intermediate results, but we do not want to count the cost for writing out the final result. Great question. All right, so in the second phase of the join, we join each hash bucket separately, and afterwards we produce the complete join result. And if you look at the cost, then the first command that is executed for each page in the enrollment table, and the inner one is executed for each page in the student table. So maybe it makes sense to have a second look to verify why that is the case. But of course, each page of the student table can only be in one of those hash buckets. So if I count together all the times that this command is invoked, then still I come back to the number of pages in the student table. All right. And this is why the total cost of this is essentially the number of pages in both the input tables. And I don't count the cost for writing out the result of that. Now, let's quickly think about how much main memory we need for that. So we will be discussing a lot about main memory consumption today, because together with runtime, that is a very important metric in the context of large-scale data processing. So for this join operator, in the first phase of the join, we first of all need to reserve one page in my buffer pool, which, as a little reminder, is the part of main memory reserved for the database management system. So I need one page in memory to store the current page for partitioning. And then I want one output buffer for each of the hash buckets. So as we will discuss in more detail later, the more hash buckets I want, the more pages in main memory do I need to reserve for this first phase. In the second phase, I want to store all pages from one hash bucket from one of the relations. So in order to minimize main memory consumption, I typically want to choose the smaller table for that. And also I need to count one page for the current page from the other table, and then I still need one output buffer. So here the number of hash buckets plus 2, basically. That's how many main memory pages I need. Now, there's a couple of constraints in terms of how much main memory I want at least, let's say. So first of all, in the first phase, I essentially want like one more page than the number of hash buckets. Also, in a second phase, in order to be able to load one partition entirely into main memory, I need to make sure that those partitions are small enough in order to fit into main memory. Now, if I assume a perfectly uniform distribution of data over hash buckets, then I can say that the size per hash bucket is simply the number of pages, let's say in the smaller table, divided by the number of hash buckets. That is the expected size of one of those hash buckets. And therefore, in the second phase, I want to make sure that the expected size of one of those hash buckets plus input buffer and output buffer plus 2 is smaller or equal to the amount of main memory that I have. And as you can verify by some calculations that I won't do here, but there is a rule of thumb that makes sure that those two conditions are satisfied. And this is that we want that the amount of main memory available is a little bit greater than the square root of the number of pages in the smaller relation, right? So if you have a number of hash buckets that corresponds to the square root of pages, then your expected size of the of each hash bucket is a total number of pages divided by the square root, and that again is the square root of the pages. So if you insert this, then both of those conditions, they approximately check out. So that is the rule of thumb, how much main memory you need for the hash join. This is a little example here, the same example that we have been using for the nested loop joins. And here we are joining the enrollment and the students tables with 1,000 enrollment pages and 100 student pages. And let's say that we have 11 buffer pages available. So the smaller input table is the students here, and it has 100 pages. So the square root of that is 10, which is a little bit smaller than the amount of main memory that we have available. So seems okay. And then the cost of this join, that is simply 3 times the size of both inputs combined. I have in the first phase of the join, I'm reading everything once and writing everything once. In the second phase of the join, I'm just reading everything once. And even if I would write out something, then I wouldn't count that cost because it's the final join result. You see the calculations in a little bit more detail, but we're just applying the formulas that we have seen on the previous slides. Now, I have described the rule of thumb about how much main memory you typically want for this join in order to execute it. If you have less main memory than that, you can of course always use a different join operator, which might be less memory hungry. Or there's also ways to adapt this join operator to deal with smaller amounts of main memory. Now, if we have not enough main memory, the problem is this. During the first phase, I need to reserve one output buffer in main memory for each of my hash buckets. So if I have less main memory, I will have less hash buckets, and that means that each hash bucket contains more data. And that creates a problem in the second phase because I cannot fit one entire hash bucket into main memory anymore because they become too large. Now, what I can do in those cases is that I don't execute one partitioning pass over the data, but that I execute multiple partitioning passes. So in each of those follow-up passes, I divide data in one bucket into sub-buckets, so to speak, which of course means that I need a different hash function. So instead of partitioning everything in one pass over the data, I would partition things into more and more fine-grained buckets by iterating over the data multiple times in the first join phase. And after enough passes, I can also say that in the second phase, I have reduced the size of those hash buckets enough such I can fit one of them entirely into main memory. So that is a possibility, but of course the join becomes less efficient because I need to make multiple passes over the data, so I need to read and write it multiple times. So at some point, it might become interesting to use one of the other join operators instead. And that is a great question here. What is basically, by how much is it recommended that we decrease the size of those buckets in each pass over the data? Well, that's a great question. You essentially want to maximize the effects of those passes over the data. You want to partition data as quickly as possible. So that means that in each pass over the data, you probably want to divide everything into the maximal number of sub-buckets you can. And if you have B buffer pages available, that always means you need one input buffer, and that leaves you with B minus one output buffers. So this is the number of sub-partitions that you probably want to create. So as much partitioning as possible per iteration. All right, so that was the hash join, one of the most popular join algorithms and heavily used in database management systems. Now in the following, I'm gonna introduce one more join, the sort merge join, which also applies to cases where I have an equality join condition. And that is also a very popular join operator. Also, this join algorithm executes two passes over the data. In the first pass over the data, we sort the two input tables according to their value in the join column. And then in the second phase, we use those sorted tables in order to merge them together and quickly identify tuple pairs that have the same value in a join column. So that is now much faster because I have previously sorted the two input tables. And by the way, in some cases, I might already have a table sorted beforehand. And then of course, the sort merge join becomes particularly interesting because you might be able to omit one of those sort operations in the first phase. In the following, we're going to assume that both of the input tables need to be sorted first. Now, you probably have heard a lot about sorting algorithms already. There's many sorting algorithms available. The problem is that most of them assume that we can access single entries in the data that I am sorting. Now, if I would do this with data that is located on hard disk, it would actually be very inefficient to jump back and forth between different single entries in that data, because as we have seen, those storage media, they often have some overhead for accessing specific locations, for instance, on hard disk. So random data access is efficient. This is why we rather want to access data in chunks, in pages of entries instead. And in order to make that efficient, you want some specialized join algorithm which takes that restriction into account. And those are called the external sort algorithms because they assume that the data to sort is not stored in main memory, but somewhere outside of main memory, meaning, for instance, on hard disk or on some flash device or on tape. So there's, in each case, on some medium that doesn't make random access very efficient. Now in the following, we're going to see a sorting algorithm which takes that into account. Now, this sorting algorithm proceeds in multiple steps. In each step, we iterate over the data and read the data once and write the data once. Now, each of those steps sorts the data more until finally all the data is sorted. In the first step, we simply do the following. We, assuming that we have a certain number of main memory pages available, we just fill all of our main memory with data from hard disk, and then we sort it in memory, and then we write the sorted version back to hard disk, potentially overriding the original unsorted data. Then so after this first step, we have multiple sorted chunks of data. We also call those sorted chunks of data runs, sorted runs. In the following steps, we are always merging together multiple of those sorted chunks in order to generate larger sorted chunks. We only can merge a limited number of chunks of runs in each step. So that means we might have to execute multiple steps until we have merged together all the data. And at that point, we get one completely sorted data. And after we have achieved one big sorted run, then we are done and the data is completely sorted. So let's see the first step in a little bit more detail. So we have B buffer pages available. We typically use the constant B in the following to designate the amount of buffer pages. So we load chunks of size B into our buffer, and then we sort the chunk via some standard sorting algorithm because now we have the data in main memory. And after we've done that, we write the sorted data back to hard disk where it forms one of those sorted runs. Let's see this by an example. So here I assume I have the hard disk content in the lower part of the screen, and in the upper part of the screen, I have the buffer pool. And as you see, which is typical, the buffer pool is of course smaller than the hard disk. Now in this first step of the sorting algorithm, I am first of all focusing on the first few pages of my hard disk content, which represents one of the two input tables to the join. And I'm loading that data into my buffer. So here the data is unsorted, as you see. So let's sort it by a standard join algorithm, by a standard sort algorithm in the buffer. And now I have sorted data in the buffer. I'm writing it back to hard disk, overriding the previously unsorted data. All right, now I've written it back to hard disk. Now we load the next chunk of data into our buffer. We sort it in our buffer, and we write it back to hard disk again. All right. So this is my second sorted run on hard disk. Now I'm loading the next chunk of data. Again, I'm sorting it. I'm writing it back to hard disk. I'm doing the same thing for the last chunk of data, sorting, writing. And now on my hard disk, I have 4 sorted chunks of data, and each of those chunks has length 3, of course, because this is the maximum number of pages that I could fit into my main memory. All right. Okay, so this is the first step. It produces a certain number of sorted runs. Now in the following steps, I'm merging those runs together in order to produce larger sorted runs. Now I can only merge a fixed number of runs in one step. More precisely, if I have B buffer pages, I can merge B-1 sorted runs, and it will become clear in a second why that is. So for each of those sorted runs, I need to reserve one input buffer in my buffer pool. So that means if I want to sort together merge together b-1 runs, I need to reserve b-1 pages. And among all the data that I have in main memory, I'm identifying the minimum entry now, and I'm copying that one into an output buffer and erase it from the corresponding input buffer. So the output buffer, this is where I'm using up my last buffer space page, because I need to write things into the output buffer before I'm writing them to hard disk. Now, whenever the output buffer becomes full, then I'm writing it back to hard disk and I clear the contents. Whenever my input buffer becomes empty, then I'm loading the next page from the corresponding sorted run. So each input buffer is associated with a different sorted run. And so if one of the input buffers becomes empty, then we load the next page from that same sorted run into the input buffer. And since those runs are sorted, I know that I am receiving the entries for each run in increasing order. All right, let's see this by a little example again. So here we assume that we have previously executed the first step of the sorting algorithm. So we have 4 sorted chunks of size 3, and now I'm merging them together. So here I have b equals 3. That means I can together merge b-1 meaning 2 sorted runs in each step. And here in the buffer pool, you see I have already written the function for each of the spaces in green. We have 1 input buffer for the first run, 1 input buffer for the second run, and we have 1 output buffer, right? So we start by loading the first page from the first 2 sorted runs. And the sorted run begins at the leftmost page and ends at the 3rd page from the left. And the next one starts from the 4th page from the left and goes until the 6th page from the left, all right? So those are the first pages of the 2 sorted runs, and now I'm loading them into the corresponding input buffers. Now I identify the smallest entry in my buffer pool, and that would currently be 1. So I'm copying that entry to the output buffer and I'm erasing it from the corresponding input buffer. This is what I have done now. Now the next smallest entry, that would be entry number 3 over here. So I'm copying that to the output buffer and erase it from the corresponding buffer. Now at this point, my output buffer has become full. So here I assume that I can only fit 2 entries on each of those pages. So since the output buffer is full, before I can continue, I first of all need to save its content to hard disk, and I need to erase it so it can accept more entries. Of course, in principle, I could also write the output buffer to hard disk before it is completely full, but you don't want to do this because each time that you're writing something to hard disk, you are paying with overheads. So I only want to write the output buffer content to hard disk when it is absolutely necessary. And in this case, it is. So let's write the output buffer to hard disk, and now we can clear it so it can receive more entries. And at this point, the smallest entry in main memory, that is 4, so I'm copying that into the output buffer. And at this point, the input buffer number 2 has become empty. So now I'm advancing the corresponding focus page in the second sorted run to the next page, and I'm loading the content into my buffer. Now, among the remaining entries, the 8 is the minimum. So I'm copying that one from the input into the output buffer and erase it in the input buffer. Here again, my output buffer has become full. So I'm copying that to hard disk and erase the output buffer in memory. At the same time, my input buffer number 1 has also become empty. So I'm loading the next page from the first sorted run. And at this point, the smallest number in main memory, that is 9. So I'm copying that to the output buffer. Next one would be 10. And here my output buffer is full, so I'm writing it to hard disk. Also, my input buffer had become empty. I'm rewinding to show that to you. So input buffer number 1 is also empty. So I'm copying the output buffer to hard disk. At the same time, I'm loading the next page from the first sorted run. All right. And now the smallest number would be 12 again, then 14. And at this point, you probably see where this is going. So I'm not going to complete the example. But if we do, then we have completely merged the two first sorted runs from the input. And then we are merging them into one sorted run that has now twice the size of the input sorted runs. Okay. All right. And there's a couple of questions. All right, and a couple of answers. Yes, we are merging the two sorted runs. So the output that I'm generating here, that will become a full merged sorted run, which contains all the elements from the first two sorted runs and combines them into one sorted run. Okay, and there's a question about why not put the first page of the third sorted run instead of iterating through a run? Does it matter? Okay, and that is a great question. In fact, it does matter, because you essentially rely in the algorithm on receiving tuples in the input buffers in increasing order. So if you switch from a page from one sorted run to a page from a different sorted run, then the entries on that other page might be larger or smaller than the ones that you have been treating before. But this algorithm here essentially assumes that at any point in time, it always has the minimum entry in main memory that hasn't been written out to hard disk yet. And in order to make that assumption, it requires that for each of the input buffers, I'm receiving the sorted runs, the entries from the corresponding run in ascending order. So it would be a violation of the assumptions that the algorithm is based upon if in one of those input buffers, I would first have a larger number and then later would have a smaller number again. Because at this point, the algorithm has already written the output buffer to hard disk, and it would assume that it doesn't have to go back and change anything anymore. So we can only merge together sorted runs. And in this case, since we have 4 sorted runs initially, it would mean that we need actually 2 passes over the data until we have merged everything. So as a summary, we have 12 pages and we have that we need to sort, and we have 3 buffer pages. The first step produces 4 sorted runs of length 3, and then I can merge together 2 runs in each of those merge steps. So the second step, which I have shown you, at least the beginning of it, it takes 2 sorted runs of length 3 and produces 1 sorted run of length. So the second step takes runs of length 3 and produces runs of length 6. And the third and final step takes 2 runs of length 6 as input and produces 1 run of length 12 as output, and that integrates all of the data that we wanted to sort. So after this third step over here, we are done. And yes, there is some connections to bottom-up merge sort indeed. All right. So if we analyze the cost of that phase, we have to execute multiple sorting passes, and in each of those passes, we read and write the data once. So if n is the number of pages to sort, then the cost per pass is 2 times n, reading and writing. Now, the interesting question is, how many passes do I need to make until all the data is sorted? And we can think about the length of the sorted runs that I'm producing, because if that length reaches the entire data set, I know that I'm done. Now, after the first step, we have sorted runs of length b, which is the number of buffer pages. In the second step, I'm merging b minus 1 sorted runs together. So the length of the output run multiplies b by b minus 1. In the third step, in the following ones, I'm also merging together b minus 1 sorted runs. So the length always multiplies by that factor. And therefore, once the length of those runs as a function of the number of steps executed has reached or exceeded the total number of pages, then I know that I am done. So you have the formula here on the bottom of the slide. And if you resolve that towards the number of steps by taking the logarithm on both sides, then you end up with a formula that depends logarithmically on the number of pages. All right, so that is the first phase of the sort merge join, where I'm sorting the input relations. And now I assume that I have both input tables sorted by their values in the join column. So after that, it becomes quite efficient to merge them together in order to produce the join result. So we proceed by first loading the first page of those both sorted tables into main memory, and then I compare the tuples that I have in main memory in order to find matching tuples. And once I have done that for all the tuples in main memory, I'm loading the next page for one of the two sorted input tables, and I'm always loading the next page for that table where the last entry is the smallest, because maybe the next page from that page still needs to be matched against some currently loaded tuple from the other table. All right, and I keep doing this essentially until for one of the two input tables I have no pages left at this point. I know that I have produced a complete join result and I can terminate. And here again, the algorithm is crucially based on the assumption that my both input tables are sorted once this phase starts, because otherwise I would miss potential join results. Now, here a little example about how I'm doing this. Now on hard disk, I have data for two tables where the first table is a little bit larger. And as you see here, we have already executed the first phase on both input tables. That is why those tables are sorted. And I still have 3 buffer pages. And for this second join phase, I also need an input and an output. 2 input buffers here and 1 output buffer. And I start by loading the first page of each input table into the associated input buffer. So I'm doing this over here. And now I'm trying to identify matching tuples here. Now in this case, there don't seem to be any matching tuples. So I am first of all excluding that it can be any matching tuple with the minimum here. Then I'm deleting the minimum that I now have in main memory. No matches so far, also no matches for the 3, so I'm deleting it. At this point, I have run out of input for the first table, so I'm loading data for the next page. And again, I'm looking at tuples in increasing order. So 4, no, there's no matches for 4, 6, no, there's no matches for 6 either. All right, at this point, my input buffer 1 has also become empty again. And so I load the next page. So I'm analyzing 8, no matches for 8, 9. And now I have a first match, because here I have a tuple with value 9. So I assume that this value is the value in the join column. So the tuples with value 9 match together. So I'm copying that to the join output. And here I'm loading the next page from both of the input tables. And again, I'm going over it. 14, no matches. Should load the next page from the first table. 15, no matches. 16, no matches. 17, no matches. I should load the next page. And here 25, no matches. I should load the next page. 26, no matches again. 29, nothing, and so on. So this is the principle how I merge together 2 sorted tables using their value in the join column in order to produce the join result. All right, one special case that I have not shown in the example, but that I quickly want to discuss is the case where we have the same value, essentially tuples that have the same value in the join column, and there's many of them in one table, so they extend across multiple pages of that table. Now, if you have that, if your first table contains many tuples with the same value in the join column, spread out over multiple pages because there's too many to fit on one single page. Whenever you load a new page from the second table, in order to be sure that you find all matches for the tuples on that page, you actually have to go back in the first table to the first page on which you find entries with the current value in the join column. So whenever you load a new page in the second table, you will have to go back a few pages and consider all the pages in the first table which have the same value in the join column. This case is rather atypical. Still, I mean, the implementations of sort merge joins consider it, but if that case happens, then of course efficiency decreases because you have to read pages multiple times. So that makes this join more expensive. Now, in the following cost analysis, we will actually assume that this case does not happen. So we assume that each of those pages is read only once. And then the cost of this merge phase is essentially proportional to the number of pages in both input tables. And as before, we're not counting the cost for writing out the result of that join. And this is the overview of the total join cost. We have two input tables with M and N pages and B buffer pages. Then in order to calculate the cost for the first phase, we have to calculate cost for sorting the two input tables. So we just use the cost formula from the previous slide, and we use it once with M and once with N pages. So here in the second formula, by the way, I see that the argument of the logarithm that should be N divided by B instead of M divided by B. For the second phase, the cost is essentially the size of our two input relations, M plus N. And so in total, we have the sum of all of those components as total cost for the join. Now, the question is, how much main memory are we using in order to execute the join? Now, in the first phase, we are essentially trying to exploit all buffer pages. Essentially, the more buffer pages we have, the more sorted runs we can merge together in one step. And that means we reduce the number of steps if we can exploit more main memory. In the second phase, however, we only exploit 3 buffer pages, one for the first input, one for the second input, and one for the output. Now, this already tells you that maybe something can be improved, because here in the first phase, we are exploiting all main memory, while in the second phase, we only exploit a part of a main memory. And in the context of data processing, you can often speed up things if you're willing to use more main memory. So this is somehow strange, and it already gives us the feeling perhaps that maybe there's something that we can improve with this join operator. There is indeed something called the refined sort merge join, which exploits that we actually have more main memory than we are using with this first version of the join operator. And the high-level idea of that join algorithm is that we can actually merge together more than 2 sorted tables in the second phase of the join, because we have more main memory available. So we can exploit that by not completely sorting the tables in the first phase of the join. So far, we assumed that those 2 input tables, they're completely sorted before the second phase of the join starts, but that is not really necessary. Now, if you don't need to sort the two tables completely, it means that we save a couple of passes over our data, and that means we are saving quite a few input like page read and write operations. So what we do with the refine, sort, merge, join, if we have enough main memory, is that in the first phase, we only sort data chunks that fit into main memory. So essentially, we're only executing the first step of the first sorting phase. So we just load chunks of data into main memory, we sort them, write them back to disk. We do this for the entire table, and afterwards we are done. So at this point, we have not completely sorted the table, but we have produced sorted runs of a length that is proportional to our main memory. And now in the second phase, instead of at the same time joining together two sorted tables, we essentially join together a number of assorted table fragments, a number of sorted runs from both input tables that is proportional to the amount of main memory that I have available. So when merging together those multiple sorted table parts, I'm reserving one input buffer for each of those sorted table parts. And if I do this, when having like the first page from each of those sorted table parts in main memory, then I can also efficiently identify the next matching tuple. So I can do the entire join in one pass over the data. Here a little bit more detail, and we're gonna discuss that in a little bit more detail next time. So we generally assume that we have B buffer pages, we have input tables with N and M pages. In the first phase, we load those chunks of maximum size, what fits into my main memory, B pages, we sort them, write them back to disk. And afterwards, when taking together both input tables with N and M pages, I will have a number of sorted table chunks that is proportional to N plus M divided by the buffer size. And then in the second phase, I will merge together V minus one sorted table chunks together, because I need for each one my input buffer and one output buffer. And if I can do this in one pass, then my total cost will be in total 2 times N plus N for the first phase, reading and writing once, and 1 times M plus N for the second phase, which is only reading the data once. All right, so I'm gonna stop here. We are gonna discuss the refined version of the sort merge join in a little bit more detail next time. This is the last join operator implementation that we will see. And finally, we will compare those different join operator implementations together. Have a nice weekend and see you again on Monday. So in the first phase of the sort merge join, we're essentially exploiting all the buffer pages in order to do the external sort algorithm that we have seen. In the second phase, we only exploit 3 buffer pages. One in order to read 1 page from the first input table, one to read 1 page from the second input table, and 1 output buffer. And we have already said last time that there is some kind of imbalance because we use a lot of main memory in the first phase, but we don't use so much main memory in the second phase. And that often means that we can make the algorithm faster if we exploit all the main memory that we have in both phases. So the last time I've already quickly mentioned that this is possible. There is something called the refine, sort, merge, join. And here the idea is that I can merge together more than 2 sorted tables in the second phase. I just need to make sure that I have 1 input buffer for each of the tables that I'm merging together. But if I have more than 2 input buffers available, I can merge together more than 2 tables at once. And this refined algorithm exploits that. the main idea is that in the first phase, I don't sort the input tables completely, but I only sort them partially. Now that produces a set of sorted table chunks, basically, so it is more than 2. And then in the second phase, I'm merging together all those sorted table chunks in one pass. All right. So in the first phase of the refined join, I'm loading the pages of data into my main memory, and then I'm sorting them, and then I'm writing the sorted version back to hard disk. So if I have n pages in one table and m pages in the other table and b buffer pages, then the number of sorted chunks that I will have stored on my hard disk will be n plus m divided by b afterwards. Now in the second phase, I'm merging all of those sorted chunks together in one step. And in order to do that, I just need to make sure that I can reserve one input buffer page for each of those sorted table chunks. And if I can do all of this, then the cost of this refined sort merge algorithm is, first of all, 2 times the sizes of both input tables in the first phase, because here I am reading all the data once and I'm writing all the data once. And in the second phase, since we don't count the cost for the output, I'm just reading all the data once in order to merge it. All right. So this is the refined sort merge join. In order to make it work, I need enough main memory. So now we can think about how much main memory we need in order to make that work. So in general, if I execute the first phase where I sort as much data as I can possibly fit into main memory, then the number of sorted chunks after the first phase is n plus m table sizes divided by b. And now the constraint for the second phase is that I need to be able to reserve one input buffer for each of those sorted chunks that I want to merge together. So I still need to reserve one output buffer, and that is why I am subtracting 1 from b, the number of buffer pages. And then I get the amount of buffer space that I have available as input buffers. So I have b minus 1 input buffers, and that must be greater or equal to the number of sorted chunks that I want to merge together in one step. And that, as we have just calculated, is the 2 table sizes divided by the buffer size. So I need this constraint to hold. B minus 1 must be greater or equal to n plus m divided by b. And as a rule of thumb, in order to satisfy this constraint, I should have something like the square root of the larger table as a main memory times 2 furthermore. If I have that, then those constraints are satisfied. So this is the refined version of the sort merge join. It is the most popular variant of the sort merge join because it only goes over the data twice, once in each phase. And in terms of cost, it is actually quite similar to the hash join algorithm. So this is why people often compare the pros and cons of the hash join algorithm and of the sort merge join algorithm, because both of them are also applicable specifically for equality join conditions. Now, this is an overview here. We have the hash join and the refined sort merge join, which both have a time complexity that is proportional, that is linear in the input data size measured by the number of pages. So time-wise, they can be near equivalent. When comparing the main memory consumption, we find that the refined sort merge join takes a little bit more main memory, because here we're taking the square root of the larger table, while for the hash join, we're taking the square root of the smaller table size, because you can choose for which of the two input tables you're loading the corresponding hash buckets into main memory at once. So slight advantage for the hash join here. And when it comes to parallelization, then the hash join is actually also a good idea. You can very easily calculate those hash functions in parallel in the first phase. And then in the second phase, you can just assign different hash buckets to different processes. So that is quite convenient. Having said that, the refined sort merge join can also be parallelized, but it is particularly convenient for the hash join. Now, when it comes to skew resistance, and that means how well does the join algorithm work if I have, for instance, lots of duplicates in my data. In that case, the hash join algorithm might not be the preferred choice, because if we have lots of duplicates, then all of them will have the same hash function value. And that means all of them will belong into the same hash bucket. And that means that it becomes very difficult to fit things into main memory. So if you have a lot of duplicates, then the hash join algorithm might not be the optimal choice. On the other side, for the sort merge join, that one can deal relatively well with skew. You just have lots of duplicates that appear one after the other in the sort order. So if you have lots of skew, then perhaps the refined sort merge join algorithm is a good choice. Another point that is not mentioned here in the slides, we will come back to that point later, but I already wanted to mention it here. One advantage of the refined sort merge join is that the output of this join is automatically sorted. And there are certain operations that become cheaper if you have sorted data. We will see some of those operations in the following. So in some cases, even if using the refined sort merge join alone is not what you want to do, maybe you still go for it because it makes the following operations cheaper. That's something that we will come back to later. All right, and this concludes our section on join algorithms. We have seen various join operator implementations. Some of them are applicable specifically for equality join conditions, which is perhaps the most common case in practice. Others are more flexible and can be applied for arbitrary join conditions. They have different pros and cons in terms of time complexity, as well as in terms of main memory consumption. And the hash join and the refined sort merge join, this is some of the most commonly used join algorithms in practice. All right. Now, we're going to see a couple of other operators in the following. And in the end, we will also start discussing about how we can compose those operators into query plans. I quickly switched the slide deck, and please let me know if there's any problems seeing those slides. Now, in the following, we're going to discuss about a couple of other operators, and finally, we will start discussing about query plans. So here, that is always the architecture slide at the beginning, but nothing has changed compared to the last slide deck. We are still discussing about the query executor, which executes those query plans. And the relevant chapter in the Ramakrishnan and Gehrke book, that is still chapter number 12. Now, first of all, we're going to discuss about the projection operator. Now, the projection operator simply means dropping away those columns that are not mentioned in the select clause. And that can be quite straightforward to implement. Where it gets, however, complicated is if you use a select distinct as opposed to a simple select. If you write select distinct, it always means that the system should eliminate duplicate results. And when implementing this in a naive way, it would require pairwise comparisons between different records in the dataset in order to identify those duplicates. So in order to avoid all those pairwise comparisons, which would be inefficient, there's a couple of ways of doing things in a smarter way. First of all, you can exploit hashing, which essentially allows you to restrict comparisons to tuples that appear in the same hash bucket. Or you can use a sorting, which means you can restrict comparisons to tuples that appear close together in the sort order. Or you can exploit indexes if available. And since an index might already give you a sort order, it means that you can exploit the sort order without having to do the actual sorting. Now, in the following, we're going to discuss about those possibilities in a little bit more detail. Now, first of all, we're going to see how we can do the projection and duplicate elimination using hashing. So this algorithm again executes in two phases. In the first phase, we are partitioning the data using the hash function. In the second phase, we eliminate duplicates for each of the hash buckets. Now, in a little bit more detail, in the first phase, we would just read the input data one page after the other one. And for each record in the input data, we would immediately calculate the projection, which essentially means that we are throwing away columns that don't appear in the select clause. Then we partition the data using the hash function. So again, we have like one output buffer associated with each hash bucket. And then based on the hash value, we are writing the tuples into the corresponding hash bucket. And whenever one of those output buffers becomes full, then we write the content back to hard disk. So this is what you have already seen when we were partitioning inputs in the context of the hash join. So the principle is exactly the same, except that we are dropping columns that don't appear in the select clause when loading data. In the second phase, we load the data for one of those hash buckets into main memory. And for the data that we have currently loaded, we eliminate the duplicates. Now, in our cost model, we only count a cost related to loading data from hard disk. So essentially, those comparisons for in-memory data are for free according to the simple model. In practice, people often try to make even the in-memory comparisons more efficient by using, for instance, a second hash function that you apply to the tuples that appear in each of those hash buckets in order to quickly find potential matches, potential duplicates to eliminate. The constraints for main memory, they are similar as for the hash join. In the first phase, you need to be able to reserve one output buffer for each hash bucket. And in the second phase, you need to be able to load into main memory one entire hash bucket. So that implies a couple of constraints on the memory size. The reasoning is the same as for the hash join. And if you do that in two phases, then the cost is at most 3 times the number of pages, because in the first phase, we are reading data once and we are writing data once. Now, the data that we write might actually be a little bit less than the data that we have read, because first of all, we are dropping unnecessary columns that don't appear in the projection. And also, if we happen to already detect some duplicates, then we can already eliminate that data. So the data that we write to hard disk after the first phase might actually be smaller than the data that we have read from hard disk at the beginning of the phase. So this is the cost, assuming that you can do the whole duplicate elimination by 2 passes over the data. Now, imagine for a second that in the second phase, we are unable to load one entire hash bucket into main memory. Does anyone have an idea about what we could do in order to deal with that situation? So we had already discussed a similar case in the context of the hash join. We also sometimes had cases where it is not possible to fit one entire hash bucket into main memory. So what can we do in order to reduce the size of those hash buckets further? Yes, exactly. Yes, very good. So here I see the right answer in the chat. Exactly. So we can just split those buckets further into sub-buckets. And in order to do that, we can just pass over the data multiple times. In the first pass, we are partitioning data into large buckets. Then in the second pass, we partition each of those buckets into smaller sub-buckets, and so on. We can iterate that until one of those hash buckets fits entirely into main memory. Of course, in order to be able to do that, we must assume that we don't have too many duplicates in our data set, because if we have too many duplicates, then all of them will end in the same hash bucket, and that can be problematic. Okay. So now the second possibility to speed up duplicate elimination, that is via sorting. So here the main idea is that duplicates must appear close together in a sort order. So also by sorting things, we can reduce the number of required comparisons, because now we only need to compare things that appear close together in the sort order. And in order to do that, I can use a variant of the external sort algorithm that we have seen before. So in the first pass over the data, I am again applying directly the projections, which means that I'm throwing away columns that don't appear in my select statement. Whenever I do one of the sorting steps, whether that is the initial step or whether that is some of the merging steps, always I eliminate duplicates immediately once I discover them. And the result of this variant of external sorting is first of all sorted, and more importantly, it will be duplicate free. All right, so this is very similar to this external sort algorithm that we have seen in the context of the sort merge join, just that here I am eliminating unnecessary columns and I'm eliminating duplicates as soon as possible. The amount of main memory is not fixed, but the more main memory you have, the faster it gets, because you have to make less passes over the data. And then the cost is at most the one of external sorting, because the data that you are sorting here, it might actually decrease over time once you drop columns or once you eliminate duplicates. All right. So that is a possibility to do duplicate elimination via sorting. If you have an index already available, you might be able to save the sorting step. The only thing you need is that the index key includes the projection columns. So first of all, we can use the index in order to retrieve all the relevant data without having to look at the actual table data. And since those indexes are typically much smaller in terms of data size compared to the actual table, that saves some cost. What's even better is if you have one of those indexes that return the data in sorted order, particularly the tree indexes that we have seen. And if the columns that you are projecting on form at least a prefix of the index key, that means that you can retrieve the tuples in sorted order from the index, and that makes it very easy to eliminate duplicates because they already appear consecutively and are easy to eliminate. So if you have an index available, that might make it much faster to execute one of those select distinct clauses. And the cost here is generally the cost of accessing the index. Now, that was the projection operator. Next, we're going to discuss about grouping and aggregation. Now, aggregation without grouping is relatively easy to do. You might still remember that SQL offers those aggregation functions you see here. You can calculate minima, maxima, sums, counts, and averages. And typically, if you don't have any groups, then you can just scan the input data and you have some fixed counter in main memory that you keep updating whenever you read new records from the data. That works with a constant amount of main memory. And once you have scanned all the data, then you have the final aggregation value in memory. So for instance, if you're calculating a minimum from all the tuples in a table, then you just maintain the current minimum, the minimum seen so far in main memory. Then you keep scanning the tuples from the table and update the minimum whenever you encounter a new minimum. The only aggregation that can become a little bit more expensive even without grouping, that is count, because inside the count operation, we can also have the distinct keyword. So you can ask the database system to specifically count distinct elements. And if you do this, then again, we need a method for duplicate elimination. And in order to do this, we can use the methods that we have seen for the projection on the previous slides. So the distinct is restricted to the count. All right. Deletions. There's a question about how minimum and maximum relates to deletions. So in general, we will discuss more in coming lectures about how we can update data. For the moment, we assume that the data remains the same and we just analyze it basically. All right. And if we have an aggregation together with grouping, then we have to do a little bit more. We have again those possibilities to use hashing, sorting, or existing indexes if they are available. So if we decide to use hashing, for instance, then we would maintain a hash table, preferably in memory, which associates the group keys with the corresponding aggregates. So we go over the data, and for each new tuple, we determine the corresponding hash bucket in our in-memory hash table, and there we update the counters that are associated with the corresponding group key. We can also use sorting, because after you sorted your data by the group keys, it means that the members of the same group appear consecutively. And because of that, you can essentially calculate the aggregation value for each group one after the other one. So here we sort by the group keys, and then we can calculate those aggregates consecutively for each separate group. And finally, if you have indexes, that might also help you to speed up things. Here we want the indexes to contain the group by keys. And then you can again treat each group separately, one after the other one, because you can use the index in order to retrieve those entries which have specific values in the group by columns. So last, we will discuss about the set operations, union, and intersection, and set minus operations. So here the principles are similar to the ones that we have already seen before. For instance, the intersection can essentially be handled by some kind of join. The only thing that you need is a join condition, which essentially makes all the columns equal. And then the result of that join will give you the intersection result. For union, the union operation eliminates duplicates by default. So you can use similar techniques to before in order to detect those duplicates. Either we can use a hash function, and then we eliminate the duplicates in each hash bucket separately, or we use the sort function, and then we know that duplicates will appear close together, so that also makes it easier to eliminate them during merging. If I have the except operation, which means that I'm subtracting one set from another one, then I can also reduce comparisons if I first partition the two relations R and S into hash buckets and then treat each hash bucket separately. Or I can again sort them such that the same entries appear close together, and then I can just check whether tuples in R also appear in S. So in general, as you notice, for many of those operations, I'm using kind of the same ideas in order to speed them up. Whenever I have something that would require pairwise comparisons, I'm typically using either hashing or sorting in order to reduce the number of comparisons required. Or if I have a suitable index, I can often use that one as well. So there's a couple of ideas about how to speed up data processing that transcend all those different operators. All right. So now we have seen all the implementations of those separate standard operators. Now in the following, we're going to discuss more about how we can compose multiple operators into one common plan, because that is what is typically required in order to answer your queries. Now, as a little reminder, query plans are typically represented as trees, and the inner nodes in those trees, they correspond to standard operators. The leaf nodes in those trees, they correspond to tables. Now, the logical query plan specifies just which operation types have to be applied in which order. The physical query plan is more detailed and additionally specifies how those operators are implemented. And now you see why that is important, because we have seen all those different operator implementations, and choosing the right one can actually make a big difference for performance. Now, this is an example logical query plan over here in order to answer the query that you see on the right lower corner of this slide. So here we are selecting the names of students from a join between students, enrollment information, and courses, matching up students with the courses that they are taking. And additionally, we are narrowing things down to the courses, to one course specifically, which is CS 4320. Now, those query plans are evaluated bottom up. So here I'm starting, for instance, by reading the courses table. Then I'm applying the filter condition, and the filter condition is represented by this little sigma together with the corresponding condition. Then I'm feeding the result of the filter into a join together with the enrollment table. And we join using the course ID. And the result of that join is fed into the next join together with the students table. And here I'm joining on the student ID. Finally, I have a projection operation where I'm eliminating the columns except for the student name column. So the data flow in this plan goes from the bottom to the top. And that is a logical plan because it only specifies that we have to do a join, for instance, but it doesn't yet specify how to execute this join. Now, this is the physical plan version, which provides more details. And here you see that I have written the way in which those operations are implemented next to each of those nodes. So here, for instance, the initial filter, that is just a scan filter, so I'm not using indexes or anything fancy. I'm just scanning the pages one after the other one, and I'm evaluating the filter condition. The join here, the first one, is implemented as a block nested loop join. And the physical plan also specifies details such as how many buffer pages do you want to reserve in order to store blocks from the outer relation. And when writing those query plans, then by convention, the left input to each operation is always the outer relation, which is important, for instance, for the cost of those join operations. Now, the second join will be the hash join that we have seen. And then finally, I am doing a projection. Now, when composing those operators, it is important how I'm passing on data from one operator to the next one. Now, in the most naive implementation, I could say that each operator simply writes the result of the operation back to hard disk. And then the next operator in the plan can read that result from hard disk again. Now, the problem with that is, of course, that it is less efficient than possible, because I keep writing things to hard disk and then reading the same things from hard disk again. So in order to make things more efficient, people typically try to keep those intermediate results in memory, if possible, in order to avoid writing and reading them. Whether that is possible or not depends on the operators involved and on the sizes of those intermediate results. So the physical plans additionally specify how those results are passed on between different operators. Now, there's the keyword pipelining, which you might already have come across. So in this context, pipelining means that one operator passes results or result pieces to the next operator in main memory. So we avoid writing results to hard disk and then reading them again, which is also called materialization. And another label that goes together with pipelining, that's the label on the fly, which is typically used for unary operators, meaning operators that have only one single input, like a filter or like a projection. And for those operators, it means that their input comes directly from main memory and doesn't have to be read from hard disk, which means that those operators in our simple model are essentially for free, at least when it comes to the input. They might still have to write their output somewhere. Okay. Now, one way in which pipelining is often used, so I'm mentioning that since it is a very common pattern, that is if you pipeline multiple nested loop joins together in a chain, basically. So you often have the problem that the full output of a join operation might be too large to fit into main memory entirely. So the idea here is that instead of producing the whole join result at once, I'm only producing small parts of it that I keep in main memory, and then immediately I invoke the next operator on that in-memory result part. And nested loop joins, they work very well with that, because if you think back of how the algorithm works, they always get this chunk of data from the outer table, and then they match that up with the pages in the inner table. That means they can already get started quickly if they only are given one block, one part of the outer table. They don't need to wait until they have seen the entire table. And here, for instance, in the example, we could also use two pipelined block nested loop joins, where essentially the first one produces always some part of the join result that is kept in memory, and then the second one processes the current part of the join result and produces again a part of the second join result. So this is the physical plan now marked up with some labels that indicate how data is passed along between those different operators. And I'm going to go over it in a little bit more detail. So again, we start by the filter operation. And here we are scanning all the pages from the courses relation. And here the output of the filter operation is pipelined to the next operation, which is a join, which means that we don't write it back to hard disk. And now there's a second join operation. It has a buffer of size 10 pages for the outer, meaning for the left table, for the left input. So that means that this filter operator will keep scanning course pages and filtering them until the filter result has filled up the entire buffer of 10 pages for the following join. And if that has happened, then the following join proceeds in order to fill up the input buffer of the next join, which also has 10 pages. And once that has happened, the next join also processes the input in the input buffer and matches up the input in the left on the left side with the pages of the student's relation, and pipelines it directly to the coming projection. And here we use the keyword on the fly for the projection, meaning that the input to the projection is in main memory and does not have to be read from hard disk. So here I'm optimizing performance by avoiding writing data to hard disk. And in the following, as a little exercise, we're gonna make more exercises on that, but I wanted to encourage you to apply this principle here in order to estimate the processing cost of the plan that we have seen on the previous slide. So I will show it again in a second. So what you essentially need to do, so you generally need to estimate the sizes of intermediate results if they are not already given. In this simple example, I'm gonna give you the intermediate result sizes. Then you have to estimate the cost of each operator, taking into account how the data is passed on between different operators. Don't forget, do not count the final output of the entire plan. You might very well have to count costs for writing out intermediate results, but not for the final result. And finally, you just sum up the cost of all operations in that query plan. So here I have the same plan together with intermediate result sizes in green and also sizes for the base table. So now have a look at this plan and try to estimate the execution cost, or think at least about how you would estimate the execution cost. I'm going to give you just a few 1-2 minutes, and while you're looking into this, I can also answer questions in the chat if there is any, and afterwards I'm going to show you the solution. And those set operations, okay, very good question. Somebody's asking what the constraints are on the inputs for those set operations like union and intersection. And indeed, you need that those inputs are compatible, meaning that they have the same number of columns and that they have the same column types. Please feel free to post the questions in the chat. And otherwise, I'm going to give you a few minutes. And yes, the column names can be different, but as long as they have the same type and there's the same number of them, you can use one of those union or intersection operations. So when trying to estimate the cost of those plans, here we have already the intermediate result sizes. So essentially, we have to go over the different operators in the plan and try to estimate the processing cost for each of them using the cost formulas that we have seen so far. All right. Now we are running out of time, so I'm gonna give you the solution here. All right. So let's first of all start with the first operation, which is this filter. And here we have a simple filter. We don't use any indexes or anything. So here we're just scanning the input pages one by one. And therefore the cost of this filter operation is simply the number of input pages, which is given here, which is 100. Now, after the filter, you see that the amount of data reduces after the filter. We have the join. And here for this join, the input buffer can contain 10 pages. So this is exactly the full filtered result. And for each block from the outer table, so whenever we fill the input buffer, we have to read the pages of the inner table, which is the enrollment table, once, simply due to the definition of how the block nested loop join works. So since we fill the input buffer once in total, it means that we have to read the pages from the inner relation, from the inner table once. And that means that our cost is simply 100. So typically, when starting a block nested loop join and having data on hard disk initially, then we'd also have to count the cost for reading the outer table. But here in this case, the filter operation pipelines the result into the join input buffer, and therefore we don't need to read any data from hard disk for that. And this is why we don't need to add anything. We simply have a cost of reading the enrollment table once. Now, the next join also has an input buffer size of 10 pages, but the total result of the previous join, because now it has more columns, it is actually 20 pages. And with 20 pages, we can fill the input buffer to the following join twice. And that means we have to read the pages from the inner table twice as well. And here we have the students table with 20 pages. If you read that twice, it will give me a cost of 2 times 20 makes 40 pages. And now the question is, how much does the final projection operation cost? And in this case, since we are immediately pipelining the output from the join into the projection is executed on the fly. It doesn't need to read any data. And the output of the projection is the final query result. So we don't count the cost for the output either. And that is why this projection operation has simply cost 0. In order to get to the cost for the entire plan, I'm simply summing up the cost for those different operations. And if I sum that up here, then it gives me a cost of 240. And that is the cost of this simple example plan. So I encourage you to have another look at this example. We're going to make more example for plan cost estimation in the following. Also, tomorrow we will release the next homework, which will focus on indexing. So I also encourage you to have another look at indexing, and if you haven't done that already. And apart from that, I wish you a nice day, and I see you again on Wednesday. All right, let's get started. Please let me know if the slides work. So I'm now switching to the architecture slide, and hopefully you see the overview picture with the query optimization component encircled. All right. Okay, seems to work. Good. So the last time we have been discussing about how we execute query plans and how we implement the different operators in those query plans. Today, we are going to discuss about how the database management system selects the optimal plan for an incoming query. And the component in the database systems which does that, that is the query optimizer, which you see here, and the relevant chapters in Ramakrishnan and Gehrke. Those are chapters 13 and 14. So this is a high-level overview of how one of those query optimizers works. So you have an SQL query incoming, which describes the data that the user wants to generate. And then the query optimizer selects the optimal, the most efficient processing plan, which is then forwarded to the execution engine that we have been discussing over the past lectures. So the job of the query optimizer is to make all of those decisions, like in which order do we do the joins, which operator implementations do we use. And in order to do that, it first of all needs to be able to consider different candidate plans for a given query. So it has a component internally which allows it to enumerate candidate plans for the given query. And it also needs to be able to compare those candidates in order to select the best one. And in order to do that, it has a cost model in order to predict the execution cost for one of those plan candidates. And then it tries to select the one where the expected execution, the predicted execution cost is minimal. That is the high-level overview of the query optimizer. And in the following, we're going to first of all discuss about how the cost estimation works. Now, this is the high-level overview of how cost estimation works. So first of all, cost estimation is typically based on data statistics. So the database system will store statistics like what is the number of distinct values in a column, what is the range of values, and those statistics are necessary in order to estimate the plan execution costs. Now, those data statistics, they are first of all used to estimate the selectivity of predicates that appear in the query. Now, those predicates which filter rows, they essentially get assigned to a probability that they are satisfied for a randomly selected row. So we basically want to know how restrictive are the predicates that appear in the query. And based on that, we try to estimate the sizes of all intermediate results that get generated when executing a certain plan. Because, for instance, depending on the order in which you join different tables, you might end up generating different intermediate results. And some of them can be quite large, so they're expensive to process. You want to avoid that, while others are fairly small, which is better. And with the cardinality model, we try to distinguish between those cases. Finally, given the size estimates for all relevant intermediate results, we are trying to predict the cost of the plan. And we do this in a similar way to what we have already seen so far. We have seen a simple cost model to estimate the cost of single operators. And last time, we also have seen how we can estimate the cost of an entire query plan with multiple operations. And the query optimizer uses a slightly more sophisticated version of that. And that is used in order to assign a candidate plan to an estimated execution cost. So let's discuss in a little bit more detail about those different steps of cost estimation, starting with the data statistics. Now, which statistics precisely we are using, that depends on the database management system. Different systems store different statistics. For instance, in Postgres, we have statistics for each column, such as the number of distinct values, the number of null values. Often database management systems store the most frequent values for each column, the heavy hitters, so to speak. And they often use histograms in order to get some coarse-grained impression of the distribution of your data. And that is used in order to estimate predicate selectivity. For instance, in Postgres, more specifically, those statistics, you force the database management system to create them by running the vacuum analyze command. Sometimes the database system might also decide itself to create those statistics, but you can force that with this command. And those statistics form the base for query optimization. So one hint from the practice, if you observe that you have strangely bad performance in query processing, then every once in a while the problem will be solved if you just run vacuum analyze, because the problem is that the query optimizer doesn't have accurate statistics and so doesn't choose good query plans. So that is good practice to run this command. You can also directly inspect the statistics that are created by the Postgres optimizer. There's the so-called PG stats view, which contains all that information. And I'm very quickly gonna demonstrate how you can access that. Quickly gonna switch to sharing my terminal. All right, you should now be able to see my terminal window. All right, let's log into the database. And the data structure, the relation containing those statistics, that is the PG stats data structure. Here you see the different columns. I'm not going to discuss all of them in detail, but you see, for instance, the column null frag, which would indicate the ratio of a null value in a given column. All right, and just to be sure, we are running the vacuum analyze command. In the last couple of times, we have already been using the table containing the results of the Stack Overflow developer survey. So let's quickly examine the statistics once this command here finishes. I'm actually sure that the statistics are up to date. Okay, good. Now it finished. All right, and now let's, for instance, say that we want to analyze for each attribute, meaning for each column, the fraction of null values, and the table that we're interested in, that is the Stack Overflow 2019 table. All right, and as you see here, now we see the statistics about which percentage of the rows contain null values for the corresponding row. All right. And here, of course, the respondent column, for instance, that one is the ID column. So here we will not have any null values because that is a primary key that is disallowed. For some of the other columns, we actually have a relatively high percentage of null values. And here you see the estimated percentage. Let's maybe look at one more statistic. Two. All right. So here we have the number of distinct values. Some of them are positive. If it is positive, it is directly the number of distinct values. Some of those values here are also negative, and that means that we are essentially talking about the percentage. So if the number is negative, then basically that is the number of distinct values divided by the number of rows. So here, for instance, in the very first attribute, the respondent attribute, that is the primary key. So here we have a distinct value ratio of 100%. So that means that every row contains a distinct value. While for some of the other columns, we have a relatively low number of distinct values. And there's many more statistics contained in this PG stats view. So if you're interested, I encourage you to explore that further. But just to give you a little bit of an expression for the types of statistics that an optimizer stores. And here we have the question in the chat about whether -1 means 100% unique. And yes, exactly, yes, and that's already the answer, great. So that is exactly the case. So -1 means 100% distinct values. All right, good. And those statistics are used by the optimizer in order to decide which query plans to use. Let me get back to my slide deck. All right. So those statistics form the input to the selectivity model, where we estimate for each predicate in the query the probability that it is satisfied for a random row. Now, generally, the selectivity is defined as the probability that the random row satisfies a predicate. In order to do that, we can generally use constraints on my database and those data statistics. Now, we have already discussed about the data statistics, constraints. We have also discussed, but already a couple of lectures ago, those are things like knowing that a certain column contains a primary key, like a certain column forms the primary key, or that there's a foreign key constraint between other columns. For instance, if you know that a certain column is the primary key, then automatically you can infer that it will contain unique values. And the query optimizer makes this kind of reasoning. Now, for instance, we could say that if we know how many distinct values we have in a certain column, and then we have a predicate of the form a column equals value, then under certain assumptions, we can say that the selectivity of the predicate is expected to be 1 divided by the number of values. Or for instance, if we know that we are talking about a primary key column, then we know that if I fix the value in that column to 1 specific value, the result must contain at most 1 single row. And in practice, I often have composite predicates. So here, for instance, if I calculate the selectivity of a conjunction between 2 predicates, A and B, then under certain assumptions, I can say the selectivity of A and B equals the selectivity of A times the selectivity of B. So I can decompose the selectivity estimation for the composite predicate into selectivity estimation for the components. Now, I have already mentioned assumptions a couple of times. So can anyone tell me in the chat which assumptions we seem to be making in order to come to those formulas here? Independence, very good. Here we have independence in the chat. And that is indeed the assumption that we are making for the last formula here. We assume that those 2 predicates, A and B, are independent, and this is why the selectivity of the composite predicate is the product of the 2 predicate selectivities. Does anyone have a different assumption? Okay, very good. And here there is the values are equally distributed. Very good. And that is indeed the assumption that we are making in order to get to the first formula. We assume that whenever I fix the column to any specific value, then we have the same selectivity. So implicitly, I'm assuming that all of those values are equally frequent. So I assume that data is uniformly distributed across different values in that column. Now here, there's the summary, and indeed, those were the 2 assumptions that I was aiming for. Now, by the way, for the case with the constraint, if you know that a certain column is a key column, then in order to get to this inequality here, we don't need to make any further assumptions. So that definitely holds. But for the other selectivity estimation formulas, we made indeed a couple of strong assumptions. And in practice, those assumptions, of course, they don't always hold. And that is also one of the main reasons why query optimization can go wrong, if some of those assumptions are not satisfied. Nevertheless, in many cases, those assumptions are not too far from the truth. So this is why those assumptions are used in practice. For instance, the Postgres optimizer will at least make the independence assumption typically, and thereby assign each of the predicates to a selectivity estimate. Now, the next step is to use those selectivity estimates in order to estimate the cardinality, meaning the number of rows in certain intermediate results. All right, so we generally assume that the cardinality of a single table is given because that is information that a database management system needs to store anyway. So we have the number of rows in each of the base tables. And if I want to calculate the cardinality estimate for a certain intermediate result, then first of all, I can consider all the tables which are involved in that result. If the result is expressed as a query, then it would be all the tables that appear in that query's from clause. So I'm taking all those tables in a from clause, and then I form the product of their cardinality values. So that result basically is the, that would be the cardinality if all the predicates involved had a selectivity of 1, meaning that they are always satisfied. So that is, of course, by far an overestimation. So we need to take into account the more realistic estimate of the predicate selectivity. So after we have multiplied all the table cardinality values, then we multiply that with all the predicate selectivity values of all involved predicates. And then all the cardinality values times all the selectivity values, that gives me a rough estimate for the size of one of those results. Okay, and that's interesting. There's a question about the seminar yesterday, which focused on approximate processing. And that's actually an interesting connection there, because indeed in approximate query processing, we work with some coarse-grained data statistics. There the goal is to produce an approximate query result, but it is true that we use somewhat similar data structures in order to get some approximation for the sizes of intermediate results. So there's some connection between those two. Very good. Okay. All right. So now we have estimated the sizes of intermediate results in terms of the number of rows. Now we still need to estimate the size in terms of the number of pages. Because, for instance, in our simplifying cost model, we have calculated the cost of an operation by looking at the number of pages that it needs to read and write from hard disk. And also those optimizers like the one from the Postgres database system, they also calculate cost based on the number of pages. All right, so in order to get from the cardinality to the number of pages, we first of all need to reason about how many rows fit on each of those pages. Afterwards, it becomes relatively natural to calculate the number of pages. Now, in order to estimate how many entries I can have, how many rows I can have on each of the pages, I essentially think about the number of bytes required for each record. And then I pretty much just divide the space on the page by that, rounding down if necessary, because pages cannot store fractional tuples. That is a question that I'm often getting here. So yes, so one page can only store entire tuples. All right, and after that I can use the number of rows estimated before and combine it with the number of rows per page, and then I get the page estimates. All right, finally, now I have all the information that I need in order to estimate the cost of different operations in my query plan. Now here we have this very simple model where we only count the number of reads and writes for this course. So the Postgres optimizer, for instance, would additionally consider some functions of the computation cost, but nevertheless, it would also consider the number of page reads and writes, and often that is in practice a significant, if not the most significant, cost component. Now, we essentially just sum up the cost of all operations in the query plan. And for each of those operators, for each of those operations in the plan, you need to consider, first of all, for each of the inputs, are those inputs read from hard disk, or are they read from, are they already in memory once the operation starts? Because we have seen that operators can sometimes pass on the result of an operation to the next operator without ever writing it to hard disk, and that makes things cheaper, of course. So for each input to an operation, think about how often we need to read it from a hard disk, if at all. And for each output, we need to consider whether we write it to hard disk or not, except for the very final output of the query plan, because that by convention, we generally don't consider in our cost calculations. And looking at the input to the operation and at the output might not be sufficient, because some of the operators that we have seen, they might internally write intermediate results to hard disk and read them again. If you, for instance, think about the sort operator, it might make multiple passes over the data and write out intermediate results. And so looking just at the output of that operator and at the input of that operator might not be sufficient. You also need to think about how often it internally writes data to disk and reads data from hard disk. All right, and in the end, you sum all, basically the cost of all data movements, you sum them up in order to get to a total cost for the entire query plan. All right, now in the following, I'm gonna make a little example for a cost estimation, just that we have seen the entire process from start to finish a little bit. This example will focus on the query that you see here. Let's say we have a little online shop, a bookseller, for instance, and we want to know how many customers in Ithaca have ordered a book called Ithaca is Gorgeous. All right, so we want to count those customers and orders. And in order to do that, we have this query here. It operates on the database that you see below on the lower half of the slide. We have a customers table with the customer ID, that is the key, and it has a name and location for the customer. So we want to restrict that location to Ithaca in the query. Then we have the orders, which connect the customer CID to products PID, and with a specific date when the product was ordered. And finally, I have the products with the product ID, which is key, the name and the price for the product. All right. So the first step here is that I need some kind of candidate plan for which I'm doing this estimation. So in the following, we're going to analyze the candidate plan that you see here. So the data always flows from the bottom to the top of those query plans, as we have seen. And here we essentially would first of all scan the customers relation and filter to those customers that live in Ithaca. Then we would we would pipeline the results of that operation, the filtered tuples, filtered customers, directly as input to an index nested loop join. So this index nested loop join here joins with the orders table. And in order to do that, it uses a hash index on the customer ID attribute of the orders table. Now the result forms one of the two inputs of the next join. The other input is the filtered products relation, where I'm filtering to products with a certain name. And the result of that and the former result forms the input to a hash join And this hash join pipelines the output to a count operator, which is executed on the fly, meaning that it doesn't need to read its input from hard disk. It just gets its input directly in memory. And the final join, by the way, joins on the product ID column. So we want to find matching entries with the same product ID. So that is the query plan that we will go over in the following. Now, the first step is to estimate the selectivity of a predicate. Now, here on the upper half of the screen, we have some information about the data, some data statistics. You have the number of rows in the different tables. You have the number of distinct values in certain columns. In the middle of the screen, you have constraints, foreign key constraints in this case more specifically. And on the bottom, you have the different predicates that appear in the query. And now I'm going to give you a minute in order to think about how you would estimate the selectivity of those predicates. And while you're doing that, I am going to look at the chat for questions before we will resolve that here. So that is the first step. We are trying to estimate for each predicate which percentage of rows satisfies that predicate. That is the selectivity. And as we have seen before, you can make those simplifying assumptions such as uniform data distribution or independent predicates. Seems there are no questions for the moment. All right. I think let's continue here. I think it might have been at least enough time to think a little bit about how you would approach this problem, perhaps not doing all the precise numbers. Let me quickly move the chat so I see the full slide. All right. So that would be some estimates for those predicates. For instance, we know that there's 100 different locations according to the statistics in the green table. And therefore, if I restrict to one of those locations, then using the formula that we have seen before, we can estimate the selectivity of 1 divided by 100. And here, if we have like the join, basically the join condition between the customers and the orders where the customer ID must be the same. So there's a foreign key constraint from the orders to the customers. That means for each order, I will have one specific customer associated with the order. So that means if I multiply the cardinality of the customers and of the orders table, then I would pair up each order with 10,000 customers, which is way too much. So in order to bring that down to a more realistic number, I want to divide that by 10,000 because each order is not associated with all customers, with all 10,000 customers, but only with one customer. In order to express that, I divide 1 by 10,000. Now, similar reasoning for the other two. Again, we have like one restriction to a single value of one column, and then we have again another join condition with a foreign key constraint. All right, so that is the principle for estimating the selectivity. All right, so now we have the selectivity for the different predicates. I marked that selectivity in the corresponding operator in purple, and we are given the number of rows in the base table. So here, for instance, if we have 10,000 rows in the customer table and the selectivity of the first predicate, as we have estimated, you see here the estimate is 1 divided by 100. So if I multiply that together, then I simply end up with an estimate of 100 rows for the output of that filter operation. And if I have the join here, then in order to estimate the size of the next join here between customers and orders, then I just multiply the input sizes. That would be 100 times 100,000, which is the number of orders, and then divide it by then multiply it by the predicate selectivity. And the result of that is simply 1,000 rows. We'll quickly see whether there are some questions in the chat. Okay, there are some questions about how we get. I don't understand how we get 1 divided by 100 and 1 divided by 5,000 and 1 divided by 1,000. Okay, so so that would be 1 divided by 100, 1 divided by 10,000. So in general, in order to get to those estimates, for instance here, the estimate 1 divided by 100, we assume that values are uniformly distributed. That means that we have 100 different values for the location column, and we filter to any single one of them. Because we assume that each location appears with equal frequency, we estimate that the selectivity is 1 divided by 100, because only every 100th row will be for one specific location. And the principle for estimating this, for instance, for the join condition is that if we pair up random combinations of customers and orders, then the probability that the order refers to the right customer, that should be 1 divided by the number of customers. And here we have 10,000 customers. This is why we are dividing 1 by 10,000. All right. Basically, for the join condition, the selectivity is the probability that a randomly selected order and a randomly selected customer match, meaning that they have the same customer ID. All right. So now we have used those selectivities in order to estimate the sizes of different intermediate results here. So we are multiplying here for the latest result, we are multiplying 100 by 100,000 and then by 1 divided by 10,000, which is the selectivity, and that gives us 1,000 rows. Now here on the other side, when applying the selectivity and the number of input rows, then we end up with 2 rows. And here, if we multiply the 2 together for the next join and multiply by the join selectivity, by the join predicate selectivity, then we end up with an estimate of 2 divided by 5 rows. So a little bit less than half a row expected. Okay. So little question. Those size estimates that we have been calculating so far, do you consider them realistic? Or is there maybe something wrong with them? Does anyone feel that those estimates might not reflect the accurate sizes for some reason? Do you believe that in the end, when asking this query, we really would get probably no single result? Okay, very good point here in the chat. Somebody, oh yes, very good, very good. Okay, so people are generally attacking our simplifying assumptions. Very good, and that is exactly, yes, yeah, okay, very good here. More propositions coming in. Exactly. So there's our simplifying assumptions, and people are already criticizing the uniform distribution. It might in reality not really be uniform, right? I mean, maybe, for instance, there's like different locations. If there's another location, New York City, for instance, it might have a slightly higher frequency than Ithaca in our data set, depending on like which customer base we are serving. Yes, so uniform distribution, that is a stretch. What else? You think about how different predicates connect together. Yes, exactly. There could be some dependency between those predicates. I mean, this book here is obviously, it is quite focused on Ithaca, it seems. So I would assume that for people living in Ithaca, there's a much higher probability to buy that specific book. So this is not independently random distributed, but probably most of the people buying the book, they will also be from Ithaca, or a large percentage of them will also be from Ithaca. And that means that probably those two predicates together, they're less selective than this analysis makes us think. So probably in the end, since there's this dependency between those two predicates, I would end up having more result rows than I'm expecting in this analysis. All right, very good. And the reason is that you're making those simplifying assumptions, which are not always justified in practice. All right, so it is not realistic. In reality, there's a couple of problems with that. Nevertheless, let's continue with those simplifying assumptions. So, I mean, in reality, those simplifying assumptions, they don't always hold, but often they at least allow us to get some rough estimate of the quality of a given parallel band. So even though it's not completely realistic, let's continue with it. And the next step here would be to use those row counts, those estimated row counts, in order to estimate the number of pages. And in order to do that, you first of all should figure out how many rows you can fit on each of those pages. For that, you need to know how much bytes are used up by one specific row. So assuming that we have a page size of 8,000 bytes, and assuming that we use up 4 bytes for integers and dates and 10 bytes for strings. So in order to, so looking at, for instance, the first table with the columns customer ID, name, and location, what would be the number of bytes per entry here, the number of bytes per row. Counting it together, and here basically we have 4 bytes for the customer ID, 10 bytes for the name field, because that is a string, and 10 bytes for the location, which is also a string. So we end up with 24 bytes per row. And if we have that, then we can simply divide 8,000, the number of bytes per page, by 24, the number of bytes per row, and round down, then we get this number of rows over here. So if we make the calculations, and I encourage you to do that in order to get the hang of it, then we end up with those numbers over here. All right, quickly move the chat. All right, so here I have already done the calculations. You see the size estimations in orange here, associated with the corresponding row counts for the different intermediate results. Now, the next step would be to do the cost estimations. So here we're going through the different operators in the plan in order to do the cost estimations. Starting, for instance, with the filter on the customer table. So if I have 31 pages as input, so here for this operator, I assume that initially all data is located on hard disk. So therefore, I need to read those 31 pages. The output is pipelined, that is good, so I don't have to count cost for writing the output to hard disk. And I simply end up with a cost of 31 pages for reading that. All right. Now, the next one is the index nested loop join between the customers and the orders. I assume that I have a hash index available on the customer ID. And now in order to estimate the cost of those index accesses, I need to make some additional assumptions here. So here I assume, to simplify things, that this is a hash index which doesn't have any overflow pages, at least at the moment. And then I simply estimate the index access cost as having to read one page from hard disk in order to look up entries in the associated hash bucket. And then if the index contains references to the data, but not the actual data, then I still need to count one page access for loading specific entries when following the references that are contained in the index. So I am making pessimistic assumptions because I assume that those different entries that the index references, that they're located on different pages. So I need to count one separate page access in order to retrieve each of them. So I'm assuming the index is unclustered. And in this case over here, my input to the index nested loop join, on the one side, I have 100 rows that is on the non-indexed, that's for the non-indexed table. So for each of those 100 rows, I need to first of all look up the corresponding hash bucket, and that gives me one page access. And now I see that in average, I have something like 10 orders for each of the customers. That means, because here you see the input to the index nested loop join is 100 customers, and after joining it with orders, I get 1,000 customer order combinations. So in average, I have 10 orders per customer. And that means that after looking up the hash bucket page, I still need to load entries from 10 pages for each of those orders for the current customer. And that means that per customer, I have essentially a cost of 11 pages. And additionally, here the output of the join is materialized. So I also need to count the cost for writing out this output. And all things considered, I'm getting 100 customers times cost 11 per customer, plus 4 pages that I need to write out to hard disk. So that is the entire cost of this join operation. All right. Now, in order to analyze the cost here of the filter on products, that works as before. Here, I'm reading 12 pages and I'm writing out 1 page. And for the hash join, as you see here, we are assuming that we only need one single pass for the partitioning because we have enough main memory available. So because of that, the cost of the hash join is simply 3 times the input size. And here that would be 3 times 4 pages plus 1 page makes 15 pages. The nice thing is that I don't need to write out the output. And also for the following count operation, we assume that this is executed on the fly. So we have a cost of 0, also because we don't count any cost for writing out the final result of the query plan. So here we have counted the cost of each single operator, And if I count all of this together, then I end up with the total cost of the plan, which is a little bit over 1,100 pages. All right, so that was the first part of the session on query optimization. So in the next lecture, we're gonna continue talking about query optimization, but now we will, in the next lecture, we will discuss about the plan enumeration step. So I recommend you to go again over this example in a little bit of detail. So this is really an end-to-end example. We start with the data statistics, we end up with cost estimates for the plan. You might also want to vary the example a little bit, and we also see a couple of other examples in this direction, but I definitely recommend you to go over this example in detail again. All right, so here, let me quickly see whether there are some quick questions I can answer in the chat, and then we're gonna stop. So here I see, for instance, one question about how we get to the 15 pages for the hash join. And we have seen a cost formula for hash joins where we just multiply the combined input size by 3, because in the partitioning pass, we are reading things once and writing things once. And then in the actual join pass in phase 2, we are reading things once again. So here I have 4 pages on the left, 1 page on the right. That means 5 pages in total, and I multiplied it by 3, gives me 15 pages. Okay, basically, there's like questions about multiple items here for the cost estimation. So in order to get to most of those page sizes, we simply look up how many rows we estimate here, and then about like how many rows we can fit per page for the corresponding result. So we had this a step where we calculated estimates for the byte size per row and for the number of rows that fit on one page. So I'm applying that here in order to get from the row estimates to the page estimates. And in order to calculate this 1,104 pages for the index cost for the index nested loop join, here I essentially assume that for each of the customers, I will have an average 10 orders, and I'm using a hash index in order to retrieve them, which means a cost of 1 page in order to read the references in the hash bucket, and then cost of 10 pages in order to read the actual data, which we assume is located on different pages. So it gives me a cost of 11 per customer. I have 100 of them. And then I need to count the cost for writing out the join result. So that is how I get to this cost value. All right, so we are at the end. I wish all of you a nice day. And then I see you again on Friday, where we continue with query optimization. Have a nice day. All right, let's get started. So the last time we have been discussing about query optimization, and we will continue discussing about query optimization today. Then we might still have enough time to start a new topic. So the last time we have stopped with this example over here. We have seen an example for how the query optimizer estimates or predicts the execution cost of a plan before the actual execution. Now here we had the example query on the example database. We want to find out how many people in Ithaca bought books about Ithaca, and this is the example plan for which we did the estimation. So the first step that we always make is to try to estimate the selectivity of the predicates that appear in the query, meaning the ratio of rows that satisfy the predicate, and we have done that here based on statistics and on constraints, and come up with those estimates over here. Now, the next step is to estimate the sizes of intermediate results based on the cardinality of the base tables here and based on the predicate selectivity values. All right, so here we have estimated the sizes of those intermediate results in the plan. And we have concluded that our estimates might not be entirely realistic because they don't take into account correlations between different predicates, but that is a simplification that query optimizers typically make. And with that simplification, now we have estimated the sizes of entries for different relations. We always add up the byte size of the different fields in a record, and then we think about how many rows you can fit on one page with that size. And if it doesn't give you an integer division, then you always have to round down because pages cannot store fractional tuples. All right, now with that, we have inserted those estimates into the plan here in order to estimate the cost of the different operations, which we also have done. That was the thing that we stopped with last time. And if you sum up all of those different cost components, then you get the entire cost of the query plan. So this example illustrates how query optimizers estimate plan execution cost, and then based on those estimates, they select the plan that they think will work best in practice. So we have been discussing about the cost prediction component of the query optimizer last time. Next, we will discuss about how the query optimizer enumerates different candidate plans. That is done in this plan enumeration component. Now, the plan space for query optimization generally includes decisions about the ordering of operations. Also, we have a choice between different operator implementations. So the query optimizer makes both types of decisions, and that gives you a pretty large search space. And of course, query optimization happens at runtime directly after a new query comes in. So you want to make sure that query optimization does not take too long. And that is why people typically try to restrict this huge plan space by using some heuristics in order to make query optimization faster. And in the following, I'm going to discuss some of the most common heuristics that query optimizers make here. Those are the 3 heuristics that you see here. First of all, we try to apply predicates and projections early. We want to avoid certain joins which cannot exploit joint predicates. And we typically focus on so-called left deep query plans. I'm going to discuss those 3 different heuristics in more detail in the following. So first of all, in general, when processing data, it's typically more expensive to process more data. And that is why we want to reduce data sizes as quickly as possible during data processing. And you can essentially do this in 2 ways. Either you throw away rows or you throw away columns. Both reduces the data size. And that means that you want to typically apply predicates like filter predicates as early as you possibly can in the query plan, whenever all the tables that a predicate refers to are present in the current intermediate result. And also for projections, you want to apply them as early as possible, meaning you want to project out a column if you are sure that it is not used anymore in the future during the same query plan. For instance, considering this plan from before, can anyone see and tell me in the chat possible improvements of that plan? Any suggestions for possible improvements? If you think about the heuristics that we have just seen. Okay, very good. All right, so people are thinking about the projection, and that is, in this case, the right track. So yes, we can try to get rid of more columns during processing. And perhaps I should show you quickly the database that this query refers to again. We had that a couple of slides ago. So here we have the customer relation, we have the customer ID, the customer name, and the location. We have the orders relation with the customer ID, product ID, and the date. And we have products with the product ID, name, and the price. So each of those tables has 3 columns. And if you look at the query plan over here, so that is the same query plan as we see later, then it turns out that we can probably get rid of some of those columns during processing without any drawback, basically. So for instance, if you think about the orders column in the, like about the date column in the orders table, for instance, that one is not used anymore. So it doesn't appear in any predicates, it doesn't appear in any aggregates. So we could immediately project out that column, the date column, for instance. And also after applying filters, for instance, after applying the filter on the customer location and restricting it to Ithaca, after that, we don't really need the location column anymore. So we could also throw that one away later. And that reduces the size of my entries, so I can fit more entries onto a single page. And that means I need less pages overall. All right. I need to be careful when projecting out columns. I don't want to project out any columns that I still need later, because later in the plan, I have a predicate that refers to that column, or an aggregate that refers to the column, or perhaps it appears in some join condition. All of those would be possible. But if none of those apply, then I can typically project out the column, and I should do that in order to reduce the data sizes. All right. Let me jump back to the example. All right, and here we are. So this is how we can improve this example further. We can project out columns early once they become useless. Very good. All right, now another heuristic that is commonly used is avoiding joins without join predicates. Now, if you need to join a set of tables, then in principle, you have a lot of choices about the order in which you do those different joins. And that means in particular, you may also decide to join together 2 tables that are not directly connected by any predicates. Well, the size of a join result is always the product of the input cardinality values, the number of rows in the 2 input tables, multiplied by the selectivity of the join predicate. And if no join predicate is directly applicable, it means that you have a selectivity of 1, which means that every possible row combination from the input satisfy the empty join condition, and therefore you typically get a very large join result. And people want to avoid that. This is why typically we do not consider any plans that contain joins with empty join conditions. There are some special cases where actually using one of those joins would be optimal. They are rare. That is why this heuristic is used quite frequently in practice, for instance, by the Postgres optimizer. And typically, the plans which pass this heuristic filter, they typically tend to contain the optimal plan. Finally, often, not always, but often people focus on left deep query plans. And a left deep query plan that is illustrated here, you see where the name derives from, because here we are going in deep towards the left in this plan tree, in this representation. So essentially, a different way of formulating what a left deep plan is would be to say that the right operand of each join in the plan is a base table. So in principle, you could join things together and then join a second set of table together and then join those 2 table sets together. That would not be a left deep plan. But if the right operand of each join is a base table, then it is a left deep query plan. And the motivation for focusing on that specific class of plans, that is, first of all, that it allows easy pipelining, because here, if you use, for instance, nested loop joins, then those joins, they can start processing if they're only given some part of the left input, which they can read from main memory. And then they produce a part of the output also in main memory and write it into the in-memory input buffer of the next join. So you have a pipeline of multiple joins where you avoid writing intermediate results to hard disk between different join operations. And with this left deep plan, doing that becomes very efficient. Now, the other motivation for using those left deep plans is that also if you have, for instance, created index data structures on columns from the base tables, then you can, as long as you have at least one base table in your joins, you can potentially exploit those previously generated indexes if those indexes refer to the join column and if you have an equality join condition. So for those reasons, left deep plans tend to work well. There is significantly less left deep query plans than general query plans. So that also is a heuristic that is frequently used in practice, but not by the Postgres optimizer, for instance. Okay, now I need to advance my slides, but all right, now it works again. All right, so this is the reason why people tend to go for left deep query plans. All right, so now we have essentially described what is the class of query plans that we want to consider for a given input query. And now we still need to somehow enumerate those potential plan candidates and estimate the cost for each of them, and then finally select the plan with minimum cost. So at least that would be the naive way of doing things, simply generating all possible plans, then evaluating them according to our cost model, and then selecting the minimum one. But doing that can actually be quite expensive, and there's a better way of doing this, as we will see in the following. Now, the thing is this. I mean, if you focus on left deep query plans, then essentially the structure of the plan tree is fixed pretty much, but you still have the choice about the order in which different tables appear in that plan. So, and in the worst case, the number of possible orderings between n tables, that would be n factorial, because you have n choices for the first table and n-1 choices for the second table, n-2 choices for the third table, and so on. And all those choices, they multiply together in order to find the total number of possibilities. And that grows very quickly in the number of input tables. So this complexity is considered highly impractical. If you would try writing a query optimizer which does that, then for most queries in practice, that would not work very well. And query optimization would probably take longer than the actual query execution, because that is also only the number of join orderings. But as we have discussed, the query optimizer makes more decisions than that. For instance, it also chooses the operator implementations, and all those choices together, they form a really large plan space, and you don't want to enumerate all possibilities. Now, this is why people in practice exploit some formal properties of the query optimization problem. In particular, what is useful is the so-called principle of optimality. And that generally means that we can get an optimal solution to a problem by combining optimal solutions to sub-problems. And in the context of query optimization, the entire problem is joining a set of tables efficiently, and the subproblem would be joining a subset of tables efficiently. And the principle of optimality, as I discuss in a little bit more detail next, will essentially tell us that by combining optimal plans for joining table subsets, we can obtain an optimal plan for joining the entire set of tables, right? So in a little bit more detail, I'm discussing that now here on that slide. So I mean, we generally want to find the cheapest plan for joining a set of tables. And that means that in order to get there, we have to first join table subsets on the way to the full join, so to speak. And if you think about it, if you have a plan which first joins a table subset and then it joins more tables until it has joined all the tables, then there's no possible motivation to use any suboptimal plan for joining one of those table subsets. I mean, whenever one part of your plan which joins a table subset is suboptimal, you could improve it, meaning to reduce the execution cost, then there's no way why you would not want to do it. The quality, the execution cost of the overall plan can only improve, meaning decrease as well, by replacing some planned part by a better plan. And that is why we can get an optimal solution to the overall problem by composing optimal solutions to sub-problems. And this is why the query optimizer typically exploits in order to avoid enumerating all possible plans. All right, so what we generally will do, and I'm going to show an illustration on the next slide, that is that we try to find optimal plans for joining subsets of tables first. Those like the task of joining one of those table subsets, that is also called a subquery in the following. All right, and then after we have created plans for joining those table subsets, we will compose them into larger and larger plans for joining more tables. So I'm going to illustrate that process in the following. It is a dynamic programming approach. We start with a set of tables that we want to join. For instance, in our example query, that would be the customers, the orders, and the products. Here you have COP. We want to join that. And in order to join that, we first of all have to join two of those tables together. So we can reduce this problem of joining three tables into one of the problems of joining two tables. And here there is three possibilities. And also, in order to join those two tables, then we essentially decompose the problem of joining two tables into the problem of joining those tables and finding some optimal access paths for those different tables, meaning deciding whether I want to use an index or whether I do not want to use an index. And if I decompose the problem in that way, it motivates the algorithm, the query optimization dynamic programming algorithm that is, for instance, used in the Postgres database system. And this algorithm essentially proceeds in multiple phases. Now, in the first phase, it would consider the optimal way of accessing different tables. Then in the second phase, it would exploit those optimal single table access plans and find optimal ways of joining table pairs. So in the actual plan at execution time, we will only make one of those three possible joins. Either we join C with O or C with P or O with P. We'll only make one of those joins, but here the algorithm needs to consider all three possibilities. And for each of those table pairs, it will calculate the optimal way of generating it by exploiting the previous results. And then finally, it will compose the optimal plan for joining all three tables by reusing the optimal plans for joining table subsets that it has calculated before. So this is how the algorithm proceeds. It executes multiple phases, and in each phase, it considers larger table subsets. So in phase number I, it will generate optimal plans for joining sets with I tables inside them. And in order to do that, it will reuse sets for joining less than I tables that were generated in previous phases. So that is, on a high level, how query optimization considers different plan candidates. And in order to decide which of them are optimal, it uses cost models such as the ones that we have seen before. Now, this was a high-level overview about query optimization. Oh, and yes, a last remark here. We have seen that the complexity for joining n tables is n factorial. And we said that this is impractical. So it is interesting to think about by how much this algorithm reduces those optimization overheads. And I'm not going to go into detail here, but if you make the calculations, then since this algorithm considers all possible table subsets, its complexity is determined mainly by a factor where we essentially account the number of table subsets, and that is not higher than 2 to the power number of tables. That is the possible number of table subsets. Okay, and this complexity is already significantly better than number of tables factorial, which we had before for the naive enumeration. So this is why this algorithm is typically used in practice for most queries. Often query optimizers actually have kind of a backup plan. If some really large query comes in, then using this algorithm can still be too inefficient, because as you see, the complexity might grow quickly as a function of the number of tables still. And this is why optimizers like Postgres, for instance, they have a backup optimizer that is using simple randomized algorithms like a genetic algorithm, for instance, and that optimizer is invoked if the query size exceeds a certain threshold. So by default, for instance, in Postgres, it switches to the backup optimizer if you have more than 12 tables. So in the following, I'm going to show you a little bit more about how to see in Postgres what is going on inside the optimizer. And I'm also going to check the chat for whether there is questions. Okay, and that is an interesting question. The question is about how the optimizer knows the cardinality of join results without executing the plans. So it does that by using the model that we have seen before, where we are estimating the selectivity of predicates that appear in the query. So it does not assume that everything is a Cartesian product, but instead it assumes that you can estimate the selectivity of the different predicates using those simplifying models that we have seen before based on data statistics and based on constraints such as foreign key constraints. All right. If there's any more questions about query optimization, please feel free to put them into the chat. I'm gonna give a little demo about the Postgres optimizer. And I'm going to have a look on the chat in case any questions pop up. All right, you should now be able to see my terminal here. Can everyone see the terminal? If not, then please complain now. All right, and here I'm using, again, the database that I have already used in the past couple of examples. It contains information about the Stack Overflow developer survey from 2019, which is stored in this table here. And as you see, there's lots of information about those developers. All right. So in the following, I'm gonna run a couple of simple queries. And by the way, before I start with that, here you see this command \d also shows you the indexes that you have created on a table. So here I still see the index that we've created during one of our previous examples on indexing. All right. So let's, for instance, say that I want to narrow down which factors contribute to the salary. So perhaps I want to compare different developers, perhaps from the same country, to make it more comparable, because different countries have different salary levels when calculated in US dollars. So I want to compare developers from different from the same country in terms of their salary. So I could do something like a self-join, meaning I join the developer survey table with another copy of the developer survey table, and I join them together on the country, meaning I want to retrieve pairs of developers from the same country. So let's actually do that here. Let's say that we want to, we are interested in the converted compensation column, which we have over here. So that column represents the salary, the yearly salary calculated in like transformed into US dollar amounts. All right, so here, for instance, if I call the first copy of the Stack Overflow table as 1, then I could retrieve the associated salary and also the compensation from the second copy. Here, that is the first copy. That is the second copy, and I want to make sure that we have the same country. Actually, I want to make this non-ambiguous. Even here, the system might recognize that it doesn't matter, because from both copies, I need to have the same value for the country. All right. And executing this query, by the way, is probably not very efficient. I'm not sure whether that finishes quickly, but probably I would want to use a limit clause or something like that in order to reduce the output size. All right. But so the query works, and I'm less interested in the result of this query, but more interested in how that query is executed. So in order to find out how Postgres intends to execute a query, we can use the Postgres explain command. So you just prefix the query with explain, and now the database system will show you the plan according to which it intends to execute the query. So what we have here is a plan which uses a hash join. We have seen the hash join in one of the previous lectures. It's a very popular join for cases with an equality join condition. And here in this query plan, you see all the different steps that the database system plans to execute once you actually submit the query. So it starts with a sequential scan over the Stack Overflow table, and then it builds a hash table, which is here the penultimate row. You see that for each row, it generates a multiple estimate. For instance, before we had a question about what the optimizer assumes about a cardinality. And here you see the estimate that the query optimizer generates for the cardinality of the output of the corresponding step. So I assume you see what I'm marking up here in the terminal. And if not, I'm talking about the penultimate row in this plan, which starts with the hash. And here we have 88,883 rows. And we also have this width estimate, which essentially estimates how many bytes we have in each of those rows. And we have a cost estimate, which is derived from the others. which tells you the estimated execution cost. There's two bounds for the cost. The first bound, that is a startup cost, meaning that is the cost for preparatory, like this is the cost of preparations, like something like creating a hash table, for instance, is counted as preparation. So this is something that needs to happen before you can have the first join result tuple. So especially if you are interested not in retrieving the full result, but only a part of the result using, for instance, a limit clause, then the first cost component becomes particularly important, because this is the time you have to wait before anything interesting happens. So here we're building the hash table, and then we execute the hash join using the hash join condition s1.country equals s2.country, and finally we get a query result. During one of the previous lectures, we had a question about whether we can force the database management system to execute queries in a certain way. And I believe I quickly mentioned already that you can at least indirectly force the database system to use certain operators by disabling other operators. So here in this case, we are currently using a hash join. So perhaps out of curiosity, I could see what happens if I disable the hash join. So the database system will not use the hash join anymore. And I can do that with the command that you see here. I disable the hash join. And if I want to know how the database management system executes the query after that, does anyone have a guess for which join operator we might be using now? If you think back about the join operators that we have seen, if you consider the type of join condition that we are currently facing, okay, and one possibility would be a block nested loop. That would definitely be possible. Yes, I agree. And perhaps when taking into account that we have an equality join condition, there's another specialized join specifically for that join condition. Very good. Yes, very good. Here I see the proposition sort merge join, and that seems like a good guess. Let's see what the query optimizer is really using. And as you see, indeed, it is using the sort merge join now that the hash join is disabled. So typically, if you have equality join conditions, then either sort merge join or hash join probably is most efficient. The advantage of all those block and generally nested loop variants is that they are quite flexible when it comes to the join condition. So let's actually see what happens if I disable the sort merge join as well. And perhaps quickly, I should say a few words about the plan that we have just seen. So here we execute a sort merge join. So that means we first of all want to sort the two input tables. And as you see here, the plan shows two sort operations on the input with the country key over here. And then finally, we have the merge join happening on the sorted inputs. And if we compare the cost estimates to the ones from before, for the hash join, you see that the total cost, that is the second bound here, was something like 8,833,000 rounded. And for the second case, we have 9,731,000 rounded. So here it seems they're close in terms of estimated cost, but the first alternative, the hash join, is at least estimated a little bit cheaper still. That's why the query optimizer prefers the first version. And here we have an excellent question in the chat. Very good. So the question is, here we have a query where I'm referencing the same table twice, and I'm using the same table for both join inputs. And here the join condition is simply equality within one join column. So it absolutely would make sense intuitively to essentially sort this table once, then write the sorted version to hard disk, and then to use that sorted version in order to make the join, right? So there is a couple of points, there are a couple of possible reasons why this might not be happening, but it is a great point. And I mean, that seems like something that might be very efficient. So, I mean, one point is that probably in this case, there's a certain cost associated with materializing the sorted relation on a hard disk. So here, overall, this is not yet a very large data set. So I could imagine that we are able to fit the sorted version into main memory. So instead of sorting it and then putting it back to hard disk and then using it for both of the join operands, it essentially sorts it in main memory. So you could imagine that even if you sort it in memory, then you could reuse the sorted version for both join inputs. I think that, yeah, I mean, that totally makes sense. So here, that one would have to analyze why precisely that is not happening. I would assume that here that is simply a limitation of the execution engine, that it can efficiently exploit having like the sorted version in main memory and using it for the two join operands. Yeah, but this is a great question. And I agree, it seems like there is some potential for optimizations. Very good. All right. Nevertheless, let's see what happens if we also disable the sort merge join. And does anyone have a guess for what join operator might be used now? Yes, and now the proposition is block nested loop join, because frankly, there's not so much left, at least among the ones that we have discussed so far. So let's see what the query optimizer says. All right, and indeed now we are down to the nested loop join, so that's the one that we are using here. All right, so here the cost is already, the estimated cost is now significantly higher than before, something around 119 million. And by the way, those cost estimates, they don't directly map to execution time. So it's a rather abstract measure of cost, but still the understanding is that the lower the cost, the lower the execution time tends to be. So it's not directly possible to calculate, to transform this cost estimate into expected execution time. But somehow better plans have lower cost estimates. All right. So now actually let's enable those join algorithms again. Now if we try it again, then we have the hash join if the optimizer has the free choice. Perhaps one little variation of that query here. So we assume that the full result is a little bit too large. So maybe I just want to get a quick impression for what the result looks like. So I'm adding the limit clause. Does anyone have a guess for which join operator the optimizer might select in this case? We know that without the limit clause, it will select the hash join. Perhaps it just selects the same one. But does anyone see a reason why we might select a different one now? Okay, very, very good. Okay, yes, very good. So here I see a proposition that perhaps now we want to find only 5 join result tuples finally. So it seems possible intuitively to generate those 5 tuples relatively quickly. And it might be disproportional to invest a lot of time into pre-processing. Something like creating a big hash table or something like sorting the entire relation that might pay off later when doing the actual join and generating the full join result. But if I only want to get the 5 join result tuples, I probably want to use something with very little pre-processing overhead. So let's see what the query optimizer actually chooses. And indeed, now that we use the limit clause, it suddenly switches back to the nested loop join, because that one can directly start producing result tuples without investing time into creating a hash table or sorting things. All right, so this gives you a little impression for how the query optimizer works internally. I encourage you to play with it a little bit. You already had, you probably have written a couple of queries already, so maybe you're interested in seeing which kind of plans the query optimizer executes internally. And by the way, one other command that I wanted to show you, we have the explain command. We also have the explain analyze command. And what happens here is that the query optimizer will show you the plan that it executes. It will execute the plan, and it will collect statistics and compare those statistics with the original estimates. So if I, for instance, do this over here, then you see now at the bottom, I'm getting planning time, which is typically short, the execution time, which in this case is also very short. And you still see the query plan on top. For each of those steps in the query plan, you see cost, cardinality, and size estimates. And behind that, you see actual time, rows, and loops, which essentially means here we see how much time it actually used for processing and how large the output size actually was. And here, when comparing those two, for instance, where can we see? Yeah, so you see that, for instance, like the number of rows, the estimate and the actual number of rows are often significantly different, not at the very end though. So if you compare that, then typically you will see some differences, which means that the estimates by the optimizer, they are not ideal. Always make sure to run vacuum analyze before doing that. Here in this database I already did, but if you run vacuum analyze, then those estimates come closer to reality, and still there will be a difference, but often in practice that difference is small enough in order to select at least reasonable query plans. All right, so this was a little impression for how you can get some insights into how the query optimizer works in practice. All right, let's get started. And today we are going to talk about transactions. I've already very quickly introduced the topic in the previous lecture. Now we're going to see the details. So we are going to define what a transaction is in a moment. Know already that the components in a database system that are important for transaction processing, they are mostly located in the storage manager. And here in particular, we are focusing on the so-called transaction manager component. But in a way, all of the other components in the storage manager, they contribute towards enabling database systems to give all the guarantees about transactions that we will discuss in more detail in the following. Now, the relevant chapter in Ramakrishnan and Gehrke, that is chapter number 18. And first of all, we're going to define what a transaction is. So a transaction is generally a sequence of updates and queries that is somewhat semantically connected. And you can tell the database management system that they are connected. We will see corresponding commands, for instance, in Postgres later. And once the database system knows that certain steps belong to the same transaction, then it ensures a certain guarantees. For instance, it makes sure that either all of the steps associated with a transaction are executed, or that none of those steps is executed. So you cannot have situations in which only part of your transaction was executed, but the other part was not executed. So one example domain in which you definitely need transactions, that is banking. And let's start with a very simple example for a transaction. Let's simply say we want to transfer $50 from the account of Alice to the account of Bob. So that means we essentially have two writing steps, two updates to the database. First of all, we need to subtract $50 from the account of Alice. And then we need to add $50 to the account of Bob. And both of those steps are semantically related. So obviously, you do not want to execute only one of those two steps, because otherwise either Bob has not as much money as one should expect, or otherwise both people have more money than they should. So those two steps are semantically linked, and you would typically represent them as one transaction to the database system. Now, for instance, in Postgres, you can start a transaction with the begin command. Then all of the following commands will be considered as part of that transaction. And then once you have finished all the steps from your transaction, then you can write the commit command. Then the database management system knows that this transaction has been finished. It now should be executed. So everything between begin and end is part of the same transaction. Database management systems, they make the so-called ACID guarantees when it comes to transaction processing. And this acronym abbreviates 4 important properties in the context of transaction processing. The A, for instance, stands for atomicity. And that means we either execute all of the steps in a transaction, or we execute none of them. There's C for consistency. And here that essentially means that the transaction leaves the database in a consistent state. So all of the constraints on your data will be satisfied. Otherwise, the transaction is aborted. Now, typically, you have multiple users executing transactions concurrently on the same database. And then it becomes important to shield one user from the actions of another user. And this is what we mean by isolation. So we make sure that those transactions from different users don't interleave in a bad manner. Finally, we have durability. And that means that once a database system has told you that a transaction has executed, at that point, it guarantees that the updates by the transaction are never lost. And that includes situations where, for instance, your server suddenly crashes, maybe there's a power outage or something like that, but the database makes sure that it can recover all the updates by a transaction. So this was a short overview. Now in the following, we're gonna see those important properties in a little bit more detail. Starting with atomicity. And as I have said before, atomicity generally means that we execute either all of the steps in a transaction, or we execute none of them. Now, first of all, why would a transaction not fully execute? There's various reasons, actually. I mean, one reason, for instance, is that the system suddenly crashes while it is in the process of executing a transaction. Maybe, for instance, there's a software bug, or maybe there's a power failure. Another possibility is that a transaction does not execute because it tries to make an update that violates some of the integrity constraints. For instance, it violates a foreign key constraint connecting two tables. Also, you have an explicit command to abort the transactions. For instance, people might use that with a condition around it. So for instance, if certain conditions are not satisfied, then a transaction is aborted. In Postgres, the corresponding command is called a rollback. Now, internally, the database management systems, of course, they don't execute the entire transaction in one atomic step, but they execute one step after the other one. So that means if there's really a problem and the transaction suddenly is interrupted, then internally the database management system actually has to execute a couple of cleanup steps in order to make sure that no partial effects of the transaction are represented in the database. Consistency is about guaranteeing that all integrity constraints on the database are satisfied. So those constraints include, for instance, primary key constraints. So transactions cannot insert any duplicate values in terms of the primary key columns. We have foreign key constraints which connect different tables together. And you can also define a more complex constraints. And in general, if a transaction tries to make an update that threatens to violate some of those constraints, then a database management system will abort the transaction. And there's a little caveat that comes with this term. There's also consistency in the context of distributed systems. You might already have taken corresponding courses. So please be aware that the consistency in the database sense is a little bit different from the consistency in the distributed system sense. So here consistency means that all the constraints on the database are satisfied. Now, isolation means that we shield users from the action of other users, which is important because different users typically execute transactions concurrently. For instance, if you have a banking application, then you would typically have many clients that are trying to transfer money or do other things with their accounts concurrently. So the database system needs to be able to handle that. Now, we could, of course, imagine maybe we just keep things simple and we just execute one transaction after the other one. The reason why we are not doing this is performance. For instance, imagine that one transaction is currently waiting to load data from hard disk. So in general, that only takes maybe a couple of milliseconds, but in the context of data processing, that is actually a long time. So instead of waiting until the data has loaded from hard disk and keeping the processor idle until then, what we could do is that instead we fit in between a step from a different transaction which executes on data that is currently already in main memory. So the access will be very fast. And doing that can often increase efficiency. So that motivates us to try to overlap operations from different transactions instead of executing them serially, meaning executing one transaction after the other one. Now, even if we internally interleave the steps of multiple transactions, we don't want users to become aware of that. Because as a user, if you're writing a transaction, things become very, very complex if you need to take into account that other users might change the data that you're working on while your transaction is executing. That would become very complex code. So in order to keep things simple, we want to simulate to users that their transaction executes as the only one in the system currently. And that guarantee is called isolation. Finally, we have durability. And that means essentially after the database system has told you that your transaction has committed, meaning the execution has finished and everything related to this transaction has been done. At that point, the database system guarantees you that the updates of the transaction will be persistent in the database state. And that holds even if we have those crashes, for instance, due to power failure. no matter, the database system must guarantee that it can recover all the effects of the transaction before it tells you that the transaction has committed. So this guarantee is about keeping your data safe. All right, so those are the 4 guarantees that database systems typically make when it comes to transaction processing, the ACID acronym. In the following, we're going to discuss those properties in more detail. Except for consistency, consistency is a fairly natural to implement. That just means that the database system checks all the constraints and aborts transactions if they don't satisfy them. So we're not going to discuss that in more detail, but we are going to discuss about isolation now in the coming slide deck. And in the later lectures, we will discuss about atomicity and durability. So in the following, we're going to first of all discuss about the isolation guarantee, where we shield users from the actions of other users. All right. And I have a little demo for showing the effects of isolation. Let me quickly prepare that. All right. Okay. And now you should be able to see my screen. All right. So now I want to give you a little demonstration for the effects of isolation. So if you have installed Postgres on your machine, then you can also try that demo yourself. So generally, we need to log into the database simulating 2 different users. So here I have opened 2 different terminals. And now I have already created a database called banking. So this is what we will use for this example. All right, so now I'm logging into the database in both of those terminals. All right, and you see that worked. So now we are connected twice to the same database. All right, so for this example, let's create a simple table representing the account balance of different users. So we have a name and we have an amount of type integer. All right, and now this table has been created, so I see it here. And of course, I also see it here because here we are connecting to the same database. Now let's insert a couple of example values into that database. Let's say that Bob, let's say that Bob has $100, and let's also give $100 to Alice. All right. So if we show the content of the table, then now both of them have $100, and here it's going to be the same thing. All right. Okay. So now in the following, we are going to start a transaction, and we're going to transfer $50 from Bob to Alice. So first of all, we are starting the transaction. So here we are marking to the database system the point where the transaction begins. And the following commands will be considered as part of that transaction. All right. So now the database system has notified us that the transaction has started. And as first part of that transaction, we reduce the amount of dollars on the account of Bob. So we said amount equal to amount minus $50, where the name equals to Bob. All right. And now here in the left terminal on the screen, let's call that user number 1. So user number 1 has now executed a first change on the database and reduced the dollar amount of Bob by $50. So if user 1 runs the corresponding query showing the content of the table, then that change is already reflected. So you see here, the dollar amount of Bob has been reduced by $50. Now on the other side, if I go to the other user, to user number 2 here in the right-hand terminal on the screen, if that user currently runs select the content from the accounts table, then as you see here, nothing has changed. And this is isolation in action. So on the left-hand side, we have already started changing the database, and we can see those changes ourselves. But on the right-hand side, a different user doesn't currently see those changes at all. Let's continue. So user number 1 now adds the $50 to the amount to the account of Alice. All right. And again, if you see what happened here, we see that Alice now has $50 more than before. Again, on the other side, for the user number 2, nothing has changed so far. Both of them still have $100. I mean, that makes sense already at this point. It could be that perhaps the transaction of user number 1 aborts for some reason, and then none of those updates should actually happen. So in order to make those updates take effect for all the other users in the database, in order to publish those changes, so to speak, the command that user number 1 has to run, that is a commit. And now the transaction has committed. So user number 1, of course, can still see those changes. But what has changed is that user number 2 now can also see those changes. And what you have seen here is an example of isolation, because as long as the transaction of user number 1 was not committed, only user number 1 was able to see the changes, while user number 2 did not see the changes yet. All right, so this is one simple example where we use isolation in the Postgres database system. Now let me quickly switch to my slides. And there's already some questions in the chat about how we can actually achieve those guarantees. We are going to discuss about that in a minute. So the operations in different transactions in general don't have to be commutative. All right. So in the following, we're going to discuss in more detail about isolation and about algorithms by which we can achieve isolation. Now, here we are again talking about the transaction manager. Specifically for isolation, the most relevant chapter in Ramakrishnan and Gehrke, that is chapter number 19. And as I have already explained, isolation is generally about simulating sequential execution to the users. Okay. Need to move something here. All right. Now, first of all, let's discuss in a little bit more detail about why we don't want to execute one transaction after another one. And there is at least two motivations. The first one being very long-running transactions. I mean, transactions like transferring a certain dollar amount from one account to another one, they are typically very fast to execute. But you could also imagine having some transactions that do very complex analysis on your database, and executing those transactions can actually take a long time. And if you imagine that we are executing all transactions one after the other one serially, then if you as a user submit one of those very short running transactions, however, your transactions gets scheduled after one of those very long running transactions. In that case, you as a user would have to wait for a long time until your transaction processes, even though your transaction is actually very short and inexpensive. So what is better here is to rather alternate between steps from different transactions, which means that the long transaction might be a tiny little bit slower because we interleave a couple of steps from the short running transaction, but the short running transaction will be as quick as one should expect. And that is why doing like interleaving steps from different transactions seems like a good idea in this scenario. Also, every once in a while, transactions might have to wait for data before executing the next step. For instance, if your data is mainly located on hard disk, then you might have to wait until we load that data from hard disk into main memory. And when waiting for data, then of course there's the choice that we just keep idle until the data arrives, but that wastes time. So it is better to rather schedule a step by a different transaction, which can already proceed because the data it needs is already in main memory. And then once that step from the other transaction finishes, maybe at that point data has been loaded, so the first transaction can make progress again. So for at least those two reasons, that people are interested in interleaving steps from different transactions. Now in the following, we're gonna discuss a lot about how we can interleave steps from different transactions to make sure that nothing bad happens. And in order to keep the examples we will see concise, we will use a short notation that is introduced on this slide. So this is important. You need to memorize the short notation because we will keep using it in all of the following examples. All right. So generally in that short notation, we describe read and write operations by transactions on database objects. So for the database objects, we typically use letters like A, B, C. And in order to distinguish different transactions, we use numbers. So that is typically represented as T1, T2, and so on. In order to represent operations by those transactions, we use R to abbreviate reads, W for abbreviating writes, and RW for abbreviating a combination of a read and a write. So for instance, if you write R1 of A, that means the transaction number 1 reads object A. You also use a C for commits and A for aborts. So if you write, for instance, C2, it means that transaction number 2 wants to commit. Now, let's make a little example with transactions, again, from the banking domain. And here we have pretty much the transaction that we have seen in our little demo. Here we are transferring $50 from the account of Bob to the account of Alice. And as we have seen, this requires 2 steps where we update the amounts in both of those accounts. Now, let's use a second transaction, which, for instance, adds the yearly interest rate. So here, let's say that we're adding 10%, and we need to add that for both of those accounts. So in principle, you could do this by one single query, of course, but here for the sake of the example, let's say that we do this for different accounts separately. All right. And if those two transactions execute at the same time, there's different possibilities about how we can interleave the steps of those transactions. So here there's a first possibility. We could, for instance, start with the first operation of the second transaction, and then do the first transaction, and finally do the second operation of the second transaction again. Second transaction in green, first transaction in blue. Now here on the left-hand side, you see the more verbose queries. On the right-hand side, you see the shorthand annotation. So here, for instance, at the beginning, we are updating the account of Bob, which means that we first of all read the current amount, and then we write an updated account after adding 10%. And that is represented by this RW for read write. 2 is the transaction ID, and B is the database object that we are writing on. So in this case, the database objects we are talking about, those are specific rows in a table. And here by B, we mean the row that is associated with Bob, and by A, we mean the row that is associated with Alice. All right. So this is one possibility of interleaving the operations of different transactions. Now, first of all, if we do this, if we interleave the operations in that way, do we have isolation? So will what we get be consistent with executing one transaction after another one? Or is that perhaps something that, do we see any effects that we would not see when executing one transaction after the other one? If anyone has an idea. Okay, somebody mentions data dependency issues. Yes, yes. Can anyone perhaps make a guess about what changes compared to executing one transaction after another one? If you think, for instance, about the final state of the database. Okay, okay, very good. All right, yes, very good. And here I see a suggestion that the amounts in the account might be higher than they should be. Yes, okay, very good. All right, so this is the, exactly, this is the right direction. So if we play it through in more detail. So if we execute one transaction after the other one, there's really only two possibilities here because we only have two transactions. So either we execute the first transaction first and then the second transaction, or we execute the second transaction, transaction number 2 first, and then transaction number 1. And here we have tried that, both possibilities. So if you first execute the transfer and then the bonus, after doing that, Bob should have $55 because the transfer was from Bob to Alice. Initially, we assume that both of them have, for instance, $100. And if you first transfer $50 from Bob to Alice, then Bob has $50 left. And if we add 10% afterwards, then Bob has $55. Alice, on the other side, since we do the transfer first, she has $150, and then 10% bonus makes $165. So if we first execute a transfer, then the bonus, then this is the amount of dollars that we should find in the end. Now, on the other side, if we first execute the bonus transaction and afterwards the transfer. Now, if both of them have $100, then after the bonus, both of them have $110 because we're adding 10%. And after that, we are transferring $50 from Bob to Alice. So Bob is left with $60, while Alice will receive $160. So those are the two possibilities. There's no more possibilities with two transactions. I only have the choice between which one of them I execute first. And as we see, both of those possibilities, they lead to a different final state in the database compared to the schedule that we have seen. Let me quickly remind you how that looks like. So here, first of all, we are adding the bonus for Bob. So if Bob has initially $100, then Bob will afterwards have $110. Now we are reducing the account of Bob by $50, so from 110 to 60, while for Alice, we increase from 100 to 150. And now we are adding still a bonus for Alice, which means that we have 165 for Alice. So in the end, we end up with $60 for Bob and $165 for Alice. And this final state is not achievable with any of the serial executions. You know, here, of course, in a certain way, you say both of them actually have more money than they should have. So from their perspective, it's a good outcome. But the bank, of course, controls the database server. And from the bank's perspective, it's not a good outcome. All right. And in any case, having this essentially destroys the illusion that your transactions execute serially that we want to give to the users. All right. Now, generally, whenever we destroy the illusion of serial execution towards the users, we call that an isolation anomaly. And in the forum, we're going to see a couple of different types of isolation anomalies. In particular, we're going to have a closer look at dirty reads, unrepeatable reads, and lost updates. So dirty reads, short description, essentially means we read data from a transaction that has only partially finished. Unrepeatable reads means we're reading data once, and then another transaction comes and changes that data. And once we read the data a second time in the same transaction, suddenly it has changed. And that also destroys the illusion of being the only one executing in the system at the same time. Also, lost updates means that different transactions essentially override the changes of other uncommitted transactions in a bad way. So all of those things can lead to problems and destroy the illusion of executing alone in the database. Following, we're going to discuss those different anomalies in a little bit more detail. All right, so first of all, we are going to discuss a little bit more about dirty reads. And that generally means that we read data from an uncommitted transaction. So if we read data from another transaction, it means that we might be influenced in what we do next by the values that we have read. And if you read data from uncommitted transactions, it's actually very risky because we never know whether that other transaction might actually finally commit or whether it might finally abort. Because if the transaction aborts, then I have read values and acted upon them, which are actually invalid because the database should in the end look as if aborted transactions have never happened. So if I read values from those uncommitted transactions and get influenced by those values, it might indirectly reflect effects caused by those transactions that might later abort, which is invalid. Even if I read data from another transaction that might finally commit, that still might lead to strange effects. So generally, dirty reads is something to avoid. And in the demo that we have seen before, for instance, you've seen that when user number 1 was updating the database, then user number 2 did still not see those updates before the transaction has committed. So this is what we are trying to do there. The database system is trying to avoid dirty reads. So user number 2 cannot yet see the uncommitted changes from user number 1. And once we think about the shorthand notation that we have introduced, then the general signature, so to speak, from those dirty reads, that is a write by some first transaction X on object A, followed by a read by another transaction, but on the same object, without any commit between those two operations. So the first transaction X has not yet committed, and still transaction Y is already reading its values. Unrepeatable reads means essentially that the data you are working on keeps changing without you being the one changing it. So that is very clearly destroying the illusion of being the only one executing transactions at the same time. So in general, an unrepeatable read means that we read the same data twice without changing it, but still suddenly the data changes, which means there must be somebody else changing the same data concurrently with me. For instance, one situation in which that can cause a problem, let's say that we are talking about the database of an online shop, and that database essentially takes in orders from customers. So before accepting an order, it needs to check whether it still has enough items in store in order to satisfy the order. So we could imagine that we check the number of items once, and we see, oh, we still have an item left, and then we do something else. But in the meantime, a different transaction, perhaps a different order, comes in and reduces the item count that I'm currently working with. And now once I try to finish the order and want to reduce the item count further, maybe the other transaction has already reduced it to 0. So now I'm trying to subtract 1 and make it negative, which probably is not permitted by the database. So at that point, I'm creating problems, and I might end up with an inconsistent database. So that is one situation in which those unrepeatable reads can create problems, but that's just one example. And the general signature of those unrepeatable reads is that one transaction X reads an object A, then another transaction comes along and changes the value of object A and commits. So even if I don't have a dirty read, then that value has changed. And now the first transaction X again reads the same object and now suddenly finds that it has changed. So that is another anomaly that we want to avoid. One more is lost updates. And that essentially means that different transactions override each other's values while they are executing. And that can create problems because it can lead to an inconsistent database state. For instance, let's say that you want to keep the salary of all employees in a certain department the same for fairness. So you have multiple transactions that update the salary. And if two of those transactions interleave their operations, it might be possible that some of the employees get salary 1 while some other employees get salary 2, which is something that you want to avoid. And you could avoid that if executing transactions one after the other one, because then it would be guaranteed that all employees always get assigned to the same salary. And that problem is generally called the lost update problem, because the updates from some transactions, they might get overridden by other transactions and without committing before. And the signature of that anomaly is the one that you see here. That's simply like one transaction X writes a value to an object A, and then before that transaction commits, another transaction Y comes along and simply overrides the value on the same object. That is the lost update problem. One more problem, one more anomaly that we will discuss a little bit more about later in the course, that is the so-called phantom problem. So I'm already mentioning it here anyway. That is kind of like an extension of the unrepeatable read, but in the context of insertions. And that is something such as, for instance, retrieving all the students whose name starts with a certain letter, all right? And doing that twice within the same transaction. Now, it might happen that when running the query the second time, suddenly more students appear in the result. And that can happen if a different transaction has inserted students between the first query and the second query. And that is also something which destroys the illusion of isolation. And therefore, we want to avoid it. So we are going to discuss this later in more detail, not now, because it essentially requires some extension of the notation. So far, in our notation, we assume that we update database objects that exist already. Like we are updating, we are reading, and we are writing objects A, B, and C, and so on. Here, what we are doing is that we are essentially inserting new objects after a query has executed the first time and before it executes the second time. And for that reason, we're going to discuss that in more detail later, and we are going to first focus on the first three anomalies. All right. Now, in the SQL standard, you actually have different isolation levels. So that means that for certain applications, it might be acceptable to have some of those anomalies, but not others. Isolation can be very expensive performance-wise. So that means that sometimes you might be willing to accept even some slightly strange behavior of your database if in exchange your database can process transactions much faster. And this is why SQL gives you the choice between different isolation levels. So here on the left column, you have the different isolation levels. Read uncommitted, which allows essentially anything. Read committed, which already avoids a dirty read because we are only allowed to read data from committed transactions. Repeatable reads, which avoids the repeat to unrepeatable read anomaly. And finally, serializable, which means that here we have a nearly perfect illusion of isolation. So here on the column on the left, you see the different isolation levels, and the top row is associated with those different anomalies. And you see for each isolation level whether the corresponding anomaly may appear or not. This is how you can change those things in Postgres. In Postgres, you can, for instance, set a default isolation level with the set session characteristics command. You can also set specific isolation levels for specific transactions, because perhaps you have some transactions that are more critical than other transactions. So you can set higher isolation levels for the more critical transactions. You can use that by writing something like set transaction isolation level serializable, for instance. And then this current transaction would be assigned to that isolation level. One thing to know is that many people think by default the database system might support the highest isolation level, but that is often not the case, and that can sometimes lead to problems. So for instance, in Postgres, the default would be a read committed. So one of the little bit weaker isolation levels actually, so some of those anomalies might appear. You can manually set that isolation level higher, and depending on what kind of application you're working on, I would recommend you to do that. So make sure when using a database system that you're well aware of which isolation level you need and which isolation level your database system is currently using. All right. Now in the following, we're going to discuss more in particular about the serializable isolation level, and we're going to discuss about protocols by which we can guarantee that. We won't have too much time to start with that anymore today, but I already give you a little teaser of what we will be doing. We will generally talk more about concurrency control, which is the process by which we achieve isolation, basically. So how that looks like is that you typically have a component somewhere in the database system which performs concurrency control. So the input to that component are the transactions, and the output of that component is a schedule, meaning an order between steps of different transactions that might interleave the steps of different transactions. And then the goal of concurrency control is to select the schedule that is cheapest to execute while still avoiding all of those anomalies that we have seen before. All right, so we're gonna discuss more about this the next time. Let me quickly see, I think there are some questions in the chat. Okay, very good question. So the question is, why would ever want to use a weaker isolation level than serializable if it means that the data in my database can, that there can be anomalies generally? So it depends on what data you are storing and what transactions you're executing on it. For instance, if you have something like, for instance, you have an online shop which has some kind of a visit counter for the website, which is also maintained in the database. Now, if the number of visits is a little bit off to what you would actually expect, it might not be the end of the world. I mean, if you can get significantly better performance and your visit counter of the website might be a little bit off, you would probably accept it. Now, on the other side, when it comes to things like orders, when it comes to updating your inventory list, then those are things that are highly critical where you want to avoid any strange behavior. So that is why SQL allows you to set the isolation level for specific transactions so you can distinguish the ones that are more important from the ones where a little bit of strange behavior might be acceptable. So it depends entirely on your application. But there is situations in which you probably want to accept a lower isolation level than serializable. Is at this point any other questions on transactions? All right, okay. And there's one question about the difference between dirty and unrepeatable read. And that is a well-justified question because there's some similarity between those two. I mean, in both cases, we are reading something that we shouldn't really read. Now, the thing is this. For dirty read, it means specifically we are reading values from an uncommitted transaction. That means between another transaction writes a value and I'm reading the value, there's no commit by the other transaction in between. Now, for an unrepeatable read, the second read might actually read some values from a transaction that has already committed. So that means the transaction I'm reading from cannot abort anymore, but nevertheless, it is an anomaly because I have already read the same value before in the same transaction, and now I see that those two values differ. So the difference between the two is really on whether I'm reading committed or potentially uncommitted values. In case of unrepeatable read, I might read a committed value, which however differs from another committed value that I have read previously in the same transaction. And there is some question about whether people could maybe exploit those lower isolation levels in order to increase the visitor count. That depends a lot on how your data looks like and how your transactions look like. I mean, in general, the visitor count, I use that as an example for something where you might be willing to accept the values that deviate from the real values. Perhaps in practice, if you see that your visit count seems to deviate by a lot from what you are actually expecting, then you might decide to also make that transaction serializable, the one that is updating the visitor count. But probably it's a piece of your database that is less critical than others. All right, good. So that was an introduction to transactions. And we have started discussing about isolation. In the following lectures, we will discuss in more detail about isolation and about methods by which we can achieve isolation. Have a nice day, and I see you again on Wednesday. All right, let's get started. So the last time we have been discussing about transactions, which is this sequence of updates and queries that are semantically connected. And we have seen a few guarantees that the database system makes when executing those transactions. And one of those guarantees is that we isolate different users from each other, which might be executing transactions concurrently on the same data. And if you are not careful, then this might lead to strange behavior from the user's perspective. So isolation is the guarantee that users will not be aware that multiple transactions are executing concurrently. And the process by which we achieve that is called a concurrency control. Here you see the overview of what concurrency control achieves. The input is a set of transactions, each transaction with a couple of steps. And the output is basically a schedule, which describes in which order the steps of different transactions are executed. Now, that would be pretty simple as long as we execute one transaction after the other one. But for performance reasons, we don't want to do that. We want to interleave the steps of different transactions. And that means that we have to be careful when selecting a schedule. So the goal of concurrency control is to select a schedule which provides isolation, while at the same time being as efficient as possible. And all of this happens at runtime. So concurrency control also needs to be very efficient. So first of all, in the following, we're going to discuss about how we select the schedule that we want to execute. Now the schedule, as I have mentioned, that is ordered steps, where each step is a read or write operation from multiple transactions. And a good schedule will provide isolation, so users don't observe any of those anomalies that we have discussed last time. At the same time, a good schedule is cheap to execute. So we want to select ideally the cheapest schedule among the ones that avoid the relevant anomalies. On the other side, we want to reduce the overhead of concurrency control itself. So that means we might make some kind of compromise. For instance, we might not consider all possible schedules when selecting the one for execution, but only a subset if doing so reduces the overheads of concurrency control. So in the following, we're gonna discuss about a couple of alternative criteria according to which we can select the schedules to execute. What we will finally come to is something like a sufficient goodness criterion for schedules that is quick to verify. So sufficient means that if this criterion is satisfied, the schedule is guaranteed to be good to avoid the anomalies that we want to avoid. On the other side, there might be some good schedules that we are overlooking according to the criterion because it is only a sufficient criterion and not a necessary criterion. So here we make a compromise, but in exchange, we get a criterion that is pretty quick to verify. So the overheads of concurrency control are low. And in the following, we're going to discuss about a few different alternatives. So what is a good schedule? Now, a good schedule generally avoids the anomalies which destroy the illusion of being the only user executing transactions at the same time. So we will define good schedules by comparing to a gold standard, which is essentially a serial schedule. So the user should feel as if transactions are executing serially, meaning one after the other one, while in reality, we interleave the steps of different transactions. But if we compare a candidate schedule to some serial schedule and we find that they are equivalent, then we can conclude that the candidate schedule is also good when it comes to isolation because it looks like one of those serial schedules. So in the following, we're going to see a couple of criteria that allow us to compare different schedules against each other. We will see final state equivalence, where we compare essentially based on the final state that you have in your database after executing the two schedules. Then we compare according to view equivalence, and that means when comparing two schedules, users essentially see exactly the same things in the same order for both of those schedules. And conflict equivalence means that if you have pairs of steps in one of those schedules which conflict with each other, because, for instance, both steps, they change the value of the same object in the database, then we essentially have those operations appear in the same order when comparing those two different schedules. So this is an overview. Now we're going to discuss those criteria in more detail. Starting with final state equivalence. So here we say that two schedules are equivalent if the final state of your database is the same after executing them, starting from an arbitrary starting state. All right. So for instance, if you look at those two example schedules here, and I'm going to seize the opportunity to quickly remind you of the short notation for schedules that we have introduced last time. So here you have those W's, which always means a write operation. So we change the value of an object in the database. Then you have those R's. Actually, here you don't have R's, but in general, for the schedules that we will see on the next slides, you have R's. And in that case, it's a read operation, where we read the value of an object in the database. With this notation, you always have, for instance, the type of operation, which here is a write operations, W, followed by the ID of the transaction executing that step. So we always use numbers for transactions. So here we are starting with a write operation by transaction 1. And then between parentheses, you always have the object in the database that the write operation refers to. So here we have object A generically. And in reality, concretely, that could, for instance, correspond to one row in your database. For instance, initially we had an example where we transferred money from the account of Alice to the account of Bob. Then you have to change values for those two database transactions. Okay, and here we have the question whether one query ever can have multiple transactions. So just to make sure, queries are included as part of a transaction. So basically, one query would be a part of a transaction, and update operations as well. All right. You also have the C's here in this example schedule. A C always means a commit operation, and after the C, you have the number of the transaction committing. So if a transaction commits, it always means that the transaction essentially is finished and wants to get executed. All right. Now here, when comparing those two example schedules, in the first schedule, transaction 1 executes first and writes values to A. And okay, so here actually in the first schedule, we have first a write operation by transaction 1 to object A. Then we have a write operation by transaction 2 to object A. So the final value for A will be written by transaction number 2. Then we have a write operation by transaction 1 to object B, followed by a write by transaction 2 to object B. So also for B, the final value will be written by transaction 2. And finally, both of those transactions commit. Now, the second schedule over here first writes a value for object A via transaction 1. Then transaction 1 writes also the value for B and commits. After that, transaction 2 writes the value for A and the value for B. So when comparing those schedules, then in both of them, transaction number 2 writes the final values for objects A and B. And that is why those two schedules are final state equivalent. If we say that a schedule is final state serializable, it means that there is some serial schedule which contains the same transactions that is a final state equivalent to that schedule that we are analyzing. And this other schedule that we are comparing against must be a serial schedule executing transactions one after the other one. So a schedule is final state serializable if we can find a final state equivalent serial schedule. Now, final state equivalence can be efficiently verified, which is good, but on the other side, it is not sufficiently strong as a criterion in order to avoid all those strange anomalies that we have discussed in the previous lecture. For instance, we have heard about this anomaly unrepeatable reads, where I read one value once, and then later I read it a second time, and the value has been changed in the meantime by another transaction. So that is bad. And even if a schedule is final state serializable, it could still have those unrepeatable read anomalies. So for instance, if you look at the schedule over here, we have first a read by transaction 1 of object A, then a write by transaction 2 to object A, and finally another read by a transaction 1 of object A. So here you have an unrepeatable read because the second transaction might have changed the value of A in the meantime. On the other side, the schedule is final state serializable because transaction number 2 writes the final value for A in any case. All right, so probably we want a stronger criterion than final state serializability. That leads to a view equivalence, and there we compare two schedules based on what the user sees in which order. And we have a whole bunch of conditions such that two schedules S1 and S2 are view equivalent. First of all, if some transaction reads the initial value before schedule execution starts of some object in one schedule, then it must also do so in the other schedule. Also, if a transaction reads the value of an object that was written by another transaction before, then it must also do so in the other schedule. And then finally, if some transaction writes the final value of an object in the first schedule, it must also do so in the second schedule. So we require all three conditions in order to say that those two schedules are view equivalent. Now you see here, we have some conditions that relate to the final state of the database, because if the final value was written by a transaction in one schedule, it must also have been written by that transaction in the other schedule. But we additionally have some conditions which refer to what the user sees or what the transaction sees. If a transaction has seen the initial value in one schedule, it must also see it in the other schedule. And if a transaction has seen the value written by another transaction in the first schedule, then it must also do so in the second one. And that is where the name view serializable comes from. And here, all right. And there's a question in the chat that refers to a little typo here. So the last point actually should be that if a transaction X writes the final value in S1, it also does so in S2. Yeah. So that is a little typo. Thank you. All right, so here the last condition basically means that the final value of those objects should not change when comparing the two schedules. So that is basically referring back to final state serializability. All right. And then view serializability again means that we find a serial schedule which is view equivalent to the schedule that we are analyzing. So for instance, here's an example where we are trying to determine whether a specific schedule is a view serializable. You see the schedule that we are analyzing here. First, we are reading the value of object A by transaction 1. Then we are writing, then transaction 2 writes the value for object A. And then transaction 1 reads the value for A again. So this is the schedule that we have already seen before. And here we have potentially an unrepeatable read. So we expect that this schedule is not view serializable, but let's make sure. So since we have two transactions that appear in this schedule, there's exactly two possible serial schedules that we can compare against. Either we first execute the first transaction and then the second transaction, or we first execute the second transaction and then the first transaction. Now, here we have both possibilities. So either we could have the first transaction execute first, then followed by the second transaction. But this schedule, the serial schedule, is not view equivalent to the schedule that we are analyzing, because the second read of object A, in one schedule, it reads the value written by the second transaction. In the other schedule, it reads the initial value. So that violates one of the three conditions. In the other case, where we execute the second transaction first, we have that both reads of A by the first transaction, they read the value written by the second transaction, but none of them reads the initial value. And in the schedule that we are comparing against, one of those two read operations reads the initial value of object A. And because we cannot find any serial schedule that is view equivalent with the schedule that we are analyzing, therefore, this schedule is not view serializable. View serializability seems like a nice criterion. It is pretty strong, so it avoids those anomalies that we have seen. The only problem with that criterion is that it is NP hard in general to verify whether a schedule is view serializable. And NP hard generally means that we don't know and don't believe that there exist any efficient algorithms in order to solve that problem. And selecting a schedule that is something that the concurrency control component needs to do at runtime very quickly once transactions are being submitted. So we most definitely don't want to solve any NP-hard problems at runtime, because that would slow down the entire database system. So this is an overview of what we have seen so far. This is an illustration of the different classes of schedules that we have been discussing about, as well as how those different classes of schedules relate to each other. You see that we have inclusions among them. We have, first of all, the set of all possible schedules which contain the same transactions. Then you have the subset of schedules that are final state serializable. Then you have the even smaller subset of schedules that are view serializable. And finally, you have the small set of schedules that are indeed serial. So all of those inclusions are proper, so you can always find the schedules that are included in the larger class, but not in the smaller class. Now, having discussed all of those different classes of schedules, our final goal is to select a class of schedules that we want to aim for in concurrency control. Now, serial schedules are easy to verify, but they are very slow to execute. We have seen a couple of motivations for why we want to avoid serial schedules that execute one transactions after the other one last time. We have seen view serializable schedules, but the problem with them is that they make concurrency control very slow because we would have to solve NP-hard problems. We have seen final state serializable schedules, but here the problem is that we might have anomalies. So we destroy the illusion of isolation. And then we have the set of all schedules, and there we have exactly the same problem. So in a way, none of those classes of schedules seems to be a good choice for aiming as a goal in concurrency control. So we need something else. And in the following, we're going to discuss an alternative class of schedules that is a much better compromise between those different quality criteria. All right. Now, the class of schedules that we will be aiming for is a conflict serializable schedules. And so first of all, we introduce a conflict equivalence and say that two schedules are conflict equivalent if they have the same conflicts appearing in them. Now, what is a conflict? So a conflict arises between two steps of like two different transactions if they operate on the same object, and one of those operations is a write operation. That is important because as long as transactions are just reading data, everything is fine and nothing bad can happen. But as soon as transactions start changing the data, this is where we need to be careful that we don't interleave transactions in a bad manner. So for a conflict, we must have two operations by different transactions, where one of those operations is a write operation. And that leaves essentially three possibilities. We could either have first a read by the first transaction, followed by a write on the same object by the second transaction. Or we could have first a write by the first transaction, followed by a read of the same object by the second transaction. Or we could have two writes by two different transactions on the same object. Those are the possibilities. Whenever I change the order of some of those conflicting operations, so I change the order in the schedule, whenever I do that, I have a risk of creating differences, either in terms of the final state of the database or in terms of what the users see in which order. On the other side, as long as I only change the ordering between non-conflicting operations, I cannot have any of those bad effects. The final state will be the same, and also users will see the same things in the same order. So I can say that two schedules are conflict equivalent if I get from one schedule to the other one by only swapping non-conflicting operations. And in line with that, we have conflict serializability. A schedule is said to be conflict serializable if there is a serial schedule, and I can make sure that the serial schedule is conflict equivalent to the schedule that I am analyzing. Now, for a given set of transactions, of course, there's many different serial schedules. So I don't want to try out all of them and compare them in terms of conflict serializability, in conflict equivalence. Instead, I want a more efficient method to test whether a given schedule is conflict serializable. And we can do that by the method that I'm going to describe in the following. It involves drawing a so-called conflict graph. We'll see in a second how to define that conflict graph for a given schedule. But it comes in the end down to testing whether this conflict graph has a cycle, and the schedule is only conflict serializable if this graph has no schedule, and that is something, it has no cycle, and that is something that we can test very efficiently. All right, so this is the definition of the conflict graph. So if we want to find out whether one schedule is conflict serializable, then we are drawing this conflict graph for it. And in the conflict graph, we are introducing one node for each of those transactions in the schedule. And then for each pair of conflicting operations by two different transactions, operation O1 and operation O2, we draw an edge from the transaction to which O1 belongs to the transaction to which O2 belongs. So this edge in the conflict graph basically indicates a conflicting operation between those two transactions. We draw that edge from the earlier transaction, from the transaction with the earlier operation, to the transaction with the later operation. Let's make a little example. So here we have a schedule given on top in purple. It involves 3 transactions. So definitely the conflict graph must have 3 nodes. Now, can anyone tell me which conflict edges I should draw in my conflict graph over here? Or at least, can anyone identify, for instance, one pair of conflicting operations and tell me what edge I need to draw in the conflict graph because of it? In the chat, please. Okay, there's a couple of things coming in. Okay, good. So in general, 2 operations conflict if they belong to different transactions. They operate on the same object, and at least one of those operations is a write operation. So here, for instance, we have the proposition R1 of C followed by W3 of C. So let's see here. R1 of C, we have it here, and then W3 of C, we have that at the very end, exactly. So here we have the same object, we have different transactions, and one of them is a write operation. And that means that we want to draw a line from the first transaction to the third transaction. All right. W2B and W3B. All right, okay, exactly. So here we have 2 conflicting operations following each other immediately. One write to B by transaction 2 and one write to B by transaction 3. Transaction 2 goes first, so we want an edge from transaction 2 to transaction 3. Now we have another one, W1A to R2A. All right, where do we have W1A? Okay. So R2A goes first, right? So we first have the read of A by transaction 2, and later we have the write to A by transaction 1. So we would want to draw a line from 2 to 1. Okay, very good. So this is the principle. Compare pairs of operations in the schedule and see whether they conflict, and then draw the corresponding edges in the conflict graph. So we have collected all of them. Here now I'm drawing the edges. I believe we covered all of them. Very good. All right, so that is the conflict graph. And finally, I would have to check whether that conflict graph has a cycle or not. And in this case, we don't have a cycle. So this one is a conflict serializable. All right. So perhaps to illustrate that point a little bit more, why is it that we are looking for cycles? So if you have an edge from some node I to a node J, representing 2 different transactions, then essentially means that any conflict equivalent serial schedule must order transaction I before transaction J in order to avoid swapping the order of those conflicting operations. And because of that semantics, the way in which I can transform one schedule that is conflict serializable into the conflict equivalent serial schedule, it's by essentially doing a topological sort in the conflict graph. So essentially I start, first of all, with the transaction whose node has no incoming edges. Then I take all the operations of the transaction and write them into my new conflict equivalent serial schedule. Then I continue finding one node where all incoming edges belong to transactions that have already been treated. And I continue doing this until finally I know that I have treated all the transactions in the current schedule. For instance, in this example over here, we would first start with a transaction 2 because node 2 has no incoming edges. So I can order the operations of that transaction first. Now, node 1 next doesn't have any incoming edges from nodes that haven't been treated yet. So I'm gonna put transaction 1 next. And now finally, I can put the operations of transaction 3. And now I have a serial schedule that is conflict equivalent to the original schedule, and can do that quite easily using the conflict graph. All right, so this is where we stand now. We have found one new class of schedules that are conflict serializable. There's one little drawback to them. They are a little bit too restrictive, meaning there's some good view serializable schedules that don't create anomalies, but they would not be allowed according to the conflict serializability criterion. But what we get in exchange is a criterion that is very efficient to verify using this conflict graph that we have seen. And that is why we will be aiming for creating conflict serializable schedules via concurrency control in the following. It is a compromise between different criteria. All right, good. Any questions on this at this point? All right, otherwise just put them into the chat. All right. So far we have been classifying schedules into this hierarchy, but we haven't really talked about aborts yet. So when testing, for instance, whether a schedule is conflict serializable, you would first of all take out the operations by all transactions that are finally aborting, because the database management system essentially guarantees that transactions that have been aborted, that everything looks like they never happened in the end. So in testing all those previous criteria, we are not at all considering transactions that have been aborted. On the other side, aborting transactions is something that is actually quite common in practice. So we also want to take it into account when choosing a schedule. So in the following, we're going to see another classification of schedules, which is orthogonal to the previous one, and it deals primarily with transaction aborts. And here there's a question, I think, that still refers to a conflict graph. If we have a cycle, is it considered as a programmer's fault, or will it be randomly selected when one starts executing? If there's a cycle in the conflict graph, it means that the selected schedule is not conflict serializable. So typically, the concurrency control component would aim to select only schedules that are conflict serializable. So if there's really a cycle in the conflict graph, that is something that should not happen when you use a concurrency control method that aims for conflict serializable schedules. So the goal of concurrency control is to avoid any cycles in a conflict graph and to select schedules which don't have them. So yeah, if that happens, would be the fault of the programmer of the database management system. Okay. All right. So first of all, we will discuss about recoverable schedules. Recoverable schedules, it's a very basic criterion saying basically that your schedule should leave the database in a consistent state. It's a very basic requirement. If you look, for instance, at the schedule marked in red over here. So what we're doing here is we first have a write to object A by transaction 1, followed by a read of object A by transaction 2, and a write by transaction 2 on object B. And now transaction 2 commits, but a bit after that, transaction 1 aborts. And that creates a huge problem for the database system, because the database wants to guarantee that committed transactions are never undone. On the other side, it wants to guarantee that aborted transactions have no effect whatsoever on your database. And the problem is this. Transaction number 2 has read the value of object A that was written by the first transaction, which means that transaction 2 might have been influenced in what it writes to object B by what it has read from object A. And that means that logically, if transaction 1 had never happened, then transaction 2 might have written a different value to object B. Now, that creates a problem. On the one side, we want to guarantee that transaction 2 will never be undone, but it was influenced by transaction 1, and we want to guarantee that transaction 1 has no effect whatsoever on our database state. So this is a situation you totally want to avoid, because here the database system essentially tries to guarantee two things that conflict with each other. We call such schedules non-recoverable. And essentially, in order to avoid such bad schedules, what we need to do is that we delay the commit of a transaction until we can be sure that all other transactions it has been influenced by have also committed. So essentially, we want to make sure that a transaction only commits after all the transactions it has read from have committed. And if I have that, then I have a recoverable schedule. Now, recoverable schedules, that is something that you want in any case, but aborts can even create problems if a schedule is recoverable. For instance, if you look at the schedule here below, here we have again, it is, and maybe I should compare to the previous one. So here we have again a write to object A by transaction 1, and then a read of A by transaction 2, followed by a write by a transaction 2 to object B. Now, what we have done here is that we wait with the commit of transaction 2 until transaction 1, which has influenced transaction 2, has also committed. So if you compare that to the previous schedule, here the problem is that transaction 2 already committed before it knew that transaction 1 commits 2, right? So here we have essentially delayed the commit by a transaction 2 until we can be sure that transaction 1 commits as well. That makes it recoverable, which is good. But on the other side, if at this point transaction number 1 decided to abort, then we would also have to abort transaction 2 because it has been tainted by reading the value of object A that has been written by transaction 1. So that means that we have essentially cascading aborts because one transaction aborts and that causes another transaction which has read from it to also abort. That is something that we want to avoid for performance reasons, because if you have like a long chain of transactions where the first one aborts and that causes all the other ones to abort too, that creates huge overheads to the database system. So that's why we're interested in creating schedules that avoid cascading aborts, also called ACA schedules. And in order to get there, the only thing we have to make sure of is that a transaction does not read uncommitted data. If we read uncommitted data, we might have a cascading abort. If we don't read uncommitted data, we avoid that possibility. So avoiding cascading aborts is good. There's still a couple of issues that can arise in the case of aborts if multiple transactions have written to the same object. So first of all, if multiple uncommitted transactions have written to the same object, it means that I need to keep track of which transaction has written which value, because if some subset of those transactions abort, I need to know which is the right value to assign to that object. Also, when, for instance, aborting one transaction and undoing values for an object, reverting them back to the original value, I need to verify whether the current value of the object is actually invalid and whether I really need to undo it. So generally, having multiple transactions write to the same object where all those transactions have not yet committed, that can create some complications in the cleanup. And that is why people in practice often try to avoid such schedules and go for strict schedules instead. Strict schedules generally means that no transactions reads or overwrites uncommitted data. So once one transaction has written a value to an object, then this value will not be read and it will not be overwritten until that transaction which has written the last value has committed. All right. So for instance, here at the bottom of the slide, you have another example schedule where 3 transactions write to object A. Now, this schedule, first of all, is recoverable. We actually don't see any commits at all in this schedule. It avoids cascading aborts because we don't see any reads of uncommitted data here in the schedule, but it is not strict because different transactions override each other's values before any of them commits. All right. So altogether, we have now seen another hierarchy of schedules. We have the set of all schedules. A subset of that is the recoverable schedules. Then we have the ACA schedules that avoid cascading aborts. And finally, we have the strict schedules. So in summary, now we have seen 2 ways of classifying schedules. First of all, based on serializability. There we have seen final state serializable, conflict serializable, and view serializable. And then we have classified them based on aborting behavior. And there we have seen recoverable schedules, schedules that avoid cascading aborts, and strict schedules. And which of those schedules you're going for, it depends on many factors. For serializability in the following, we will be aiming for conflict serializable schedules because it's a good compromise between the quality of the schedules and the overheads of concurrency control. For abort behavior, we will definitely go for recoverable schedules, but then depending on the variant of concurrency control that we are discussing, we might sometimes consider only recoverable schedules, sometimes ACA schedules, and sometimes strict schedules, whatever provides the best performance in certain circumstances. So we will start now to discuss about mechanisms for concurrency control. And one of the most popular mechanisms, that is two-phase locking. Here we are discussing about the transaction manager component of the database system, the relevant chapter in Ramakrishnan and Gehrke, that is chapter number 19. So generally, what we are discussing about now is the algorithms that run inside of that concurrency control component. So what we have seen in the previous slide deck was generally a classification of schedules. So we have seen that we probably want to aim for conflict serializable schedules. We want recoverable schedules, and depending on the situation, sometimes we want ACA schedules, and sometimes we want strict schedules. So now we're going to discuss about protocols which generate those schedules. There's always trade-offs. Ideally, we want a mechanism that allows many possible schedules to consider, because then we can select the most efficient one for execution. On the other side, we want a mechanism that is very cheap to execute. So we might be willing to accept considering less schedules if in exchange it reduces the cost of concurrency control. So in the next lecture, mainly we will be discussing about locking-based concurrency control methods. Now, we're going to discuss more detail in the next lecture, but already tell you a few basics. So generally, those concurrency control mechanisms will be based on locks, which essentially represent a permission to operate on a specific object. And the mechanisms that we will see essentially force transactions to first acquire a lock on an object before they can work with it. They submit those lock requests to the lock manager, and then they wait until the lock request is granted. And only then do they proceed. The lock manager generally keeps track of which locks has been assigned to which transactions, and it also keeps track of which transaction is interested in what lock, and it queues them, and then it grants transactions with locks and makes sure that no two transactions have conflicting locks on the same object in the database. That is the high-level principle. In the next lecture, we're going to discuss more details for one very popular concurrency control mechanism. Have a nice day, and then I see you on Friday. All right, let's get started. So today we are still going to talk about isolation and concurrency control, and we are going to see a specific algorithm in order to do concurrency control. That the algorithm is called two-phase locking. We are still discussing about the transaction manager in the database system, and the relevant chapter for what we discuss here, that is chapter 19 in the Ramakrishnan and Gehrke book. So generally, we're currently discussing about concurrency control. And as a little reminder, concurrency control essentially takes as input a set of transactions which want to execute read and write operations on the database. The output of concurrency control, that is a schedule which orders the steps, the read and write operations from different transactions. And it may do so in a way such that it interleaves the steps from different transactions. So we do not execute one transaction after the other one, but we might execute a few steps from transaction number one, then a step from transaction number two, and then again some steps from transaction number one. But if we do this, we have to be very careful, because otherwise we create strange effects for the user and inconsistent data. And concurrency control is about making sure that this does not happen. So we want to find algorithms that can actually do concurrency control, and we're going to discuss about one of the most popular ones today. So far, we have been mostly discussing about what properties we want in one of those schedules. In particular, we have seen that conflict serializability is kind of a good compromise, because if your schedule is conflict serializable, it means that those strange effects due to interleaving multiple transactions, they cannot occur. So to the users, it looks as if everything executes serially, one transaction after the other one. On the other side, conflict serializability has a nice property that we can quite efficiently verify for a given schedule whether it is conflict serializable. And efficiency is very important since concurrency control happens at runtime. So we do not want concurrency control to become the bottleneck. So we want conflict serializable schedules. We also want recoverable schedules. And as we have seen last time, that means essentially that one transaction does not commit until all the other transactions that it has read values from have committed before. Because otherwise you might end up with a database in an inconsistent state from which it is impossible to recover. So we want recoverable schedules. And we have seen a couple of other properties, avoiding cascading aborts and strict schedules. And depending on the scenarios, we might also want some of those properties. Now in the following, we're gonna discuss about protocols, about algorithms that allow us to enforce schedules with those desired properties. And generally, ideally, we want mechanisms that allow as many schedules as possible that have those properties that we're interested in. Because if we can consider more candidate schedules, then we have better chances of finding one that is particularly efficient to execute. And therefore, we want to be able to consider as many schedules as possible. Now, a very popular variant of concurrency control is based on locks. A lock generally means the permission to operate on a specific object in your database. And before a transaction can do anything with a database object, which could, for instance, be one row in one specific table. Before a transaction can do anything with it, be it a read operation or write operation, it first must acquire a lock. So in order to acquire a lock, a transaction submits a lock request for the specific object to the lock manager, which is a component that generally administers the different locks and keeps track of which transaction has acquired which lock. Now, if a transaction requests a lock, that lock might not be immediately available because maybe currently another transaction has the lock on the corresponding object, and we have to wait until the other transactions gives back the lock to the lock manager, and then the lock manager can distribute that lock again to the waiting transaction. So a transaction might have to wait a little bit until it obtains the lock. Once it has the lock, then it can start working on the object. Now, this is the high-level outline of locking-based concurrency control, but there is many variants, and in the following, we're going to see a couple of them. Let's start with something very, very simple. Let's say that we just make one big lock for the entire database. So if a transaction wants to do anything with the database, it first has to request the lock on that database, and it waits until it gets it. Then it performs its operations, and at the end, the transaction gives back the lock on the database to the lock manager. So that means that essentially only one transaction can hold this lock on the database at the same time. Does anyone have a quick comment about how you expect this scheme to perform? In the chat? Yes, very good. Okay, very good. I see multiple comments and all of them are correct. So yes, indeed. If we make one big lock for the entire database, then we're often unnecessarily blocking transactions from proceeding because different transactions might be able to work on different parts of the database at the same time. And if I really only have one big lock for the entire database, what happens means essentially only one transaction can execute at the same time. It acquires the lock at the beginning, it gives it back at the end. So that means what I'm essentially doing is that I'm executing transactions serially, one transaction after the other one. And the whole point of concurrency control and preparing transaction schedules was that we want to get better performance than when executing transactions serially. So this is probably not what we want. Let's refine it. Now, a first refinement uses the observation that there's many objects in a database, and what are the chances that two transactions want to access exactly the same object? So we should refine our logs to refer not to the entire database as a whole, but rather to specific objects in the database. So those objects could have different granularities. It depends on the implementation. For instance, we could say that one row in a table is an object. And if we have that, then transactions, they first of all decide which objects they are interested in. Then they request the logs for all those objects and wait until they get them. Then it executes. And finally, the transactions gives back all the logs at the end of execution. All right. So this already works better than before, because now different transactions can proceed in parallel on multiple parts of your database. Now, another refinement is the following. So we have seen, when discussing about conflict serializability, that conflicting operations, they always involve at least one write operation on the same object. On the other side, as long as I only have read operations, I could actually allow many transactions to proceed in parallel. The problematic operation is really the write operation. And in order to increase the number of transactions that can execute at the same time, I could start to distinguish between read logs and write logs. So a read log, those are also called shared logs, allows you to only read the values of an object, but not to change them. A write log, also called an exclusive log, allows a transaction to read and to write the corresponding object. And if I have those different log types, I can exploit them, because as long as transactions only want read logs, I can grant multiple logs on the same object to different transactions. All right, and now all of the transactions essentially have to decide whether they want to read an object only, or whether they want to read and possibly write an object. Then they have to request the corresponding log type for the corresponding object. All right, and again, the effect of that is that we can possibly allow more transactions to execute in parallel on our database. All right, now so far we have assumed that transactions request and wait for all the logs at the beginning of execution, and then they hold those logs until the very end of the execution. So at the beginning of execution, a transaction requests all the logs. At the end of execution, the transaction gives back all the logs. Now, sometimes it might not be necessary to hold an object, to hold a log on an object until the very end of execution. If a transaction is done working on an object, it seems reasonable that that transaction already gives back the log on that object, so that another transaction can start working on that object before the first transaction is finished. Now, this refinement can be a good idea, but it doesn't have to be. It can be a good idea because it might again allow more transactions to proceed in parallel. On the other side, if you allow this, then you might have cascading aborts. And there's a little reminder what is a cascading abort. So if a transaction aborts, it generally means that all direct and indirect effects of this transaction should completely vanish from the database. So it should look as if the transaction had never happened. And if a transaction writes a value to an object and that value is read by a different transaction, the value could have influenced what the different transaction is doing. That means if the first transaction aborts, it has indirectly influenced the behavior of another transaction. So if you abort the first transaction, you also have to implicitly abort the other transaction that has been influenced by it. That is a cascading abort. And if you allow transactions to hand back locks before they finish executing, before they have to decide whether they commit or whether they abort, then what you see in this example here can happen. So here we have a write operation by transaction 1 on object A. And now let's say transaction 1 is done with object A, so it could already hand back the lock on A, right? So the lock manager accepts the lock from transaction 1 again, and then it immediately hands it out to transaction number 2, which is requesting the lock on A because it wants to read the value of that object. So this is what you see here. Basically, the lock changes hands from transaction 1 to transaction 2. And now, unfortunately, transaction number 1 decides to abort. And in that case, we would also implicitly have to abort transaction number 2 because something that this transaction did could have been influenced by the value that it read from A, and that value has been written by the aborted transaction. So if we allow transactions to hand back locks early, it means that we must accept cascading aborts, and then it becomes a design decision. There's a performance trade-off here, and depending on the scenario, one possibility might work better or the other. Now you might already guess the next refinement. So here we have relaxed the requirement that transactions hold their locks until the very end of execution. And now the next refinement is that we allow transactions to acquire locks not at the very beginning of execution, but sometime during their execution. Quickly checking the chat here. All right, and here there's a question about the last example. I'm quickly going to answer that before continuing. So here the question is, if R2 had read a different object, whether it could have been influenced by A or not. It could not have been influenced by A. So we assume that the database system knows all the values in the database that transactions read or write. So if the database system doesn't know about any read operation on A, then the transaction hasn't read the value of A and cannot have been influenced by it. And at least in the short example, it seems that transaction 1 is only writing to object A. So unless transaction 2 is reading the value of A, it cannot be influenced by transaction number 1. So here we only talk about influence because one transaction reads a value written by another transaction. So in this case, if transaction 2 had read a different object than A, we wouldn't have a cascading abort. Great question. Let me quickly move the chat to the side. All right. Okay. Here we have refined and allowed transactions to release locks early. Now we're going to allow them to acquire locks late. So essentially, we have so far required a transaction get all the read and write locks before transaction processing starts. But strictly speaking, that's not always necessary. Because maybe a transaction wants to start working with object A, and it can already do this as soon as it has the lock on object A. Afterwards, it will continue working with object B. So it can delay acquiring the lock for object B until it is done with object A. And as always, if we reduce the time that locks are held by a transaction, it allows more transactions to proceed in parallel. That's always the advantage. One drawback about acquiring locks late is what you see in this example here. It's called a deadlock. You might already have heard about it. And it essentially means that transactions are mutually waiting for each other and nobody can make progress. So here, for instance, a simple example of 2 transactions. In general, a deadlock might involve more than 2 transactions, but in this example, it's only 2. And here, transaction number 1 acquires a lock on A, and at the same time, transaction 2 acquires a lock on B. Now, transaction 1 has the lock on A, transaction 2 has the lock on B. Now, transaction 1 wants to do something with object B, so it is now requesting the lock for object B. This lock is currently held by transaction 2. At the same time, transaction 2 is requesting the log for object A, which is currently held by transaction number 1. So those two transactions each have one log that the other one needs to make progress. And that means that none of them can make progress because they will wait indefinitely. And what happens in reality is that the database system detects the situation and resolves the deadlock by aborting one of the participating transactions, so at least the other ones can make progress. We're going to discuss much more about deadlock handling in the following lecture. But just so you know, there's again a performance trade-off here. If we allow transactions to acquire logs late, we might increase the number of transactions that can proceed in parallel. On the other side, we might have deadlocks, and that can have a bad impact on performance. So depending on the scenario, this is either a good idea or not a good idea for performance. Now, the title of this lecture is two-phase locking, which is one very popular locking protocol, which essentially combines all of the advantages that we have seen so far. Namely, first of all, it allows for fine-grained logs. We don't have one big log for the entire database, but specific logs for database objects. It distinguishes different log types, shared, meaning read logs, and exclusive, meaning write logs. Depending on the variant of two-phase locking, it might allow transactions to acquire logs late. Also, depending on the variant, it might allow transactions to release logs early. There is, however, some restrictions in general about when transactions might acquire and might release logs. This is an illustration of those restrictions. As the name two-phase locking suggests, we must have two phases when it comes to locking. In the first phase, the transaction can only acquire logs on objects but not release any. In the second phase, a transaction can release logs on objects, but it cannot acquire any. So if you look at the number of logs held by a transaction over its execution time, as illustrated in this plot here, on the x-axis, you have the execution time starting with the transaction start at the left and ending with the end of execution of one specific transaction. And on the y-axis, you have the number of logs that a transaction holds at the same time. And as you see here, during the first phase, the number of logs held can only increase, while in the second phase, the number of logs held can only decrease. So those are the two phases of two-phase locking. You have a summary of what I have just said. We have the phase in which we can acquire logs, and we have the phase in which we can only release logs. And that becomes very important, as we will see later, when we try to prove that this protocol guarantees that generated schedules are conflict serializable. And for that proof, we need that two-phase property. There's a couple of different variants of two-phase locking. First of all, we have conservative two-phase locking, which means that we do not allow transactions to acquire logs late. We require them to get all their logs at the beginning of execution. Also, there is strict two-phase locking, which means that we do not allow transactions to release logs early. They have to keep them until the end of execution. You can also combine those two, and then you get conservative strict two-phase locking, and the plain two-phase locking makes no restrictions whatsoever. So we can illustrate those different variants using the same graph as we have seen before, where we see how the number of logs of a transaction evolves over time. And as you see here, for the conservative two-phase locking variants, at the very beginning of execution, we always have a spike in the number of logs held. This is because we require conservative two-phase locking requires transactions to obtain all of their logs at once at the beginning of transaction execution. On the other side, you have the strict variants, and here you have the sudden drop at the end of the transaction. So this is because strict two-phase locking requires transactions to hold on to their locks until the end of execution, and they release all of those locks at once. Now, if you look at the non-conservative, non-strict two-phase locking, that's the plot that we have seen previously. Here we can have some kind of ramp up in the first phase and then some decrease in the second phase. Of course, this figure here is simplifying. If you would draw that plot for an actual transaction execution, you would get something much more messy, but the general tendencies that you see here, they do apply. So all of those variants of two-phase locking are used, and depending on the scenario, it depends on the scenario which one of them performs best. There's a couple of pros and cons about those different variants that I'm summarizing here. So generally, if you are non-conservative and non-strict, you are more permissive, which can be good for performance because it allows more transactions to interleave their steps and to essentially execute in parallel. The nice thing about conservative two-phase locking is that we prevent deadlocks, which can be bad for performance because you might have to abort transactions and restart them. On the other side, if we go for strict two-phase locking, then we avoid cascading abort. So especially in scenarios where it is quite likely that transactions abort. In those scenarios, it can be helpful to have something which essentially localizes the abort and avoids the chains of transactions that all have to abort because some initial transaction that they have directly or indirectly read from had to be aborted. So in general, you cannot say that one of them is better than the other one. It always depends on the specific workload, which of them works best. All right. So now we have seen two-phase locking. We need to convince ourselves that using it is really a good idea. Ultimately, what we want are conflict serializable schedules. We have justified why we want conflict serializable schedules in the last lecture. Now we have seen a concurrency control protocol, which seems to make sense. But at this point, how can we be sure that two-phase locking indeed leads to conflict serializable schedules? How can we exclude that users see any of the anomalies that we have discussed in previous lectures? In the following, we're gonna analyze two-phase locking formally, and we will prove that two-phase locking can only generate conflict serializable schedules. Is there any questions on two-phase locking before I proceed with that proof? If so, please ask them now in the chat. Otherwise, we will proceed. Okay. All right, one question is about a reminder of what conflict serializable was again. So conflict serializable essentially means that for a given schedule, we find another schedule that is serial, meaning it executes one transaction after the other one. And we find that our current schedule is conflict equivalent to the serial schedule. And two schedules are conflict equivalent if you can get from one schedule to the other one by only swapping operations that do not conflict. And two operations conflict if they execute on the same object, if they belong to different transactions, and if one of those two operations, at least one, is a write operation. And the point of plain two-phase locking, we could say yes, so conservative two-phase locking has this advantage that it avoids deadlocks, and strict two-phase locking has the advantage that it avoids cascading abort. So what is the point of plain two-phase locking without any of those extensions? The thing is that plain two-phase locking allows transactions to acquire locks late and to release them early, meaning that the total time that a transaction holds a lock decreases in average. And if a transaction holds a lock on an object, it prevents other transactions from accessing the same object. So the longer a transaction holds locks, the longer it makes other transactions wait. And that is bad for performance. So if you reduce the time that a transaction is holding a lock, you reduce the lock waiting time for other transactions. That means that you reduce idle time and your transactions in the system can process faster. So if deadlocks and cascading avoids are unlikely to happen, then you probably get the best performance with plain two-phase locking. And yeah, it's a justified question. I mean, it sounds scary. Deadlocks, cascading aborts. So one might think, why would people allow that to happen? But it really depends on the probability that it happens. If a deadlock is so unlikely that you would only have one deadlock per day and you process millions of transactions, then probably you would still do it. But same for cascading aborts. If transactions essentially never abort, then cascading aborts are also extremely unlikely. So probably if you have only one cascading abort per day or per year, then you probably want to reap the performance benefits offered by reducing lock waiting times. So in the end, it's a trade-off. You cannot say a priori which variant is best. It depends a lot on the properties of the workloads. And this is why different variants are implemented in practice. And yeah, so in the end, if you're really serious about performance tuning, then you might even try for a specific workload which of those variants works best. But a priori, you cannot say which one of them is the best. And plain 2PL, why is it better than a transaction that simply grabs the lock before it meets an object and releases it directly afterward? That's a great question. What is suggested here basically is something which doesn't necessarily follow the two phases of acquiring locks and releasing locks. So one could think, yes, why not? A transaction needs access to object A, so it acquires a lock on A, does what it needs to do with A, and then releases the lock on A. And then it needs to do something with object B, so it acquires the lock on B, operates on B, and releases the lock on B, and so on. In that way, I'm reducing the time during which locks are held. However, I'm not following those two phases of a two-phase locking because the transaction would first release the lock on A and then again acquire a lock on B. And at this point, it is probably not clear why that is a problem. But during the proof that we are about to do, we will actually see why we need those two phases in order to guarantee that two-phase locking generates conflict serializable schedules. So this is a great question. Let's table it for the moment, but it will become clear during the proof. Okay, great questions. All right, I think let's proceed with the proof. Okay. So this is an overview of the proof that we will do in the following. So we will essentially analyze schedules that were generated using a two-phase locking concurrency control protocol. And now we assume essentially, could it be that one of those generated schedules has a cycle in the conflict graph? Because if it has a cycle in the conflict graph, it means that it is not conflict serializable as we have seen before. Now, in the following, we will essentially prove that if a schedule was generated using two-phase locking, it cannot have a cycle in the conflict graph, and therefore it must be conflict serializable. In order to conduct this proof, as a lemma, we will prove the following. We will prove this, what I call the release first lemma, which essentially says that if in the conflict graph I have a path from transaction 1 to transaction 2, then I must have that transaction 1 releases a lock on some object before transaction 2 acquires a lock on some object. So very important, we don't even require that transaction 1 and 2 are releasing and acquiring locks on the same object. It could be different objects. But if there's a path from one transaction to the other one in the conflict graph, then the first one must release a lock on some object before the second one acquires some lock. This lemma will be proven via induction. And induction generally means that you first prove something about a trivial case, and then you make the induction step, where you essentially reduce larger instances to smaller instances. Now, in this specific case, what we will do is we will first of all prove that this lemma holds for paths of length 1. So basically, we have just one step from one transaction to another one in the conflict graph. And in the induction step, we'll prove that if the lemma holds for paths up to length I, then it will also hold for paths of length I plus 1. So we always extend the coverage of the lemma in terms of path length. This is the induction start. So we have two transactions, 1 and 2, and they have an edge connecting them in the conflict graph of the schedule. That means they have a conflict. And a conflict generally means that both of them work on the same object, and at least one of them is writing to the object. So we essentially have three possibilities. Either transaction 1 is reading object A and then transaction 2 is overriding it, or transaction 1 is writing to object A and then transaction 2 is reading it, or both of the transactions are writing to object A. So the second transaction is essentially overriding the value of the first transaction for A. Now, in all of those cases, what I need to have is that transaction 1 releases the object on A before transaction 2 acquires the lock on A. Now, transactions generally need locks in order to operate on objects. And here, for instance, for possibility 1, it seems that transaction 1 had at least the read lock on object A, so it can read the value. Transaction 2 needs a write lock, an exclusive lock, in order to write something to object A. Now, an exclusive lock and the read lock, they are mutually exclusive. So in order to grant an exclusive lock on object A to transaction 2, the lock manager first needs to get back the read lock for object A from transaction number 1. So here definitely, in order to make this possible, in order to enable possibility 1, the lock, some lock on object A needs to get released and by transaction 1, and a lock on object A needs to be acquired by transaction 2. Now the principle is similar for possibility 2, also for possibility 3. So here basically transaction 1 needs first to hold an exclusive lock on object A, and it needs to release that exclusive lock so that transaction 2 can acquire another exclusive lock on object A. So here again, we have what we want to prove in all of those cases. Because there's a conflict between them, we must have that transaction 1 releases a lock on some object before transaction 2 acquires a lock on some object. So this is what we want to prove. We have proven it for pairs of length 1. Now let's say that we have proven things for path length of up to I. And now we want to prove that this implies that it also holds for paths that are one step longer. So here we want to extend for paths with I nodes to paths with I plus 1 nodes. All right. So first of all, we assume that we have already proven via induction that if I have a path of length with up to I nodes, that the first transaction in that path releases a lock on some object before the last transaction on that path acquires a lock on some object. It doesn't have to be the same object. So we have proven this. We assume that we have proven this via induction. Now, looking at the connection between transaction I and I plus 1, using the same reasoning as on the previous slide, we also know that since there is a conflict between them, transaction I must release a lock on some object Z before transaction I plus 1 acquires a lock on Z. So this is even more specific than on the other side of the screen, because as long as we only consider one step and there's a conflict, we know that the conflict must concern the same object. So the locks get released and acquired for the same object. All right, so now those things. So I'm already close to proving the lemma. I want to prove that transaction 1 releases a lock on some object before transaction I plus 1 acquires a lock on some object. The question is just this. If I compare the lock acquirage, like the operation by which transaction I acquires a lock, and the operation by which transaction I releases a lock, which one of them happens first? We have had the question about why we need those two phases of a two-phase locking, and this is exactly the point at which we need them. Due to the properties, to the constraints of two-phase locking, I know that I have those two phases where first I only acquire locks and then I only release locks. And that means when considering this transaction I, if I have I acquires lock on Y and I releases lock on Z, due to the constraints of two-phase locking, I know which of them must happen first, because transactions always acquire locks first before they release locks later. And that means, due to the properties of two-phase locking, I know that we must acquire the lock on Y before we release the lock on Z. Now I have here a happens before chain of events, and taken together, that means again that transaction 1 on that path releases a lock on X before transaction I plus 1 on that path acquires a lock on Z. And this concludes the induction step. So by applying this recursively, I can essentially expand the lemma to paths of infinite length. And therefore, I know that if I have a path in the conflict graph from one transaction to the other one, the first transaction must release a lock before the last transaction acquires a lock. Now, how does this help me with the proof? Now, if I have this lemma, and I assume that I have a cycle in the conflict graph, then due to this lemma, it essentially says that some transaction in that cycle releases a lock before that same transaction acquires a lock, right? So we have a path from T1 to T2, means according to lemma, T1 releases lock before T2 acquires lock. Now I have a path from a transaction to itself, a cycle basically. That means that T1 releases a lock before T1 acquires a lock. And now again, we use the properties of two-phase locking, because that is not possible. Transaction cannot acquire a lock after it has released the first lock on any object. And because of that, I can conclude that I cannot have any cycles in a conflict graph as long as I use two-phase locking in order to generate them. had I not used the constraints of two-phase locking, then there could very well be a cycle in the conflict graph that I'm generating. And that means that I don't get a conflict serializable schedule. But since I made those restrictions of two-phase locking, because of that, I can be sure that all the schedules that I'm generating are conflict serializable. All right, so now we have shown that using two-phase locking, we generate only conflict serializable schedules. Now, the last interesting question, perhaps, when comparing two-phase locking to conflict serializability here, is what about the other way around? Could two-phase locking, at least in principle, generate all schedules that are conflict serializable? And as we see here, using an example, that is not the case. In fact, I wanted to ask you whether that can be the case based on the example that you see here. All right, I already gave you that. Okay, and it is also said on the slide. So we could not, in general, generate all the conflict serializable schedules using two-phase locking. If you consider, for instance, this example here, this example schedule, transaction 1 writes something to object A, transaction 2 reads from object A and commits, transaction 3 reads object B and commits, transaction 1 writes again to object B and then commits. So if you would draw the conflict graph, we have 3 nodes, and we have 2 actors, and we have no cycle here. We have only this conflict on object A between transaction 1 and transaction 2, and then we have the conflict on B from transaction 3 to transaction 1. So this is conflict serializable. But the question is, could this have been generated using two-phase locking? If you have a second to think about it and put a proposition into the chat. If you think about where locks are requested and granted, could we have had this? If you think about which locks transaction 1, for instance, is acquiring and releasing. Okay, some first propositions here. Okay, very good. Yes, very good. Okay, so very good. Okay, so I have the correct solution by multiple people. Very good. Okay. All right, let's discuss it quickly in more detail. All right, so if you think about the lock requests when transactions acquire locks and release locks, and we focus on transaction 1. All right, so the very first operation in the schedule is a write operation by transaction 1 on object A. And that means that transaction 1 clearly must have the write lock for object A, otherwise it couldn't write to it. Now, immediately after that, transaction 2 seems to be reading from object A. That means transaction 1 must have given up the write lock on A, because otherwise the read would not be permitted by a different transaction. So clearly, between the first step in the schedule and the second step, transaction 1 must have given up the lock on A. Now things continue. Here we have the commit, okay, and now transaction 3 is reading object B. So clearly at this point, transaction 3 must have a read lock on object B, and then it commits. And now transaction 1 writes to object B. That means that at this point, transaction 1 would need to have a write lock on object B. Now the question is, could it have had that lock maybe since transaction start? The answer is no, since just before that, transaction 3 has read from object B, so obviously transaction 3 had a read lock on B at that point. So transaction 1 must have acquired the lock on B directly before the write operation. But on the other side, it has released the lock on A after the first step in order to make it accessible to transaction 2. So what we would have here is that the first transaction first releases a lock before the lock on A, before it acquires another lock, which is the lock on B. And since two-phase locking does not allow transactions to acquire locks after they have released any, it means that this schedule here, despite being conflict serializable, it could not have been generated by two-phase locking. And that essentially answers the question. Now we have the full overview picture here. So we've discussed about all those different classes of schedules. We have all schedules contained within them are the finite state serializable schedules, then the view serializable schedules, then the conflict serializable schedules. And now we know that two-phase locking essentially is a subset, like the schedules that could have been generated using two-phase locking, they are a subset of the conflict serializable schedules. And a small subset of that again would be the actually serial schedules. So this is basically what we can hope for. We guarantee that two-phase locking generates conflict serializable schedules, so we have no strange anomalies. Ideally, we of course would like two-phase locking to be able to consider all conflict serializable schedules. That is not the case, but nevertheless, two-phase locking is one of the most popular locking protocols used in practice. In the next lecture, we're going to discuss about a couple of extensions before we also discuss about different concurrency control methods. Wish you a nice weekend, and then I see you again next week. Okay, good. So let's get started. Sorry for the delay. Today we are going to talk more about locking, two-phase locking. That's one of the most popular locking protocols, and we have seen the basics of two-phase locking last time. In this lecture, we're going to discuss about a couple of special cases and scenarios. We are still discussing about the transaction manager, the database system, and the relevant chapter in Ramakrishnan and Gehrke, that is chapter number 19. Now, in this lecture, we're going to discuss about a couple of special scenarios. We're going to discuss about what happens if we have a deadlock. We're going to discuss about an anomaly called phantoms. I have already mentioned that anomaly quickly at the beginning, but I have told you that we will postpone the discussion until later. We're also going to discuss about locking specifically in index data structures. And in the end, we're going to discuss about multi-granularity locking, which essentially means that we can acquire locks on different type of objects, such as tables, as well as single pages from a table. All right, we're going to start a discussion with deadlocks. And as a little reminder, a deadlock is something which arises if multiple transactions are mutually waiting for each other in a cycle. Why are they waiting for each other? Because each transaction is waiting to obtain a lock from the next transaction in this waits for cycle. This can happen only if you use non-conservative two-phase locking. We have discussed multiple locking variants last time, and some of them have the nice property that they avoid deadlocks. And I believe one of your peers asked the question, if we have a mechanism that avoids deadlocks, why would we ever use something else? That's a good question. Now, it is true that the deadlocks can lead to problems, and we are about to discuss more about how to address those problems. On the other side, if you choose to accept deadlocks, you often get something nice in return. For instance, when comparing conservative and non-conservative two-phase locking, it turns out that the non-conservative two-phase locking allows potentially more transactions to proceed in parallel, and that can increase performance. So there's a trade-off, and it depends on the scenario which one of them works best. Now, in the following, we're gonna discuss more about how deadlocks are handled. And there is essentially two possibilities. Either you can essentially passively wait for deadlocks to happen. You try to detect them and to resolve them if you encounter them. The other possibility is that you are proactively preventing deadlocks from happening in the first place. One version of that, so to speak, is to use a concurrency control protocol where this is guaranteed not to happen, but in the following, we're gonna see a few alternative methods. Now, before we continue, first of all, we have been discussing a lot about deadlocks, but maybe many of you haven't experienced a deadlock in practice yet. So I want to encourage you, if you have Postgres installed, to try to generate a deadlock. You don't need to worry, nothing bad is going to happen. The database system will resolve it. But we have seen last time that we can simulate multiple clients connecting to the same database in Postgres simply by opening up two terminals, for instance, and having that try to generate a deadlock in the next couple of minutes using two transactions is enough. If you don't have Postgres installed, then think about how you would generate a deadlock in Postgres with at most two transactions. Now, I give you a little bit, 1 to 2 minutes of time. You can try to do it, or you can just think about how you would do it. If you have any questions about two-phase locking, which is the basis for what we are discussing today, please feel free to ask them in the chat. And after that, I'm going to show you on my computer how to realize one deadlock. Any questions on two-phase locking in the meantime? No questions on two-phase locking, it seems. All right, let's try it together. I'm gonna share my entire screen now by closing the chat. All right. So let's see how we generate a deadlock. So last time we have created a little banking database which contained information about the accounts of different customers together with an amount. Let me log into that banking database here with both terminals. So I'm simulating two clients, and as a reminder, we had this accounts table with two columns. The first one is the name of a customer. The second one is the amount on that account. All right. And as you might remember from last time, we are starting transactions with the begin keyword. So here we have started a transaction, and we're also going to start a transaction for the other customer. Now, in Postgres, logs are associated with rows in a table. In this case here, we have one row for each customer account. So if I want to perform an operation on one of those rows, then first of all, the transaction needs to acquire a log from the log manager. So let's, for instance, say that here we are trying to add $5 to each account. Maybe that's the yearly interest or some other bonus. So let's start with Alice over here. And let's say that we update the accounts and we set the amount to the amount plus $5, where the name equals to Alice. All right. So we do this operation, it works, not a problem. So in order to make this happen, the transaction must have acquired the log for the corresponding row for Alice from the log manager in the database. Now on the other side, let's say we want to do the same thing. We are adding a bonus twice. So here we also update the accounts. We set the amount to $5 more. Here, however, we start not with Alice, but with Bob. All right. Oops, and here I forgot the equality sign. And now, since I made a mistake, I actually need to, first of all, let me start this again. All right. Okay. And now we have made it. We have increased in this transaction. We have added $5 to the account of Bob. All right. And in order to make that happen, this transaction over here must have acquired a log for the row that represents the account of Bob. So now the transaction in the left terminal holds a log on the Alice row, and the transaction in the right screen holds a log on the Bob row. So I have to speed it up a bit because otherwise you might run into a timeout and then I have to start again. So let's say that now here in the left terminal, now I want to increase the amount for Bob. All right. And what happens here, you see that with the previous command, the database system immediately confirmed that a command has been received and executed. Now, in this case, this doesn't happen. Here, actually, the database system seems to block and it doesn't immediately execute the command. The reason is that here, I want to access the row of Bob. So in order to do that, the transaction, first of all, needs the log on the Bob row. And that block is currently not available because the transaction on the right-hand side of the screen is still running. And that transaction is currently holding onto the log on the Bob row. So now I have one transaction waiting for another one. The transaction on the left terminal is waiting for the transaction in the right terminal. In order to create a deadlock, I need to close the cycle and make the transaction on the right-hand side wait for the one on the left-hand side as well. So let's actually accomplish this by trying to update the account of Alice here on the right-hand side. In order to do that, the transaction would need the lock for the address row, but that lock is currently held by the transaction on the left-hand side. And so by doing this, we should create a deadlock. All right. And as you see here, this is what happens. We get the error deadlock detected. So here we have a deadlock indeed, and the transactions and the database system detects that, and it resolves the deadlock by aborting one of those transactions. And as you can see here, the transaction on the right-hand side is aborted. On the other side, the transaction on the left-hand side of the screen, this one has finally produced the output saying, yes, we have updated the account of Bob, because as the transaction on the right-hand side has aborted, it also must release all of its locks so they become available. And finally, the transaction on the left-hand side can acquire the lock for Bob. And now we have done that, and we have successfully updated the database. And here we have created a deadlock. It was resolved by aborting one of the transactions. All right. All right. Let me quickly check whether there's questions in the chat. All right. And here a great question about how we make sure that locks are released, for instance, on the Bob row. So in general, those locks are released automatically in the background once the transaction finishes. It depends actually on the specific variant of two-phase locking when locks are released precisely. Often in practice, we use strict two-phase locking, and then the locks are released once the transaction has finished executing at the very end. And okay, that's another great question. So in this case, how many updates have actually executed? Okay, great question. All right, so we had two transactions that were in a deadlock with each other. So they were mutually waiting for each other, and nobody was able to make progress. Now the database system typically resolves those deadlocks by aborting only one of those transactions that are waiting for each other. So we want to avoid aborting transactions if we don't have to. So in order to break the cycle, it is typically sufficient to abort only one transaction within that cycle. And in this case, Postgres decided to abort the transaction on the right-hand side of the screen, which was trying to do two updates, but those updates, they have not happened because the transactions was aborted and all its effects were rolled back. The transaction on the left screen was able to proceed after aborting the other transaction, because by aborting the other transaction, its locks become available. So the transaction on the left-hand side has succeeded and has executed two updates. Very good questions. All right, so now you should see my slides again. Let me actually check whether, okay, this still getting a little error message. Okay, so let's continue with our presentation mode. All right, so now we have seen how to generate one of those deadlocks and how they are automatically resolved. Now, what Postgres is doing internally is a deadlock detection. So typically, we try to detect deadlocks by creating a so-called waits for graph. The waits for graph is sometimes confused with the conflict graph, because in both cases, the nodes are transactions. But the semantics of the edges differs, because in the waits for graph, you have an edge from one node to another one if the first transaction is waiting for a lock by the second transaction. So the lock manager keeps track of this waits for graph. Whenever a transaction requests a lock, then that is not immediately available, then we draw a cycle, and then we draw an edge within the conflict graph. And periodically, we check for cycles in the waits for graph. If we have a cycle, it means we have a deadlock and we need to take care of that. That is one of the standard methods to detect the deadlocks. Perhaps one of the simplest methods is to simply say that we assume there has been a deadlock if a transaction cannot make any progress within a given amount of time. However, of course, here it becomes difficult to choose an appropriate timeout. Maybe the transaction is not deadlocked, but just a little bit slow for the moment. So the method with the waits for graph is more reliable. If we have detected a deadlock, the database system tries to abort one of the transactions within the cycle. You have already seen this in practice here in Postgres. We automatically had one of the deadlock transactions aborted. Now, depending on the settings, the aborted transaction might be restarted. Here that was not the case. You can also try to optimize the selection of which transaction to abort, because if you have a cycle, you might have multiple possibilities to break the cycle. And there's a couple of heuristics that database systems use. For instance, you might say that the youngest transaction that has started most recently, it has done perhaps the least amount of work. So by aborting that transaction, we lose the fewest number of operations, which might be good for performance. So here, the high-level idea is we detect, we look out for deadlocks, and if we encounter them, we resolve them by aborting transactions. The other possibility is that we proactively avoid deadlocks, and we proactively abort transactions that might cause a deadlock. So that is a little bit more careful, because I'm aborting transactions even if I don't have a deadlock yet. On the other side, it can save overheads for deadlock detection, for instance. So again, you cannot say which of those methods is better. It always depends on the particularities of the scenario. Now, the strategies that we will see for avoiding deadlocks are based on transaction timestamps. So if transactions come into the system, they get assigned a timestamp, and we say that older transactions that run for longer, they have higher priority. Now in the following, we're going to see two very popular deadlock avoidance protocols. The first one is called wound wait, and the second one is called wait die. Now, in this naming of the protocols, the first part of the protocol name essentially tells you what happens if a higher priority transaction wants a lock held by a lower priority transaction. The second part of it tells you what happens if a lower priority transaction is waiting for a lock held by a higher priority transaction. All right. So, for instance, in the first case, wound wait, we have a transaction T1 that needs a lock which is held by T2. Then T1, so to speak, wounds or aborts the second transaction if T1 has a higher priority than the transaction which is currently holding the lock. So the higher priority transaction essentially goes ahead and grabs the lock and aborts the other transactions in the process. In the second case, if a lower priority transaction wants a lock that is currently held by a higher priority transaction, then the lower priority transaction politely waits until the lock becomes available. So the wait die protocol works differently. So here, if a higher priority transaction wants a lock held by a lower priority transaction, then the higher priority transaction is allowed to wait until the lock becomes available. On the other side, if a lower priority transaction wants a lock held by a higher priority transaction, then the lower priority transaction is proactively aborted. So it's not allowed to wait until the log becomes available. So those are the two possibilities, and we're gonna see in more detail in the following how they make sure that no deadlocks can happen. Here we start by analyzing the wound wait protocol, and we justify why we cannot get any deadlocks when applying this protocol. A deadlock always means that transactions are mutually waiting for each other in a cycle. And as I mentioned in those protocol names, the first part always says what happens if a higher priority transaction wants the log of a lower priority transaction. The second part says what happens if a lower priority wants a log from a higher priority transaction. And we assume that the timestamps that those priorities are based upon are unique. All right. So, which means that if you compare two transactions, then one of them will be higher priority, the other one will be lower priority. So there's only two possible comparisons. All right. So with the wound wait protocol, it only has one wait in the name. That means that transactions can only wait in one order of priority, so to speak. We have the wait as the second component, so only lower priority transactions can wait for higher priority transactions, but not the other way around. All right. And if we now assume that we had a cycle in the waits for graph, each edge means that one transaction is waiting for the other one. So you always must have a lower priority transaction connected and waiting for a higher priority transaction. So if you have a path in the waits for graph with the wound wait protocol, it means that the first transaction in that path has a strictly lower priority than the last transaction on that path. And that means if you have a cycle closing the path, then there must be a transaction that has a lower priority than itself. And that cannot be. This is why you cannot get any deadlocks when applying the wound wait protocol. The reasoning for the wait die protocol is similar. Here it's the inverse. We also have only one wait action, and this appears as the first component. That means that higher priority transactions can wait for lower priority transactions. And that means again that if you have a path from one transaction to another one in the waits for graph, then the first transaction on that path must have a strictly higher priority than the last transaction on that path. Now we are closing the path into a cycle. That means that there must be a transaction which has a higher priority than itself, and that obviously cannot be again. So we have shown again that we cannot have a cycle in the waits for graph with the wait die protocol. So those are those deadlock avoidance strategies which allow you to skip tracing the waits for graph, because you know that if you apply those protocols, you're safe from deadlocks. All right. So if we compare those two different protocols, wound wait and wait die, it again depends a lot on the scenario, which of them works best. Advantages that are often cited for the wait die protocol, for instance, include that a transaction which has all the logs that it needs in order to proceed with execution, it will never get aborted. You don't have any wound operations where another transaction gets aborted because the first transaction wants to acquire a log. A disadvantage of wait die is that you might have young, low priority transactions that try to acquire the same logs multiple times once they get restarted, and they get aborted multiple times for the same reasons, which is inefficient. But again, which of those protocols works best, that really depends on the particularities of the scenario. One little detail you have to consider when implementing this: you want to avoid starvation. So you want to enable each transaction to eventually proceed, which might mean that we restart it after it was aborted. Both of those deadlock avoidance protocols have the property that the higher priority transactions, they are never aborted and restarted. So in order to make sure that a transaction eventually processes, we have to make sure that it gets a higher and higher priority as time progresses. So if we restart a transaction, we don't want to give it a new younger timestamp because that would mean it has lower priority. Instead, we want to restart it with the same timestamp that it had when it originally entered the system. So it means that over time, the priority of a transaction will grow and eventually it must get processed. And there's a question on the wound weight protocol. How can T2 abort if T1 has higher priority? To me, that implies that T2 already began, so it automatically has an older timestamp. So the point in time at which transactions are requesting locks might not necessarily be aligned with the time at which those transactions start. If transactions acquire all their locks at the very beginning of transaction start, then we have conservative two-phase locking, and in that case, deadlocks cannot occur from the beginning. So here we have a non-conservative two-phase locking. So transactions might, even if one transaction starts after another one, it might still be the first one to acquire the lock on one specific object because they don't need to acquire all their locks at the beginning of transaction execution. All right. So this is deadlock avoidance protocols. And in general, you have always those two possibilities. Either you detect deadlocks and react, or you avoid them by using one of those protocols. Now, next, we're going to discuss about an anomaly that I had quickly mentioned at the beginning, which are those so-called phantoms. A phantom arises, for instance, in the following example. So let's say that a transaction selects all the students with a name starting with F. Now, transaction 2 inserts a new student called Frank. And after that, transaction 1 again selects all the students starting with F. Now, from the perspective of that first transaction, it suddenly sees a new student named Frank appearing in the result set. So this is kind of a variant of the unrepeatable read, just that in this case, it connects to an insertion. The phantom is characterized by the fact that somebody inserted a new object in the database and it suddenly appears if you run a query with the same predicates twice. All right. Now, if you use naive two-phase locking, then you are not safe from that problem because two-phase locking a priori only locks the objects that are currently in the database. So if somebody had tried to change one of the existing students that start with F, then two-phase locking would have prevented that from happening. On the other side, it didn't prevent us from inserting a new student into the database because the lock for that object did not exist when we acquired the locks at the first query of the first transaction. Now, what we want to do here is essentially to lock all the tuples, all the students in the database that satisfy a certain predicate. Here, the predicate is name starts with F. So we don't only want to lock all the rows with that property which are currently in the database. Instead, we want to also lock all future entries with that property. So we essentially proactively want to log entries which have that property, name starting with F, but are currently not yet in the database. That is generally called predicate locking, because we don't log a specific object, but we log everything that satisfies a certain predicate. Predicate locking can be extremely complex depending on which class of predicates you are considering. Considering arbitrary predicates that can get extremely expensive, almost impossible to implement. So typically people focus on a reasonably simple cases. Now, one common case is that we focus, for instance, on equality or on range predicates, name starting with F. That would essentially be an example of a range predicate. And in those cases, if we have an index on the corresponding table, with the students, for instance, if we had an index with the student name as an index, a search key, then we know that after each insertion, we need to update the index as well. So an efficient way in which people often realize predicate locking is by not directly locking a table, but rather locking an index which refers to the table and has the right index search key. So if we identify for the index leaf page, for instance, on which students with F would have to be inserted. If we lock that page, it is as good as if we had locked the original data, because the second transaction cannot proceed with inserting students with F unless it also is able to acquire the lock of the associated index. And if the first transaction holds the lock on that index, it implicitly means that a second transaction cannot proceed inserting students with F because it has to wait until the associated lock on the index becomes available again. That is a great question. The question is, at which point in time does predicate locking actually acquire the locks? And if we use an index for predicate locking, then we would acquire the lock on the index as soon as transaction number one checks for students with with names starting with F for the first time. So essentially, if we have predicate locking, then we prevent insertions from happening. So we will not insert the corresponding objects into the database at all. And one common way is to do this with indexing, and then you acquire a lock on the corresponding index pages. Now, in order to realize predicate locking, we can use indexes. More generally, we often have indexes associated with tables. And the question is, how do we treat indexes in the locking protocol? So in the following, we're going to discuss about efficient locking for indexes, which helps us when implementing predicate locking with indexes, but which also helps us in general in order to process data faster, which has some indexes created over it. All right. So first of all, a little question. So in the end, an index, it's just a collection of data pages. And we have seen two-phase locking, which works for data in general. So in principle, we could use two-phase locking as usual and apply it in order to lock different data, different pages in my indexes. The question is, why is doing that not efficient? Can anyone write into the chat the reason why you do not want to use generic two-phase locking on index data structures? If you think about the specific access patterns for indexes, is there anything that comes to mind? Yes, exactly. So the high level point here is that if we use generic two-phase locking in order to lock pages of an index, then things become more sequential. Indexes, they're used frequently, and even more, even worse. If you think about the different pages in an index that are used, every single index search starts with the root node of the index. So the root page of the index will receive a lot of traffic. And essentially, if we give to some transaction a lock on the root node of the index and allow that transaction to hold this lock until the very end of transaction execution, then none of the other transactions can get any locks on the same index. And if they are trying to update the table that the index refers to, it means that none of the other transactions can make progress. So the problem is really that we need to, that all the transactions need to pass through the same index page when starting their searches. And here one question is about which pages in an index transactions lock in the first place. And when doing it naively, then the transactions would need to lock all the index pages from the root node to one of the leaf pages, because if you make a change in one of the leaf nodes, there's always a chance that it propagates up the different levels of the tree until the root node. We have seen a couple of examples for index updates in the indexing lecture, and in some of those examples, we had updates, insertions or deletions in one of the index leaf nodes that propagated up to the very root of the index tree. And that is why, in principle, when doing it naively, then transactions would need to acquire locks on the entire path from the root to one of the leaf nodes, and that is very inefficient, but a great question. Okay, good. Now, in order to lock indexes more efficiently, we can exploit a couple of particularities of indexes. So first of all, we traverse indexes only in one direction. So at least as long as we're only searching, we're starting from the root, then we always step to one of the leaf nodes or one of the child nodes until we finally reach one of the leaf nodes. So since we know that all the transactions traverse the index from top to bottom, it means that in principle, in order to block other transactions from acquiring locks in the same subtree that you are currently working in as a transaction, it is enough to just hold one lock on your current node, and that will block all the other transactions from passing you over and entering the subtree that you are currently interested in. So this insight is extremely important because it essentially means that we can, specifically for indexes, sometimes release locks early, and that allows other transactions to proceed in parallel. The technique is called crabbing because it is supposed to resemble a little bit the movements of a crab. And what you do essentially is that you at each step identify the next child node in the index that is relevant, starting with the root node as usual. Then you lock the next child node. After you have the lock, you unlock the parent, and then you repeat until you have reached one of the leaf nodes. So that is the method that we will use for index lookups, which do not change the tree. They only need to read it. Let's quickly illustrate how that looks. So here, those blue nodes represent the part of an index tree. And here we start from the root here. We lock the root node, and then we check which of the child nodes is most relevant. So here I'm only drawing part of the index, so that's why you only see one leaf node. We are locking that one, and after we have the lock, now we release the lock on the parent. And now we do the same thing. We identify the relevant child node, we lock it. After we have the lock, we release the lock on the parent node. That is scrapping. All right. So this works as long as we are only looking up things with the index. But what about index updates? I have already just mentioned that in the extreme case, some of those updates could propagate from one of the leaf nodes up to the very top of the index tree. At least we can guarantee in certain cases that an update cannot propagate beyond the current node. This is what we call a safe node in the index. For instance, for insertions, if I insert things into one of the leaf pages and it becomes overly full, then I would have to split the leaf page. And because I'm splitting the leaf page, it means I need to insert one more entry into the parent, and potentially the parent also becomes overly full. I need to split that one, which means I might have to add one more entry into the parents of the parents, and that might split them as well, and so on and so forth. Now, a precondition for one of those splits propagating up the tree is that I have too many entries in one of those nodes. So if in going down from the root to one of the leaf nodes, I suddenly encounter a node in the index that is not entirely full, then I know that even if I have a split below that node, that split will not propagate beyond the current node because it has still some slots available, so it will not run out of space. So that would be a safe node in case of insertions. In case of deletions, it's the other way around. Here in deletions, I am deleting an entry on a leaf page, it becomes underfull. That's why I need to merge it with one of its siblings. And because I'm merging the two, now I also need to delete one entry in the parent, which might mean that the parent also becomes underfull, so I have to merge the parent again, and so on. In case of deletions, I know that one of those merge operations cannot propagate beyond above the current node if the current node has a little bit more entries than necessary. So I know that even if I delete one of them, it cannot lead to a merge for the current node. So one first strategy is that at least I take this into account. Instead of holding all the locks from the root to one of the leaf nodes, when going down, I quickly release locks above from safe nodes. So if I know that the current node is safe and updates cannot propagate beyond it, then I can release the nodes on its, the locks on its ancestors. All right. So that I can do. Now the question is which type of lock I want to acquire. Now, when being very pessimistic, I would have to assume that updates always propagate up to the current safe node. And that means that I probably want write locks up to the current safe node. Now, write locks, aka exclusive locks, they will prevent other transactions even from reading the associated data. So they are bad for concurrency performance. So what I could also do is that I'm being optimistic and I assume that updates do not propagate up to the current safe nodes. That means that essentially I'm only acquiring a write lock on the leaf page, and I'm betting that no updates propagate beyond the leaf node. Now, if I win that bet, it means that I get better performance than I would have gotten with the pessimistic approach. If I lose the bet, it means that I might have to abort and restart, and this time I'm more pessimistically acquiring all the locks. So again, here, you cannot say which one is better. It always depends on the particularities of the scenario. All right, so that was index locking. We will not be able to discuss multi-granularity locking in all detail. Just already as a little teaser, I want to tell you that multi-granularity locking essentially allows us to define locks at different granularities. For instance, we could have logs on entire tables together with logs on specific rows in specific tables. And the next time we're going to discuss about how we can make sure that we grant those multi-granularity logs in a consistent manner. And all right. And if we have multiple, there's a question in the chat. If we have multiple lookups and all of them only want to read the data, then indeed you only need, you can allow multiple transactions to read in parallel as long as none of them is changing the entries. And there's also a question about why we actually need read logs if we don't want to change or if we don't expect that we need to change nodes above the current leaf node. The thing is that even if we don't want to change the data in those nodes, we have to make sure that none of the concurrent transactions is changing those nodes above the node that we are currently working on, because those nodes, they contain the references to the leaf node that we are currently working on, for instance. And if somebody suddenly changes those other nodes, then I might end up with inconsistent data. So getting those read logs is just about preventing other transactions from proceeding in parallel. All right, good. So we are at the end of the time slot. I wish you a nice day, and then I see you again later this week. We will also have our third homework coming out tomorrow, and that homework focuses on joint processing. So this might be a good opportunity to review again the corresponding material in case you haven't done so already. Have a nice day, and then see you later this week. Okay, awesome. Good. All right. So today we are going to discuss more about concurrency control. The last time we have been discussing about a couple of specialized topics around locking. We have discussed, for instance, about deadlocks. So here we had discussed about how to detect them or how to avoid them. Then we have discussed about phantoms, which is this additional anomaly where I am retrieving a set of objects from the database based on predicates. And when running the query twice, then I get suddenly different results because other transactions inserted something. We have discussed how we can avoid that using indexes. And we have discussed about locking in tree indexes, where you can use the generic locking protocols, but that is inefficient. So instead, you want to use a specialized locking protocol. And we have seen how we can minimize the number of locks that we need to hold at the same time when accessing an index. Now, the final topic around locking that we will be discussing, this is multi-granularity locking. After that, we're going to switch to discuss about concurrency control methods that are not based on locking. First of all, let's discuss about multi-granularity locks. And the motivation for multi-granularity lock is that there is a trade-off about the granularity of locks. At the very, very beginning, when we started discussing about locking-based concurrency control, we had an example protocol that was very simple, and it just locked the entire database. So only one transaction was able to operate at the same time. Later, we have discussed that granting more fine-grained locks on single tables or in single rows in single tables provides you with a higher number of transactions that can execute at the same time. So it's probably good for performance. The drawback of that, on the other side, is that if you have very fine-grained locks, then transactions typically need to a lot of those fine-grained logs in order to do what they want to do. And each log request and log management also means a certain overhead in the log manager. And if the log manager has to manage lots of very small logs on many objects in the database, then that might actually become a performance bottleneck. So there is some motivation for granting fine-grained logs. There's also some motivation for granting more coarse-grained logs. And it is difficult to say which of those works best in general. So with multi-granularity logging, we don't have to make that choice because we can dynamically choose between obtaining logs at different granularity. So if a transaction wants to read most of the rows in a table, it may just get one log on the entire table. But if a transaction only wants to access one specific row in a large table, in that case, we can get a log specifically for that row. And multi-granularity logging allows you both types of logs. The big challenge here is to make sure that we grant those logs consistently. So if one transaction has obtained a log on the entire table, we cannot give out any logs for specific rows anymore, which conflict with the first log. And making sure that we grant those log requests in a consistent manner, that is the focus of what we discuss in the following. So in general, we assume that we have a hierarchy of database objects. So here there would be at the root of that hierarchy the entire database, and then it splits up into single tables, and for each table it splits up into pages, and each page splits up into different tuples again. So that is the hierarchy of database objects. And with multi-granularity logging, we can obtain logs at different layers of this hierarchy. Now, the way in which we make sure that we don't grant any conflicting logs is by introducing new types of logs. Those are those intention logs. We have two types. We have the intention shared log and we have the intention exclusive log. And what that means essentially, if you acquire an intention shared log on some object in that object hierarchy that we have just seen, it essentially means that you intend to acquire a shared log on one of the contained objects. So if you have an intention shared log on a table, it could, for instance, mean that you intend to acquire a shared log on one of the pages in that table, or on one of the tuples on one page of that table. And similarly, for the intention exclusive logs, if you acquire an intention exclusive log on a table, for instance, it means that you intend to acquire an exclusive, meaning a write log for instance, some tuple or for instance, some page within that table. And we will see in the following why using those logs prevents bad things from happening when granting logs at multiple granularities. Now, this is an overview of which of those logs are compatible. We have started out with only two types of logs, the shared logs, meaning logs for reading data, and exclusive logs, meaning logs for writing data. For shared logs, we can grant the same shared log on the same object to multiple transactions. For exclusive logs, that is not possible. Now we've introduced two more types of logs, so it gets a little bit more complex to keep track of which combinations of logs are allowed and which combinations are not allowed. Here you see the full overview. I guess many of those combinations are intuitive, so you always see the green check mark if the combination of logs is allowed, meaning if the log manager could grant those two different logs to different transactions on the same object. Now, for instance, clearly we can grant the same shared log on the same object to different transactions. That's why we have a tick at the corresponding position. One question that I often get about this matrix is, for instance, why is it that intention shared and intention exclusive logs should be compatible? Because as we know, shared logs and exclusive logs are not compatible. So why is this version of the logs more permissive? And so let's perhaps quickly discuss that point. So for intention exclusive logs, it essentially means that you want to acquire an exclusive log on some contained object. So if you get this on a table, it means you might want to get an exclusive log on a row. On the other side, the intention shared log means that you want to acquire a shared log on a contained object. So that could be also a row. But the point is that if you grant an intention shared log on one table to a first transaction and an intention exclusive log to a transaction on a table to a second transaction, at this point, things could still go well because maybe the first transaction is interested in a different row than the second transaction. So we don't know at this point whether two transactions are really interested in the same contained objects or in different ones. And as long as they're interested in different contained objects, like different rows contained in a table, everything is fine. All right. And the general rules to use those intention logs is before you can request a shared log on an object, you first must have obtained intentioned shared logs on all the ancestors of that object in the object hierarchy. So if you want to acquire a shared log on a row in the table, you first must acquire intention shared logs on the containing page, on the containing table, and potentially on the containing database. Similarly, for intention exclusive logs, if you want to acquire an exclusive log on a row, for instance, you first need to acquire intention exclusive logs on the containing page, table, and so on. All right, so you need to acquire those intention logs before you can acquire logs that you actually want. One little detail about the point where you release those logs again, it is important that you release those intention logs not starting from the root of the object hierarchy, but rather starting from the leaves of that object hierarchy and release them in this order. Otherwise, there's a small time frame in which inconsistent logs could be granted if you release those logs the other way around. And now let's make it a little bit more concrete why those intention logs can help. For instance, imagine this situation here. Transaction number 1 drawn in green wants a shared log on table 1. On the other side, transaction 2, here drawn in pink, wants an exclusive log on one specific page in that table. And clearly, those two logs are mutually exclusive. So if we use the system with the intention logs, then here you see the intention logs that would be acquired. So here at the beginning, both transactions acquire intention logs on the entire database, one intention shared and one intention exclusive. But those two logs are compatible because at this point, we don't know whether those transactions are maybe interested in completely different objects that have nothing to do with each other, except that they're both located in the same database. Now we continue to table 1, and for table 1, transaction 2 wants an intention exclusive log, while transaction 1 has already arrived at its goal and wants to acquire the shared log directly. And at this point, the intention exclusive conflicts with the shared log. This is why the situation that we grant inconsistent logs to those transactions cannot happen because we're using intention logs. I believe there might be some questions in the chat. Let me quickly check that out. And those intent, okay, this is a great question. The question is essentially about like how long we hold those intention logs. And the thing is that, I mean, for instance, in this example here, if let's say that the or let's say that the second transaction goes first and maybe succeeds in obtaining the exclusive log for the page that it is interested in, and now it would decide to release those intention exclusive logs on the answer stores. Now, at that point, a transaction number 1, drawn in green, might actually proceed and acquire the intention shared log on the database and the shared log on the table. But that would be inconsistent with the log that transaction 2 has acquired. So it is very important that we do not release those logs on the answer stores, because otherwise we might grant inconsistent logs. Great question. All right. Now let me quickly change my set of slides. If there's any follow-up questions or any other questions, then please don't hesitate to put them into the chat. And there was one more question about like the benefits of intention shared and intention exclusive logs. Perhaps we can even quickly go back to that one, to this example over here. All right, so now you should see the example again. And here, essentially, if you would not use any intention shared or intention exclusive logs, then the database might grant inconsistent logs at different layers of that hierarchy. Here, for instance, transaction 2 wants an exclusive log on one specific page, which is contained in table 1. And transaction 1 wants a shared log on table 1. And logically, if some transaction has a shared log on the entire table, it implicitly means that it has a shared log on each page in that table. So that would be inconsistent with granting an exclusive log to transaction 2. And I mean, an alternative to intention logs would be, for instance, that transaction 1, before acquiring the shared log on table 1, first checks all the pages and all the tuples of the table in order to see whether maybe some other transaction has acquired a conflicting log on some element within the table. But doing that, of course, is very inefficient. So the whole reason for multi-granularity logging is that we want to improve efficiency. Because of that, it is much better if the second transaction marks up not only the specific object, the specific node in the object hierarchy that it is interested in, but also all the ancestor nodes on the path from the root to the logged node in order to indicate that there is some object within the table and within the database where we have an exclusive log. So marking up the path from the root to those objects in the object hierarchy is a means of avoiding checking overheads when granting logs to coming transactions. So there would be different ways of solving that, but via those intention logs, it's pretty efficient. So, so far we have been discussing a lot about locking-based concurrency control. Now in the following, we're gonna discuss about alternative methods to do a concurrency control without locking. Now, it may seem a little bit imbalanced, the amount of time that we dedicate to talking about locking-based concurrency control and the amount of time that we'll be talking about all other concurrency control methods. But in practice, locking is perhaps the most popular concurrency control method. This is why we spend more time discussing about that. But there is various alternatives, and in the following, we're gonna see a little overview of those alternatives. So within this course overview slide, we are still talking about the transaction manager, and the relevant chapter in Ramakrishnan and Gehrke is specifically chapter 19.5 for those concurrency control methods which are not based on locking. Now in the following, we're gonna discuss about those 4 concurrency control methods: optimistic concurrency control, timestamp concurrency control, multi-version concurrency control, and snapshot isolation. And many of those concurrency control protocols, they have some common ideas to them. For instance, many of them, they use timestamps in one way or in another one, but in general, they are different. And you might find that for specific databases and workloads, one of those works better than the others. And it is difficult to say a priori which one it is. Now, first of all, let's talk a bit about optimistic concurrency control. Now, in a way, locking-based concurrency control is rather pessimistic, because before doing anything, transactions always have to acquire those locks in order to avoid any conflicts before they actually happen. Now, that means that we have to pay with overheads for lock management, and depending on the locking variant, we might also have things such as stat locks, for instance. So we are avoiding conflicts between transactions, but it comes at a cost. And so in a way, it is a pessimistic strategy that assumes that those conflicts between transactions are somewhat likely. So transactions will probably sooner or later try to write to the same object, or one transaction tries to read an object written by another transaction. Now, the premise of optimistic concurrency control is kind of the opposite. It's saying that those conflicts, they are rather unlikely. So let's maybe just proceed and do things and just assume that nothing bad will happen. And then at the very end, we will verify whether our assumption was actually justified. If it was not justified, we have to pay the overhead of, for instance, aborting and restarting the current transaction. So with optimistic concurrency control, we essentially trade locking overheads for potentially higher overheads due to aborts. We will discuss about the pros and cons in a little bit. So let's first get some overview of how optimistic concurrency control can work. In order to make it work, we first of all need to do some bookkeeping. For each transaction, we need to keep track of the objects that the transaction has read and the objects that the transaction has written. This is what we call the read set and the write set in the following. And based on those read and write set, we can validate whether any bad conflicts happened or not. Now, in more detail, the execution of a transaction consists of 3 phases. First, the read phase, then the validation phase, and finally, the write phase. What happens in the read phase is this. The transaction, first of all, identifies the objects that it is interested in the database. And then it essentially copies those objects into some private transaction-specific memory location. So it gets its private copy of the relevant objects in the database. And then it also executes the entire transaction on this private copy of the relevant data. There is sometimes confusion about this phase in my experience because the official name of that phase is a little bit misleading because it's the read phase, while in reality we're not only reading data, but we are also kind of executing the transaction on the private copy of the database. So read phase, that is the official name, that is why I'm using it here, but I noticed that people tend to get confused about it. This is why I want to proactively avoid that confusion. So read phase means reading the data, but also executing the transaction on a private copy. Now, before we can actually publish the things that have changed in the private copy of the data, we first have to validate in order to ensure that no conflicts have happened. During the validation phase, I'm essentially checking whether any other transactions have accessed the same objects that the first transaction being validated was working on. And if those changes to those other objects or those accesses to those other objects conflict with what my current transaction has done, then I actually have to abort and later restart the current transaction. So this is where optimistic concurrency control is optimistic, because it assumes that in almost all cases, this validation will check out okay, and there haven't been any conflicts in the meantime. Now, if the validation succeeds, then we proceed to the final phase, which is the write phase. And here we essentially publishing the changes from the private transaction-specific copy of the relevant data to the public overall database. So we are writing those private copy changes to the public database where other transactions can see it as well. Now that is the high-level overview of how optimistic concurrency control works. Let's discuss about the validation phase in a little bit more detail, because that is the key to concurrency control. It generally works by assigning unique timestamps to transactions at validation time. So essentially our goal is to create like a serialization order of the transactions that is consistent with those timestamps. So in the end, the database should look as if those transactions had executed in timestamp order. And also what other transactions see, which transactions sees the changes from which other transactions, that also should be consistent with those timestamps. During the validation, we essentially check a sufficient condition in order to make sure that no bad conflicts between transactions have appeared. Now, we can be sure that there was no bad conflict between two transactions. For instance, if the first transaction has entirely completed before the second transaction. Now, in that case, clearly, there cannot have been any conflict. Also, we might refine that and say, we also can be sure that there is no bad conflict if the first transaction completes before the second transaction starts writing. Also, in this case, what could happen is that the first transaction writes values to objects that are read by the second transaction. So here, there could be some kind of bad influence linking the two transactions, but we can be sure that this does not happen if the write set of the first transaction, the objects that the transaction has written to and changed, is disjunct with the set of objects that the second transaction has read. So if that holds, then we can be sure that the first transaction hasn't influenced the second transaction. So here, both of them cannot have conflicted in a bad way. And as an extension of that, perhaps the first transaction completes before the first transaction completes its read phase, before the second transaction completes its read phase. That means that we could, for instance, have overlapping writes in addition to the first transaction writing objects read by the second transaction. So as an extension, we also want to ensure that the write set of the first transaction, the objects it has changed, is disjunct from the write set of the second transaction. In that case, they cannot override each other's changes in a bad way. And we can also be sure that no bad conflicts have happened. So those three conditions is what we can verify in the validation phase. And if one of them holds, then we can be sure that there have been no conflicts. Those conditions, they are perhaps overly conservative in some cases. None of those conditions might be satisfied, but still everything would be okay. In those cases, well, there's some trade-off between bookkeeping and between the probability that we have to abort the transaction, even if there's no real reason for it. So typically, this provides a nice trade-off between those conflicting motivations. All right, but just so you know, even if none of those conditions is satisfied, you might still actually have a good case without bad conflicts, but nevertheless here we would abort a transaction in this case. So at the validation phase, we are verifying that with all the other transactions currently in the system, at least one of those three conditions is satisfied, and if so, we can allow the currently validated transaction to proceed to the write phase. One simplification that people often make in implementations in practice is that we combine the validation and write phase essentially into one single phase. Then we need to make sure that only one transaction can be in this combined validation and write phase at the same time. So while one transaction validates and writes, other transactions are blocked from access to the public database. If you do that, the conditions simplify. You only need to consider the first two of them. This is a simplification often encountered in practice. All right. Of course, there is some overheads. I'm saving the overheads for locking, but now I need to keep track of the read set and the write set. And of course, if my validation phase does not check out, then I have to restart, to first abort and then restart the current transaction. And if conflicts are quite frequent, that is a high source of overhead. Also, depending on implementation, there might be a critical section where I reduce concurrency because only one transaction can operate at the same time if it is in this combined validation and write phase, for instance. So there's pros and cons. Probably you want to use optimistic concurrency control in scenarios where conflicts are rather infrequent. Another non-locking based concurrency control is a timestamp based locking. So here we associate again each transaction in the system with a timestamp, and our goal is to serialize those transactions in the order of those timestamps. So the database should look as if those transactions had executed in the order of those timestamps. Now, we not only associate transactions with timestamps, we also associate objects in the database with timestamps. Each object is associated with a read timestamp, which essentially is the timestamp of the last read operation on it, and with a write timestamp, which is the timestamp of the last write operation on it. So essentially, those read and write timestamps for objects are set based on the timestamps of those transactions. So if a transaction with a certain timestamp reads an object, then the read timestamp of the object is updated to the timestamp of the transaction, because logically, essentially, each transaction executed instantaneously at its assigned timestamp. And this is why we update read and write timestamps from the transaction timestamps. Now, we have to essentially check a couple of conditions whenever a transaction wants to read and write objects in the database. Those conditions essentially tell us whether if we proceed with an operation, whether we are still consistent with the timestamp order of the transactions. Now, here I outline those rules that we have to verify, and if a transaction tries to do an operation that would violate one of those rules, then this transaction is aborted and restarted later. So here we use TS of t as the timestamp of a transaction, and RTS of A and WTS of A. Those are read and write timestamps of the object A. And now if a transaction wants to read some database object A, we have to abort and restart the transaction if its timestamp is smaller than the write timestamp of the object that it is trying to read. Logically, this makes sense because of the following. So if a transaction has a certain timestamp, it means that everything should be as if the transaction had executed at that time. And if the transaction had really executed at a specific time, then the version of an object that it reads must have been written by a transaction that executed before. Now, in this case, we see that the object A has been updated by a transaction with a higher timestamp than the transaction that is trying to read. That means if we would allow the transaction to proceed and to read the current value of A, we would be inconsistent with the timestamp order because the transaction should have read an earlier value of object A written by a transaction with a smaller timestamp. And because of that, if we have this condition here, it means that we have to abort the transaction trying to do the read and restart it with a higher timestamp. All right. Now, on the other side, what happens if a transaction tries to write an object in the database? So logically, if a transaction executes at a certain time and writes a value for an object A, then all transactions that are executing later than the current transaction should read the value written by the current transaction, because then logically it is as if everything had executed in transaction timestamp order. Now, if we see that the timestamp of the transaction trying to do the write is actually smaller than the read timestamp of that object we are trying to write to, it means that another transaction with a higher timestamp has already read the current value of object A. And that means that allowing the transaction to proceed with the write operation would mean that we are becoming inconsistent with the timestamp order, because had the transaction really executed at time t, it would have written the value read by the later transaction, but that has not happened. All right. So one interesting case that we might also think about is what about multiple writes on the same object? And for instance, we could think about aborting and restarting a transaction if the transaction timestamp is smaller than the current write timestamp of that object. So because logically, if transactions had really executed in a timestamp order, then the final write to object A would have been executed by the later transaction. But here we are essentially trying to override the later value with an earlier value. So a naive way of doing this is to just say, okay, in those cases, we abort and restart the transaction. Okay, and actually, before I continue, okay, there's one question here in the chat. Wouldn't aborting T and restarting still give you the same problem? Okay, that is a great question. And actually, it depends on the timestamp that you restart the transaction with. So what we are doing is, if our current timestamp ordering does not succeed, if we would try to restart the transaction with the original timestamp, we would run into the same problem again. So that's a great point. But what we are doing instead is that we are restarting the transaction now with a higher timestamp. And this is why things change. So in theory, even with the higher timestamp, we might again have to abort and restart the transaction a couple of times, but at least now we have the chance with the higher timestamp that the thing which led to the abort before won't happen again. Great question. And here, okay, that is the question about the case at the bottom of the slide here. So I already said that one possibility to deal with this case would be to abort and restart the transaction. But since I marked this up and formulated it so tentatively, you can imagine that there might be a different way of doing things, and that is the so-called Thomas Wright rule. This rule applies in the case that we have just seen, where the timestamp of the transaction trying to do a write is smaller than the current write timestamp of that object, which conflicts with serialization order. So clearly we cannot allow the transaction to proceed with the write. But on the other side, we don't really have to abort the transaction either, because we can just say this transaction would have written some value to object A. Analyzing the read timestamp, we can see that the value of object A written by the transaction would never have been read. So essentially, we can just act as if that write operation had never happened. So we don't necessarily have to abort the transaction trying to do the write. And that is what the Thomas Wright rule essentially states. It states that we can ignore outdated writes and don't even need to abort the transaction causing it. So essentially, what it does, if you consider it from the perspective of the schedules that it allows, if you look, for instance, at this first schedule here marked up in red, I have a read of object A by transaction 1, followed by a write by transaction 2 on the same object, then transaction 2 commits, and now I have still a write of transaction 1 on object A. Now, so first of all, this schedule is not conflict serializable, because here, if you see, we have a conflict on object A between transaction 1 and 2. So the corresponding graphic would have an edge from transaction 1 to transaction 2 due to the read followed by the write. And also we would have an edge from transaction 2 to transaction 1 because of the write followed by the final write by transaction 1. So we have a cycle, and that means this schedule is non-conflict serializable. But on the other side, it would be view serializable, because here the final value of object A is written by transaction 1, and transaction 1 also reads the original value of object A. So this write by transaction 2 to object A is kind of pointless. It is not read by anyone, and it is changed again later by the first transaction. So actually, we could kind of act as if that write to object A had never happened. And at the bottom, you see the corresponding schedule. So here we just remove this write operation, which doesn't really have any effect whatsoever. And here we end up with a schedule that is serial. So actually, we could move the commit by transaction 2 even before to make that more clear. But clearly, transaction 2 doesn't have any operations anymore. Here, you only have a read by transaction 1 followed by a write of transaction 1. And those two schedules, they are view equivalent. And the Thomas Wright rule essentially allows us to capture such cases to avoid aborts and restarts in cases where writes don't really matter. So that is an optimization to the simple handling strategy that we have discussed before. But what if W2A affected different rows in A than W1 of A? And the thing, I think there's a misunderstanding about like, basically, which types of objects we are granting those locks for. So that's a great question. So here we essentially assume that those objects A, they refer to things like, that could, for instance, refer to one single row. So here we are not considering multi-granularity locking. We're only considering atomic objects in our database, which typically are rows. So here, A, that could, for instance, be the row in your accounts table, which represents the account of one specific customer, of Alice, for instance, right? So we don't consider multi-granularity locking. So if we have two operations on the same object A, it means that they refer to exactly the same object in the database. All right, good. So for timestamp concurrency control, we also have a couple of overheads. Like for the optimistic concurrency control, we also might have overheads due to restarting and aborting transactions in case of conflicts. Also, here we need to keep track of object timestamps. We need to keep track of the read and the write timestamp for all objects in my database. And depending on the granularity, if you're talking, for instance, about a single rows, which is typical, then having to store some values to timestamps for each of those rows, that could actually mean a little bit of space overhead. Also, there is the overhead of updating those object timestamps, because for everything to work correctly, we need to keep track of those timestamps. Might have to recover them, for instance, during a recovery operation, which we will discuss quite soon. And also, if you're just reading an object, if a transaction is just reading an object, then still we have an associated write operation because we need to update the corresponding timestamp. And that means that we have quite a bit of additional overheads, especially because of the last point, because now every object access essentially transforms into a write operation. And better using this is a good idea in practice. It depends again on various factors, but those overheads, they make it a little bit less attractive than some of the other concurrency control methods. All right, so we might not finish completely with multi-version concurrency control anymore, but I already want to give a little intro there. As the name suggests, the main idea of multi-version concurrency control is that we keep around multiple versions of each object in the database. So the protocols that we have seen so far, they would assume one single value for an object in the database. Here we have multiple versions that are associated with different timestamps. And this example here shows why doing that can be a good idea. Here, for instance, we have a schedule which is not conflict serializable in the way in which it is written. So we have an edge in the conflict graph from transaction 1 to transaction 2 because of the write to A followed by the read of A by the second transaction. And we also have an edge from transaction 2 to transaction 1 because of those conflicting writes and reads on object B. And those two are marked up in green and blue in this schedule. Now, we would have a conflict serializable schedule had the read on object B happened before the write to object B. So if those two would be swapped. So in order to essentially get there, what we could do is that when having the read on object B, we just show to the requesting transaction an old version of object B before the write by the second transaction. So keeping around those multiple objects and choosing which version to show to a transaction is essentially a way of avoiding conflicts that are caused by reads, like the one that you see here in the example. And because of that, it might allow us to avoid some conflicts due to those reads. On the other side, of course, here now I have to keep multiple versions of an object around, which is also associated with overheads. All right. So here again, we assign timestamps to the transactions once they enter the system. And the next time we will see in more detail how we check whether transactions can proceed and how we decide which version of an object to show to a reading transaction. So we're going to discuss that in more detail next time, but the main idea here is to keep around multiple versions of an object, and that can help to resolve certain conflicts where other protocols would have to abort the corresponding transaction. All right, thanks, and I see you again next week. Have a great weekend. All right, let's get started. So today we first of all going to discuss a little bit more about concurrency control. And for the past couple of lectures, we have been mostly discussing about concurrency control methods that use locking. And in the last lecture, we have started discussing about concurrency control methods that work without locks. And depending on the scenario, that can have performance advantages because we save the overhead for lock management. The last time we have already discussed two of them. First of all, oops, I cannot advance the slides here. All right. So first of all, we have been discussing about optimistic concurrency control, which essentially assumes that everything goes well and then checks at the very end. And if it is wrong, we have to abort and restart the transaction, but otherwise it is very efficient. Then we have talked about timestamp-based concurrency control, where we essentially associate objects with timestamps indicating when they were read or written for the last time. And those object timestamps are based or are derived from the timestamps of the transactions. We assign them to timestamps at the beginning, and then we try to simulate an execution in that timestamp order. Now, in the following, we're going to discuss about two more concurrency control methods that work without locking. And both of them actually use different object versions. We have quickly discussed this slide last time. I'm going to start here again. And the concurrency control method that we will discuss about is called multi-version concurrency control. And as the name suggests, the main idea is that instead of one version of an object, we might have we will keep multiple versions of an object that are associated with timestamps. And to see why that can be helpful, we have a little example over here. So if you look at the schedule, that is marked here in the third line, we have a non-conflict serializable schedule. There is a conflict between transaction 1 and 2 on the A object at the beginning. So in the conflict graph, you would have an edge from 1 to 2. And later, there is a conflict on B as well. So in the conflict graph, we also have an edge from transaction 2 to transaction 1. And that is why you have a cycle. So it is non-conflict serializable. Now, this would not happen had we read the B object a little bit earlier for the first transaction. So if you imagine that we are moving this read of B by transaction 1, which is marked in blue, a little bit earlier, then we wouldn't have the cycle in the conflict graph. And maintaining multiple versions of object B gives you essentially that possibility, because once transaction 1 is requesting to read an object from B, in that case, we could just serve it the previous version of object B before the write by transaction 2 has happened. And because this is the conflict that is causing the cycle in the conflict graph. If we resolve it, we get a serializable, conflict serializable schedule again, right? So that is the idea behind the multi-version concurrency control. We essentially eliminate conflicts by serving older versions of an object, which of course requires us to keep around those multiple object versions. So this is the high-level outline of the multi-version concurrency control protocol. First of all, each transaction gets a timestamp when entering the system. That's a unique timestamp, and we try to make everything look as if those transactions had executed in the order of those timestamps. Whenever a transaction writes an object, in other concurrency control protocols, it means that the old value is overwritten by the new value. But in this case here, it means that a new write creates a new version of an object. First of all, before the transaction is actually allowed to write something, before we allow that to happen, we perform a check, which I will describe in more detail on the next slide. If the check fails, then the transaction actually has to be aborted. But if the check succeeds, then the transaction proceeds and creates a new version of the object. And the creation timestamp of that version, that is equal to the timestamp of the transaction. Because logically, we want to make everything look as if each transaction had executed precisely, atomically, at its timestamp. And therefore, if that transaction had really created the object, then it should get the timestamp of the transaction. Whenever we have a read, we can exploit the fact that we have multiple versions. So we choose which version we want to show to the transaction. Whenever a transaction that has timestamp I tries to read an object, then we serve the version of the object that has the largest timestamp, which is still smaller than I. And that is logical, because if transactions had really executed at their timestamps, then of course the transaction with timestamp I would see the last written version of the object. And that is just the version with the largest timestamp that is still smaller than the transaction timestamp I. All right. Now, I have mentioned a write check on the last slide, and this is a test that we do whenever a transaction tries to write an object. As always, we have to be consistent with the timestamp order of the transactions. So now let's assume that a transaction with timestamp I wants to write to an object A. Now, logically, if there is another transaction with a higher timestamp than I, then that other transaction, when reading object A, should have read the version written by transaction I, or even a later version. But for sure, it wouldn't have read an earlier version, because at the time I, the transaction which is currently being checked would have written the object with a timestamp of I, right? So here, basically, if we find out that there is currently a transaction with a higher timestamp than I, and that version has already read object A, then we must abort the checked transaction, because if it had written the object at timestamp I, then the later transaction would have read that value or a later one. So if we would allow the transaction to proceed, it creates an inconsistency. All right, so that is the write check, and we perform it whenever a transaction tries to write an object. And in order to perform it, we need to not only keep track of the time at which objects are created, but also we have to keep track of the last read timestamp for an object. All right. So what we have seen so far, it serves to create conflict serializable schedules. We have seen in the last lectures those two hierarchies for schedules. The first one was about serializability. The second one was about abort-related properties. So what we have seen so far for multi-version concurrency control essentially only deals with serializability, but it doesn't give you any abort-related properties. For instance, one important property is that the schedule is recoverable, because we don't commit a transaction before other transactions it has been influenced by have committed before. And the protocol we have seen so far does not yet take care of those properties. In order to get them, you can, however, extend the protocol and, for instance, delay commits until all influencing transactions have committed. So just so you know, if you ever choose to implement it, then you probably want to take care of those properties as well, and that requires some extensions to the protocol. So that was a short overview of a multi-version concurrency control. And now we are going to see a little bit of a different variant of that, which is also very commonly used in practice, and that is called snapshot isolation. Now, snapshot isolation essentially means that whenever a transaction starts, we are conceptually taking a snapshot of the database, which contains for each object the value of the last committed transaction. And then those transactions, they essentially operate on this frozen snapshot. So in a way, here we also keep around multiple versions of the database, but whenever a transaction starts, then it gets this frozen snapshot of the database, which doesn't change over time. With multi-version concurrency control, in principle, while the transaction is executing, the values of different objects could change and new versions could be added. Here, that cannot happen. So when reading data, transactions rely on the snapshot of the database that has been taken once they started executing. When writing to objects, in this case, we have to pay attention if multiple transactions are trying to write to the same object. If so, we could create conflict, so we cannot allow this to happen. So in this case, essentially, after a transaction has executed, we are checking in order to make sure that no other transaction was already writing to objects that the current transaction is trying to write to. If that is the case, then the current transaction can go ahead and commit. But if there has been overlapping writes to the same object by a concurrent transaction, then essentially the first writer wins and the other transaction has to be aborted in order to avoid conflict. Now, this may sound great, but there's a little catch to it. Let's make an example with two tables, A and B, which both have one integer column. And now imagine those two transactions that we see here. The first transaction essentially tries to insert the count of rows in A as a value into B. And the second transaction tries to insert the count of rows from table B as a value into table A. And now we assume that both of those transactions start at the same time, which means that they will operate on the same snapshot of the database. Now, imagine that those transactions execute and insert their values. Does anyone have a suspicion about whether the result of that can be equivalent to a serial execution of those transactions? If you have an opinion, please put it into the chat. All right. And here we have the suggestion that one of the inserted values will be one less than it should be. Okay, very good. All right. Let's analyze that in a little bit more detail. Let me move the chat around. Okay, so if we want to find out whether we get to a result that could have been generated by a serial execution, then maybe first of all, we want to think about all the possibilities for serial execution. So here we have two transactions. So we have a choice about which of them we execute first, and that creates two possibilities. Now, for instance, we could start by executing the first transaction. So the first transaction executes the query which inserts the count in A into table B. And assuming that at the start, those two tables are empty, we would insert a 0 into table B. And now we have one row in table A. So if the second transaction runs, which inserts into table A the count of rows in table B. So since we just inserted a row into table B, it means that we would now insert a 1 instead of a 0 into table A. If we do it the other way around, if we start with transaction 2 would first of all calculate the number of rows in B, which initially is 0, and insert that into A. So this is why in A we have now the 0. Now the first transaction runs and it inserts into table B the count of rows in table A. And since we have just inserted a row into table A, it would mean that we insert a 1 into table B. Now, if we use snapshot isolation, it means that both of those transactions start from the same snapshot of the database. And in this snapshot, both of the tables are empty. And since both of them execute concurrently on the same snapshot, it means that both of them will account 0 rows for both of the tables, and then they will insert the 0 into those two tables, A and B. And that is an anomaly that is called write skew. All right, so this is maybe something that is worth having another look at if that seems strange. But here we have definitely a behavior that couldn't happen if executing transactions one after the other one. Now, write skew is one example for an anomaly that isn't really mentioned in those anomalies that we have seen initially. The anomalies that we have seen initially, they are based on the SQL standard. And the fact that there is some concurrency control protocols which have anomalies that are not really mentioned in the standard has actually led to criticism of the SQL standard. So that is maybe the last thing that I want you to know about concurrency control, that we have seen those different SQL isolation levels, but depending on the system, for some of those isolation levels, you might actually still have some anomalies such as write skew, which are not mentioned in the SQL standard. But if you are running your database system with an important application, they might still lead to problems. So be very careful when using your database system in practice. Make sure that you understand well not only which isolation level you're dealing with, but also how precisely that isolation level is implemented and whether there might still be some anomalies that could appear. All right, so that was concurrency control. We have mostly been talking about locking-based concurrency control, and now we have also talked about a couple of alternatives without locking. In practice, locking-based concurrency control is very common. This is why we have spent more time discussing that. But as you have seen here, there's also many alternatives, and which one of them works best depends on the particularities of the scenario. All right. So we will now switch to a different topic. I'm gonna switch the slide set. If you have any questions about concurrency control currently, please feel free to put them into the chat. All right. Seems no all too urgent question for the moment, so we will directly dive into the next topic, which is about recovery after system crashes. This is the component that we will be talking about. That is the recovery manager marked up here, and the relevant chapter in Ramakrishnan and Gehrke, that is chapter number 20. So we have talked about the guarantees that database systems make when it comes to transaction processing, atomicity, which means no partial executions, consistency, which means that your data remains consistent and satisfies all constraints. We have talked a lot about isolation, which means we simulate different transactions executing serially. And finally, we have durability, which means that we do not lose data that belongs to committed transactions. Now, the recovery component essentially takes care of those two properties. First of all, atomicity, and then durability. So what we essentially want is this. So if we assume that we have multiple transactions executing in our system, and then suddenly a crash happens. And a crash could happen for many reasons. One of the reasons, for instance, is a sudden power outage. But it could also be other things such as a hardware fault or perhaps a software bug that suddenly makes the system crash. But in any case, we are currently executing lots of transactions, and then suddenly something happens and the database server has to shut down. Now, in this graph, basically, we have some transactions that have already executed, by which I mean they have already committed. So we have informed the user, this transaction has executed, you have nothing to worry about, and the effects will be persisted. And because of that, for those transactions that are now marked in green, we want to make sure that the effects of those transactions, they are actually persistent and will be recovered once the system comes back online. On the other side, for the transactions that are running during the crash, for those transactions, we want to abort them, and we want to essentially undo them such that no traces of those transactions remains in the system. This refers back to the atomicity guarantee, right? So this is what we want to achieve once the system comes back online after the crash. This is a little reminder here of the memory hierarchy. And the memory hierarchy makes it difficult to achieve the behavior that I have just shown. Because in the memory hierarchy, we have essentially two parts. We have a volatile memory, which will be erased if there is a sudden power failure, for instance. And we have non-volatile memory, such as hard disk, which will remain, where the content will remain, even during a system crash. Of course, from the safety perspective, we might choose to always write to a non-volatile storage. But of course, that would be very slow because, as the memory hierarchy shows, there's a higher level of the memory hierarchy which are volatile. They are at the same time much faster than the lower levels of the memory hierarchy. And for performance reasons, we therefore must work even with the volatile levels of the memory hierarchy. And that makes it challenging to guarantee that even during a crash, we won't lose any important data or end up with the effects of half-finished transactions in our system. Let's first of all discuss about challenges related to durability, which essentially means we guarantee that the effects of all committed transactions persist even if there is a system crash. Now, initially, once a transaction change data, their changes are written, first of all, to pages in the buffer pool. And as we have seen, the buffer pool, that is the main memory portion that is essentially reserved to the database system. And since it lives in main memory, it means it is volatile. And once the power cuts, all the content of the buffer pool will be lost. Now, one thing we could do, of course, is that every change is not only written into the buffer pool, but we also write it to hard disk. And if we do this immediately, or at least before the corresponding transaction commits, the problem is that we might get pretty bad performance because we have to write a lot of pages on hard disk. And on most of those pages, we actually have only very small changes because those transactions, they typically just change the data maybe in one row of your table, while they leave the other rows in the table unchanged. And that means if you're trying to immediately write those data pages from the buffer pool onto hard disk, then you're writing a lot of bytes where most of them are actually unchanged, but just a few bytes have changed. And for that, you're actually performing a lot of page writes, and that is very inefficient. So here the naive approaches don't work well. So in the following, we're going to see a way to improve over that. First of all, let's discuss about atomicity, which essentially means we guarantee that no transaction is partially executed. And one easy way to guarantee that even during a crash would be just to leave all those changes to the data of a transaction in main memory. So we only change things in the buffer pool, and then we know if there's a crash, then the buffer pool is erased. So automatically all the changes by the uncommitted transactions are erased, which is actually quite convenient. And that would be an easy way of getting atomicity. The problem with this approach is this. Each transaction might change multiple pages. So if you want to avoid that those changes get written to hard disk before the transaction commits, it means that the transaction has to hold on to all of those pages in main memory until it commits. And that means that each concurrently executing transaction might have to hold many pages in main memory at the same time. And that means we cannot execute too many transactions at the same time. And all of those things that we discussed about concurrency control, a lot of it was exactly about allowing as many transactions as possible to execute at the same time in order to increase the throughput of your system, meaning the number of transactions that get finished per time unit. So if you would introduce a constraint that transactions have to reserve many pages in main memory, since the amount of main memory we have is typically limited, it would mean that we limit the number of transactions that can execute at the same time and therefore our throughput, which is something that we want to avoid. So the alternative to that is, of course, that we allow transactions to let go of their pages in main memory, and therefore we have more flexibility about how we use those precious pages in main memory. We essentially allow ourselves to swap those pages in main memory between different transactions. The problem with this is the following. So if a transaction has performed some changes on a data page in main memory, and now we want to assign that page, we want to lend that page to a different transaction, which needs to do something else. So at that point, of course, if we simply erase the current page in main memory, it would mean that we would lose the changes by the transaction, which because of durability, we obviously don't want to do. On the other side, if we choose to keep the changes, and since we don't have that much main memory, we need to write those changes to a different layer in the memory hierarchy. So typically, we would need to write those changes to hard disk. Here the changes are persistent. So if the current transaction successfully executes, then we are okay with writing those changes to hard disk. But if the current transaction suddenly aborts, or if there is a crash so that the current transaction is implicitly aborted, then it means that now suddenly on hard disk, we have the changes by some half finished, by some aborted transaction, and that we don't want to have due to atomicity. So again, there is different naive solutions, but all of them come with a serious drawback. So in the following, we're going to see how we can improve over that. I think there might have been a question in the chat. Let me quickly check. So the question is whether in the alternative we are writing directly to the database data. So I have pointed out multiple alternatives for durability and for atomicity. And indeed, one of them was that we essentially directly write changes to our database data so we directly can write changes to a hard disk, and that has the advantage that they persist even after a system crash, which is good if the transaction is committed. On the other side, if the transaction doesn't finish before the crash and must be aborted, it means that we now have changes on hard disk that belong to a half-finished transaction, and we need to sooner or later undo those changes again. All right. So this here is a summary of the different options that we have and that we have essentially discussed in the previous slides. So we can choose to use a so-called force policy, which means that we make all changes to the data persistent on hard disk before the corresponding transaction commits. The advantage of that is that we are safe from losing data in the case of a system crash. The disadvantage of that is that we have a lot of page writes by each transaction, and that leads to poor response time. The other the other choice that we have is how flexible we are in assigning buffer slots to transactions. A no-steal policy essentially means that each transaction must hold on to its pages in the buffer pool until it commits. The advantage of that is that we don't have to deal with undoing changes on hard disk by aborted transactions. The disadvantage of it is that each transaction will actually consume a lot of main memory pages, which severely limits our transaction throughput. So for performance reasons, what we want is a policy that allows a stealing, which essentially means that one transaction can steal a buffer slot from another transaction before the other transaction is actually committed. So allowing stealing leads to a higher throughput, and having a no force policy, which means we do not force transactions to write all the changes to hard disk, that leads to better response time. So for performance reasons, we want to allow stealing, and we don't want to force writes to hard disk. The problem with that is, of course, what do we do about durability and atomicity guarantees? Now, the high-level solution that we will discuss in the following, that is logging, which essentially means that we don't write the actual data on hard disk, but we write a highly compressed representation just of the deltas, of the changes to the data to hard disk. And this is what we call a log. Now in the following, we're going to discuss in more detail about how logging can help us to resolve those performance challenges that I have discussed on the last slides. Now, if we want to guarantee durability, it generally means that we have to make changes persistent of a transaction before the transaction commits, because durability means that after the transaction commits, it is guaranteed to stay in the system even if there is a crash. And very clearly, since everything in volatile memory is lost during a crash, we must make changes persistent on hard disk before we allow a transaction to commit. We have already discussed the possibility to update the actual data before the commit, which is what we call the force policy. The reason why that is inefficient is that the changes that a transaction needs to make, they're typically distributed over many different data pages. And this means that we would actually have a lot of page writes just for making persistent a lot of small changes in the data. The idea behind logging is that we don't do that, but instead we just collect all those updates to the data in a very compressed representation. So for one transaction, you typically can collect all its updates in compressed representation on one single log data page. And if we want to make that persistent, we can just write the log data to hard disk, typically with one single page write. And that is much more efficient than writing all those different data pages that the transaction has changed. And then we just have to make sure that this logging related data are written to hard disk before the transaction commits. And so even if we haven't changed the actual data, since we have a list of the updates to the data, that is sufficient in order to recover the data if there's a crash once the system comes back online. Now let's see how logging can help us to deal with atomicity. Now, we have already discussed why we want to swap the pages in the buffer pool between different transactions. And once we swap ownership of one slot in the buffer pool from one transaction to another one, we first of all have to preserve the changes of the first transaction. And that means that we need to write the current content of the buffer pool slot to hard disk, because otherwise the changes would be lost, and that is incompatible with the durability requirement. So the thing is this: if we swap pages and we write changes to the current page by the current transaction on hard disk, if the current transaction later aborts, which could, for instance, be because the system crashes, but also because of a different reason, in that case, we need to take care of those changes to the data that we now have already written to hard disk, because we need to undo those changes in order to guarantee that the database looks as if the aborted transaction had never happened. And in order to enable this, we will expand our log with information that allows us to undo each change to the data in case the corresponding transaction aborts. And we just have to make sure that we write those log entries for a specific page to hard disk, which means that if the system crashes immediately after we have written the current page content from the buffer slot to hard disk, then we still have the required information in order to undo the changes by the current transaction in order to bring the data back into a consistent state. So now we have discussed how logging can help with durability and atomicity. The general term for the class of logging algorithms that we will discuss about in the following is write-ahead logging. And write-ahead logging is essentially characterized by the two rules that you see here. First of all, we have to write all the log entries that relate to a transaction before the transaction commits. And the second rule is we have to write all log entries that concern a page in the buffer pool to hard disk before that a page is written to hard disk itself. Rule number one is important to guarantee durability, because if a transaction commits and we have the log entries from that transaction on hard disk, then we can use that in order to redo the changes of the transaction, even if the system immediately crashes after the transaction commit. Rule number two is important for atomicity, because if you write a change data page to hard disk and those changes have been made by a transaction that will later abort, if we have the log entries about that page on hard disk already, then we can undo the changes in order to erase the effects of the aborted transaction. So this is the two rules of a write-ahead logging. And in the following, we're going to see one specific algorithm that uses write-ahead logging. This algorithm is called the Arias algorithm. It is a very classical algorithm. It has been proposed decades ago, but the variants of it are still quite popular in database systems. Now, this algorithm uses a write-ahead logging, and we will see in the following how precisely it implements it. And after we boot the system up again after a crash, this Arias algorithm will perform 3 recovery phases. It first of all will analyze the last log entries that it finds on hard disk in order to decide which transactions need to be undone and for which transactions we need to redo data changes. Then it will have the redo phase in which we redo the changes of committed transactions that were lost due to the crash. And finally, we have the undo phase in which we undo the changes of all transactions that have still been active during the crash and must be aborted. So we're going to see that in much more detail in the following. It is an algorithm that has quite a few moving parts, so we will take some time to discuss the different parts of the algorithm and the different data structures in this lecture and also still in the next lecture. In general, we're going to break it down into 3 phases. First of all, we're going to discuss about the data structures of the algorithm. Then we're going to talk about the behavior that it has at runtime, where it generates log entries that help with recovery later. And finally, we're going to discuss in detail about how recovery proceeds precisely. Now, in the following, we still have a little bit of time to talk about the different data structures of the Arias algorithm. And all of those different data structures, I have them represented here. So here we have some data structures in gray, and those are the data structures that do not directly relate to the Arias algorithm. So here we have, of course, the data pages on a hard disk, and we have the buffer pool pages in main memory. So you see the divider in the middle of the screen. Everything on top of it is stored in main memory, which means it is volatile and will be lost during a crash. Everything below the divider is stored on hard disk. It is non-volatile and will persist after a crash. So here we have data pages on hard disk in gray, and we have buffer pool pages in main memory in gray. Now, the first thing that I want to discuss here is you see those little blue rectangles for the buffer pool and for the data pages. Those are essentially timestamps that tell the Arias algorithm when those pages have changed for the last time. Beyond that, there's a couple of specific data structures of the Arias algorithm here drawn in blue. The following, we're gonna go over all of those different data structures and explain at a high level what they are about. Now, first of all, log entries are first written not to hard disk, but into main memory. We postpone writing them to hard disk for as long as possible. And the log tail is stored in main memory. And those are essentially the most recent log entries which have been generated, but which haven't made it to hard disk yet. So this log tail, those are log entries which are eventually written to hard disk unless there's a crash, because in that case, the log tail is essentially lost. The flushed LSN keeps track essentially of where the log tail starts. So using the flushed LSN, we keep track of which log entries have already been made persistent on hard disk. So this essentially captures the LSN, which stands for the log sequence number, and that is a unique identifier for the line in the log file, essentially. And the flushed LSN, that is essentially the last log line that made it already to hard disk. So in several cases, it is important to verify whether log entries, for instance, about a transaction have already made it to hard disk, because then we can allow that transaction to commit. And the flushed LSN essentially keeps track of which log entries have already been made persistent. Now, the log tail is essentially a buffer, and in the context of buffers, we often use the word flushed in order to say that we essentially write the buffer content to a persistent storage, and then we erase it to make it available again and enable it to receive more data. And this is why we use this terminology here when it comes to the log. So the log tail is a buffer, and every once in a while we flush it, meaning we write its content to hard disk, and flushed LSN keeps track of when that has happened for the last time. Now, here on hard disk, we have the actual log that will be used for recovery. It is stored on persistent storage, so after we come back online after a crash, we will be able to access those entries here. And the recovery phase of the Aries algorithm uses exactly this log in order to bring the data back into a consistent state. The transaction table is an auxiliary data structure which keeps track of transactions that are currently active. For each transaction, it stores the current status, whether the transaction is currently running or whether it has already decided to commit, for instance. And also for each transaction, we keep track of the last log line, of the last log sequence number that this transaction has generated. I see there's a couple of questions in the chat. Let me quickly bring the chat back. Okay, very good. Okay, so here there was a great question and already the answer. So LSN stands for log sequence number. So you can imagine that all those log entries, they are numbered essentially. Each log entry has a unique number, and this number is monotonically increasing. So if you imagine your entire log as a text file, for instance, then the LSN would essentially be the line number. And we keep appending lines to the end of that file. All right, so that is the transaction table, and we also have a so-called dirty page table, and that essentially keep track of pages which are currently loaded into the buffer pool in main memory, and they have been changed in some way, and those changes have not yet made it to hard disk. So this essentially keeps track of pages that might be potentially problematic, because I might lose changes to those pages which have only been made in main memory, but haven't been persisted on hard disk yet. All right, and as I have already said here, associated with each slot in the buffer pool, we have the log sequence number of the last log entry, which changed the corresponding page. And we also have the same on hard disk. So this is a high-level overview of the different data structures that the algorithm uses. So here you see already there's quite a few different data structures. And in the following, we're going to see in more detail how the algorithm updates those data structures at runtime and how it will exploit those data structures during recovery. So this is what we are going to do next time. And in the following, probably in the following two lectures, we will keep discussing about this algorithm. Have a nice day, and then I see you again on Wednesday. Good. All right. So today we're going to continue discussing about recovery, and that essentially means that after the system crashes, we want to restore the database into a consistent state. We want to guarantee durability, which means that the changes of committed transactions persist, and atomicity, which means that we won't have the effects of any partially executed transactions. Now, the component which guarantees that is the recovery manager. And the last time we have started discussing about one of the most popular algorithms for recovery, which is the areas algorithm. And in the following, we're going to discuss this algorithm in detail. It has quite a few moving parts, so it will take a little bit of time. We first will discuss the data structures. We already talked about that a little bit last time. And we're going to discuss about the runtime phase of the algorithm as long as everything is going well. And then finally, we will talk about the recovery phase, so how we bring the database back into a consistent state after we had a crash. So this over here is a high-level overview of all the data structures that the areas algorithm uses. You can see it's a couple of different data structures. Some of them are stored in main memory, and some are stored on hard disk. And everything which is in main memory will be lost during a crash, while the things on hard disk persist. Now here, first of all, two components that we have seen before, which are not directly part of the areas algorithm. We have the buffer pool, which is the portion of main memory reserved for the database system. And we have slots in order to store pages of data. And on hard disk, we have, of course, the data pages themselves. Everything marked in blue is specific to the areas algorithm. And in the following, we're going to quickly go over those different data structures and say what they are all about. First of all, we have seen that the idea in order to be efficient and still allow a recovery after a crash is to do logging. So we produce a small entries that essentially describe what changed. And when we generate those entries, first of all, they are stored in main memory in the log tail buffer. So the last few log entries will always be buffered here in main memory. And that means, of course, that they are not yet persistent. So if the system crashes, then we would lose this last part of the log. The flushed LSN essentially tells us until which log entry the log has been persisted. So each log entry is associated with a so-called LSN, which means a log sequence number, which is just some monotonically increasing ID number for those log entries. If you imagine the log as a text file, then it could, for instance, be the line number. And the flushed LSN essentially tells us up to which line we have written the log to hard disk already, where it will be safe in case of a crash. And in order to make certain guarantees, it's very important that we keep track which part of the log is currently safe and which part of the log is currently in volatile storage. And this flushed LSN that keeps track of that last log entry that was written to hard disk. And that here, as already discussed, is the hard disk portion of the log. So those are the log entries that will be used during the recovery. Every once in a while, we are writing out the content of this log tail buffer to a hard disk. We say that we flush it. And here on hard disk, we have the persistent portion of the log. We have a transaction table data structure, which essentially gives an overview of active transactions. So it stores for each transaction that is currently executing some additional information, which makes it easier to recover operations from that transaction. And then the dirty page table that keeps track essentially of pages that are currently on hard disk and in memory, and the in-memory version differs from the hard disk version. So that happens if we have loaded one of those data pages from hard disk into the buffer pool, and then we changed it. At that point, it becomes a dirty page because we have two different versions. And if we had a crash at this point, then the main memory version would be lost, and along with it, all the associated changes. So dirty pages, those are pages where we might have problems in case of a sudden crash. For other pages, we still have the most recent version on hard disk, and that version will still be available after the system comes back online. Then, for each of the pages in our buffer pool, we now introduce the page last LSN or page LSN, which essentially indicates for each of the currently loaded pages in the buffer pool, what was the last log entry that changed this page. So when we are keeping track of log entries, we are always referring to them by the log sequence number LSN. And here we keep track of the last LSN that affected each of those buffer pages. And we don't only have this in memory, but we also have this on a hard disk. So the on-disk version also captures the last LSN that affected this on-disk version. And if we have a page in a version on hard disk and in a version in memory, then we can use this page LSN to decide in certain situations how much those two pages differ, for instance. Right? So basically, this is like a timestamp of the last change. All right. Now, so in the following, I'm going to discuss those data structures in more detail. That was now the high-level overview. We are not now going to go more into detail. Starting with the structure of the log. So far, I've generically talked about log entries. So let's see how they actually look. So first of all, there's multiple types of log entries depending on the event that they are describing. So for instance, if we are updating data, then associated with that, we generate an update log record. This log record contains fields to store the value before and after an update, which is important because we might have to redo operations whose effects were lost due to a crash, but we also might have to undo operations of transactions that have only partially executed once the crash comes in. And in order to make an undo, we also need the old value before the corresponding change. That's why the update log records store both the old and the new version of the value. If a transaction commits, then we also need to keep track of that in the log. During recovery, we essentially need to decide for each transaction, is this a transaction that had already committed once we crashed, or is this a transaction which was still running during the crash? In that case, we want to abort it. So it's very important that we keep track in our log of those transaction commits. On the other side, transaction might also abort. We also keep track of that with the corresponding log entry. And so far, we always have talked only about transaction commit and transaction abort. Here, we additionally have the transaction end. And that is something which happens after the commit and after the abort. It is essentially indicating that the recovery manager has now done everything that it needs to for a transaction. For instance, for an aborted transaction, that would mean that we have undone all of the associated changes. And so essentially the end log record for transaction means that everything is done and we can now forget about this transaction. One final type of a log record is the compensation log record. And that essentially keeps track of when we undo the operations of transactions. Doing that is important already because while you are recovering your database system after a crash, in some cases, if you're really unlucky, you might have another crash while you are recovering your database. Perhaps the reason for the first crash is that the power supply is currently unstable, and maybe it remains unstable for a certain amount of time. So then it might actually increase the chances that you have another crash while you're currently recovering things. And those compensation log records, among other things, they allow us to keep track of which operations have already been undone, such that we don't try to undo the same thing multiple times if we can avoid it. So compensation log records essentially keep track of which undo operations we have already done. Now, the structure of a generic log entry, and that applies to all of those different types of log entries that we have seen. First of all, a log entry has a log sequence number, of course, that is the ID by which we reference specific log entries. Then log entries always relate to specific transactions, which can, for instance, be the transaction which updated the data. And the transaction ID in the log entry keeps track of which transaction is associated with the event that we are logging. There's also a field named pref_lsn, and that is essentially a pointer back to the last log entry that was generated by the same transaction. Now, very strictly speaking, that would not be required, but it often makes things more efficient because, for instance, if you want to undo the operations of one transaction, you undo them in reverse order. And this is when you want to jump, ideally, through your log only to the operations by that specific transaction. And this pref_lsn field essentially allows you to do that. So this is for efficiency reasons. And then, of course, since we have seen there's multiple types of log entries, we need to keep track of which type we currently have. So we have also a field in order to store the type of the log entry. Specifically for update log records, there is a couple of additional fields. If we have an update, it always refers to specific bytes on a specific page. So in that log entry, we additionally store the page ID to which the update refers. The length indicates how many bytes were changed, and we assume it's consecutive bytes for one specific log entry. An offset indicating what was the first byte that we changed on the page. And then, as discussed, we need the before image and the after image, which means essentially the value before and after the update, such that we can redo the operations or undo the operation if we need to. So that was the log. The flushed LSN is relatively quick to explain. It essentially just indicates up to which log sequence number we have already written log entries to hard disk. And there's a little reminder, we have started last time the recovery chapter by discussing about write-ahead logging. And that generally means that we follow two rules when we do logging. Before a transaction commits, we write all the log entries about a transaction to permanent to persistent storage. And before we write some page from our buffer pool to hard disk, which might contain changes by transactions that are currently not committed yet, whenever we do that, we first should write to hard disk all the log entries which concern the page that we are about to write to hard disk. And the flushed LSN essentially allows us to keep track whether those two conditions are satisfied. And if they're not satisfied, then we can react by writing more log entries from volatile storage to hard disk. So first of all, we need to persist log entries that refer to a transaction before the transaction commits. And we can test that by looking whether the flushed LSN is greater or equal to the last LSN of the corresponding transaction. The last LSN of that transaction, which is stored in the transaction table that I'm going to discuss in more detail in a minute, indicates essentially the last log entry generated by that transaction. And if flushed LSN is at least as large as that last log entry, we know that all log entries related to the transaction must have been written to hard disk. Now, the other rule refers to the case where we write one data page from our buffer pool onto hard disk. And for those pages, we store the page LSN, which was essentially the last log entry that affected the page. And if we can make sure that the flushed LSN is greater or equal to the page LSN of the page that we want to write to hard disk, then we can be sure that all the log entries which refer to that page, they have been made persistent. So the rules of write-ahead logging are satisfied. There might be a question in the chats. Yes, exactly. So flushed LSN essentially gives you the last log sequence number that was written to hard disk. And after that, the log entries are in volatile memory. So if there's a crash, then they will be lost. And the question here is whether the flushed LSN data structure is just a single entry. And that is correct. So the flushed LSN, that is the simplest data structure that we have seen on the screen, it essentially is just one single number. Very good question. Is there any other questions at this point about the data structures? The ones that we have discussed so far? All right. And yes, in general, with this algorithm, I encourage you to ask questions once something is unclear, because it has lots of moving parts that build on each other. So yes, don't hesitate to ask questions in the chat. Okay, good. So this is the purpose of the flushed LSN, which essentially is just one single number stored in main memory. All right, now let's discuss a little bit about the transaction table. So the transaction table contains entries for active transactions. And for each of those transactions, it essentially stores 3 fields. First of all, it stores the transaction ID. Then it stores the status of the transaction, which can be running, committed, or aborted. And then it stores the last LSN of that transaction. And that is essentially the last log entry generated by that transaction. That is the transaction table. The dirty page table stores information about pages that are currently loaded into the buffer pool. A dirty page is generally a page where the in-memory version differs from the hard disk version, which means that the changes that we currently have in the in-memory version would be lost in case of a crash. So the dirty page table stores one entry for each of those dirty pages. First of all, of course, the page ID, and then the so-called rec LSN. And that is the earliest log entry which made the page dirty, basically. So starting from that log entry, the on-disk version starts deviating from the in-memory version. And that is very useful knowledge during recovery, because we know when it comes to the changes of a specific page, we only need to redo those changes starting from the rec LSN. All right. One source of confusion in my experience when it comes to this data structure, that's why I'm proactively pointing it out, is what happens if you have multiple updates to the same page. It is easy to make the mistake to believe that the rec LSN, for instance, changes if you have multiple updates to the same page. That's tempting, but actually the rec LSN is set only once a page becomes dirty for the first time. once there's further updates to the same page, we don't change the rec LSN anymore. So just pointing out one possible source of confusion here. All right, that was the dirty page table. Now finally, let's discuss a little bit about the page LSN or page last LSN, which is essentially just the log sequence number of the last operation that changed the page. So this is stored in memory and on hard disk. And if I have the same page on hard disk and also in an in-memory version, then those two might actually differ. So we always adapt the one in main memory if there is updates. And if at some point one of those pages get written to hard disk, then we essentially overwrite the old page LSN on hard disk. One little question to test your understanding. So if we consider the page LSN of the in-memory and of the disk version of the same page, what can we say about the two, about how they relate to each other if we know that the page is dirty? Exactly. So the last LSN for the page in memory will be strictly greater than the last LSN or page LSN of the corresponding disk page. Exactly. Yeah. Good. So now we have discussed all the data structures of the Aries algorithm. In the following, we're going to discuss about how they are updated. So I'm quickly changing my slide deck here. Let me know if there's any questions so far. All right, so we continue discussing about the Aries algorithm. So we are still talking about the recovery manager, and the relevant chapter in Ramakrishnan and Gehrke is still number 20. So we have discussed about the data structures of the Aries algorithm. Now in the following, we're going to discuss about the runtime behavior. So we're going to discuss about how we update those data structures under normal conditions until there is a crash. And once we have a crash, then we enter the last phase, which we will discuss later, which is when the Aries algorithm uses the log in order to recover the database. All right, so those are the data structures that we have seen. And now in the following, we're going to discuss about how they are being updated, starting with the transaction table. So the transaction table keeps track of which transactions are currently active and when they have last generated any log entries. So we have 4 possible scenarios when it comes to the transaction table. So on the left side, you see an event, and on the right side, you see how we need to update the transaction table in case of that event. So first of all, it might happen that a transaction updates data. So in that case, we simply have to update the last LSN of the corresponding transaction. And as a little reminder, the last LSN essentially is the last log entry generated by one specific transaction. If a transaction commits, then we have to update the status of the transaction to committed. And similarly, we have to register if a transaction aborts in the transaction table. If a transaction ends, it essentially means that we have done all the cleanup we need to do for this transaction after the commit or after the abort. If that happens, at that point, we really consider the transaction as finished, and we can remove it from the transaction table. So that is how we update the transaction table. All right. Now for the dirty page table, there is the scenario that a page changes. Then what we do is that we first of all check in the dirty page table whether the page is already in the table. If that is the case, we don't actually need to do anything because, as I quickly mentioned before, the reg LSN, which is the earliest time at which the page became dirty, that doesn't change in case of further updates. But if the page is not in the dirty page table, then we have to insert it, and we set its reg LSN to the current log sequence number, because this is when the page became dirty. The other side of it is a page gets written to hard disk. So a dirty page, by definition, was always a page where the in-memory version differs from the hard disk version. And if we write one of those pages back to hard disk, then essentially the current in-memory version overrides the on-disk version. And it means that now there is no difference anymore between the two. This is why we take out the corresponding page from the dirty page table. Now, for the page last LSN or page LSN here, we need to keep track of a data update. So whenever we have a data update, we update the page LSN in main memory. So important, we don't update the page LSN on hard disk. That would be bad for performance because we would have disk writes. Instead, we only update it in main memory. And then every once in a while, one of those in-memory pages overrides the disk version. And when that happens, the corresponding page LSN also overrides the on-disk page LSN, right? So those disk page LSNs, they're only updated whenever we write one of those pages in our buffer pool back to hard disk. All right. Now, the log tail is the portion of the log which has not been made persistent yet. So this is still in a main memory. And in general, we have to generate log entries essentially whenever one of the events occurred that we have log entries associated with. We have seen those different types of log entries. And essentially, whenever a transaction updates data, we generate an update log entry. Whenever a transaction commits, we generate a commit log record. Whenever one transaction aborts, we generate an abort log record. And whenever we undo something, we generate a compensation log record. Whenever we finish cleanup for a transaction, we write the end log record. So essentially, we write log records for the different events that we have specific types of log entries for. And first of all, we write them into this log tail buffer in a main memory. Every once in a while, that buffer gets written to hard disk. All right, so now finally, let's come to the hard disk version of the log. So here, generally, we need to follow the rules of write-ahead logging. So whenever a transaction commits, we need to make sure that we add to the log on hard disk all the log entries that relate to this transaction. And in order to proactively avoid another possible source of misunderstandings. So those log entries, they are generated in a sequence, and the log entries generated by different transactions, they might alternate. So if a transaction commits, we're not writing only the log entries to hard disk which connect to that specific transaction, but we just write sequentially all log entries up to the last log entry from the transaction to hard disk. So in passing, we will also make log entries from other transactions persistent once we do that. Also, before we write some of our in-memory pages to hard disk, we need to make sure that we have all required information in order to undo changes on that page later. So we require that all the log entries that relate to this page are made persistent on hard disk. All right. And yes, quickly the flushed LSN. So, and here there is pretty much on the one scenario, if we write more log entries to hard disk, then we also have to update the flushed LSN accordingly and set it to the last log entry that was written to hard disk. All right, so this was an overview of how those different data structures are updated. Before I pass on to the recovery part, I'm gonna make a little example here. So what you see here again is the expanded version of those different data structures that we have seen. We have pages stored on hard disk. Currently, our buffer pool is empty. And currently, all of our data structures here are empty as well. So in the following, we're gonna simulate a couple of execution steps and see how those different data structures are updated while doing that. So first of all, we have a transaction 1, which updates page number 2. So when writing those log entries here in the examples, then of course, I'm not gonna try to represent the entire log entry, but I am focusing on the essentials. In the following, I'm gonna just report which transaction made the update and on which page the update occurred. But just so you know, of course, the real log entry would contain many more fields, as we have seen on one of the past slides. And this initial number, the 1 in this case, that is essentially the log sequence number. And as you will see, it will keep monotonically increasing. So here, transaction number 1 wants to update page number 2. That means, first of all, we need to load page number 2 from hard disk into main memory. It needs to come into our buffer pool. That is one of the changes. Let me just make this step and now explain what happened here. So you see here, first of all, as promised, page number 2 has been copied into the buffer pool in main memory. Now, the first thing that you see, the page LSN of the in-memory version of page number 2 has been updated to 1, because here we are processing log sequence number 1, first log entry, and it has affected page number 2. So we keep track of that, but also note that for the on-disk version of the page, which has not been changed yet, here we still have a page LSN of 0 because the newest changes are not yet reflected on the hard disk version. Also, we have to enter the transaction into our transaction table. So you see here, the first entry, we are noting down transaction 1 as running with a last LSN of 1. The last LSN is always the last log entry generated by this transaction, and that is number 1. Also, page number 2 has become dirty because we have now diverging in-memory and hard disk versions. That is why we enter it into our dirty page table with the rec LSN, the most recent log entry making the page dirty, set to 1, right? So that covers everything. Let's process the next operation. And here there's another transaction number 2, which updates a page number 5. All right. Maybe actually, before continuing, I give you a second to think about what you expect to happen in those different data structures, and perhaps somebody can make a little proposition in the chat. Does anyone have a proposition about how the different data structures change due to this entry? All right, very good. Okay, so I have a first proposition that page 5 will get moved into the buffer pool in main memory, and the page LSN, the page last LSN, will be set to 2. Okay, very good. Is there anything else that happens? Ah, very good. Okay, very good. So P5 gets added, the page number 5 that we are updating gets added to the dirty page table. And the last LSN, the rec LSN in this case, exactly will be set to 2 because this is when the page became dirty. And somebody else is proposing here also that we insert into the transaction table the entry transaction 2 running last LSN2. Absolutely correct. Yes. So those are the changes that we make in this case here. Very good. Exactly. So now we have moved page 5 from hard disk, copied it into main memory. We have changed it and kept track of that change with the page LSN. And we have inserted P5 into the dirty page table with rec LSN2. And we have marked transaction 2 as running with last LSN2. All right. Next operation is an update by a transaction 1 of page 2 again. All right. So what happens here is that we already have page number 2 in main memory. So we still change it and have to update the page LSN here in memory to 3. And for the other changes, so now some temptation might be to update something in the dirty page table, but that is not necessary because page number 2 is already in the dirty page table, and we only keep track of the first log entry by which the page became dirty. So here, the dirty page table, nothing changes, even if we have another update to page number 2. On the transaction table, in the transaction table on the other side, we have a change for transaction 1. It is still running, but now the last LSN, the last log entry it generated must be set to 3 because that is the current log sequence number. All right, let's continue. And at this point, a transaction 2 must commit. All right, so now let's see what changes here. That is actually an interesting case. So maybe let me just ask you that question again. I give you a couple of seconds to think about it, and maybe anyone can make a suggestion about what could change in those data structures. If you think about the rules of write-ahead logging, okay, great proposition here. So people start talking about flushing the log, which is probably what we want to do, because for write-ahead logging, if you remember the rules, there was something that had to happen when transactions commit and something that had to happen when we write pages to hard disk, and both related to we have to write log entries to hard disk. And so here the suggestion is that we flush the first 2 log entries, and that is definitely required. Anyone does anyone suggest to flush more perhaps, or suggest to change some of the other data structures as well? So when we come back online after the crash, we want to know which transactions have been running during the crash. So we will abort those transactions, and which transactions have already committed before the crash. So it's very important that we are aware that which transactions have already committed before the crash. And there's also some Okay, the transaction table, yeah, it is updated with information about the commits. And here that is a little bit tricky because a priori, it is unclear in which order those different data structures are updated. So for the what needs to happen for a commit, we generally said that the transaction needs that we need to write log entries to hard disk up to the last log entry of that transaction. So in this drawing here, right now I have only put the commit log entry, but I have not yet updated the associated data structures. So right now, transaction 2 is still set to a last LSN of 2, but now that we have just added this log entry, the last LSN would be updated to a 4, and then we would want to write all of the associated log entries to hard disk. And indeed, we have to update the last LSN of the transaction. We also have to update the status of the transaction. And beyond that, the only other thing that changes is the flushed LSN in order to keep track of which portion of the log has already been persisted. So this is, yeah, very good replies here. So exactly, this is what I wanted to hear, that we have to write part of the log back to hard disk in order to make those changes, in order to persist those changes. Okay, let me quickly show that here. Actually, let me move the chat away so you can see my slide. All right, so now we have already updated the transaction table. And all right, and now we have written the log to hard disk. So here multiple things have happened at the same time when going from one to the other one. Strictly speaking, the status of transaction 2 should also be updated to a commit instead of running. Once we have the end log record for transaction number 2, then it gets deleted out of the transaction table anyway, but nevertheless, strictly speaking, this running should actually be committed now in the transaction table for transaction number 2. Beyond that, you see here that we have updated the flushed LSN to 4 because now we have persisted the first 4 log entries. We have the end log record for transaction 5, which means that we can take out this transaction from the transaction table. And of course, since we haven't written any pages to hard disk, we still have those entries in the dirty page table. Now let's continue a little bit further. Now we have transaction number 3, which updates a page number 7. And again, we have to move page number 7 from hard disk into main memory. Let me do that here. We have to update the page LSN of page number 7 to 6 because that is the current log sequence number. Also, transaction number 3 is fresh, so we have to add it to the transaction table. And page 7 had been clean before, now it becomes dirty, so we have to add it to the dirty page table with log sequence number 6 as the rec LSN. All right. So one more, transaction 1 now updates page number 8. So we move page number 8 into main memory. It also becomes dirty, so we added with rec LSN 7, and transaction 1 gets updated in terms of last LSN, and we set that to the current log sequence number as well. All right, so at this point, note that the buffer pool is filled up. So if we want to do any further operations on different pages than what we have in the buffer pool now, then we first would have to write some of those pages to hard disk. We quickly check whether there's questions. All right, and this is a great question. So the question was when transaction number 2 finished, why didn't we write the associated pages, the pages that were changed by this transaction, to hard disk? So that's a great question. In fact, there is a policy which is called the force policy. I can hear some noise here. Let me quickly. Okay. All right. So the question was, if a transaction commits, why don't we write the pages that were changed by this transaction to hard disk? And there's indeed a policy which does exactly that. This is the force policy. We have discussed it very quickly last time. We went over it relatively very fast. It essentially means that before a transaction commits, I write all the associated changes to hard disk. The problem with that is efficiency. Because if a transaction made lots of small changes on many different pages, then you would have to write all of those pages in their entirety to hard disk. So you would have many page write operations, and it would degrade, it would increase response time by quite a lot. So this is why people don't use it in practice because of performance reasons. The nice thing about logging is that the log essentially contains the same information. It also tells you which pages were changed and how they were changed. And it allows you to compress those changes into much fewer pages. So instead of writing lots of data pages with small changes, you can just write at most one page with log entries which describe those changes in a very concise manner. So we avoid writing the pages for efficiency reasons, but instead we make sure that we write the log, which means that we could redo those changes if there was a crash. Otherwise, we just rely on the changes to the data that they are written to disk eventually once we need more space in the buffer pool and need to free up one of the slots. Great question. So that is why we do the logging, so we don't need to write the corresponding data pages to hard disk. And now I already mentioned the case where we eventually write the pages to hard disk if we need space in a buffer pool. And with the next entry, we have an update to page number 6 by transaction 1. And unfortunately, we don't have page number 6 in our buffer pool. And we also don't have any space left in our buffer pool. So we need to select one of those slots in a buffer pool in order to free it up. And since we currently have unpersisted changes in those buffer pool pages, before I can free it up, I first need to back up the changes to hard disk. We have discussed about buffer replacement policies. So in this case, let's just see that the buffer replacement policy selects the rightmost slot for replacement, this one over here. So what I need to do is that I write the content of this page back to a hard disk. And before I can do that, in order to follow the rules of write-ahead logging, I need to make sure that I persist all the log entries that affect the page number 8 to hard disk first. I need to do that if, for instance, the transaction that made the change to page number 8 later decides to abort, or if it is running and there's a crash, which means that we want to abort it by default, then I need to be able to undo those changes of the partially executed transaction that I'm now about to write to hard disk. And this is why I need to ensure that all the log entries that affected this page are written to hard disk first. And here, the page LSN of page 8 is 7. So I have to write all the log entries up to log entry 7 from the log tail to hard disk. And I have to update the flushed LSN. And now I'm ready to write page number 8 to hard disk. You see that the page LSN on hard disk finally changes. And also Now I want to take out the page number 8 from the dirty page table. All right, so that was a little example for the runtime phase. Next time, we're going to discuss about the recovery phase, which is invoked after the system comes back online after a crash. Have a nice day, and then I see you on Friday. So, hello everyone, let's get started. And today we are going to conclude our discussion of recovery when we want to bring the database back into a consistent state after a system crash. And the last time we have been discussing about one algorithm to do that, which is the Aries algorithm. Now, for this algorithm, we have first of all discussed about the data structures it uses, which include some data structures in main memory and some on hard disk. Then we have discussed about how the algorithm behaves under normal circumstances. And now in the following, we're going to discuss about how the algorithm does the recovery after a system crash. So the recovery has 3 phases. First of all, we have the analysis phase, then we have the redo phase, and finally we have the undo phase. So during the analysis phase, the algorithm restores a certain data structures, which is the transaction table and the dirty page table. The transaction table essentially gives an overview of the transactions that are currently running and their status. The dirty page table keeps track of pages where the in-memory version deviates from the hard disk version. So we have changes in main memory that have not been made persistent yet. And with the dirty page table, we keep track of which pages are concerned by that. During the redo phase, we are redoing changes of committed transactions or of transactions in general that have not been made persistent yet. During the undo phase, we are undoing the operations of transactions that are aborted, for instance, because they have been running at the point of the crash. So for those transactions, in the end, the database should look as if those transactions had never happened. Now in the following, we're going to discuss those different phases in more detail. Now, one remark about the analysis phase. So I have already quickly mentioned that during the analysis phase, our goal is to restore the transaction table and the dirty page table. Now we are restoring those data structures by reading the log entries, which describe the different updates to the data, transaction commits, and so on and so forth. And without any checkpoints, we would essentially have to read that log from the beginning of time in order to restore our data structures. And of course, that would be very inefficient. So we want to make the recovery as efficient as possible, and checkpoints are a way to make it more efficient. So during a checkpoint, we essentially save the current state of the transaction table and dirty page table to hard disk. And those checkpoints are also written to the log. We have one so-called master record stored on hard disk, which gives us the location within the log of the last checkpoint. So because of that, we can avoid reading the log from the very beginning. Now, this is how we write those checkpoints. One important thing that we want to avoid having to stop the database in order to write out those checkpoints. So we want to continue processing transactions as they come in, while in the background, we are processing the checkpoint. Now, writing out those data structures, the transaction table and the dirty page table, it takes a little bit of time. So if we let the transactions continue, it means that the state of the transaction table and dirty page table that we write out to the log, they will be probably outdated before we even finish writing. And this is why it is very important to mark up in the log the point in time at which this checkpoint is valid. So once we begin checkpointing, then we first of all write a begin checkpoint a record into our log, and that essentially marks the point in time at which the checkpoint is valid. And after writing this begin checkpoint record, we start writing the actual content of the transaction and a dirty page table, while the transactions, they keep coming in and processing and thereby changing the transaction table and the dirty page table. So once we have finished writing the transaction and dirty page table, then we write the end checkpoint record. So we know that checkpointing has finished, but the state of the transaction and dirty page table that we have written to hard disk is only valid at the begin checkpoint record. All right. Now, this is an overview of which portion of the log the different phases looked at. So for the analysis phase, we started from the last checkpoint. More precisely, we start looking at log entries at the begin checkpoint record, because starting from there, we might encounter log entries that are not reflected in the transaction and dirty page table as it is represented in the checkpoint. So starting from there, starting from the checkpoint, we read the log until we have reached the final entries before the system crash. And in the redo phase, we start potentially even earlier. We essentially start with the earliest log entry that might have changed one of our data pages and is not yet persistent on hard disk. So the dirty pages are those pages where the in-memory version deviates from the hard disk version. In the analysis phase, we restore the dirty page table, and we can use it in order to identify the log entry starting from which we might have changes to the data that have not been made persistent yet, so we have to consider them during the redo phase. So in the dirty page table, as a little reminder, each page is associated with the so-called reg-LSN entry, which gives essentially the earliest log entry that made the page dirty, meaning that the in-memory version deviates from the hard disk version. So in order to know where to start the redo phase from, we just look at all the entries in the dirty page table and identify the minimum reg-LSN. This is where we start the redo phase from. For the undo phase, we are undoing the operations of aborted transactions or transactions that have been running at the point of the crash. So we want to undo them. And here we want to undo the operations of a transaction in reverse order. So this is why we traverse the log backward, starting from the most recent entries and going back to the earliest entries from transactions that are now aborted. So this is the high-level overview of how those different phases of recovery use the log. On the following, we're going to discuss them in a little bit more detail. So the analysis phase, as discussed, is about restoring the transaction and the dirty page table. So we start scanning from the last checkpoint. And if, for instance, we encounter a log entry stating that some transaction TY has updated some page p set, and the log entry has the log sequence number LX. Then we first of all update the dirty page table. We check whether the page p set is not in the dirty page table. If it is not included, then we insert it, and we insert it with reglsn set to the current log entry number LX, because the reglsn always gives you the earliest log entry that made a page dirty. If the transaction ty is not in a transaction table, then we add it and we mark the status as running. And if the transaction is already in the transaction table, then we still need to update the last LSN, which always gives the last log entry created by a transaction. So we update that to the current log entry, and this is what we have to update if we encounter one of those log entries that describe an update to our data. Now, if a transaction commits and we see a corresponding log entry, then we change in the transaction table the status of the transaction to committed and update the last LSN. If a transaction aborts, then correspondingly we update the status to aborted. And if we encounter an end log record for a transaction, which essentially means that all the cleanup for this transaction has been done. So we can forget about the transaction, and this is why in this case we remove it from the transaction table. Now, one question to you, and I give you a couple of seconds to think about it, is whether we get a precise transaction table and dirty page table that we had directly before the system crash after the analysis phase. So basically, will we always be successful in restoring the transaction table and dirty page table precisely to their state immediately before the system crash because of the analysis phase? In the end here, we restore the transaction table and dirty page table based on log entries. And now if you think about the way that log entries have to make until they become persistent on hard disk. So the right answer here is that in some cases, we might not be able to restore the transaction table and dirty page table exactly into the state they were in before the system crash, because log entries are first of all written into the log tail in main memory, which means that it will vanish if there is a system crash. And only every once in a while, we write the log tail entries to hard disk where they become persistent. So the last few log entries directly before the crash might get lost, which means that we might have a slightly earlier state of the transaction and dirty page table. But the nice thing about this is that we can be sure that those log entries that we lost, they don't refer to any transactions that have already committed, for instance, because due to the rules of write-ahead logging that the Aries algorithm is following, if a transaction commits, then we have to make all its log entries persistent on hard disk. So in the following, we're going to make a little example about the analysis phase. We continue with the example that we had before. And by the way, here in this graphic, you also see again the log tail buffer on the right upper corner, which is in main memory, which is volatile. And on the bottom, you see the persistent part of the log, which is stored on hard disk. So let's assume that we have a crash in our system. For instance, suddenly the power supply fails and the server is shut down because we don't have power anymore. In that case, once the system comes back online after the crash, everything we have in main memory will be erased, of course. So here, now we don't have anything in our buffer pool and we don't have anything in the remaining data structures. So at this point, perhaps I'm quickly going to remind you of the semantics of those different data structures that you see here. First of all, we have data structures that are not specific to the Aries algorithm, but relate to things that we have seen before in the course. On hard disk, of course, we have stored our actual data at the granularity of pages. And then in main memory, we always have the buffer pool, which is the portion of main memory reserved for the database system. And also it is divided into slots where each of those slots can store one of the pages. Now, first of all, specific to the Aries algorithm, we associate those pages on hard disk and in main memory with this page last LSN or simply page LSN, which essentially gives you the last log sequence number that has changed the page. So the log entries are always associated with the log sequence number. It's an ID of the log entry. If you imagine the log as a text file, you can think of the log sequence number simply as the line number. And here for the in-memory version and for the hard disk version, we have the log sequence number that has last changed the corresponding page. Then we have the transaction table, which keeps track of the status of different transactions. We have the dirty page table, which keeps track of pages where the in-memory version in the buffer pool on the left-hand side on top deviates from the corresponding page on hard disk on the bottom, and keeps track of the log entry at which that happened. We have the log tail buffer in main memory, which stores the last few log entries that haven't made it to hard disk yet. And we have the flushed LSN, which stores up to which log entry I have already written them to hard disk. And then finally, here on hard disk, you have the log portion that has already made it to persistent storage. So now we had the crash. We have to recover the transaction table and the dirty page table based on the entries that we find in the log on hard disk. So here currently, we don't have a checkpoint yet. So we simply start from the beginning of the log, starting with log sequence number 1. So here a transaction T1 updates a page P2. So first of all, we have to insert the transaction into the transaction table. We mark it as running, and the last LSN, which indicates the last log entry of that transaction, that is currently set to 1. So in the syntax that you see in the log, you always have the log sequence number, then followed by the high-level information about the log entry. So here T1 updates the page P2 by changing something on that page. And because of that, the page now deviates from the main memory version of the page, deviates from the hard disk version of the page, and the earliest log entry that has caused that is the current one, number 1. So we insert into the dirty page table page 2 with reg LSN set to 1. Now we continue here. We find a log entry stating that transaction 2 has updated page 5, and that is a log sequence number 2. So we insert a transaction into the transaction table with last LSN set to 2 and marked as running. And in the dirty page table, we insert page number 5 with the reg LSN set to 2. Now transaction 1 decides again to update page number 2. So first of all, we update the transaction table and set the last LSN for transaction 123, the current log sequence number. Now, this is often a source of confusion in my experience. Don't update the dirty page table if you have another update on the same page. Now, the dirty page table only stores the rec LSN, which is the earliest log entry that made the page dirty. So if we have repeated changes to the same page, which is already dirty, then we don't need to change anything in the dirty page table. So we leave that one, the rec LSN of page 2 set to 1. Now here transaction number 2 commits. So we set the status to committed and update the last LSN. And now it even ends, which means that we remove transaction 2 from the transaction table here. Now we encounter a new transaction, transaction 3. So we insert that into the transaction table with a last LSN set to 6, and it updates page number 7. So we insert page number 7 with a rec LSN 6 into the dirty page table. Finally, transaction 1 updates page 8 as well. So here, transaction 1, we update the last LSN in the transaction table, and here we insert page number 8 with rec LSN 7 into the dirty page table. All right, so this is the analysis phase. In a simple example, we have restored the transaction table and dirty page table using the log entries that we still find on hard disk after the crash. The next is the redo phase. And the redo phase needs to start from the earliest point at which changes occurred where that may not have made it to hard disk yet. In order to find that point, we analyze the dirty page table, which contains for each page the earliest log entry that made it dirty. So if we take the minimum over all dirty pages, then we have the starting point for the redo phase. And during the redo phase, we focus on data updates and compensation log records, which also correspond to data updates, but it is a specific type of update because here we're talking about updates that revert a previous update because the corresponding transaction has aborted. So both are interesting for the redo phase. And if we encounter one of those entries, then typically we have to redo it, which means that we redo the corresponding, so we load the corresponding page into main memory, we execute the change, and we update the corresponding page LSN of that in-memory page. There is certain conditions under which we can avoid redoing an operation, which of course we avoid if we can, because then things become more efficient. We can avoid the redo if one of the following 3 conditions is satisfied. So let's see under which conditions we can avoid the redo. So a first condition, if it holds, we can avoid the redo. It's the following. If the page affected by the update we are currently looking at is not in the dirty page table anymore, then we know that the corresponding log entry must already have been made persistent, so we don't need to redo the corresponding change. Also, assuming that the page is in the dirty page table, but the rec LSN of that page is greater than the current log sequence number. That essentially means that the page is dirty, but it becomes dirty by a later log entry than the current one. So also in this case, we can avoid the redo. And finally, we can avoid the redo as well if the page LSN of the corresponding page on hard disk is greater or equal to the current log sequence number. So those are 3 conditions if any of them holds, we don't have to redo the current update. We check those 3 conditions in the order that you see here. So one interesting question is, why do we check those conditions in precisely that order? So I give you a few seconds to think about that. And I'm actually going to show you those conditions again. And when thinking about why we check them in this order, perhaps think about efficiency and performance. Think about where the information required to check those conditions is stored, whether it's stored in main memory or on hard disk. And we know that accessing main memory is more efficient than accessing hard disk. And the right answer is that here the dirty page table is stored in main memory. So the first 2 conditions can be verified relatively efficiently, while the last condition refers to the page address n that is stored on hard disk. And in order to get that, we already have to load that page from hard disk into main memory, which takes time. So this is why we check the last condition indeed last. The first 2 are much cheaper to verify. All right, and so now we continue with the same running example where we have just executed the analysis phase. So now the transaction table and the dirty page table, they have been restored as good as possible. So in the following, we start the redo phase. And first of all, we need to figure out, starting from which log entry we need to read the log. And in order to find that out, we analyze the dirty page table. We take the minimum rec address n that we have stored there. That is the one that I have marked up here. So we do have to start the redo phase indeed from log entry number 1. So let's start from log entry number 1, which is transaction 1 updating page number 2. And first of all, we want to check whether we actually need to redo this log entry or not. So first 2 conditions refer to the dirty page table. So let's first of all check page number 2. Is it in the dirty page table? And yes, indeed, it is in the dirty page table. Now we look at the rec address n. And unfortunately, the rec address n, which is 1, in this case, is not greater than the current log sequence number, which is also 1. So the first 2 conditions are not satisfied. So now let's check for the last condition, the page address n on hard disk. And for page number 2, that is 0, which is unfortunately not greater or equal to 1. And this is why we have to probably redo this change. So we are loading that page into main memory. We are executing the change in main memory, and we are updating the page address n to 1. All right, so in this case, we had to redo. Next, we encounter an update by transaction 2 of page number 5. And here again, page 5 is in the dirty page table. The rec address n is not greater than 2. It is exactly 2. And if you look at the hard disk page address n, then page 5 has a 0, which again is not greater or equal to the current log sequence number, which is number 2. So we have to load it into the buffer pool. We update the page LSN to the current log sequence number, which is 2, and execute the associated change. Now here again, T1 updates page 2, and page 2 is in the dirty page table with a lower rec LSN. The on-disk page LSN is lower. We already have it loaded into main memory, so we just need to execute the corresponding change and update the page LSN to the current one, which is 3. So commit and end log records, they are not interesting for redo. So we jump directly to the update of page number 7 by transaction 3. So here again, the page number 7 is in the dirty page table. Its rec LSN is not greater than the current one. And looking at the page version on hard disk, the page LSN is unfortunately lower than the current log sequence number. So we have to redo the operation. We load the page into main memory, execute the change, and set the page LSN to 6. So now let's look at the last update. Transaction 1 is updating page number 8. So I give you a few seconds to think about whether we need to redo this change or not by verifying those 3 conditions that we have seen before. The first condition was checking whether the page is in the dirty page table. And then the second condition is looking at the rec LSN. Third condition is looking at the hard disk version of the page. And in this case, the page is in the dirty page table. We find page number 8. So that condition is not verified. The rec LSN of the page is not greater than the current one. So that condition is not verified either. Now, if we, however, look at the hard disk version of the page, here for page number 8, we find that the page LSN is actually equal to 7. That means that all the changes up to log sequence number 7 have already been made persistent on hard disk. And this is why in this case, we don't actually need to redo the corresponding change. So here the final one does not need to be redone. That was the redo phase here. The next up is the undo phase. Now here we want to undo transactions that were running at the time of the crash, transactions that have not committed before the crash, and we want to undo those changes of those transactions in reverse order. Of course, we could just keep reading log entries in reverse order, but that would be inefficient. Some time ago, when discussing the structure of the log entries, I introduced the so-called pref LSN field. And for a given log entry, the pref LSN field essentially points backwards to the last log entry generated by the same transaction. So here this is essentially like a pointer. We just store the log sequence number of the last log entry. So when going back through the log in order to undo the changes of one specific transaction, then we use those pointers in order to efficiently jump through the log along the operations, along the log entries generated by the same transaction. And while we are undoing those changes, we also write those compensation log records, which always keep track of changes that have already been undone. So let's again see how we do this in the example here. So here in the log on hard disk, you can see that I symbolize those pref LSN pointers by those red arrows, which are connecting log entries that belong to the same transaction. And we are undoing things in a reverse order. So here we have two transactions running, transaction 1 and transaction 3. They were running at the time of the crash. So we start undoing the last operation of transaction 1, which updated page number 8. So in order to undo this, so first of all, we write a compensation log record in our concise notation. Here for those examples, it is simply CLR, then the transaction identifier, and then the page identifier. And in order to undo the change, we have to load the page from hard disk into main memory. And we undo the change. And undoing the change is also a change. So therefore, we also update the page LSN to the current log sequence number from the compensation log record. So now the next log entry in reverse order would belong to transaction 3, which also has to be undone. So here transaction 3 updates page number 7. So we write the compensation log record again in order to undo this change. And page number 7 is already in our buffer pool, so we don't need to load it anymore. We just undo the change and update the page LSN to number 9. So now we use those pointers in order to identify candidates for the next log entry that we might want to undo, which is one change by one of the transactions that we are undoing. So here we jump to the update of transaction 1 to page number 2. And again, we write the corresponding compensation log record. And page number 2 is already in main memory, so we don't need to load it. We update the page LSN and we undo the corresponding change. Now, we jump over the next one because that one belongs to transaction 2, which committed, so we don't want to undo that, of course. So we're going directly to the first log entry by transaction 1, which updated page number 2. And here, page number 2 again is already in main memory. We write the corresponding compensation log record, update the page LSN and the page itself. And now we have undone all the associated operations. So here we could now in the next steps delete those transactions, for instance, from the transaction table. All right. Now, one last point that I want to discuss is crashes during recovery. Now, that might at first sound a little bit unlikely. You just had a crash. What are the chances that it crashes while you're in the process of recovering? But for instance, if you have an unreliable power supply and that has caused the first crash, then maybe directly after it is still a little bit unreliable. So you might actually have increased chances for a second crash. And in general, the Arias algorithm has the nice property that it can deal with crashes during the recovery. So let's quickly go over the possibilities. So, I mean, if you have a crash during the analysis phase, then you simply restart the analysis phase. If you have a crash during the redo phase, then of course, after the system comes back online again after the second crash, you still have to re-execute the analysis phase. And finally, you have to restart the redo phase as well. Now, perhaps if you're lucky, then some of the redo operations, they have become unnecessary because during the first recovery try, you manage to get some of those changes to hard disk, for instance. And similarly, for the undo phase, if we have a crash there, then we again start all phases from the analysis phase. Here, we might already have started to undo some operations from transactions. In that case, we have written the corresponding compensation log records. So we would have redone those compensation log records during the redo phase. So we can essentially start the undo. So some of the undo operations have already happened in the redo phase. All right. So that is the Argus algorithm, and that concludes the chapter on a recovery. We have now essentially seen all the different components of a traditional relational database management system. In the next lecture, we're gonna go a little bit over the material that we have seen in the previous lectures, and there will be opportunities to ask a question also about material that we haven't seen in a while. I wish you a nice weekend, and then I see you next week.